Chapter 6. The Sun's Distance. The question of the Sun's distance arises naturally from the consideration of his temperature, since the intensity of the radiations emitted as compared with those received and measured, depends upon it. But the knowledge of that distance has a value quite apart from its connection with solar physics. The semi-diameter of the Earth's orbit is our standard measure for the universe. It is the great fundamental datum of astronomy, the unit of space, any error in the estimation of which is multiplied and repeated in 1,000 different ways, both in the planetary and sidereal systems. Hence its determination was called by Airy the noblest problem in astronomy. It is also one of the most difficult. The quantities dealt with are so minute that their sure grasp tasks all the resources of modern science. An observational inaccuracy which would set the moon nearer to, or farther from us than she really is by 100 miles, would vitiate an estimate of the Sun's distance to the extent of 16 million. What is needed in order to attain knowledge of the desired exactness is no less than this, to measure an angle about equal to that subtended by a halfpenny 2,000 feet from the eye, within a little more than 1,000th part of its value. The angle thus represented is what is called the horizontal parallax of the Sun. By this amount, the breadth of a halfpenny at 2,000 feet, he is, to a spectator on the rotating earth, removed at rising and setting from his meridian place in the heavens. Such, in other terms, would be the magnitude of the terrestrial radius as viewed from the Sun. If we knew this magnitude with certainty and precision, we should also know with certainty and precision, the dimensions of the earth being, as they are, well ascertained, the distance of the Sun. In fact, the one quantity commonly stands for the other in works treating professedly of astronomy. But this angle of parallax or apparent displacement cannot be directly measured, cannot even be perceived with the finest instruments. Not from its smallness. The parallactic shift of the nearest of the stars as seen from opposite sides of the Earth's orbit, is many times smaller. But at the Sun's limb, and close to the horizon, where the visual angle in question opens out to its full extent, atmospheric troubles become overwhelming, and altogether swamp the far more minute effects of parallax. There remain indirect methods. Astronomers are well acquainted with the proportions which the various planetary orbits bear to each other. They are so connected, in the manner expressed by Kepler's third law, that the periods being known, it only needs to find the interval between any two of them in order to infer at once the distances separating them all from one another and from the Sun. The plan is given, what we want to discover is the scale upon which it is drawn, so that, if we can get a reliable measure of the distance of a single planet from the Earth, our problem is solved. Now some of our fellow travelers in our unending journey round the Sun, come at times well within the scope of celestial trigonometry. The orbit of Mars lies at one point not more than 35 million miles outside that of the Earth. And when the two bodies happen to arrive together in or near the favorable spot, a conjuncture which occurs every 15 years, the desired opportunity is granted. Mars is then, in opposition, or on the opposite side of us from the Sun, crossing the meridian consequently at midnight. It was from an opposition of Mars, observed in 1672 by Richer at Cayenne in concert with Cassini in Paris, that the first scientific estimate of the Sun's distance was derived. It appeared to be nearly 87 millions of miles, parallax 9.5. While Flamsteed deduced 81,700,000, parallax 10, from his independent observations of the same occurrence, a difference quite insignificant at that stage of the inquiry. But Picard's result was just half Flamsteed's, parallax 20. Distance 41 million miles, and Lahire considered that we must be separated from the hearth of our system by an interval of at least 136 million miles. So that uncertainty continued to have an enormous range. Venus, on the other hand, comes closest to the Earth when she passes between it and the Sun. At such times of inferior conjunction she is, however, still 26 million miles, or, in round numbers, 109 times as distant as the Moon. Moreover, she is so immersed in the Sun's rays that it is only when her path lies across his disk that the requisite facilities for measurement are afforded. These partial eclipses of the Sun by Venus, as Encke termed them, are coupled together in pairs, of which the components are separated by 8 years, recurring at intervals alternately of 105.5 and 121.5 years. Thus, the first calculated transit took place in December, 1631, and its companion, observed by Horrocks, in the same month, NS, 1639. Then, after the lapse of 121.5 years, came the June couple of 1761 and 1769. And again after 105.5, the two last observed, December 8, 1874, and December 6, 1882. Throughout the 20th century there will be no transit of Venus. But the astronomers of the 21st will only have to wait for years for the first of a June pair. The rarity of these events is due to the fact that the orbits of the Earth and Venus do not lie in the same plane. If they did, there would be a transit each time that our twin planet overtakes us in her more rapid circling, that is, on an average, every 584 days. As things are actually arranged, she passes above or below the Sun, except when she happens to be very near the line of intersection of the two tracks. Such an occurrence as a transit of Venus seems, at first sight, full of promise for solving the problem of the Sun's distance. For nothing would appear easier than to determine exactly either the duration of the passage of a small, dark orb across a large brilliant disk, or the instant of its entry upon or exit from it. And the differences in these times, which, owing to the comparative nearness of Venus, are quite considerable, as observed from remote parts of the Earth, can be translated into differences of space, that is, into apparent or parallactic displacements, whereby the distance of Venus becomes known, and thence, by a simple sum in proportion, the distance of the Sun. But in that word exactly what snares and pitfalls lie hid. It is so easy to think and to say, so indefinitely hard to realize. The astronomers of the 18th century were full of hope and zeal. They confidently expected to attain, through the double opportunity offered them, to something like a permanent settlement of the statistics of our system. They were grievously disappointed. The uncertainty as to the Sun's distance, which they had counted upon reducing to a few 100,000 miles, remained at many millions. In 1822, however, Encke, then director of the Seeberg Observatory near Gotha, undertook to bring order out of the confusion of discordant, and discordantly interpreted observations. His combined result for both transits, 1761 and 1769, was published in 1824, and met universal acquiescence. The parallax of the Sun thereby established was 85776, corresponding to a mean distance of 95.25 million miles. Yet this abolition of doubt was far from being so satisfactory as it seemed. Serenity on the point lasted exactly 30 years. It was disturbed in 1854 by Hansen's announcement that the observed motions of the Moon could be drawn into accord with theory only on the terms of bringing the Sun considerably nearer to us than he was supposed to be. Dr. Matthew Stewart, professor of mathematics in the University of Edinburgh, had made a futile attempt in 1763 to deduce the Sun's distance from his disturbing power over our satellite. Tobias Mayer of Göttingen, however, whose short career was fruitful of suggestions, struck out the right way to the same end. And Laplace, in the 7th book of the Mécanique Céleste, gave a solar parallax derived from the lunar parallactic inequality substantially identical with that issuing from Encke's subsequent discussion of the 18th century transits. Thus, two wholly independent methods, the trigonometrical, or method by survey, and the gravitational, or method by perturbation, seemed to corroborate each the upshot of the use of the other until the 19th century was well past its meridian. It is singular how often errors conspire to lead conviction astray. Hansen's note of alarm in 1854 was echoed by Leverrier in 1858. He found that an apparent monthly oscillation of the Sun which reflects a real monthly movement of the Earth round its common center of gravity with the Moon, and which depends for its amount solely on the mass of the Moon and the distance of the Sun, required a diminution in the admitted value of that distance by fully 4 million miles. 3 years later he pointed out that certain perplexing discrepancies between the observed and computed places both of Venus and Mars, would vanish on the adoption of a similar measure. Moreover, a favorable opposition of Mars gave the opportunity in 1862 for fresh observations, which, separately worked out by Stone and Winnock, agreed with all the newer investigations in fixing the great unit at slightly over 91 million miles. In Newcomb's hands they gave 92.5 million. The accumulating evidence in favor of a large reduction in the Sun's distance was just then reinforced by an auxiliary result of a totally different and unexpected kind. The discovery that light does not travel instantaneously from point to point, but takes some short time in transmission, was made by Olaus Römer in 1675, through observing that the eclipses of Jupiter's satellites invariably occurred later when the Earth was on the far side, than when it was on the near side of its orbit. Half the difference, or the time spent by a luminous vibration in crossing the mean radius of the Earth's orbit, is called the light equation. And the determination of its precise value has claimed the minute-care distinctive of modern astronomy. D'Alembert in 1792 made it 493 seconds. Glasenapp, a Russian astronomer, raised the estimate in 1874 to 501. Professor Harkness adopts a safe medium value of 498 seconds. Hence, if we had any independent means of ascertaining how fast light travels, we could tell at once how far off the Sun is. There is yet another way by which knowledge of the swiftness of light would lead us straight to the goal. The heavenly bodies are perceived, when carefully watched and measured, to be pushed forward out of their true places, in the direction of the Earth's motion, by a very minute quantity. This effect, already adverted to, has been known since Bradley's time as aberration. It arises from a combination of the two movements of the Earth round the Sun and of the light waves through the ether. If the Earth stood still, or if light spent no time on the road from the stars, such an effect would not exist. Its amount represents the proportion between the velocities with which the Earth and the light rays pursue their respective journeys. This proportion is, roughly, 1 to 10,000. So that here again, if we knew the rate per second of luminous transmission, we should also know the rate per second of the Earth's movement, consequently the size of its orbit and the distance of the Sun. But, until lately, instead of finding the distance of the Sun from the velocity of light, there has been no means of ascertaining the velocity of light except through the imperfect knowledge possessed as to the distance of the Sun. The first successful terrestrial experiments on the point date from 1849, and it is certainly no slight triumph of human ingenuity to have taken rigorous account of the delay of a sunbeam in flashing from one mirror to another. Fizeau led the way, and he was succeeded, after a few months, by Léon Foucault, who, in 1862, had so far perfected Wheatstone's method of revolving mirrors, as to be able to announce with authority that light traveled slower, and that the Sun was in consequence nearer than had been supposed. Thus a third line of separate research was found to converge to the same point with the two others. Such a conspiracy of proof was not to be resisted, and at the anniversary meeting of the Royal Astronomical Society in February, 1864, the correction of the solar distance took the foremost place in the annals of the year. Lest, however, a sudden bound of 4 million miles nearer to the center of our system should shake public faith in astronomical accuracy, it was explained that the change in the solar parallax corresponding to that huge leap amounted to no more than the breadth of a human hair 125 feet from the eye. The Nautical Almanac gave from 1870 the altered value of 8.95, for which Newcomb's result of 8.85, adopted in 1869 in the Berlin Ephemeris, was substituted some 10 years later. In astronomical literature the change was initiated by Sir Edmund Beckett in the first edition, 1865, of his Astronomy Without Mathematics. If any doubt remained as to the misleading character of Encke's deduction, so long implicitly trusted in, it was removed by Pauwelke's and Stone's rediscussions, in 1864 and 1868 respectively, of the transit observations of 1769. Using improved determinations of the longitude of the various stations, and a selective judgment in dealing with their materials, which, however indispensable, did not escape adverse criticism. They brought out results confirmatory of the no longer disputed necessity for largely increasing the solar parallax, and proportionately diminishing the solar distance. Once more in 1890, and this time with better success, the 18th century transits were investigated by Professor Newcomb. Turning to account the experience gained in the interim regarding the optical phenomena accompanying such events, he elicited from the mass of somewhat discordant observations at his command a parallax, 879, in close agreement with the value given by sundry modes of recent research. Conclusions on the subject, however, were still regarded as purely provisional. A transit of Venus was fast approaching, and to its arbitrament, as to that of a court of final appeal, the pending question was to be referred. It is true that the verdict in the same case by the same tribunal a century earlier had proved of so indecisive a character as to form only a starting point for fresh litigation. But that century had not passed in vain, and it was confidently anticipated that observational difficulties, then equally unexpected and insuperable, would yield to the elaborate care and skill of forewarned modern preparation. The conditions of the transit of December 8, 1874, were sketched out by Sir George Airy, then Astronomer Royal, in 1857, and formed the subject of eager discussion in this and other countries down to the very eve of the occurrence. In these Mr. Proctor took a leading part, and it was due to his urgent representations that provision was made for the employment of the method identified with the name of Halley, which had been too hastily assumed inapplicable to the first of each transit pair. It depends upon the difference in the length of time taken by the planet to cross the Sun's disk, as seen from various points of the terrestrial surface, and requires, accordingly, the visibility of both entrance and exit at the same station. Since these were, in 1874, separated by about 3½ hours, and the interval may be much longer, the choice of posts for the successful use of the method of durations is a matter of some difficulty. The system described by Delisle in 1760, on the other hand, involves merely noting the instant of ingress or egress, according to situation, from opposite extremities of a terrestrial diameter. The disparity in time giving a measure of the planet's apparent displacement, hence of its actual rate of travel in miles per minute, from which its distances severally from Earth and Sun are immediately deducible. Its chief attendant difficulty is the necessity for accurately fixing the longitudes of the points of observation. But this was much more sensibly felt a century ago than it is now, the improved facility and certainty of modern determinations tending to give the Delislean plan a decided superiority over its rival. These two traditional methods were supplemented in 1874 by the camera and the heliometer. From photography, above all, much was expected. Observations made by its means would have the advantages of impartiality, multitude, and permanence. Peculiarities of vision and bias of judgment would be eliminated, the slow progress of the phenomenon would permit an indefinite number of pictures to be taken, their epochs fixed to a fraction of a second. While subsequent leisurely comparison and measurement could hardly fail, it was thought, to educe approximate truth from the mass of accumulated evidence. The use of the heliometer, much relied on by German observers, was so far similar to that of the camera that the object aimed at by both was the determination of the relative positions of the centers of the Sun and Venus viewed at the same absolute instant, from opposite sides of the globe. So that the principle of the two older methods was to ascertain the exact times of meeting between the solar and planetary limbs. That of the two modern to determine the position of the dark body already thrown into complete relief by its shining background. The former are methods by contact, the latter methods by projection. Every country which had a reputation to keep or to gain for scientific zeal was forward to cooperate in the great cosmopolitan enterprise of the transit. France and Germany each sent out 6 expeditions. 26 stations were in Russian, 12 in English, 8 in American, 3 in Italian, 1 in Dutch occupation. In all, at a cost of nearly $250,000, some 40 distinct posts of observation were provided. Among them such inhospitable, and all but inaccessible rocks in the bleak Southern Ocean, as St. Paul's and Campbell Islands, swept by hurricanes, and fitted only for the habitation of seabirds, where the daring votaries of science, in the wise provision of a long leaguer by the elements, were supplied with stores for many months, or even a whole year. Siberia and the Sandwich Islands were thickly beset with observers. Parties of 3 nationalities encamped within the mists of Kerguelen Island, expressively termed the Land of Desolation, in the sanguine, though not wholly frustrated hope of a glimpse of the sun at the right moment. M. Jansen narrowly escaped destruction from a typhoon in the China Seas on his way to Nagasaki. Lord Lindsay, now Earl of Crawford and Bucharest, equipped, at his private expense, an expedition to Mauritius, which was in itself an epitome of modern resource and ingenuity. During several years, the practical methods best suited to ensure success for the impending enterprise formed a subject of European debate. Official commissions were appointed to receive and decide upon evidence. And experiments were in progress for the purpose of defining the actual circumstances of contacts, the precise determination of which constituted the only tried, though by no means an assuredly safe road to the end in view. In England, America, France, and Germany, artificial transits were mounted. And the members of the various expeditions were carefully trained to unanimity in estimating the phases of junction and separation between a moving dark circular body and a broad illuminated disk. In the previous century, a formidable and prevalent phenomenon, which acquired notoriety as the black drop or black ligament, had swamped all pretensions to rigid accuracy. It may be described as substituting adhesion for contact, the limbs of the sun and planet, instead of meeting and parting with the desirable clean definiteness, clinging together as if made of some glutinous material, and prolonging their connection by means of a dark band or dark threads stretched between them. Some astronomers ascribed this baffling appearance entirely to instrumental imperfections, others to atmospheric agitation, others again to the optical encroachment of light upon darkness known as irradiation. It is probable that all these causes conspired, in various measure, to produce it, and it is certain that its conspicuous appearance may, by suitable precautions, be obviated. The organization of the British forces reflected the utmost credit on the energy and ability of Lieutenant Colonel Tupman, who was responsible for the whole. No useful measure was neglected. Each observer went out ticketed with his personal equation, his senses drilled into a species of martial discipline, his powers absorbed, so far as possible, in the action of a cosmopolitan observing machine. Instrumental uniformity and uniformity of method were obtainable, and were attained, but diversity of judgment unhappily survived the best directed efforts for its extirpation. The eventful day had no sooner passed than telegrams began to pour in, announcing an outcome of considerable, though not unqualified success. The weather had proved generally favorable, the manifold arrangements had worked well. Contacts had been plentifully observed, photographs in lavish abundance had been secured, a store of materials, in short, had been laid up, of which it would take years to work out the full results by calculation. Gradually, nevertheless, it came to be known that the hope of a definitive issue must be abandoned. Unanimity was found to be as remote as ever. The dreaded black ligament gave, indeed, less trouble than was expected. But another appearance supervened which took most observers by surprise. This was the illumination due to the atmosphere of Venus. Astronomers, it is true, were not ignorant that the planet had, on previous occasions, been seen girdled with a lucid ring, but its power to mar observations by the distorting effect of refraction had scarcely been reckoned with. It proved, however, to be very great. Such was the difficulty of determining the critical instant of internal contact, that, in Colonel Tupman's words, observers side by side, with adequate optical means, differed as much as 20 or 30 seconds in the times they recorded for phenomena which they have described in almost identical language. Such uncertainties in the data admitted of a corresponding variety in the results. From the British observations of ingress and egress Sir George Airy derived, in 1877, a solar parallax of 876, corrected to 8754, indicating a mean distance of 93,375,000 miles. Mr. Stone obtained a value of 92 millions, parallax 888, and held any parallax less than 884 or more than 893 to be absolutely negatived by the documents available. Yet, from the same, Colonel Tupman deduced 881, implying a distance 700,000 miles greater than Stone had obtained. The best French observations of contacts gave a parallax of about 888. French micrometric measures the obviously exaggerated one of 905. Photography, as practiced by most of the European parties, was a total failure. Utterly discrepant values of the microscopic displacements designed to serve as sounding lines for the solar system, issued from attempts to measure even the most promising pictures. "You might as well try to measure the zodiacal light," it was remarked to Sir George Airy. Those taken on the American plan of using telescopes of so great focal length as to afford, without further enlargement, an image of the requisite size, gave notably better results. From an elaborate comparison of those dating from Vladivostok, Nagasaki, and Pekin, with others from Kerguelen and Chatham Islands, Professor D.P. Todd, of Amherst College, deduced a solar distance of about 92 million miles, parallax 8,883 plus or minus 0034, and the value was much favored by concurrent evidence. On the whole, estimates of the great spatial unit cannot be said to have gained any security from the combined effort of 1874. A few months before the transit, Mr. Proctor considered that the uncertainty then amounted to 1,448,000 miles. 5 years after the transit, Professor Harkness judged it to be still 1,575,950 miles, yet it had been hoped that it would have been brought down to 100,000. As regards the end for which it had been undertaken, the grand campaign had come to nothing. Nevertheless, no sign of discouragement was apparent. There was a change of view, but no relaxation of purpose. The problem, it was seen, could be solved by no single heroic effort, but by the patient approximation of gradual improvements. Astronomers, accordingly, looked round for fresh means or more refined expedients for applying those already known. A new phase of exertion was entered upon. On September 5, 1877, Mars came into opposition near the part of his orbit which lies nearest to that of the Earth, and Dr. Gill, now Sir David, took advantage of the circumstance to appeal once more to him for a decision on the quaestio vexata of the Sun's distance. He chose, as the scene of his labors, the island of Ascension, and for their plan a method recommended by Airy in 1857, but never before fairly tried. This is known as the diurnal method of parallaxes. Its principle consists in substituting successive morning and evening observations from the same spot, for simultaneous observations from remote spots, the rotation of the Earth supplying the necessary difference in the points of view. Its great advantage is that of unity in performance. A single mind, looking through the same pair of eyes, reinforced with the same optical appliances, is employed throughout, and the errors inseparable from the combination of data collected under different conditions are avoided. There are many cases in which one man can do the work of two better than two men can do the work of one. The result of Gill's skillful determinations, made with Lord Lindsay's heliometer, was a solar parallax of 878, corresponding to a distance of 93,080,000 miles. The bestowal of the Royal Astronomical Society's gold medal stamped the merit of this distinguished service. But there are other subjects for this kind of inquiry besides Mars and Venus. Professor Gall of Breslau suggested in 1872 that some of the minor planets might be got to repay astronomers for much disinterested toil spent in unraveling their motions, by lending aid to their efforts towards a correct celestial survey. 10 or 12 come near enough, and are bright enough for the purpose. In fact, the absence of sensible magnitude is one of their chief recommendations, since a point of light offers far greater facilities for exact measurement than a disk. The first attempt to work this new vein was made at the opposition of Phocea in 1872, and from observations of Flora in the following year at 12 observatories in the northern and southern hemispheres, Gall deduced a solar parallax of 887. At Mauritius in 1874, Lord Lindsay and Sir David Gill applied the diurnal method to Juno, then conveniently situated for the purpose. And the continued use of similar occasions affords an unexceptionable means for improving knowledge of the Sun's distance. They frequently recur, they need no elaborate preparation. A single astronomer armed with a heliometer can do all the requisite work. Dr. Gill, however, organized a more complex plan of operations upon Iris in 1888, and upon Victoria and Sappho in 1889. A novel method was adopted. Its object was to secure simultaneous observations made from opposite sides of the globe just when the planet lay in the plane passing through the center of the Earth and the two observers. The same pair of reference stars being used on each occasion. The displacements caused by parallax were thus in a sense doubled, since the star to which the planet seemed approximated in the northern hemisphere, showed as if slightly removed from it in the southern, and vice versa. As the planet pursued its course, fresh star couples came into play, during the weeks that the favorable period lasted. In these determinations, only heliometers were employed. Dr. Elkin, of Yale College, cooperated throughout, and the heliometers of Dresden, Göttingen, Bamberg, and Leipzig, shared in the work, while Dr. Ors of Berlin was Sir David Gill's personal coadjutor at the Cape. Voluminous data were collected. Meridian observations of the stars of reference for Victoria occupied 21 establishments during 4 months, the direct work of triangulation kept 4 heliometers in almost exclusive use for the best part of a year. And the ensuing toilsome computations, carried out during 3 years at the Cape Observatory, filled 2 bulky tomes with their details. Gill's final result, published in 1897, was a parallax of 8802, equivalent to a solar distance of 92,874,000. And it was qualified by a probable error so small that the value might well have been accepted as definitive but for an unlooked-for discovery. The minor planet Eros, detected August 14, 1898, was found to pursue a course rendering it an almost ideal intermediary in solar parallax determinations. Once in 30 years, it comes within 15 million miles of the Earth. And although the next of these choice epochs must be awaited for some decades, an opposition too favorable to be neglected occurred in 1900. At an international conference, accordingly, held at Paris in July of that year, a plan of photographic operations was concerted between the representatives of no less than 58 observatories. Its primary object was to secure a large stock of negatives showing the planet with the comparison stars along the route traversed by it from October, 1900, to March, 1901, and this at least was successfully attained. Their measurement will in due time educe the apparent displacements of the moving object as viewed simultaneously from remote parts of the Earth. And the upshot should be a solar parallax adequate in accuracy to the exigent demands of the 20th century. The second of the 19th century pair of Venus transits was looked forward to with much abated enthusiasm. Russia refused her active cooperation in observing it, on the ground that oppositions of the minor planets were trigonometrically more useful, and financially far less costly, and her example was followed by Austria. While Italian astronomers limited their sphere of action to their own peninsula. Nevertheless, it was generally held that a phenomenon which the world could not again witness until it was 4 generations older should, at the price of any effort, not be allowed to pass in neglect. The persuasion of its importance justified the summoning of an international conference at Paris in 1881, from which, however, America, preferring independent action, held aloof. It was decided to give Delisle's method another trial. And the ambiguities attending and marring its use were sought to be obviated by careful regulations for ensuring agreement in the estimation of the critical moments of ingress and egress. But in fact, as M. Puiseux had shown, contacts between the limbs of the Sun and planet, so far from possessing the geometrical simplicity attributed to them, are really made up of a prolonged succession of various and varying phases. Impossible either to predict or identify with anything like rigid exactitude. Sir Robert Ball compared the task of determining the precise instant of their meeting or parting, to that of telling the hour with accuracy on a watch without a minute hand, and the comparison is admittedly inadequate. For not only is the apparent movement of Venus across the Sun extremely slow, being but the excess of her real motion over that of the Earth. But 3 distinct atmospheres, the solar, terrestrial, and Cytherean, combine to deform outlines and mask the geometrical relations which it is desired to connect with a strict count of time. The result was very much what had been expected. The arrangements were excellent, and were only in a few cases disconcerted by bad weather. The British parties, under the experienced guidance of Mr. Stone, the late Radcliffe observer, took up positions scattered over the globe. From Queensland to Bermuda, the Americans collected a whole library of photographs, the Germans and Belgians trusted to the heliometer. The French used the camera as an adjunct to the method of contacts. Yet little or no approach was made to solving the problem. Thus, from 606 measures of Venus on the Sun, taken with a new kind of heliometer at Santiago in Chile, M. Houzeau, of the Brussels Observatory, derived a solar parallax of 8.907, and a distance of 91,727,000 miles. But the probable errors of this determination amounted to 0.084 either way. It was subject to a more or less of 900,000, or to a total uncertainty of 1,800,000 miles. The probable error of the English result, published in 1887, was less formidable, yet the details of the discussion showed that no great confidence could be placed in it. The Sun's distance came out 92,560,000 miles. While 92,360,000 was given by Professor Harkness's investigation of 1,475 American photographs. Finally, Dr. Oers deduced from the German heliometric measures the unsatisfactorily small value of 92 million miles. The transit of 1882 had not, then, brought about the desired unanimity. The state and progress of knowledge on this important topic were summed up by Faye and Harkness in 1881. The methods employed in its investigation fall, as we have seen, into three separate classes: the trigonometrical, the gravitational, and the phototachymetrical, an ungainly adjective used to describe the method by the velocity of light. Each has its special difficulties and sources of error, each has counterbalancing advantages. The only trustworthy result from celestial surveys was at that time furnished by Gill's observations of Mars in 1877. But the method by lunar and planetary disturbances is unlike all the others in having time on its side. It is this which Leverrier declared with emphasis must inevitably prevail, because its accuracy is continually growing. The scarcely perceptible errors which still impede its application are of such a nature as to accumulate year by year. Eventually, then, they will challenge, and must receive, a more and more perfect correction. The light velocity method, however, claimed, and for some years justified, M. Faye's preference. By a beautiful series of experiments on Foucault's principle, Michelson fixed in 1879 the rate of luminous transmission at 299,930, corrected later to 299,910 kilometers a second. This determination was held by Professor Todd to be entitled to 4 times as much confidence as any previous one. And if the solar parallax of 8,758 deduced from it by Professor Harkness errs somewhat by defect, it is doubtless because Glasenapp's light equation, with which it was combined, errs slightly by excess. But all earlier efforts of the kind were thrown into the shade by Professor Newcomb's arduous operations at Washington in 1880 to 1882. The scale upon which they were conducted was in itself impressive. Foucault's entire apparatus in 1862 had been enclosed in a single room. Newcomb's revolving and fixed mirrors, between which the rays of light were to run their timed course, were set up on opposite shores of the Potomac, at a distance of nearly 4 kilometers. This advantage was turned to the utmost account by ingenuity and skill in contrivance and execution. And the deduced velocity of 299,860 kilometers equals 186,328 miles a second, had an estimated error, 30 kilometers, only 1/10 that ascribed by Cornu to his own result in 1874. Just as these experiments were concluded in 1882, M. Magnus Nyren, of St. Petersburg, published an elaborate investigation of the small annular displacements of the stars due to the successive transmission of light, involving an increase of Struve's constant of aberration, from 2445 to 2492. And from the new value, combined with Newcomb's light velocity, was derived a valuable approximation to the Sun's distance, concluded at 92,905,021 miles, parallax equals 8,794. Yet it is not quite certain that Nyren's correction was an improvement. A differential method of determining the amount of aberration, struck out by M. Loewy of Paris, avoids most of the objections to the absolute method previously in vogue. And the upshot of its application in 1891 was to show that Struve's constant might better be retained than altered, Loewy's of 2447 varying from it only to an insignificant extent. Professor Hall had, moreover, deduced nearly the same value, 2454, from the Washington observations since 1862, of Alpha Lyrae, Vega, whence, in conjunction with Newcomb's rate of light transmission, he arrived at a solar parallax of 881. Inverting the process, Sir David Gill in 1897 derived the constant from the parallax. If the Earth's orbit have a mean radius, as found by him, of 92,874,000 miles, then, he calculated, the aberration of light, Newcomb's measures of its velocity being supposed exact, amounts to 20.467. This figure can need very slight correction. Professor Harkness surveyed in 1891, from an eclectic point of view, the general situation as regarded the Sun's parallax. Convinced that no single method deserved an exclusive preference, he reached a plausible result through the combination, on the principle of least squares, that is, by the mathematical rules of probability, of all the various quantities upon which the great datum depends. It thus summed up and harmonized the whole of the multifarious evidence bearing upon the point, and, as modified in 1894, falls very satisfactorily into line with the Cape determination. We may, then, at least provisionally, accept 92,870,000 miles as the length of our measuring rod for space. Nor do we hazard much in fixing 100,000 miles as the outside limit of its future correction. Footnotes. Airy, Month. Not, Volume 17, p. 210. Mars comes into opposition once in about 780 days, but owing to the eccentricity of both orbits, his distance from the Earth at those epochs varies from 35 to 62 million miles. J. D. Cassini, Hist. Abrégé de la Parallaxe du Soleil, page 122, 1772. The present period of coupled eccentric transits will, in the course of ages, be succeeded by a period of single, nearly central transits. The alignments by which transits are produced, of the Earth, Venus, and the Sun, close to the place of intersection of the two planetary orbits, now occur, the first a little in front of, the second, after 8 years less 2.5 days. A little behind the node. But when the first of these two meetings takes place very near the node, giving a nearly central transit, the second falls too far from it, and the planet escapes projection on the Sun. The reason of the liability to an 8-yearly recurrence is that 8 revolutions of the Earth are accomplished in only a very little more time than 13 revolutions of Venus. Die Entfernung der Sonne, Fortsetzung, page 108. Encke slightly corrected his results of 1824 in Berlin ABH, 1835, page 295. Owing to the ellipticity of its orbit, the Earth is nearer to the Sun in January than in June by 3,100,000 miles. The quantity to be determined, or mean distance, is that lying midway between these extremes, is, in other words, half the major axis of the ellipse in which the Earth travels. Month. Not, Volume 15, page 9. The distance of the Sun from the Earth determined by the theory of gravity, Edinburgh, 1763. Opera, T. 3, page 326. Comptes rendus, T. 46, page 882. The parallax 895 derived by Leverrier from the above described inequality in the Earth's motion, was corrected by Stone to 891. Month. Not, Volume 28, page 25. Month. Not, Volume 35, page 156. Washington OBS, 1865, App. 2, page 28. Comptes rendus, T. 29, page 90. Ibid, T. XXX, page 551. Ibid, T. LV, page 501. The previously admitted velocity was 308 million meters per second, Foucault reduced it to 298 million. Combined with Struve's constant of aberration, this gave 8.86 for the solar parallax, which exactly agreed with Cornu's result from a repetition of Foucault's experiments in 1872. Comptes Rendus, T. 76, page 338. Month. Not, Volume 24, page 103. Astre. Papers of the American Ephemeris, Volume 2, page 263. Month. Not, Volume 17, page 208. Because closely similar to that proposed by him in Phil. Trans for 1716. Month. Not, Volume 38, page 447. Ibid, page 11. Ibid, page 294. Ibid, page 334. Comptes Rendus, T. 92, page 812. Observatory, Volume 5, p. 205. Transits of Venus, page 89, first edition. A.M. Jour of SC, Volume 20, page 393. Month. Not, Volume 17, page 219. MEM. Roy. Astre. SOC, Volume 46, page 163. Astre. Nock, number 1897. Hilfiger, Bern Mittheilungen, 1878, page 109. Annals of the Cape Observatory, Volume 6, 7. Rapport sur l'état de l'Observatoire de Paris pour l'année 1900, page 7. Observatory, Volume 23, page 311, Newcomb, Astre. Jour, number 480. Comptes Rendus, T. 93, page 569. Ibid, T. 92, page 481. Bull. De l'Académique, T. 6, page 842. Month. Not, Volume 48, page 201. Astre. Jour, number 182. Astre. Nock, number 3066. Comptes Rendus, T. 92, page 375, A.M. Jour of SC, Volume 22, page 375. Month. Not, Volume 35, page 401. A.M. Jour of SC, Volume 18, p. 393. Nature, Volume 34, page 170, Astron, Papers of the American Ephemeris, Volume 2, page 113. Comptes Rendus, T. XIII, page 549. Astre. Journ, numbers 169, 170. The Solar Parallax and its Related Constants, Washington, 1891. Astre. An Astrophysics, Volume 13, page 626. Chapter 7. Planets and Satellites. Johann Hieronymus Schroeder was the Herschel of Germany. He did not, it is true, possess the more brilliant gifts of his rival. Herschel's piercing discernment, comprehensive intelligence, and inventive splendor were wanting to him. He was, nevertheless, the founder of descriptive astronomy in Germany, as Herschel was in England. Born at Erfurt in 1745, he prosecuted legal studies at Göttingen, and there imbibed from Kastner a lifelong devotion to science. From the law, however, he got the means of living, and, what was to the full as precious to him, the means of observing. Entering the sphere of Hanoverian officialism in 1788, he settled a few years later at Lilienthal, near Bremen, as Oberamtmann, or chief magistrate. Here he built a small observatory, enriched in 1785 with a 7-foot reflector by Herschel, then one of the most powerful instruments to be found anywhere out of England. It was soon surpassed, through his exertions, by the first fruits of native industry in that branch. Schrader of Kiel transferred his workshops to Lilienthal in 1792, and constructed there, under the superintendence and at the cost of the astronomical Oberamtmann, a 13-foot reflector. Declared by Lalande to be the finest telescope in existence, and 127 feet in focal length, probably as inferior to its predecessor in real efficiency as it was superior in size. Thus, with instruments of gradually increasing power, Schroeder studied during 34 years the topography of the Moon and planets. The field was then almost untrodden. He had but few and casual predecessors, and has since had no equal in the sustained and concentrated patience of his hourly watchings. Both their prolixity and their enthusiasm are faithfully reflected in his various treatises. Yet the one may be pardoned for the sake of the other, especially when it is remembered that he struck out a substantially new line, and that one of the main lines of future advance. Moreover, his infectious zeal communicated itself. He set the example of observing when there was scarcely an observer in Germany, and under his roof Harding and Bessel received their training as practical astronomers. But he was reserved to see evil days. Early in 1813 the French under Vandamme occupied Bremen. On the night of April 20th, the Vale of Lilies was, by their wanton destructiveness, laid waste with fire. The government offices were destroyed, and with them the chief part of Schroeder's property, including the whole stock of his books and writings. There was worse behind. A few days later, his observatory, which had escaped the conflagration, was broken into, pillaged, and ruined. His life was wrecked with it. He survived the catastrophe 3 years without the means to repair, or the power to forget it, and gradually sank from disappointment into decay, terminated by death, August 29, 1816. He had, indeed, done all the work he was capable of. And though not of the first quality, it was far from contemptible. He laid the foundation of the comparative study of the Moon's surface. And the descriptive particulars of the planets laboriously collected by him constituted a store of more or less reliable information hardly added to during the ensuing half-century. They rested, it is true, under some shadow of doubt. But the most recent observations have tended on several points to rehabilitate the discredited authority of the Lilienthal astronomer. We may now briefly resume, and pursue in its further progress, the course of his studies, taking the planets in the order of their distances from the Sun. In April, 1792, Schroeder saw reason to conclude, from the gradual degradation of light on its partially illuminated disk, that Mercury possesses a tolerably dense atmosphere. During the transit of May 7, 1799, he was, moreover, struck with the appearance of a ring of softened luminosity encircling the planet to an apparent height of 3 seconds, or about a quarter of its own diameter. Although a mere thought, in texture, it remained persistently visible both with the 7-foot and the 13-foot reflectors, armed with powers up to 288. It had a well-marked grayish boundary, and reminded him, though indefinitely fainter, of the penumbra of a sunspot. A similar appendage had been noticed by de Plantade at Montpellier, November 11, 1736, and again in 1786 and 1789 by Prosperin and Flaugerx. But Herschel, on November 9, 1802, saw the preceding limb of the planet projected on the Sun cut the luminous solar clouds with the most perfect sharpness. The presence, however, of a halo was unmistakable in 1832, when Professor Moll, of Utrecht, described it as a nebulous ring of a darker tinge approaching to the violet color. Again, to Huggins and Stone, November 5, 1868, it showed as lucid and most distinct. No change in the color of the glasses used, or the powers applied, could get rid of it, and it lasted throughout the transit. It was next seen by Christie and Duncan at Greenwich, May 6, 1878, and with much precision of detail by Trouvelot at Cambridge, U.S. Professor Holden, on the other hand, noted at Hastings-on-Hudson the total absence of all anomalous appearances. Nor could any vestige of them be perceived by Barnard at Lick on November 10, 1894. Various effects of irradiation and diffraction were, however, observed by Lowell and W. H. Pickering at Flagstaff. And Davidson was favored at San Francisco with glimpses of the historic aureola, as well as of a central whitish spot, which often accompanies it. That both are somehow of optical production can scarcely be doubted. Nothing can be learned from them regarding the planet's physical condition. Airy showed that refraction in a Mercurian atmosphere could not possibly originate the noted aureola, which must accordingly be set down as strictly an ocular nervous phenomenon. It is the less easy to escape from this conclusion that we find the virtually airless moon capable of exhibiting a like appendage. Professor Stephen Alexander, of the United States Survey, with 2 other observers, perceived, during the eclipse of the Sun of July 18, 1860, the advancing lunar limb to be bordered with a bright band. And photographic effects of the same kind appear in pictures of transits of Venus and partial solar eclipses. The spectroscope affords little information as to the constitution of Mercury. Its light is of course that of the Sun reflected, and its spectrum is consequently a faint echo of the Fraunhofer spectrum. Dr. H.C. Vogel, who first examined it in April, 1871, suspected traces of the action of an atmosphere like ours, but, it would seem, on slight grounds. It is, however, certainly very poor in blue rays. More definite conclusions were, in 1874, derived by Zollner from photometric observations of Mercurian phases. A similar study of the waxing and waning moon had afforded him the curious discovery that light changes dependent upon phase vary with the nature of the reflecting surface. Following a totally different law on a smooth homogeneous globe and on a rugged and mountainous one. Now the phases of Mercury, so far as could be determined from only 2 sets of observations, correspond with the latter kind of structure. Strictly analogous to those of the moon, they seem to indicate an analogous mode of surface formation. This conclusion was fully borne out by Müller's more extended observations at Potsdam during the years 1885 to 1893. Practical assurance was gained from them that the innermost planet has a rough rind of dusky rock, absorbing all but 17% of the light poured upon it by the fierce adjacent sun. Its albedo, in other words, is 0.17, which is precisely that ascribed to the moon. The absence of any appreciable Mercurian atmosphere followed almost necessarily from these results. On March 26, 1800, Schroeder, observing with his 13-foot reflector in a peculiarly clear sky, perceived the southern horn of Mercury's crescent to be quite distinctly blunted. Interception of sunlight by a Mercurian mountain rather more than 11 English miles high explained the effect to his satisfaction. By carefully timing its recurrence, he concluded rotation on an axis in a period of 24 hours 4 minutes. The first determination of the kind rewarded 20 years of unceasing vigilance. It received ostensible confirmation from the successive appearances of a dusky streak and blotch in May and June, 1801. These, however, were inferred to be no permanent markings on the body of the planet, but atmospheric formations, the streak at times drifting forwards, it was thought, under the fluctuating influence of Mercurian breezes. From a rediscussion of these somewhat doubtful observations Bessel inferred that Mercury rotates on an axis inclined 70 degrees to the plane of its orbit in 24 hours 53 seconds. The rounded appearance of the southern horn seen by Schroeder was more or less doubtfully caught by Noble, 1864, Burton, and Franks, 1877, but was obvious to Mr. W. F. Denning at Bristol on the morning of November 5, 1882. That the southern polar regions are usually less bright than the northern is well ascertained, but the cause of the deficiency remains dubious. If inequalities of surface are in question, they must be on a considerable scale. And a similar explanation might be given of the deformations of the terminator, or dividing line between darkness and light in the planet's phases, first remarked by Schroeder, and again clearly seen by Trouvelot in 1878 and 1881. The displacement, during 4 days, of certain brilliant and dusky spaces on the disk indicated to Mr. Denning in 1882 rotation in about 25 hours, while the general aspect of the planet reminded him of that of Mars. But the difficulties in the way of its observation are enormously enhanced by its constant close attendance on the Sun. In his sustained study of the features of Mercury, Schroeder had no imitator until Schiaparelli took up the task at Milan in 1882. His observations were made in daylight. It was found that much more could be seen, and higher magnifying powers used, high up in the sky near the sun, than at low altitudes, through the agitated air of morning or evening twilight. A notable discovery ensued. Following the planet hour by hour, instead of making necessarily brief inspections at intervals of about a day, as previous observers had done, it was found that the markings faintly visible remained sensibly fixed, hence that there was no rotation in a period at all comparable with that of the Earth. And after long and patient watching, the conclusion was at last reached that Mercury turns on his axis in the same time needed to complete a revolution in his orbit. One of his hemispheres, then, is always averted from the Sun, as one of the Moon's hemispheres from the Earth, while the other never shifts from beneath his torrid rays. The librations, however, of Mercury are on a larger scale than those of the Moon, because he travels in a more eccentric path. The temporary inequalities arising between his even pacing on an axis and his alternately accelerated and retarded elliptical movement occasion, in fact, an oscillation to and fro of the boundaries of light and darkness on his globe over an arc of 47 degrees 22, in the course of his year of 88 days. Thus the regions of perpetual day and perpetual night are separated by two segments, amounting to 1/4 of the entire surface, where the sun rises and sets once in 88 days. Else there is no variation from the intense glare on one side of the globe, and the nocturnal blackness on the other. To Schiaparelli's scrutiny, Mercury appeared as a spotty globe, enveloped in a tolerably dense atmosphere. The brownish stripes and streaks, discerned on his rose-tinged disk, and judged to be permanent, were made the basis of a chart. They were not indeed always equally well seen. They disappeared regularly near the limb, and were at times veiled even when centrally situated. Some of them had been clearly perceived by de Ball at Bothkamp in 1882. Mr. Lowell followed Schiaparelli's example by observing Mercury in the full glare of noon. The best time to study him, he remarked, is when planetary almanacs state Mercury invisible. A remarkable series of drawings executed, some at Flagstaff in 1896, the remainder at Mexico in 1897, supplied grounds for the following, among other, conclusions. Mercury rotates synchronously with its revolution, that is, once in 88 days, on an axis sensibly perpendicular to its orbital plane. No certain signs of a Mercurian atmosphere are visible. The globe is seamed and furrowed with long narrow markings, explicable as cracks in cooling. It is, and always was, a dead world. From micrometrical measures, moreover, the inferences were drawn that the planet's mass has a probable value about 1/20th that of the Earth, while its mean density falls considerably short of the terrestrial standard. The theory of Mercury's movements has always given trouble. In Lalande's, as in Maslin's time, the planet seemed to exist for no other purpose than to throw discredit on astronomers. And even to Leverrier's powerful analysis it long proved recalcitrant. On the 12th of September, 1869, however, he was able to announce before the Academy of Sciences the terms of a compromise between observation and calculation. They involved the addition of a new member to the solar system. The hitherto unrecognized presence of a body about the size of Mercury itself revolving at somewhat less than half its mean distance from the Sun, or, if farther, then of less mass, and vice versa, would, it was pointed out, produce exactly the effect required, of displacing the perihelion of the former planet 38 a century more than could otherwise be accounted for. The planes of the two orbits, however, should not lie far apart, as otherwise a nodal disturbance would arise not perceived to exist. It was added that a ring of asteroids similarly placed would answer the purpose equally well, and was more likely to have escaped notice. Upon the heels of this forecast followed promptly a seeming verification. Dr. Lescarbault, a physician residing at Orgeries, whose slender opportunities had not blunted his hopes of achievement, had, ever since 1845, when he witnessed a transit of Mercury, cherished the idea that an unknown planet might be caught thus projected on the solar background. Unable to observe continuously until 1858, he, on March 26, 1859, saw what he had expected, a small perfectly round object slowly traversing the Sun's disk. The fruitless expectation of re-observing the phenomenon, however, kept him silent, and it was not until December 22, after the news of Leverrier's prediction had reached him, that he wrote to acquaint him with his supposed discovery. The imperial astronomer thereupon hurried down to Orgeries, and by personal inspection of the simple apparatus used, by searching cross-examination and local inquiry, convinced himself of the genuine character and substantial accuracy of the reported observation. He named the new planet Vulcan, and computed elements giving it a period of revolution slightly under 20 days. But it has never since been seen. M. Liais, director of the Brazilian Coast Survey, thought himself justified in asserting that it never had been seen. Observing the sun for 12 minutes after the supposed ingress recorded at Orgeries, he noted those particular regions of its surface as trace uniforms d'intensite. He subsequently, however, admitted Lescarbault's good faith, at first rashly questioned. The planet-seeking doctor was, in truth, only one among many victims of similar illusions. Waning interest in the subject was revived by a fresh announcement of a transit witnessed, it was asserted, by Weber at Pecolo, April 4, 1876. The pseudo-planet, indeed, was detected shortly afterwards on the Greenwich photographs, and was found to have been seen by M. Ventosa at Madrid in its true character of a sunspot without penumbra. But Leverrier had meantime undertaken the investigation of a list of 20 similar dubious appearances, collected by Hasse, and republished by Wolf in 1872. From these, 5 were picked out as referring in all likelihood to the same body, the reality of whose existence was now confidently asserted, and of which more or less probable transits were fixed for March 22, 1877, and October 15, 1882. But, widespread watchfulness notwithstanding, no suspicious object came into view at either epoch. The next announcement of the discovery of Vulcan was on the occasion of the total solar eclipse of July 29, 1878. This time it was stated to have been seen at some distance southwest of the obscured sun, as a ruddy star with a minute planetary disk, and its simultaneous detection by 2 observers, the late Professor James C. Watson, stationed at Rawlins, Wyoming Territory, and Professor Lewis Swift at Denver, Colorado, was at first readily admitted. But their separate observations could, on a closer examination, by no possibility be brought into harmony, and, if valid, certainly referred to 2 distinct objects, if not to 4, each astronomer eventually claiming a pair of planets. Nor could any one of the 4 be identified with Lescarbault's and Leverrier's Vulcan, which, if a substantial body revolving round the sun, must then have been found on the east side of that luminary. The most feasible explanation of the puzzle seems to be that Watson and Swift merely saw each the same 2 stars in Cancer, haste and excitement doing the rest. Nevertheless, they strenuously maintained their opposite conviction. Intramercurian planets have since been diligently searched for when the opportunity of a total eclipse offered, especially during the long obscuration at Caroline Island. Not only did Professor Holden sweep in the solar vicinity, but Palisa and Trouvelot agreed to divide the field of exploration, and thus make sure of whatever planetary prey there might be within reach, yet with only negative results. Photographic explorations during recent eclipses have been equally fruitless. Belief in the presence of any considerable body or bodies within the orbit of Mercury is, accordingly, at a low ebb. Yet the existence of the anomaly in the Mercurian movements indicated by Leverrier has been made only surer by further research. Its elucidation constitutes one of the pending problems of astronomy. From the observation at Bologna in 1666–67 of some very faint spots, Domenico Cassini concluded a rotation or libration of Venus, he was not sure which, in about 23 hours. By Bianchini in 1726 the period was augmented to 24 days 8 hours. J. Cassini, however, in 1740, showed that the data collected by both observers were consistent with rotation in 23 hours 20 minutes. So the matter rested until Schroeder's time. After watching 9 years in vain, he at last, February 28, 1788, perceived the ordinarily uniform brightness of the planet's disk to be marbled with a filmy streak. which returned periodically to the same position in about 23 hours 28 minutes. This approximate estimate was corrected by the application of a more definite criterion. On December 28, 1789, the southern horn of the crescent Venus was seen truncated, an outlying lucid point interrupting the darkness beyond. Precisely the same appearance recurred 2 years later, giving for the planet's rotation a period of 23h. 21 m. To this only 22 seconds were added by de Vico, as the result of over 10,000 observations made with the Cauchois refractor of the Collegio Romano, 1839–41. The axis of rotation was found to be much more bowed towards the orbital plane than that of the Earth, the equator making with it an angle of 53 degrees 11. These conclusions inspired, it is true, much distrust, consequently there were no received ideas on the subject to be subverted. Nevertheless, a shock of surprise was felt at Schiaparelli's announcement, early in 1890, that Venus most probably rotates after the fashion just previously ascribed to Mercury. A continuous series of observations, from November, 1877, to February, 1878, with their records in above 100 drawings, supplied the chief part of the data upon which he rested his conclusions. They certainly appeared exceptionally well grounded, and the doubts at first qualifying them were removed by a fresh set of determinations in July, 1895. Most observers had depended, in their attempts to ascertain the rotation period of Venus, upon evanescent shadings, most likely of atmospheric origin, and scarcely recognizable from day to day. Schiaparelli fixed his attention upon round, defined, lustrously white spots, the presence of which near the cusps of the illuminated crescent has been attested for close upon 2 centuries. His steady watch over them showed the invariability of their position with regard to the terminator, and this is as much as to say that the regions of day and night do not shift on the surface of the planet. In other words, she keeps the same face always turned towards the sun. Moreover, since her orbit is nearly circular, libratory effects are very small. They amount in fact to only just 1/30th of those serving to modify the severe contrasts of climate in Mercury. Confirmatory evidence of Schiaparelli's result for Venus is not wanting. Thus, observations irreconcilable with a swift rate of rotation were made at Bothkamp in 1871 by Vogel and Losey. And the drawing executed by Professor Holden with the Great Washington Reflector, December 15, 1877, showed the same markings in the positions recorded at Milan to have been occupied by them 8 hours previously. Further, a series of observations, carried out by M. Perrotin at Nice, May 15 to October 4, 1890, and from Mount Mounier in 1895–6, with the special aim of testing the inference of synchronous rotation and revolution, proved strongly corroborative of it. A remarkable collection of drawings made by Mr. Lowell in 1896 appeared decisive in its favor, Tacchini at Rome, Mascari at Catania and Etna, Cerulli at Turano, obtained in 1892–6 evidence similar in purport. On the other hand, Neeson of Brussels found reason to revert to Vico's discarded elements for the planet's rotation. And Trouvelot, Stanley Williams, Villager, and Leo Brenner, so far agreed with him as to adopt a period of approximately 24 hours. Finally, E. von Apolzer suggested an appeal to the spectroscope. And Belopolsky secured in 1900 spectrograms apparently marked by the minute displacements corresponding to a rapid rate of axial movement. But they were avowedly taken only as an experiment, with unsuitable apparatus. And the desirable verification of their supposed import is not yet forthcoming. Until it is, Schiaparelli's period of 225 days must be allowed to hold the field. Effects attributed to great differences of level in the surface of Venus have struck many observers. Francesco Fontana at Naples in 1643 noticed irregularities along the inner edge of the crescent. Lahire in 1700 considered them, regard being had to difference of distance, to be much more strongly marked than those visible in the moon. Schroeder's assertions to the same effect, though scouted with some unnecessary vehemence by Herschel, have since been repeatedly confirmed. Amongst others by Madler, de Vico, Langdon, who in 1873 saw the broken line of the terminator with peculiar distinctness through a veil of auroral cloud, by Denning, March 30, 1881, despite preliminary impressions to the contrary, as well as by C. V. Zenger at Prague, January 8, 1883. The great mountain mass, presumed to occasion the periodical blunting of the southern horn, was precariously estimated by the Lilienthal observer to rise to the prodigious height of nearly 27 miles. Or just 5 times the elevation of Mount Everest. Yet the phenomenon persists, whatever may be thought of the explanation. Moreover, the speck of light beyond, interpreted as the visible sign of a detached peak rising high enough above the encircling shadow to catch the first and last rays of the sun, was frequently discerned by Baron van Ertborn in 1876. While an object near the northern horn of the crescent, strongly resembling a lunar ring mountain, was delineated both by de Vico in 1841 and by Denning 40 years later. We are almost equally sure that Venus, as that the Earth is encompassed with an atmosphere. Yet, notwithstanding luminous appearances plainly due to refraction during the transits both of 1761 and 1769, Schroeder, in 1792, took the initiative in coming to a definite conclusion on the subject. It was founded, first, on the rapid diminution of brilliancy towards the terminator, attributed to atmospheric absorption, next, on the extension beyond a semicircle of the horns of the crescent. Lastly, on the presence of a bluish gleam illuminating the early hours of the Cytherean night with what was taken to be genuine twilight. Even Herschel admitted that sunlight, by the same effect through which the heavenly bodies show visibly above our horizons while still geometrically below them, appeared to be bent round the shoulder of the globe of Venus. Ample confirmation of the fact has since been afforded. At Dorpat in May, 1849, the planet being within 3 degrees 26 of inferior conjunction, Madler found the arms of waning light upon the disk to embrace no less than 240 degrees of its extent. And in December, 1842, Mr. Guthrie, of Burvey, N.B., actually observed, under similar conditions, the whole circumference to be lit up with a faint nebulous glow. The same curious phenomenon was intermittently seen by Mr. Leeson Prince at Uckfield in September, 1861, but with more satisfactory distinctness by Mr. C.S. Lyman of Yale College, before and after the conjunction of December 11, 1866, and during nearly 5 hours previous to the transit of 1874, when the yellowish ring of refracted light showed at one point an approach to interruption. Possibly through the intervention of a bank of clouds. Again, on December 2, 1898, Venus being 1 degree 45 from the Sun's center, Mr. H. N. Russell, of the Halstead Observatory, described the coalescence of the cusps, and founded on the observation a valuable discussion of such effects. Taking account of certain features in the case left unnoticed by Neison and Proctor, he inferred from them the presence of a Cytherean atmosphere considerably less refractive than our own, although possibly, in its lower strata, encumbered with dust or haze. Similar appearances are conspicuous during transits. But while the Mercurian halo is characteristically seen on the Sun, the silver thread round the limb of Venus commonly shows on the part off the Sun. There are, however, instances of each description in both cases. Mr. Grant, in collecting the records of physical phenomena accompanying the transits of 1761 and 1769, remarks that no one person saw both kinds of annulus, and argues a dissimilarity in their respective modes of production. Such a dissimilarity probably exists, in the sense that the inner section of the ring is illusory, the outer, a genuine result of the bending of light in a gaseous envelope. But the distinction of separate visibility has not been borne out by recent experience. Several of the Australian observers during the transit of 1874 witnessed the complete phenomenon. Mr. J. McDonnell, at Eden, saw a shadowy nebulous ring surround the whole disk when ingress was 2/3 accomplished. Mr. Tornaghi, at Goulburn, perceived a halo, entire and unmistakable, at half egress. Similar observations were made at Sydney, and were renewed in 1882 by Lescarbault at Orgeries, by Metzger in Java, and by Barnard at Vanderbilt University. Spectroscopic indications of aqueous vapor as present in the atmosphere of Venus were obtained in 1874 and 1882 by Tacchini and Rico in Italy, and by Young in New Jersey. Janssen, however, who made a special study of the point subsequently to the transit of 1882, found them much less certain than he had anticipated. And Vogel, by repeated examinations, 1871–73, could detect only the very slightest variations from the pattern of the solar spectrum. Some additions there indeed seem to be in the thickening of a few water and oxygen lines, but so nearly evanescent as to induce the persuasion that most of the light we receive from Venus has traversed only the tenuous upper portion of its atmosphere. It is reflected, at any rate, with comparatively slight diminution. On the 26th and 27th of September, 1878, a close conjunction gave Mr. James Naismith the rare opportunity of watching Venus and Mercury for several hours side by side in the field of his reflector. When the former appeared to him like clean silver, the latter as dull as lead or zinc. Yet the light incident upon Mercury is, on an average, 3.5 times as strong as the light reaching Venus. Thus, the reflective power of Venus must be singularly strong. And we find, accordingly, from a combination of Zollner's with Muller's results, that its albedo is but little inferior to that of new fallen snow. In other words, it gives back 77% of the luminous rays impinging upon it. This extraordinary brilliancy would be intelligible were it permissible to suppose that we see nothing of the planet but a dense canopy of clouds. But the hypothesis is discountenanced by the Flagstaff observations, and is irreconcilable with the visibility of mountainous elevations, and permanent surface markings. To Mr. Lowell these were so distinct and unchanging as to furnish data for a chart of the Cytherean globe, and the peculiar arrangement of divergent shading exhibited in it cannot offhand be set down as unreal. In view of Perrotin's earlier discernment of analogous linear traces. Gruithuisen's snow caps, however, it is safe to say, do not exist as such, although shining regions near the poles form a well-attested trait of the strange Cytherean landscape. The secondary, or ashen light, of Venus was first noticed by Riccioli in 1643, it was seen by Derham about 1715, by Kirch in 1721, by Schroeder and Harding in 1806. And the reality of the appearance has since been authenticated by numerous and trustworthy observations. It is precisely similar to that of the old moon in the new moon's arms. And Zenger, who witnessed it with unusual distinctness, January 8, 1883, supposes it due to the same cause, namely, to the faint gleam of reflected earthlight from the night side of the planet. When we remember, however, that full earthlight, on Venus, at its nearest, has little more than 1/12,000 its intensity on the moon, we see at once that the explanation is inadequate. Nor can Professor Safaric's, by phosphorescence of the warm and teeming oceans with which Zollner regarded the globe of Venus as mainly covered, be seriously entertained. Vogel's suggestion is more plausible. He and O. Losey, at Both Camp, November 3 to 11, 1871, saw the dark hemisphere partially illuminated by secondary light, extending 30 degrees from the terminator, and thought the effect might be produced by a very extensive twilight. Others have had recourse to the analogy of our aurorae, and J. Lampe suggested that the grayish gleam, visible to him at Both Camp, October 21 and 26, 1887, might be an accompaniment of electrical processes connected with the planet's meteorology. Whatever the origin of the phenomenon, it may serve, on a night-enwrapped hemisphere, to dissipate some of the thick darkness otherwise encroached upon only by the pale light of stars. Venus was once supposed to possess a satellite. But belief in its existence has died out. No one, indeed, has caught even a deceptive glimpse of such an object during the last 125 years. Yet it was repeatedly and, one might have thought, well observed in the 17th and 18th centuries. Fontana discovered it in 1645, Cassini, an adept in the art of seeing, recognized it in 1672, and again in 1686, Short watched it for a full hour in 1740 with varied instrumental means, Tobias Mayer in 1759, Montaigne in 1761. Several astronomers at Copenhagen in March, 1764, noted what they considered its unmistakable presence, as did Horbo in 1768. But M. Paul Strobent, who in 1887 submitted all the available data on the subject to a searching examination, identified Horbo's satellite with Theta Libri, a fifth magnitude star. And a few other apparitions were, by his industry, similarly explained away. Nevertheless, several withstood all efforts to account for them, and together form a most curious case of illusion. For it is quite certain that Venus has no such conspicuous attendant. The third planet encountered in traveling outward from the Sun is the abode of man. He has in consequence opportunities for studying its physical habitudes altogether different from the baffling glimpse afforded to him of the other members of the solar family. Regarding the Earth, then, a mass of knowledge so varied and comprehensive has been accumulated as to form a science, or rather several sciences, apart. But underneath all lie astronomical relations, the recognition and investigation of which constitute one of the most significant intellectual events of the present century. It is indeed far from easy to draw a line of logical distinction between items of knowledge which have their proper place here, and those which should be left to the historian of geology. There are some, however, of which the cosmical connections are so close that it is impossible to overlook them. Among these is the ascertainment of the solidity of the globe. At first sight it seems difficult to conceive what the apparent positions of the stars can have to do with subterranean conditions. Yet it was from star measurements alone that Hopkins, in 1839, concluded the Earth to be solid to a depth of at least 800 or 1,000 miles. His argument was, that if it were a mere shell filled with liquid, precession and nutation would be much larger than they are observed to be. For the shell alone would follow the pull of the sun and moon on its equatorial girdle, leaving the liquid behind, and being thus so much the lighter, would move the more readily. There is, it is true, grave reason to doubt whether this reasoning corresponds with the actual facts of the case, but the conclusion to which it led has been otherwise affirmed and extended. Indications of an identical purport have been derived from another kind of external disturbance, affecting our globe through the same agencies. Lord Kelvin, then Sir William Thomson, pointed out in 1862 that tidal influences are brought to bear on land as well as on water, although obedience to them is perceptible only in the mobile element. Some bodily distortion of the Earth's figure must, however, take place, unless we suppose it of absolute or preternatural rigidity. And the amount of such distortion can be determined from its effect in diminishing oceanic tides below their calculated value. For if the Earth were perfectly plastic to the stresses of solar and lunar gravity, tides, in the ordinary sense, would not exist. Continents and oceans would swell and subside together. It is to the difference in the behavior of solid and liquid terrestrial constituents that the ebb and flow of the waters are due. 6 years later, the distinguished Glasgow professor suggested that this criterion might, by the aid of a prolonged series of exact tidal observations, be practically applied to test the interior condition of our planet. In 1882, accordingly, suitable data extending over 33 years having at length become available, Mr. G.H. Darwin performed the laborious task of their analysis, with the general result that the effective rigidity of the Earth's mass must be at least as great as that of steel. Ratification from an unexpected quarter has lately been brought to this conclusion. The question of a possible mobility in the Earth's axis of rotation has often been mooted. Now at last it has received an affirmative reply. Dr. Kustner detected, in his observations of 1884–85, effects apparently springing from a minute variation in the latitude of Berlin. The matter having been brought before the International Geodetic Association in 1888, special observations were set on foot at Berlin, Potsdam, Prague, and Strasbourg, the upshot of which was to bring plainly to view synchronous and seemingly periodic fluctuations of latitude to the extent of half a second of arc. The reality of these was verified by an expedition to Honolulu in 1891–92, the variations there corresponding inversely to those simultaneously determined in Europe. Their character was completely defined by Mr. S. C. Chandler's discussion in October, 1891. He showed that they could be explained by supposing the pole of the Earth to describe a circle with a radius of 30 feet in a period of 14 months. Confirmation of this hypothesis was found by Dr. B. A. Gould in the Cordoba observations, and it was provided with a physical basis through the able cooperation of Professor Newcomb. The Earth, owing to its ellipsoidal shape, should, apart from disturbance, rotate upon its axis of figure, or shortest diameter, since thus alone can the centrifugal forces generated by its spinning balance each other. Temporary causes, however, such as heavy falls of snow or rain limited to one continental area, the shifting of ice masses, even the movements of winds, may render the globe slightly lopsided, and thus oblige it to forsake its normal axis and rotate on one somewhat divergent from it. This instantaneous axis, for it is incessantly changing, must, by mathematical theory, revolve round the axis of figure in a period of 306 days. Provided, that is to say, the Earth were a perfectly rigid body. But it is far from being so. It yields sensibly to every strain put upon it, and this yielding tends to protract the time of circulation of the displaced pole. The length of its period, then, serves as a kind of measure of the plasticity of the globe, which, according to Newcomb's and S. Hoff's independent calculations, seems to be a little less than that of steel. In an Earth compacted of steel, the instantaneous axis would revolve in 441 days. In the actual Earth, the process is accomplished in 428 days. By this new path, accordingly, astronomers have been led to an identical estimate of the consistence of our globe with that derived from tidal investigations. Variations of latitude are intrinsically complex. To produce them, an incalculable interplay of causes must be at work, each with its proper period and law of action. All the elements of the phenomenon are then in a perpetual state of flux, and absorb for their continual redetermination, the arduous and combined labors of many astronomers. Nor is this trouble superfluous. Minute in extent though they be, the shiftings of the pole menace the very foundations of exact celestial science, their neglect would leave the entire fabric insecure. Just at the beginning of the present century they reached a predicted minimum, but are expected again to augment their range after the year 1902. The interesting suggestion has been made by Mr. J. Halm that such fluctuations are, in some obscure way, affected by changes in solar activity, and conform like them to an 11-year cycle. In a paper read before the Geological Society, December 15, 1830, Sir John Herschel threw out the idea that the perplexing changes of climate revealed by the geological record might be explained through certain slow fluctuations in the eccentricity of the Earth's orbit, produced by the disturbing action of the other planets. Shortly afterwards, however, he abandoned the position as untenable, and it was left to the late Dr. James Croll, in 1864 and subsequent years, to reoccupy and fortify it. Within restricted limits, as Lagrange and, more certainly indefinitely, Leverrier proved, the path pursued by our planet round the Sun alternately contracts, in the course of ages, into a moderate ellipse, and expands almost to a circle. The major axis, and consequently the mean distance, remaining invariable. Even at present, when the eccentricity approaches a minimum, the Sun is nearer to us in January than in July by above 3 million miles, and some 850,000 years ago this difference was more than 4 times as great. Dr. Croll brought together a mass of evidence to support the view, that, at epochs of considerable eccentricity, the hemisphere of which the winter, occurring at aphelion, was both intensified and prolonged, must have undergone extensive glaciation. While the opposite hemisphere, with a short, mild winter, and long, cool summer, enjoyed an approach to perennial spring. These conditions were exactly reversed at the end of 10,500 years, through the shifting of the perihelion combined with the precession of the equinoxes. The frozen hemisphere blooming into a luxuriant garden as its seasons came round to occur at the opposite sites of the terrestrial orbit, and the vernal hemisphere subsiding simultaneously into ice-bound rigor. Thus a plausible explanation was offered of the anomalous alternations of glacial and semi-tropical periods, attested, on incontrovertible geological evidence, as having succeeded each other in times past over what are now temperate regions. They succeeded each other, it is true, with much less frequency and regularity than the theory demanded, but the discrepancy was overlooked or smoothed away. The most recent glacial epoch was placed by Dr. Clerke about 200,000 years ago, when the eccentricity of the Earth's orbit was 3-4 times as great as it is now. At present a faint representation of such a state of things is afforded by the southern hemisphere. One condition of glaciation in the coincidence of winter with the maximum of remoteness from the Sun, is present, the other, a high eccentricity, is deficient. Yet the ring of ice-bound territory hemming in the southern pole is well known to be far more extensive than the corresponding region in the north. The verification of this ingenious hypothesis depends upon a variety of intricate meteorological conditions, some of which have been adversely interpreted by competent authorities. What is still more serious, its acceptance seems precluded by time relations of a simple kind. Dr. Wright has established with some approach to certainty that glacial conditions ceased in Canada and the United States about 10 or 12,000 years ago. The erosive action of the Falls of Niagara qualifies them to serve as a clepsydra, or water clock on a grand scale. And their chronological indications have been amply corroborated elsewhere and otherwise on the same continent. The astronomical ice age, however, should have been enormously more antique. No reconciliation of the facts with the theory appears possible. The first attempt at an experimental estimate of the mean density of the Earth was Maskelyne's observation in 1774 of the deflection of a plumb line through the attraction of Schiehallion. The conclusion thence derived, that our globe weighs 4.5 times as much as an equal bulk of water, was not very exact. It was considerably improved upon by Cavendish, who, in 1798, brought into use the torsion balance, constructed for the same purpose by John Michell. The resulting estimate of 5.48 was raised to 5.66 by Francis Bailey's elaborate repetition of the process in 1838–42. From experiments on the subject made in 1872–73 by Cornu and Bailey, the slightly inferior value of 5.56 was derived. And it was further shown that the data collected by Bailey, when corrected for a systematic error, gave practically the same result, 5.55. M. Wilsing's of 5.58, obtained at Potsdam in 1889, nearly agreed with it. While Professor Poynting, by means of a common balance, arrived at a terrestrial mean density of 5.49. Professor Boys next entered the field with an exquisite apparatus, in which a quartz fiber performed the functions of a torsion rod. And the figure 5.53 determined by him, and exactly confirmed by Dr. Braun's research at Mariaskian, Bohemia, in 1896, may be called the standard value of the required datum. Newton's guess at the average weight of the Earth as 5 or 6 times that of water has thus been curiously verified. Operations for determining the figure of the Earth were carried out during the last century on an unprecedented scale. The Russo-Scandinavian arc, of which the measurement was completed under the direction of the elder Struve in 1855, reached from Hammerfest to Ismailia on the Danube, a length of 25 degrees 20. But little inferior to it was the Indian arc, begun by Lambton in the first years of the century, continued by Everest, revised and extended by Walker. Both were surpassed in compass by the Anglo-French arc, which embraced 28 degrees. And considerable segments of meridians near the Atlantic and Pacific shores of North America were measured under the auspices of the United States Coast Survey. But these operations shrink into insignificance by comparison with Sir David Gill's grandiose scheme for uniting two hemispheres by a continuous network of triangulation. The history of geodesy in South Africa began with Lacaille's measurements in 1752. They were repeated and enlarged in scope by Sir Thomas MacLear in 1841–48. And his determinations prepared the way for a complete survey of Cape Colony and Natal, executed during the 10 years 1883–92 by Colonel Morris, R.E., under the direction of Sir David Gill. Bechuanaland and Rhodesia were subsequently included in the work, and the royal astronomer obtained, in 1900, the support of the International Geodetic Association for its extension to the mouth of the Nile. Nor was this the limit of his design. By carrying the survey along the Levantine coast, connection can be established with Struve's system, and the magnificent amplitude of 105 degrees will be given to the conjoined African and European arcs. Meantime, the French have undertaken the remeasurement of Bugger's Peruvian arc, and a corresponding Russo-Swedish enterprise is progressing in Spitsbergen. So that abundant materials will ere long be provided for fresh investigations of the shape and size of our planet. The smallness of the outstanding uncertainty can be judged of by comparing J.B. listings with General Clerke's results, published in the same year, 1878. Listings stated the dimensions of the terrestrial spheroid as follows: equatorial radius equals 3,960 miles, polar radius equals 3,947 miles, ellipticity equals 1/288.5. Clerke's corresponding figures were 3,963 and 3,950 miles, giving an ellipticity of 1/293.5. The value of the latter fraction at present generally adopted is 1/292. That is to say, the thickness of the protuberant equatorial ring is held to be 1/292 of the equatorial radius. From astronomical considerations, it is true, Newcomb estimated the ratio at 1/308. But for obtaining this particular datum, geodetical methods are unquestionably to be preferred. The Moon possesses for us a unique interest. She in all probability shared the origin of the Earth, she perhaps prefigures its decay. She is at present its minister and companion. Her existence, so far as we can see, serves no other purpose than to illuminate the darkness of terrestrial nights, and to measure, by swiftly recurring and conspicuous changes of aspect, the long span of terrestrial time. Inquiries stimulated by visible dependence, and aided by relatively close vicinity, have resulted in a wonderfully minute acquaintance with the features of the single lunar hemisphere open to our inspection. Selenography, in the modern sense, is little more than 100 years old. It originated with the publication in 1791 of Schroeder's selenotopographic fragment. Not but that the lunar surface had already been diligently studied, chiefly by Hevelius, Cassini, Riccioli, and Tobias Mayer. The idea, however, of investigating the Moon's physical condition, and detecting symptoms of the activity there of natural forces through minute topographical inquiry, first obtained effect at Lilienthal. Schroeder's delineations, accordingly, imperfect though they were, afforded a starting point for a comparative study of the superficial features of our satellite. The first of the curious objects which he named Rills was noted by him in 1787. Before 1801 he had found 11, Lohrmann added 75, Madler 55, Schmidt published in 1866 a catalogue of 425, of which 278 had been detected by himself, and he eventually brought the number up to nearly 1,000. They are, then, a very persistent lunar feature, though wholly without terrestrial analogue. There is no difference of opinion as to their nature. They are quite obviously clefts in a rocky surface, 100 to 500 yards deep, usually a couple of miles across, and pursuing straight, curved, or branching tracks up to 150 miles in length. As regards their origin, the most probable view is that they are fissures produced in cooling, but Nissen inclines to consider them rather as dried watercourses. On February 24, 1792, Schroeder perceived what he took to be distinct traces of a lunar twilight, and continued to observe them during 9 consecutive years. They indicated, he thought, the presence of a shallow atmosphere, about 29 times more tenuous than our own. Bessel, on the other hand, considered that the only way of saving a lunar atmosphere was to deny it any refractive power. The sharpness and suddenness of star occultations negativing the possibility of gaseous surroundings of greater density, admitting an extreme supposition, than 1/500 that of terrestrial air. Newcomb places the maximum at 1/400. Sir John Herschel concluded the non-existence of any atmosphere at the Moon's edge having January 1980 part of the density of the Earth's atmosphere. This decision was fully borne out by Sir William Huggins's spectroscopic observation of the disappearance behind the Moon's limb of the small star Epsilon Piscium, January 4, 1865. Not the slightest sign of selective absorption or unequal refraction was discernible. The entire spectrum went out at once, as if a slide had suddenly dropped over it. The spectroscope has uniformly told the same tale, for M. Tholen's observation during the total solar eclipse at Sohag of a supposed thickening at the Moon's rim of certain dark lines in the solar spectrum, is now acknowledged to have been illusory. Moonlight, analyzed with the prism, is found to be pure reflected sunlight, diminished in quantity, owing to the low reflective capability of the lunar surface, to less than 1/5 its incident intensity, but wholly unmodified in quality. Nevertheless, the diameter of the Moon appeared from the Greenwich observations discussed by Airy in 1865 to be 4 smaller than when directly measured. And the effect would be explicable by refraction in a lunar atmosphere 2,000 times thinner than our own at the sea level. But the difference was probably illusory. It resulted in part, if not wholly, from the visual enlargement by irradiation of the bright disk of the Moon. Professor Comstock, employing the 16-inch Clerke equatorial of the Washburn Observatory, found in 1897 the refractive displacements of occulted stars so trifling as to preclude the existence of a permanent lunar atmosphere of much more than January 50 the density of the terrestrial envelope. The possibility, however, was admitted that, on the illuminated side of the Moon, temporary exhalations of aqueous vapor might arise from ice strata evaporated by sun heat. Meantime, some renewed evidence of actual crepuscular gleams on the Moon had been gathered by M. Paul and Prosper Henry of the Paris Observatory, as well as by Mr. W. H. Pickering, in the pure air of Arequipa, at an altitude of 8,000 feet above the sea. An occultation of Jupiter, too, observed by him August 12, 1892, was attended with a slight flattening of the planet's disk through the effect, it was supposed, of lunar refraction, but of refraction in an atmosphere possessing, at the most, January 40 the density at the sea level of terrestrial air, and capable of holding in equilibrium no more than 1/250 of an inch of mercury. Yet this small barometric value corresponds, Mr. Pickering remarks, to a pressure of hundreds of tons per square mile of the lunar surface. The compression downward of gaseous strata on the Moon should, in any case, proceed very gradually, owing to the slight power of lunar gravity. And they might hence play an important part in the economy of our satellite while evading spectroscopic and other tests. Thus, as Mr. Ranyard remarked, the cliffs and pinnacles of the Moon bear witness, by their unworn condition, to the efficiency of atmospheric protection against meteoric bombardment, and Mr. Pickering shows that it could be afforded by such a tenuous envelope as that postulated by him. The first to emulate Schroeder's selenographical zeal was Wilhelm Gotthelf Lohrmann, a land surveyor of Dresden, who, in 1824, published 4 out of 25 sections of the first scientifically executed lunar chart, on a scale of 37.5 inches to a lunar diameter. His sight, however, began to fail 3 years later, and he died in 1840, leaving materials from which the work was completed and published in 1878 by Dr. Julius Schmidt, late director of the Athens Observatory. Much had been done in the interim. Beer and Madler began at Berlin in 1830 their great trigonometrical survey of the lunar surface, as yet neither revised nor superseded. A map, issued in 4 parts, 1834-36, on nearly the same scale as Lohrmann's, but more detailed and authoritative, embodied the results. It was succeeded, in 1837, by a descriptive volume bearing the imposing title, Der Mond. Oder allgemeine Vergleichen Selenography. This summation of knowledge in that branch, though in truth leaving many questions open, had an air of finality which tended to discourage further inquiry. It gave form to a reaction against the sanguine views entertained by Hevelius, Schroeder, Herschel and Gruithuisen as to the possibilities of agreeable residence on the Moon, and relegated the Selenites, one of whose cities Schroeder thought he had discovered, and of whose festal processions Gruithuisen had not despaired of becoming a spectator, to the shadowy land of the Ivory Gate. All examples of change in lunar formations were, moreover, dismissed as illusory. The light contained in the work was, in short, a dry light, not stimulating to the imagination. A mixture of a lie, Bacon shrewdly remarks, doth ever add pleasure. For many years, accordingly, Schmidt had the field of selenography almost to himself. Reviving interest in the subject was at once excited and displayed by the appointment, in 1864, of a lunar committee of the British Association. The indirect were of greater value than the direct fruits of its labors. An English school of selenography rose into importance. Popularity was gained for the subject by the diffusion of works conspicuous for ingenuity and research. Naismith's and Carpenter's beautifully illustrated volume, 1874, was succeeded, after 2 years, by a still more weighty contribution to lunar science in Mr. Neeson's well-known book, accompanied by a map, based on the survey of Beer and Madler, but adding some 500 measures of positions, besides the representation of several thousand new objects. With Schmidt's Chart der Gebirge der Monds, Germany once more took the lead. This splendid delineation, built upon Lohrmann's foundation, embraced the detail contained in upwards of 3,000 original drawings, representing the labor of 34 years. No less than 32,856 craters are represented in it, on a scale of 75 inches to a diameter. An additional help to lunar inquiries was provided at the same time in this country by the establishment, through the initiative of the late Mr. W. R. Burt, of the Selenographical Society. But the strongest incentive to diligence in studying the rugged features of our celestial helpmate has been the idea of probable or actual variation in them. A change always seems to the inquisitive intellect of man like a breach in the defenses of nature's secrets, through which it may hope to make its way to the citadel. What is desirable easily becomes credible. And thus statements and rumors of lunar convulsions have successively, during the last 100 years, obtained credence, and successively, on closer investigation, been rejected. The subject is one as to which illusion is peculiarly easy. Our view of the moon's surface is a bird's-eye view. Its conformation reveals itself indirectly through irregularities in the distribution of light and darkness. The forms of its elevations and depressions can be inferred only from the shapes of the black, unmitigated shadows cast by them. But these shapes are in a state of perpetual and bewildering fluctuation, partly through changes in the angle of illumination, partly through changes in our point of view, caused by what are called the moon's librations. The result is, that no single observation can be exactly repeated by the same observer, since identical conditions recur only after the lapse of a great number of years. Local peculiarities of surface, besides, are liable to produce perplexing effects. The reflection of earth light at a particular angle from certain bright summits completely, though temporarily, deceived Herschel into the belief that he had witnessed, in 1783 and 1787, volcanic outbursts on the dark side of the moon. The persistent recurrence, indeed, of similar appearances under circumstances less amenable to explanation inclined Webb to the view that effusions of native light actually occur. More cogent proofs must, however, be adduced before a fact so intrinsically improbable can be admitted as true. But from the publication of Beer and Madler's work until 1866, the received opinion was that no genuine sign of activity had ever been seen, or was likely to be seen, on our satellite. That her face was a stereotyped page, a fixed and irrevisable record of the past. A profound sensation, accordingly, was produced by Schmidt's announcement, in October, 1866, that the crater, Lynn, in the Mare Serenitatis, had disappeared, effaced, as it was supposed, by an igneous outflow. The case seemed undeniable, and is still dubious. Lynn had been known to Lohrmann and Madler, 1822–32, as a deep crater, 5 or 6 miles in diameter, the third largest in the dusky plain known as the Mare Serenitatis. And Schmidt had observed and drawn it, 1840–43, under a practically identical aspect. Now it appears under high light as a whitish spot, in the center of which, as the rays begin to fall obliquely, a pit, scarcely 2 miles across, emerges into view. The crateral character of this comparatively minute depression was detected by Father Secchi, February 11, 1867. This is not all. Schroeder's description of Lynn, as seen by him November 5, 1788, tallies quite closely with modern observation. While its inconspicuousness in 1797 is shown by its omission from Russell's lunar globe and maps. We are thus driven to adopt one of two suppositions: either Lohrmann, Madler, and Schmidt were entirely mistaken in the size and importance of Lynn, or a real change in its outward semblance supervened during the first half of the century, and has since passed away, perhaps again to recur. The latter hypothesis seems the more probable, and its probability is strengthened by much evidence of actual obscuration or variation of tint in other parts of the lunar surface. More especially on the floor of the great walled plain named Plato. From a re-examination with a 13-inch refractor at Arequipa in 1891–92 of this region, and of the Mare Serenitatis, Mr. W. H. Pickering inclines to the belief that lunar volcanic action, once apparently so potent, is not yet wholly extinct. An instance of an opposite kind of change was alleged by Dr. Hermann J. Klein of Cologne in March 1878. In Lynn the obliteration of an old crater had been assumed. In AGNES M, the formation of a new crater was asserted. Yet, quite possibly, the same cause may have produced the effects thought to be apparent in both. It is, however, far from certain that any real change has affected the neighborhood of AGNES. The novelty of Klein's observation of May 19, 1877, may have consisted simply in the detection of a hitherto unrecognized feature. The region is one of complex formation, consequently of more than ordinary liability to deceptive variations in aspect under rapid and entangled fluctuations of light and shade. Moreover, it seems to be certain, from Messrs. Pratt and Capron's attentive study, that AGNES M is no true crater, but a shallow, saucer-like depression, difficult of clear discernment. Under suitable illumination, nevertheless, it contains, and is marked by, an ample shadow. In both these controverted instances of change, lunar photography was invoked as a witness. But, notwithstanding the great advances made in the art by de la Rue in this country, by Draper, and, above all, by Rutherford in America, without decisive results. Investigations of the kind began to assume a new aspect in 1890, when Professor Holden organized them at the Lick Observatory. Autographic moon pictures were no longer taken casually, but on system, and Dr. Wynek's elaborate study, and skillful reproductions of them at Prague, gave them universal value. They were designed to provide materials for an atlas on the scale of Beer and Madler's, of which some beautiful specimen plates have been issued. At Paris, in 1894, with the aid of a large equatorial coude, a work of similar character was set on foot by M. Loewy and Puiseux. Its progress has been marked by the successive publication of 5 installments of a splendid atlas, on a scale of about 8 feet to the lunar diameter, accompanied by theoretical dissertations, designed to establish a science of selenology. The moon's formations are thus not only delineated under every variety of light incidence, but their meaning is sought to be elicited, and their history and mutual relations interpreted. Henceforth, at any rate, the lunar volcanoes can scarcely, without notice taken, breathe hard in their age-long sleep. Melloni was the first to get undeniable heating effects from moonlight. His experiments, made on Mount Vesuvius early in 1846, were repeated with like result by Zantedeschi at Venice 4 years later. A rough measure of the intensity of those effects was arrived at by Piazzi Smith at Guajara, on the peak of Tenerife, in 1856. At a distance of 15 feet from the thermal multiplier, a Price's candle was found to radiate just twice as much heat as the full moon. Then, after 13 years, in 1869–72, an exact and extensive series of observations on the subject were made by the present Earl of Rosse. The lunar radiations, from the first to the last quarter, displayed, when concentrated with the Parsonstown 3-foot mirror, appreciable thermal energy, increasing with the phase, and largely due to dark heat. Distinguished from the quicker vibrating sort by inability to traverse a plate of glass. This was supposed to indicate an actual heating of the surface, during the long lunar day of 300 hours, to about 500 degrees Fahrenheit, corrected later to 197 degrees, the moon thus acting as a direct radiator no less than as a reflector of heat. But the conclusion was very imperfectly borne out by Dr. Bodeker's observations with the same instrument and apparatus during the total lunar eclipse of October 4, 1884. This initial opportunity of measuring the heat phases of an eclipsed moon was used with the remarkable result of showing that the heat disappeared almost completely, though not quite simultaneously, with the light. Confirmatory evidence of the extraordinary promptitude with which our satellite parts with heat already to some extent appropriated, was afforded by Professor Langley's bolometric observations at Allegheny of the partial eclipse of September 23, 1885. Yet it is certain that the moon sends us a perceptible quantity of heat on its own account, besides simply throwing back solar radiations. For in February, 1885, Professor Langley succeeded, after many fruitless attempts, in getting measures of a lunar heat spectrum. The incredible delicacy of the operation may be judged of from the statement that the sum total of the thermal energy dispersed by his rock salt prisms was insufficient to raise a thermometer fully exposed to 1/1000th of a degree centigrade. The singular fact was, however, elicited that this almost evanescent spectrum is made up of two superposed spectra, one due to reflection, the other, with a maximum far down in the infrared, to radiation. The corresponding temperature of the moon's sunlit surface Professor Langley considers to be about that of freezing water. Repeated experiments having failed to get any thermal effects from the dark part of the moon, it was inferred that our satellite has no internal heat sensible at the surface. So that the radiations from the lunar soil giving the low maximum in the heat spectrum, must be due purely to solar heat which has been absorbed and almost immediately re-radiated. Professor Langley's explorations of the terra incognita of immensely long wavelengths where lie the unseen heat emissions from the Earth into space, led him to the discovery that these, contrary to the received opinion, are in good part transmissible by our atmosphere, although they are completely intercepted by glass. Another important result of the Allegheny work was the abolition of the anomalous notion of the temperature of space, fixed by Pouillet at -140 degrees Celsius. For space in itself can have no temperature, and stellar radiation is a negligible quantity. Thus, it is safe to assume that a perfect thermometer suspended in space at the distance of the Earth or Moon from the Sun, but shielded from its rays, would sensibly indicate the absolute zero, ordinarily placed at -273 degrees Celsius. A prize essay on the distribution of the Moon's heat, The Hague, 1891, by Mr. Frank W. VIII, who had taken an active part in Professor Langley's long-sustained inquiry, embodies the fruits of its continuation. They show the lunar disk to be tolerably uniform in thermal power. The brighter parts are also indeed hotter, but not much. The traces perceived of a slight retention of heat by the substances forming the lunar surface, agreed well with the Parsonstown observations of the total eclipse of the moon, January 28, 1888. For they brought out an unmistakable divergence between the heat and light phases. A curious decrease of heat previous to the first touch of the Earth's shadow upon the lunar globe remains unexplained, unless it be admissible to suppose the terrestrial atmosphere capable of absorbing heat at an elevation of 190 miles. The probable range of temperature on the moon was discussed by Professor VIII in 1898. He concluded it to be very wide. Hotter than boiling water under the sun's vertical rays, the arid surface of our dependent globe must, he found, cool in the 14-day lunar night to about the temperature of liquid air. Although that fundamental part of astronomy known as celestial mechanics lies outside the scope of this work, and we therefore pass over in silence the immense labors of Plana, Damoiseau, Hansen, Delaunay, G. W. Hill, and Airy in reconciling the observed and calculated motions of the moon, there is one slight but significant discrepancy which is of such importance to the physical history of the solar system, that some brief mention must be made of it. Halley discovered in 1693, by examining the records of ancient eclipses, that the moon was going faster then than 2,000 years previously, so much faster, as to have got ahead of the place in the sky she would otherwise have occupied. by about 2 of her own diameters. It was one of Laplace's highest triumphs to have found an explanation of this puzzling fact. He showed, in 1787, that it was due to a very slow change in the ovalness of the Earth's orbit, tending, during the present age of the world, to render it more nearly circular. The pull of the Sun upon the Moon is thereby lessened. The counterpull of the Earth gets the upper hand, and our satellite, drawn nearer to us by something less than an inch each year, proportionately quickens her pace. Many thousands of years hence the process will be reversed. The terrestrial orbit will close in at the sides, the lunar orbit will open out under the growing stress of solar gravity, and our celestial chronometer will lose instead of gaining time. This is all quite true as Laplace put it. But it is not enough. Adams, the virtual discoverer of Neptune, found with surprise in 1853 that the received account of the matter was essentially incomplete, and explained, when the requisite correction was introduced, only half the observed acceleration. What was to be done with the remaining half? Here Delaunay, the eminent French mathematical astronomer, unhappily drowned at Cherbourg in 1872 by the capsizing of a pleasure boat, came to the rescue. It is obvious to anyone who considers the subject a little attentively, that the tides must act to some extent as a friction brake upon the rotating Earth. In other words, they must bring about an almost infinitely slow lengthening of the day. For the two masses of water piled up by lunar influence on the hither and farther sides of our globe, strive, as it were, to detach themselves from the unity of the terrestrial spheroid, and to follow the movements of the Moon. The Moon, accordingly, holds them against the whirling Earth, which revolves like a shaft in a fixed collar, slowly losing motion and gaining heat, eventually dissipated through space. This must go on, so far as we can see, until the periods of the Earth's rotation and of the Moon's revolution coincide. Nay, the process will be continued, should our oceans survive so long, by the feebler tide-raising power of the Sun, ceasing only when day and night cease to alternate. When one side of our planet is plunged in perpetual darkness and the other seared by unchanging light. Here, then, we have the secret of the Moon's turning always the same face towards the Earth. It is that in primeval times, when the Moon was liquid or plastic, an Earth-raised tidal wave rapidly and forcibly reduced her rotation to its present exact agreement with her period of revolution. This was divined by Kant nearly a century before the necessity for such a mode of action presented itself to any other thinker. In a weekly paper published at Königsberg in 1754, the modern doctrine of tidal friction was clearly outlined by him, both as regards its effects actually in progress on the rotation of the Earth, and as regards its effects already consummated on the rotation of the Moon, the whole forming a preliminary attempt at what he called a natural history of the heavens. His sagacious suggestion, however, remained entirely unnoticed until revived, it would seem independently, by Julius Robert Mayer in 1848. While similar, and probably original, conclusions were reached by William Ferrel of Allensville, Kentucky, in 1858. Delaunay was not then the inventor or discoverer of tidal friction, he merely displayed it as an effective cause of change. He showed reason for believing that its action in checking the Earth's rotation, far from being, as Ferrel had supposed, completely neutralized by the contraction of the globe through cooling, was a fact to be reckoned with in computing the movements, as well as in speculating on the history, of the heavenly bodies. The outstanding acceleration of the Moon was thus at once explained. It was explained as apparent only, the reflection of a real lengthening, by 1 second in 100,000 years, of the day. But on this point the last word has not yet been spoken. Professor Newcomb undertook in 1870 the onerous task of investigating the errors of Hansen's lunar tables as compared with observations prior to 1750. The results, published in 1878, proved somewhat perplexing. They tend, in general, to reduce the amount of acceleration left unaccounted for by Laplace's gravitational theory, and proportionately to diminish the importance of the part played by tidal friction. But, in order to bring about this diminution, and at the same time conciliate Alexandrian and Arabian observations, it is necessary to reject as total the ancient solar eclipses known as those of Thales and Larissa. This may be a necessary, but it must be admitted to be a hazardous expedient. Its upshot was to indicate a possibility that the observed and calculated values of the moon's acceleration might after all prove to be identical. And the small outstanding discrepancy was still further diminished by Tisserand's investigation, differently conducted, of the same Arabian eclipses discussed by Newcomb. The necessity of having recourse to a lengthening day is then less pressing than it seemed some time ago, and the effect, if perceptible in the moon's motion, should, M. Tisserand remarked, be proportionately so in the motions of all the other heavenly bodies. The presence of the apparent general acceleration that should ensue can be tested with most promise of success, according to the same authority, by delicate comparisons of past and future transits of Mercury. Newcomb further showed that small residual irregularities are still found in the movements of our satellite, inexplicable either by any known gravitational influence, or by any uniform value that could be assigned to secular acceleration. If set down to the account of imperfections in the timekeeping of the Earth, it could only be on the arbitrary supposition of fluctuations in its rate of going themselves needing explanation. This, it is true, might be found in very slight changes of figure, not altogether unlikely to occur. But into this cloudy and speculative region astronomers for the present decline to penetrate. They prefer, if possible, to deal only with calculable causes, and thus to preserve for their most perfect of sciences its special prerogative of assured prediction. Footnotes. Neueste Beitrage zur Erweiterung der Sternkunde, BD, 3, p. 14, 1800. Ibid, page 24. Phil. Trans, volume 93, page 215. MEM. Roy. Astr. SOC, volume 6, page 116. Month. Not, volume 19, pages 11, 25. Ibid, volume 38, page 398. AM. Jour of SC, volume 16, page 124. Washington OBS for 1876, part 2, page 34. Pop. Astr, volume 2, page 168, Astr. Jour, number 335. Astr. And Astrophysics, volume 13, page 866. Ibid, page 867. Month. Not, volume 24, page 18. Ibid, volume 23, page 234, Chalice. Untersuchungen über die Spektra der Plane 10, page 9. Sirius, volume 7, p. 131. Potsdam Publ, number 30, Astr. Nock, number 3171, Frost, Astr. And Astrophysics, volume 12, page 619. Zollner and Winnick made it equals oath 13, Astr. Nock, number 2245. Neueste Beitrage, BD, 3, page 50. Astr. Jarbuch, 1804, pages 97 to 102. Webb, Celestial Objects, page 46, 4th edition. L'Astronomie, T. 2, page 141. Observations sur les planètes Venus et Mercure, page 87. Observatory, volume 6, page 40. Adi del Akkad. De Lincei, T. v. 2, page 283, 1889, Astr. Nock, number 2944. Astr. Nock. Number 2479. Memoirs America Academic, volume 12, number 4, page 464. Histoire de l'Astre, page 682. Comptes Rendus, T. 49, page 379. Comptes Rendus, T. L., page 40. Ibid, page 46. Astre. Nock, numbers 1248 and 1281. Comptes Rendus, T. 83, pages 510, 561. Handbuch der Mathematik, BD, 2, page 327. Comptes Rendus, T. 83, page 721. Nature, volume 18, pages 461, 495, 539. Appolzer, Astr. Nock, number 2239. Ibid, numbers 2253-4, C. H. F. Peters. Ibid, numbers 2263 and 2277. See also Tisserand in N. Bur de Long, 1882, page 729. C. J. Boschinger's Untersuchungen, 1884, summarized in Bull. Astr. T. I., page 506, and Astr. Nock, number 2594. Newcomb finds the anomalous motion of the perihelion to be even larger, 43 instead of 38, than Leverrier made it. Month. Knott, February, 1884, page 187. Harzer's attempt to account for it in Astra. Nock, number 3030, is more ingenious than successful. Jour de Scavens, December, 1667, page 122. Elements d'Astre, page 525. C. F. Chandler, Pop Astre, February, 1897, page 393. Beobachtungen über die sehr betrachtlichen Geberge und Rotation der Venus, 1792, page 35. Schroeder's final result in 1811 was 23H. 21M, 7, 977S. Monat. Core, BD, 25, page 367. Astra. Nock, number 404. Rendiconti dell'R. Istituto Lombardo, T. 23, Serie 2. Astra. Nock, number 3304. Bothkamp Beobachtungen, Heft 2, page 120. Comptes Rendus, T. XIII, page 542, T. XIII, page 395. Month. Knott, volume 57, page 402, Astra. Nock, number 3406. MEM. Spettroscopisti Italiani, T. 25, page 93, Nature, volume 53, page 306. Astra. Nock, number 3329. Ibid. Bull. De l'Académique. De Belgique, T. 21, page 452, 1891. Observations sur les planètes Venus et Mercure, 1892. Astra. Nock, number 3300. Ibid, number 3332. Ibid, number 3314. Ibid, number 3170. Ibid, number 3641. The velocity of a point on the equator of Venus, if Brenner's period of 23h. 57 m. were exact, would be 0.28 miles per second, but the displacements due to this rate would be doubled by reflection. Novi Observations, page 92. MEM. De LAC, 1700, page 296. Phil. Trans, volume 83, page 201. Webb, Cell. Objects, page 58. Month. Knott. Volume 42, page 111. Bull. A.C. de Bruxelles, T. 43, page 22. Phil. Trans, volume 82, page 309, Aphroditographisch Fragment, page 85, 1796. Astra. Nock, number 679. Month. Knott, volume 14, page 169. Ibid, volume 24, page 25. A.M. Jour of SC, volume 43, page 129, 2d ser. Volume 9, page 47, 3d ser. Astroph. Jour, Volume 9, page 284. Month. Not, Volume 36, page 347. Old and New Astronomy, page 448. History Phys. Astr, page 431. MEM. Roy. Astr. SOC, Volume 47, pages 77, 84. Astr. Reg, Volume 13. Page 132. L'Astronomie, T. 2, page 27, Astr. Nock, number 2021, AM. Jour of SC, Volume 25, page 430. MEM. Spetcher. Idle, December, 1882, AM. Jour of SC, Volume 25, page 328. Comptes rendus, T. XIII, page 288. Vogel, Spectrator Plane 10, page 15. Nature, Volume 19, page 23. Nova Acta Academic Naturae Curiosorum, BD, X, 239. Astr. Jarbuch, 1809, page 164. Month Not, Volume 43, page 331. Report Brit. As, 1873, page 407. The paper contains a valuable record of observations of the phenomenon. Photom. Untersuchungen, page 301. Bothkamp Beobachtungen, Heft 2, page 126. Astr. Nock, number 2818. Memoires de l'Académique. De Bruxelles, T. 49, number 5, 42, Astr. Nock, number 2809, F. Shore, Der Venusmond, 1875. Phil. Trans, 1839, 1841, 1842. Delaunay objected, Comptes rendus, T. 67, p. 65, that the viscosity of the contained liquid, of which Hopkins took no account, would, where the movements were so excessively slow as those of the Earth's axis, almost certainly cause it to behave like a solid. Lord Kelvin, however, Report Brit. As, 1876, 2, page 1, considered Hopkins's argument valid as regards the comparatively quick solar semiannual and lunar fortnightly nutations. Phil. Trans, Clerke, page 573. Report Brit. As, 1868, page 494. Ibid, 1882, page 474. Albrecht, Astr. Nock, number 3131. Astr. Jour, numbers 248, 249. Ibid, number 258. Month. Not, volume 52, page 336. Astr. Nock, number 3097, Phil. Trans, volume Clerke, A, page 469, Proc. Roy. SOC, volume 59. See Chandler's Searching Investigations, Astr. Jour, Nos. 329, 344, 351, 392, 402, 406, 412, 446, 489, 490, 494, 495. Rees, Pop Astr, number 74, 1900. Nature, volume 61, page 447, see also A. V. Backlund, Astr. Nock, number 3787. Transgeology, SOC, volume 3. 2D Serre, page 293. See his treatise on astronomy, p. 199, 1833. Phil. Mag, volume 28. 4th Serre, page 121. Climate and Time, 1875, Discussions on Climate and Cosmology, 1885. See for a popular account of the theory, Sir R. Ball's The Cause of an Ice Age, 1892. C. A. Woikoff, Phil. Mag, Volume 21. Page 223. The Ice Age in North America, London, 1890. Phil. Trans, Volume 68, page 783. Comptes Rendus, T. 76, page 954. Potsdam Publ, numbers 22, 23. Phil. Trans, Volume Clerke, page 565, Adams Prize Essay for 1893. Denkschriften Akkad. Der Wiss. Wien, B.D., 64, quoted by Poynting. Nature, Volume 62, page 404. Report on the Geodetic Survey of S. Africa, 1894. Nature, Volume 62, page 622, Hollis, Observatory, Volume 23, page 337, Poincaré, Comptes Rendus, July 23, 1900. Astre. Knock, number 2228. Young's General Astre, page 601. Astre. Constance, page 195. The second volume was published at Göttingen in 1802. Überrillen auf dem Mond, page 13. Cf. The Moon, by T. Gwyn Elgar, page 20. W. H. Pickering, Harvard Annals, volume 32, page 249. The Moon, p. 73. Seelen. Fragm, th2, page 399. Astre. Knock, number 263, 1834, Popvorl, pages 615 to 620, 1838. Outlines of Astre, par. 431. Month. Knot, volume 25, page 61. Month. Knot, volume 25, page 264. Astroph. Jour, volume 6, page 422. Harvard Annals, volume 32, page 81. Astre. And Astrophysics, volume 11, page 778. Nissen, The Moon, page 25. Knowledge, volume 17, page 85. Nissen, The Moon, page 104. The combination of a uniform rotational with an unequal orbital movement causes a slight swaying of the Moon's globe, now east, now west, by which we are able to see round the edges of the averted hemisphere. There is also a parallactic libration, depending on the Earth's rotation. And a species of nodding movement, the libration in latitude, is produced by the inclination of the Moon's axis to her orbit, and by her changes of position with regard to the terrestrial equator. Altogether, about 2/11ths of the invisible side come into view. Cell. Objects, page 58, 4th edition. Astre. Knock, number 1631. C.F. Leo Brenner, Naderwiss. Wochenschrift, January 13, 1895, Jour, Brit. Astre. As, volume 5, pages 29, 222. Respighi, Les Mondes, T. 14, page 294, Huggins, month. Knot, volume 27, page 298. Burt, Ibid, page 95. Report Brit. As, 1872, page 245. Observatory, volume 15, page 250. Astre. Reg, volume 16, page 265, Astre. Knock, number 2275. Lindsay and Copeland, month. Knot, volume 39, p. 195. Observatory, volumes 2, page 296, 4, page 373. N. E. Green, Astre. Reg, volume 17, p. 144, concluded the object a mere spot of color, dark under oblique light. Webb, Cell. Objects, page 101. Publ, Lick Observatory, Volume 3, page 7. Ibid, page 21. Me, Knowledge, Volume 18, page 135. Comptes Rendus, T. XIII, page 967, Bull. Astre, August, 1899, and Bureau de Langue, 1898, Nature, Volumes Lee, page 439, LV, page 280, Lix, page 304, LX, page 491, Astroph. Jour, Volume 6, page 51. Comptes Rendus, T. 22, page 541. Phil. Trans, Volume XIII, page 502. Proc. Roy. SOC, Volume 17, page 443. Phil. Trans, Volume XIII, page 623. Trans R. Dublin SOC, Volume 3, page 321. Science, Volume 7, page 9. America Jour of Science, Volume 38, page 428. The Temperature of the Moon, Memoirs National Academic of Sciences, Volume 4, page 193, 1889. Temperature of the Moon, page 3, see also App. 2, page 206. Trans R. Dublin SOC, Volume 4, page 481, 1891, Ross, Proc. Roy. Institution, May 31, 1895. Astroph. Jour, Volume 8, pages 199, 265. Airy, Observatory, Volume 3, page 420. Phil. Trans, Volume XIII, page 397, Proc. Roy. SOC, Volume 6, page 321. Comptes Rendus, T. LXI, page 1023. Professor Darwin calculated that the heat generated by tidal friction in the course of lengthening the Earth's period of rotation from 23 to 24 hours, equal 23 million times the amount of its present annual loss by cooling. Nature, Volume 34. Page 422. Sample. Werke, edition 1839, th 6, pages 5 to 12. See also C. J. Monroe's Useful Indications in Nature, Volume 7, page 241. Dynamique des Himmels, page 40. Gould's Astre. Jour, Volume 3, page 138. Washington OBS for 1875, Volume 22, App. 2. Comptes Rendus, T. XIII, page 669, and Ware, Paris, 1892. Newcomb, Pop Astre. 4th edition, page 101. Sir W. Thomson, Report Brit. As, 1876, page 12. Chapter 8. Planets and Satellites, continued. The analogy between Mars and the Earth is perhaps by far the greatest in the whole solar system. So Herschel wrote in 1783, and so we may safely say today, after 60 further years of scrutiny. The circumstance lends a particular interest to inquiries into the physical habitudes of our exterior planetary neighbor. Fontana first caught glimpses, at Naples in 1636 and 1638, of dusky stains on the ruddy disk of Mars. They were next seen by Hooke and Cassini in 1666, and this time with sufficient distinctness to serve as indexes to the planet's rotation, determined by the latter as taking place in a period of 24 hours 40 minutes. Increased confidence was given to this result through Maraldi's precise verification of it in 1719. Among the spots observed by him, he distinguished two as stable in position, though variable in size. They were of a peculiar character, showing as bright patches round the poles, and had already been noticed during 60 years back. A current conjecture of their snowy nature obtained validity when Herschel connected their fluctuations in extent with the progress of the Martian seasons. The inference of frozen precipitations could scarcely be resisted when once it was clearly perceived that the shining polar zones did actually by turns diminish and grow with the alternations of summer and winter in the corresponding hemisphere. This, it may be said, was the opening of our acquaintance with the state of things prevailing on the surface of Mars. It was accompanied by a steady assertion, on Herschel's part, of permanence in the dark markings, notwithstanding partial obscurations by clouds and vapors floating in a considerable but moderate atmosphere. Hence the presumed inhabitants of the planet were inferred to probably enjoy a situation in many respects similar to ours. Schroeder, on the other hand, went altogether wide of the truth as regards Mars. He held that the surface visible to us is a mere shell of drifting cloud, deriving a certain amount of apparent stability from the influence on evaporation and condensation of subjacent but unseen aerographical features. And his opinion prevailed with his contemporaries. It was, however, rejected by Kinosky in 1822, and finally overthrown by Beer and Madler's careful studies during 5 consecutive oppositions, 1830–39. They identified at each the same dark spots, frequently blurred with mists, especially when the local winter prevailed, but fundamentally unchanged. In 1862 Lockyer established a marvelous agreement with Beer and Madler's results of 1830, leaving no doubt as to the complete fixity of the main features, amid daily, nay, hourly, variations of detail through transits of clouds. On 17 nights of the same opposition, F. Kaiser of Leyden obtained drawings in which nearly all the markings noted in 1830 at Berlin reappeared, besides spots frequently seen respectively by Arago in 1813, by Herschel in 1783. And one sketched by Huygens in 1672 with a writing pen in his diary. From these data the Leyden observer arrived at a period of rotation of 24h. 37 m, 2262 s, being just 1 second shorter than that deduced, exclusively from their own observations, by Beer and Madler. The exactness of this result was practically confirmed by the inquiries of Professor Bequesin of Leyden. Using for a middle term of comparison the disinterred observations of Schroeder, with those of Huygens at one, and of Schiaparelli at the other end of an interval of 220 years, he was enabled to show, with something like certainty, that the time of rotation, 24h. 37 m, 22,735 s, ascribed to Mars by Mr. Proctor in reliance on a drawing executed by Hooke in 1666, was too long by nearly 1/10 of a second. The minuteness of the correction indicates the nicety of care employed. Nor employed vainly. For, owing to the comparative antiquity of the records available in this case, an almost infinitesimal error becomes so multiplied by frequent repetition as to produce palpable discrepancies in the positions of the markings at distant dates. Hence Bequesin's period of 24h. 37 m, 2266 s. is undoubtedly of a precision unapproached as regards any other heavenly body save the Earth itself. 2 facts bearing on the state of things at the surface of Mars were, then, fully acquired to science in or before the year 1862. The first was that of the seasonal fluctuations of the polar spots. The second, that of the general permanence of certain dark gray or greenish patches, perceived with the telescope as standing out from the deep yellow ground of the disk. That these varieties of tint correspond to the real diversities of a terraqueous globe, the ripe cornfield sections representing land, the dusky spots and streaks, oceans and straits, has long been the prevalent opinion. Sir J. Herschel in 1830 led the way in ascribing the redness of the planet's light to an inherent peculiarity of soil. Previously it had been assimilated to our sunset glows rather than to our red sandstone formations, set down, that is, to an atmospheric stoppage of blue rays. But the extensive Martian atmosphere, implicitly believed in on the strength of some erroneous observations by Cassini and Roemer in the 17th century, vanished before the sharp occultation of a small star in Leo, witnessed by Sir James South in 1822. And Dawes's observation in 1865, that the ruddy tinge is deepest near the central parts of the disk, certified its non-atmospheric origin. The absolute whiteness of the polar snowcaps was alleged in support of the same inference by Sir William Huggins in 1867. All recent operations tend to show that the atmosphere of Mars is much thinner than our own. This was to have been expected a priori, since the same proportionate mass of air would on his smaller globe form a relatively sparse covering. Besides, gravity there possesses less than 4/10 its force here, so that this sparser covering would weigh less, and be less condensed, than if it enveloped the Earth. Atmospheric pressure would accordingly be of about 2¼ instead of 15 terrestrial pounds per square inch. This corresponds with what the telescope shows us. It is extremely doubtful whether any features of the Earth's actual surface could be distinguished by a planetary spectator, however well provided with optical assistance. Professor Langley's inquiries led him to conclude that fully twice as much light is absorbed by our air as had previously been supposed, say 40%, of vertical rays in a clear sky. Of the 60 reaching the Earth, less than a quarter would be reflected even from white sandstone, and this quarter would again pay heavy toll in escaping back to space. Thus not more than perhaps 10 or 12 out of the original 100 sent by the Sun would, under the most favorable circumstances, and from the very center of the Earth's disk, reach the eye of a Martian or lunar observer. The light by which he views our world is, there is little doubt, light reflected from the various strata of our atmosphere, cloud or mist-laden or serene, as the case may be, with an occasional snow mountain figuring as a permanent white spot. This consideration at once shows us how much more tenuous the Martian air must be, since it admits of topographical delineations of the Martian globe. The clouds, too, that form in it seem in general to be rather of the nature of ground mists than of heavy cumulus. Occasionally, indeed, durable and extensive strata become visible. During the latter half of October, 1894, for instance, a region as large as Europe remained apparently cloud-covered. Yet most recent observers are unable to detect the traces of aqueous absorption in the Martian spectrum noted by Huggins in 1867 and by Vogel in 1873. Campbell vainly looked for them, visually in 1894, spectrographically in 1896. Keeler was equally unsuccessful. Joule holds that they could, with present appliances, only be perceived if the atmosphere of Mars were much richer in water vapor than that of the Earth. There can be little doubt, however, that its supply is about the minimum adequate to the needs of a living, and perhaps a life-nurturing planet. The climate of Mars seems to be unexpectedly mild. Its theoretical mean temperature, taking into account both distance from the Sun and albedo, is 34 degrees Celsius, below freezing. Yet its polar snows are both less extensive and less permanent than those on the Earth. The southern white hood, noticed by Schiaparelli in 1877 to have survived the summer only as a small lateral patch, melted completely in 1894. Moreover, Mr. W. H. Pickering observed with astonishment the disappearance, in the course of 33 days of June and July, 1892, of 1,600,000 square miles of southern snow. Curiously enough, the initial stage of shrinkage in the white calotte was marked by its division into two unequal parts, as if in obedience to the mysterious principle of duplication governing so many Martian phenomena. Changes of the hues associated respectively with land and water accompanied in lower latitudes, and were thought to be occasioned by floods ensuing upon this rapid Antarctic thaw. It is true that scarcity of moisture would account for the scantiness and transitoriness of snowy deposits easily liquefied because thinly spread. But we might expect to see the whole wintry hemisphere, at any rate, frostbound, since the Sun radiates less than half as much heat on Mars as on the Earth. Water seems, nevertheless, to remain, as a rule, uncongealed everywhere outside the polar regions. We are at a loss to imagine by what beneficent arrangement the rigorous conditions naturally to be looked for can be modified into a climate which might be found tolerable by creatures constituted like ourselves. Martian topography may be said to form nowadays a separate subdepartment of descriptive astronomy. The amount of detail become legible by close scrutiny on a little disk which, once in 15 years, attains a maximum of about January 5000 the area of the full moon, must excite surprise and might provoke incredulity. Spurious discoveries, however, have little chance of holding their own where there are so many competitors quite as ready to dispute as to confirm. The first really good map of Mars was constructed in 1869 by Proctor from drawings by Dawes. Kaiser of Leyden followed in 1872 with a representation founded upon data of his own providing in 1862–64. And Terby, in his valuable areography, presented to the Brussels Academy in 1873 a careful discussion of all important observations from the time of Fontana downwards, thus virtually adding to knowledge by summarizing and digesting it. The memorable opposition of September 5, 1877, marked a fresh epoch in the study of Mars. While executing a trigonometrical survey, the first attempted, of the disk, then of the unusual size of 25 across, G.V. Schiaparelli, director of the Milan Observatory, detected a novel and curious feature. What had been taken for Martian continents were found to be, in point of fact, agglomerations of islands, separated from each other by a network of so-called canals, more properly channels. These are obviously extensions of the seas, originating and terminating in them, and sharing their gray-green hue, but running sometimes to a length of 3,000 or 4,000 miles in a straight line, and preserving throughout a nearly uniform breadth of about 60 miles. Further inquiries have fully substantiated the discovery made at the Brera Observatory. The canals of Mars are an actually existent and permanent phenomenon. An examination of the drawings in his possession showed M. Terby that they had been seen, though not distinctively recognized, by Dawes, Secchi, and Holden. Several were independently traced out by Burton at the opposition of 1879, all were recovered by Schiaparelli himself in 1879 and 1881–82. And their indefinite multiplication resulted from Lovell's observations in 1894 and 1896. When the planet culminated at midnight, and was therefore in opposition, December 26, 1881, its distance was greater, and its apparent diameter less than in 1877, in the proportion of 16–25. Its atmosphere was, however, more transparent, and hours of less impediment to northern observers, the object of scrutiny standing considerably higher in northern skies. Never before, at any rate, had the true aspect of Mars come out so clearly as at Milan, with the 8 3/4 inch Mers refractor of the observatory, between December, 1881, and February, 1882. The canals were all again there, but this time they were, in as many as 20 cases, seen in duplicate. That is to say, a twin canal ran parallel to the original one at an interval of 200 to 400 miles. We are here brought face to face with an apparently insoluble enigma. Schiaparelli regards the germination of his canals as a periodical phenomenon depending on the Martian seasons. It is, assuredly, not an illusory one, since it was plainly apparent, during the opposition of 1886, to MM Periton and Tholen at Nice, and to the former, using the new 30-inch refractor of that observatory, in 1888, Mr. A. Stanley Williams, with the help of only a 6 1/2 inch reflector, distinctly perceived in 1897 of the duplicate objects noted at Milan, and the Lick observations, both of 1890 and of 1892. Together with the drawings made at Flagstaff and Mexico during the last favorable oppositions of the 19th century, brought unequivocal confirmation to the accuracy of Schiaparelli's impressions. Various conjectures have been hazarded in explanation of this bizarre appearance. The difficulty of conceiving a physical reality corresponding to it has suggested recourse to an optical rationale. Proctor regarded it as an effect of diffraction. Stanislas Meunier, of oblique reflection from overlying mist banks, Flammarion considers it possible that companion canals might, under special circumstances, be evoked by refraction as a kind of mirage. But none of these speculations are really admissible, when all the facts are taken into account. The view that the canals of Mars are vast rifts due to the cooling of the globe, is recommended by the circumstance that they tend to follow great circles. Nevertheless, it would break down if, as Schiaparelli holds, the fluctuations in their visibility depend upon actual obliterations and re-emergencies. Fantastic though the theory of their artificial origin appear, it is held by serious astronomers. Its vogue is largely due to Mr. Lowell's ingenious advocacy. He considers the Martian globe to be everywhere intersected by an elaborate system of irrigation works, rendered necessary by a perennial water famine, relieved periodically by the melting of the polar snows. Nor does he admit the existence of oceans, or lakes. What have been taken for such are really tracts covered with vegetation, the bright areas intermixed with them representing sandy deserts. And it is noteworthy in this connection that Professor Barnard obtained in 1894, with the Great Lick refractor. Suggestive and impressive views, disclosing details of light and shade on the gray-green patches so intricate and minute as almost to preclude the supposition of their aqueous nature. The closeness of the terrestrial analogy has thus of late been much impaired. Even if the surface of Mars be composed of land and water, their distribution must be of a completely original type. The interlacing everywhere of continents with arms of the sea, if that be the correct interpretation of the visual effects, implies that their levels scarcely differ. And Schiaparelli carries most observers with him in holding that their outlines are not absolutely constant, encroachments of dusky upon bright tints suggesting extensive inundations. The late N.E. Green's observations at Madeira in 1877 indicated, on the other hand, a rugged south polar region. The contour of the snowcap not only appeared indented, as if by valleys and promontories, but brilliant points were discerned outside the white area, attributed to isolated snow peaks. Still more elevated, if similarly explained, must be the ice island first seen in a comparatively low latitude by Dawes in January, 1865. On August 4, 1892, Mars stood opposite to the Sun at a distance of only 34,865,000 miles from the Earth. In point of vicinity, then, its situation was scarcely less favorable than in 1877. The low altitude of the planet, however, practically neutralized this advantage for northern observers, and public expectation, which had been raised to the highest pitch by the announcements of sensation-mongers, was somewhat disappointed at the meagerness of the news authentically received from Mars. Valuable series of observations were, nevertheless, made at Lick and Arequipa. And they unite in testifying to the genuine prevalence of surface variability, especially in certain regions of intermediate tint, and perhaps of the crude consistence of boggy surtees, neither sea, nor good dry land. Professor Holden insisted on the enormous difficulties in the way of completely explaining the recorded phenomena by terrestrial analogies. Mr. W. H. Pickering spoke of conspicuous and startling changes. They, however, merely overlaid, and partially disguised, a general stability. Among the novelties detected by Mr. Pickering were a number of lakes, or oases, in Lowell's phraseology, under the aspect of black dots at the junctions of two or more canals, and he, no less than the Lick astronomers and M. Perrotin at Nice, observed brilliant clouds projecting beyond the terminator, or above the limb, while carried round by the planet's rotation. They seemed to float at an altitude of at least 20 miles, or about 4 times the height of terrestrial cirrus, but this was not wonderful, considering the low power of gravity acting upon them. Great capital was made in the journalistic interest out of these imaginary signals from intelligent Martians, desirous of opening communications with, to them, problematical terrestrial beings. Similar effects had, however, been seen before by Mr. Noble in 1873, by M. Turby in 1888, and at the Lick Observatory in 1890, and they were discerned again with particular distinctness by Professor Hussey at Lick, August 27, 1896. The first photograph of Mars was taken by Gould at Cordoba in 1879. Little real service in planetary delineation has, it is true, been so far rendered by the art, yet one achievement must be recorded to its credit. A set of photographs obtained by Mr. W. H. Pickering on Wilson's Peak, California, April 9, 1890, showed the southern polar cap of Mars as of moderate dimensions, but with a large dim adjacent area. 24 hours later, on a corresponding set, the dim area was brilliantly white. The polar cap had become enlarged in the interim, apparently through a widespreading snowfall, by the annexation of a territory equal to that of the United States. The season was towards the close of winter in Mars. Never until then had the process of glacial extension been actually, it might be said, superintended in that distant globe. Mars was gratuitously supplied with a pair of satellites long before he was found actually to possess them. Kepler interpreted Galileo's anagram of the triple Saturn in this sense: they were perceived by Micromegas on his long voyage through space. And the Laputan astronomers had even arrived at a knowledge, curiously accurate under the circumstances, of their distances and periods. But terrestrial observers could see nothing of them until the night of August 11, 1877. The planet was then within 1 month of its second nearest approach to the Earth during the last century, and in 1845 the Washington 26-inch refractor was not in existence. Professor Asaph Hall, accordingly, determined to turn the conjecture to account for an exhaustive inquiry into the surroundings of Mars. Keeping his glaring disk just outside the field of view, a minute-attendant speck of light was glimpsed August 11. Bad weather, however, intervened, and it was not until the 16th that it was ascertained to be what it appeared, a satellite. On the following evening a second, still nearer to the primary, was discovered, which, by the bewildering rapidity of its passages hither and thither, produced at first the effect of quite a crowd of little moons. Both these delicate objects have since been repeatedly observed, both in Europe and America, even with comparatively small instruments. At the opposition of 1884, indeed, the distance of the planet was too great to permit of the detection of both elsewhere than at Washington. But the Lick equatorial showed them, July 18, 1888, when their brightness was only 0.12 its amount at the time of their discovery, so that they can now be followed for a considerable time before and after the least favorable oppositions. The names chosen for them were taken from the Iliad, where Deimos and Phobos, fear and panic, are represented as the companions in battle of Ares. In several respects, they are interesting and remarkable bodies. As to size, they may be said to stand midway between meteorites and satellites. From careful photometric measures executed at Harvard in 1877 and 1879, Professor Pickering concluded their diameters to be respectively 6 and 7 miles. This is on the assumption that they reflect the same proportion of the light incident upon them that their primary does. But it may very well be that they are less reflective, in which case they would be more extensive. The albedo of Mars is put by Muller at 0.27, his surface, in other words, returns 27% of the rays striking it. If we put the albedo of his satellites equal to that of our Moon, 0.17, their diameters will be increased from 6 and 7 to 7.5 and 9 miles, Phobos, the inner one, being the larger. Mr. Lowell, however, formed a considerably larger estimate of their dimensions. It is interesting to note that Deimos, according to Professor Pickering's very distinct perception, does not share the reddish tint of Mars. Deimos completes its nearly circular revolutions in 30 hours 18 minutes, at a distance from the surface of its ruling body of 12,500 miles. Phobos traverses an elliptical orbit in 7 hours 39 minutes 22 seconds, at a distance of only 3,760 miles. This is the only known instance of a satellite circulating faster than its primary rotates, and is a circumstance of some importance as regards theories of planetary development. To a Martian spectator the curious effect would ensue of a celestial object, seemingly exempt from the general motion of the sphere, rising in the west, setting in the east, and culminating twice, or even thrice a day. Which, moreover, in latitudes above 69 degrees north or south, would be permanently and altogether hidden by the intervening curvature of the globe. The detection of new members of the solar system has come to be one of the most ordinary of astronomical events. Since 1846 no single year has passed without bringing its tribute of asteroidal discovery. In the last of the 70s alone, a full score of miniature planets were distinguished from the thronging stars amid which they seemed to move. 1875 brought 17 such recognitions, their number touched a minimum of 1 in 1881. It rose in 1882, and again in 1886, to 11, dropped to 6 in 1889, and sprang up with the aid of photography to 27 in 1892. That high level has since, on an average, been maintained. And on January 1, 1902, nearly 500 asteroids were recognized as revolving between the orbits of Mars and Jupiter. Of these, considerably more than 100 are claimed by one investigator alone, Dr. Max Wolf of Heidelberg, M. Charleroi of Nice comes second with 102, while among the earlier observers Palisa of Vienna contributed 86, and C. H. F. Peters of Clinton, N.Y., whose varied and useful career terminated July 19, 1890, 52 to the grand total. The construction by Chacornac and his successors at Paris, and more recently by Peters at Clinton, of ecliptical charts showing all stars down to the 13th and 14th magnitudes respectively, rendered the picking out of moving objects above that brightness a mere question of time and diligence. Both, however, are vastly economized by the photographic method. Tedious comparisons of the sky with charts are no longer needed for the identification of unrecorded, because simulated stars. Planetary bodies declare themselves by appearing upon the plate, not in circular, but in linear form. Their motion converts their images into trails, long or short according to the time of exposure. The first asteroid, No. 323, thus detected was by Max Wolf, December 22, 1891. 18 others were similarly discovered in 1892, by the same skillful operator. And 10 more through Charleroi's adoption at Nice of the novel plan now in exclusive use for picking up errant light specks. Far more onerous than the task of their discovery is that of keeping them in view once discovered, of tracking out their paths, fixing their places, and calculating the disturbing effects upon them of the mighty Jovian mass. These complex operations have come to be centralized at Berlin under the superintendence of Professor Tietjen, and their results are given to the public through the medium of the Berliner Astronomisches Jahrbuch. The CUI Bono, however, began to be agitated. Was it worthwhile to maintain a staff of astronomers for the sole purpose of keeping hold over the identity of the innumerable component particles of a cosmical ring? The prospect, indeed, of all but a select few of the asteroids being thrown back by their contemptuous captors into the sea of space seemed so imminent that Professor Watson provided by will against the dereliction of the 22 discovered by himself. But the fortunes of the whole family improved through the distinction obtained by one of them. On August 14, 1898, the trail of a rapidly moving, star-like object of the 11th magnitude imprinted itself on a plate exposed by her wit at the Urania Observatory, Berlin. Its originator proved to be unique among asteroids. Eros is, in sober fact, one of those mysterious stars which hide themselves between the Earth and Mars. Divined or imagined by Shelley. True, several of its congeners invade the Martian sphere at intervals. But the proper habitat of Eros is within that limit, although its excursions transcend it. In other words, its mean distance from the Sun is about 135, as compared with the Martian distance of 141 million miles. Further, its orbit being so fortunately circumstanced as to bring it once in 67 years within some 15 millions of miles of the Earth, it is of extraordinary value to celestial surveyors. The calculation of its movements was much facilitated by detections, through a retrospective search, of many of its linear images among the stardots on the Harvard plates. The little body, which can scarcely be more than 20 miles in diameter, shows peculiarities of behavior as well as of position. Dr. von Apolzer, in February, 1901, announced it to be extensively and rapidly variable. Once in 2 hours 38 minutes it lost about 3/4 of its light, but these fluctuations quickly diminished in range, and in the beginning of May ceased altogether. Evidently, then, they depend upon the situation of the asteroid relatively to ourselves, and, so far, events lent countenance to M. André's eclipse hypothesis, since mutual occultations of the supposed planetary twins could only take place when the plane of their revolutions passed through the Earth, and this condition would be transitory. Yet the recognition in Eros of an Algol asteroid seems on other grounds inadmissible, nor until the phenomenon is conspicuously renewed, as it probably will be at the opposition of 1903, can there be much hope of finding its appropriate rationale. The crowd of orbits disclosed by asteroidal detections invites attentive study. D'Arrest remarked in 1851, when only 13 minor planets were known, that supposing their paths to be represented by solid hoops, not one of the 13 could be lifted from its place without bringing the others with it. The complexity of interwoven tracks thus illustrated has grown almost in the numerical proportion of discovery. Yet no two actually intersect, because no two lie exactly in the same plane, so that the chances of collision are at present nil. There is only one case, indeed, in which it seems to be eventually possible. M. Lesbiault has pointed out that the curves traversed by VIII and Maya approach so closely that a time may arrive when the bodies in question will either coalesce or unite to form a binary system. The maze threaded by the 500 asteroids contrasts singularly with the harmoniously ordered and rhythmically separated orbits of the larger planets. Yet the seeming confusion is not without a plan. The established rules of our system are far from being totally disregarded by its minor members. The orbit of Pallas, with its inclination of 34 degrees 42, touches the limit of departure from the ecliptic level. The average obliquity of the asteroidal paths is somewhat less than that of the Sun's equator. Their mean eccentricity is below that of the curve traced out by Mercury, and all without exception are pursued in the planetary direction, from west to east. The zone in which these small bodies travel is about 3 times as wide as the interval separating the Earth from the Sun. It extends perilously near to Jupiter, and dovetails into the sphere of Mars. Their distribution is very unequal. They are most densely congregated about the place where a single planet ought, by Bode's law, to revolve. It may indeed be said that only stragglers from the main body are found more than 50 million miles within or without a mean distance from the Sun 8 times that of the Earth. Significant gaps, too, occur where some force prohibitive of their presence would seem to be at work. The probable nature of that force was suggested by the late Professor Kirkwood, first in 1866, when the number of known asteroids was only 88, and again with more confidence in 1876, from the study of a list then run up to 172. It appears that these bare spaces are found just where a revolving body would have a period connected by a simple relation with that of Jupiter. It would perform 2 or 3 circuits to his 1, 5 to his 2, 9 to his 5, and so on. Kirkwood's inference was that the gaps in question were cleared of asteroids by the attractive influence of Jupiter. For disturbances recurring time after time, owing to commensurability of periods, nearly at the same part of the orbit, would have accumulated until the shape of that orbit was notably changed. The body thus displaced would have come in contact with other cosmical particles of the same family with itself, then, it may be assumed, more evenly scattered than now, would have coalesced with them, and permanently left its original track. In this way the regions of maximum perturbation would gradually have become denuded of their occupants. We can scarcely doubt that this law of commensurability has largely influenced the present distribution of the asteroids. But its effects must have been produced while they were still in an unformed, perhaps a nebular condition. In a system giving room for considerable modification through disturbance, the recurrence of conjunctions with a dominating mass at the same orbital point need not involve instability. On the whole, the correspondence of facts with Kirkwood's hypothesis has not been impaired by their more copious collection. Some chasms of secondary importance have indeed been bridged. But the principles stand out more conspicuously through the denser scattering of orbits near their margins. Nor is it doubtful that the influence of Jupiter in some way produced them. M. De Freycinet's study of the problem they present has, however, led him to the conclusion that they existed ab origin, thus testifying rather to the preventive than to the perturbing power of the giant planet. The existence, too, of numerous asteroidal pairs traveling in approximately coincident tracks, must date from a remote antiquity. They result, Professor Kirkwood believed, from the benevolent action of Jupiter upon embryo pygmy planets, just as comets moving in pursuit of one another are a consequence of the sundering influence of the Sun. Leverrier fixed, in 1853, 1/4 of the Earth's mass as the outside limit for the combined masses of all the bodies circulating between Mars and Jupiter, but it is far from probable that this maximum is at all nearly approached. M. Berberick held that the Moon would more than outweigh the whole of them, a million of the lesser bodies shining like stars of the 12th magnitude being needed, according to his judgment, to constitute her mass. And M. Neeson estimated that the whole of the 216 asteroids discovered up to August, 1880, amounted in volume to only 1/4000th of our globe, and we may safely add, since they are tolerably certain to be lighter, bulk for bulk, than the Earth, that their proportionate mass is smaller still. A fairly concordant result was published in 1895 by Mr. B. M. Rosell. He found that the lunar globe probably contains 40 times, the terrestrial globe 3,240 times the quantity of matter parceled out among the first 311 minor planets. The actual size of a few of them may now be said to be known. Professor Pickering, from determinations of light intensity, assigned to Vesta a diameter of 319 miles, to Pallas 167, to Juno 94, down to 12 and 14 for the smaller members of the group. An albedo equal to that of Mars was assumed as the basis of the calculation. Moreover, Professor G. Muller of Potsdam examined photometrically the phases of 7 among them, of which 4, namely, Vesta, Iris, Massalia, and Amphitrite, were found to conform precisely to the behavior of Mars as regards light change from position, while Ceres, Pallas, and Irene varied after the manner of the Moon and Mercury. The first group were hence inferred to resemble Mars in physical constitution, nature of atmosphere, and reflective capacity, the second to be moon-like bodies. Finally, Professor Barnard, directly measuring with the Yerkes refractor the minute disks presented by the original quartet, obtained the following authentic data concerning them: diameter of Ceres, 477 miles, albedo equals 0.18. Diameter of Pallas, 304 miles, albedo equals 0.23, diameter of Vesta, 239 miles, albedo equals 0.74, diameter of Juno, 120 miles, albedo equals 0.45. Thus, the rank of premier asteroid proves to belong to Ceres, and to have been erroneously assigned to Vesta in consequence of its deceptive brilliancy. What kind of surface this indicates, it is hard to say. The dazzling whiteness of snow can hardly be attributed to bare rock, yet the dynamical theory of gases, as Dr. Johnstone Stoney pointed out in 1867, prohibits the supposition that bodies of insignificant gravitative power can possess aerial envelopes. Even our Moon, it is calculated, could not permanently hold back the particles of oxygen, nitrogen, or water gas from escaping into infinite space, still less, a globe 1,000 times smaller. Vogel's suspicion of an airline in the spectrum of Vesta has, accordingly, not been confirmed. Crossing the zone of asteroids on our journey outward from the Sun, we meet with a group of bodies widely different from the inferior, or terrestrial planets. Their gigantic size, low specific gravity, and rapid rotation, obviously from the first through the superior planets into a class apart, and modern research has added qualities still more significant of a dissimilar physical constitution. Jupiter, a huge globe 86,000 miles in diameter, stands preeminent among them. He is, however, only primus inter pares. All the wider inferences regarding his condition may be extended, with little risk of error, to his fellows. And inferences in his case rest on surer grounds than in the case of the others, from the advantages offered for telescopic scrutiny by his comparative nearness. Now the characteristic modern discovery concerning Jupiter is that he is a body midway between the solar and terrestrial stages of cosmical existence, a decaying sun or a developing earth. As we choose to put it, whose vast unexpended stores of internal heat are mainly, if not solely, efficient in producing the interior agitations betrayed by the changing features of his visible disk. This view, impressed upon modern readers by Mr. Proctor's popular works, was anticipated in the last century. Buffon wrote in his Époques de la Nature, 1778, La surface de Jupiter est, comme elle en sait, sujet à de changements sensibles, que semblent indiquer que cette grosse planète est encore dans un état d'inconstance et de bouillonnement. Primitive incandescence, attendant, in his fantastic view, on planetary origin by cometary impacts with the Sun, combined, he concluded, with vast bulk to bring about this result. Jupiter has not yet had time to cool. Kant thought similarly in 1785. But the idea did not commend itself to the astronomers of the time, and dropped out of sight until Mr. Nasmyth arrived at it afresh in 1853. Even still, however, terrestrial analogies held their ground. The dark belts running parallel to the equator, first seen at Naples in 1630, continued to be associated, as Herschel had associated them in 1781, with Jovian trade winds, in raising which the deficient power of the Sun was supposed to be compensated by added swiftness of rotation. But opinion was not permitted to halt here. In 1860 G.P. Bond of Cambridge, U.S., derived some remarkable indications from experiments on the light of Jupiter. They showed that 14 times more of the photographic rays striking it are reflected by the planet than by our Moon, and that, unlike the Moon, which sends its densest rays from the margin, Jupiter is brightest near the center. But the most perplexing part of his results was that Jupiter actually seemed to give out more light than he received. Bond, however, rightly considered his data too uncertain for the support of so bold an assumption as that of original luminosity, and, even if the presence of native light were proved, thought that it might emanate from auroral clouds of the terrestrial kind. The conception of a sun-like planet was still a remote, and seemed an extravagant one. Only since it was adopted and enforced by Zollner in 1865, can it be regarded as permanently acquired to science. The rapid changes in the cloud belts both of Jupiter and Saturn, he remarked, attest a high internal temperature. For we know that all atmospheric movements on the Earth are sun heat transformed into motion. But sun heat at the distance of Jupiter possesses but 1/27th, at that of Saturn 1/100 of its force here. The large amount of energy, then, obviously exerted in those remote firmaments must have some other source, to be found nowhere else than in their own active and all-pervading fires, not yet banked in with a thick solid crust. The same acute investigator dwelt, in 1871, on the similarity between the modes of rotation of the great planets and of the Sun, applying the same principles of explanation to each case. The fact of this similarity is undoubted. Cassini and Schroeder both noticed that markings on Jupiter traveled quicker the nearer they were to his equator, and Cassini even hinted at their possible assimilation to sunspots. It is now well ascertained that, as a rule, not without exceptions, equatorial spots give a period some 5½ minutes shorter than those in latitudes of about 30 degrees. But, as Mr. Denning has pointed out, no single period will satisfy the observations either of different markings at the same epoch, or of the same markings at different epochs. Accelerations and retardations, depending upon processes of growth or change, take place in very much the same kind of way as in solar maculae, inevitably suggesting similarity of origin. The interesting query as to Jupiter's surface incandescence has been studied since Bond's time with the aid of all the appliances furnished to physical inquirers by modern inventiveness, yet without bringing to it a categorical reply. Zollner in 1865, Muller in 1893, estimated his albedo at 0.62 and 0.75 respectively, that of fresh-fallen snow being 0.78, and of white paper 0.70. But the disk of Jupiter is by no means purely white. The general ground is tinged with ochre. The polar zones are leaden or fawn-colored, large spaces are at times stained or suffused with chocolate browns and rosy hues. It is occasionally seen ruled from pole to pole with dusky bars, and is never wholly free from obscure markings. The reflection, then, by it, as a whole, of about 70% of the rays impinging upon it, might well suggest some original reinforcement. Nevertheless, the spectroscope gives little countenance to the supposition of any considerable permanent light emission. The spectrum of Jupiter, as examined by Huggins, 1862-64, and by Vogel, 1871–73, shows the familiar Fraunhofer rays belonging to reflected sunlight. But it also shows lines of native absorption. Some of these are identical with those produced by the action of our own atmosphere, especially one or more groups due to aqueous vapors, others are of unknown origin. And it is remarkable that one among the latter, a strong band in the red, agrees in position with a dark line in the spectra of some ruddy stars. There is, besides, a general absorption of blue rays, intensified, as Lesueur observed at Melbourne in 1869, in the dusky markings, evidently through an increase of depth in the atmospheric strata traversed by the light proceeding from them. All these observations, however, setting aside the stellar line as of doubtful significance, point to a cool planetary atmosphere. One spectrograph, it is true, taken by Dr. Henry Draper, September 27, 1879, seemed to attest the action of intrinsic light, but the peculiarity was referred by Dr. Vogel, with convincing clearness, to a flaw in the film. So far, then, native emissions from any part of Jupiter's diversified surface have not been detected. And, indeed, the blackness of the shadows cast by his satellites on his disk sufficiently proves that he sends out virtually none but reflected light. This conclusion, however, by no means invalidates that of his high internal temperature. The curious phenomena attending Jovian satellite transits may be explained, partly as effects of contrast, partly as due to temporary obscurations of the small disks projected on the large disk of Jupiter. At their first entry upon its marginal parts, which are several times less luminous than those near the center, they invariably show as bright spots, then usually vanish as the background gains luster, to reappear, after crossing the disk. Thrown into relief, as before, against the dusky limb. But instances are not rare, more especially of the third and fourth satellites standing out, during the entire middle part of their course, in such inky darkness as to be mistaken for their own shadows. The earliest witness of a black transit was Cassini, September 2, 1665, Romer in 1677, and Maraldi in 1707 and 1713, made similar observations, which have been multiplied in recent years. In some cases the process of darkening has been visibly attended by the formation, or emergence into view, of spots on the transiting body, as noted by the two Bonds at Harvard, March 18, 1848. The third satellite was seen by Dawes, half dark, half bright, when crossing Jupiter's disk, August 21, 1867, one-third dark by Davidson of California, January 15, 1884, under the same circumstances. And unmistakably spotted, both on and off the planet, by Schroeder, Secchi, Dawes, and Lassell. The first satellite sometimes looks dusky, but never absolutely black, in traveling over the disk of Jupiter. The second appears uniformly white, a circumstance attributed by Dr. Spitta to its high albedo. The singularly different aspects, even during successive transits, of the third and fourth satellites, are connected by Professor Holden with the varied luminosity of the segments of the planetary surface they are projected upon, and W.H. Pickering inclines to the same opinion, but fluctuations in their own brightness may be a concurrent cause. Herschel concluded in 1797 that, like our moon, they always turn the same face towards their primary, and as regards the outer satellite, Engelmann's researches in 1871, and C.E. Burton's in 1873, made this almost certain. While both for the third and fourth Jovian moons it was completely assured by W.H. Pickering's and A.E. Douglas's observations at Arequipa in 1892, and at Flagstaff in 1894–95. Strangely enough, however, the interior members of the system have preserved a relatively swift rotation, notwithstanding the enormous checking influence upon it of Jove-raised tides. All the satellites are stated, on good authority, to be more or less egg-shaped. On September 8, 1890, Barnard saw the first elongated and bisected by a bright equatorial belt, during one of its dark transits. And his observation, repeated August 3, 1891, was completely verified by Skeeberl and Campbell, who ascertained, moreover, that the longer axis of the prolate body was directed towards Jupiter's center. The ellipticity of its companions was determined by Pickering and Douglas, indeed, that of number 3 had long previously been noticed by Secchi. No. 3 also shows equatorial stripes, perceived in 1891 by Skibrel and Campbell, and evident later to Pickering and Douglas. Nor need we hesitate to admit as authentic their records of similar, though less conspicuous markings on the other satellites. A constitution analogous to that of Jupiter himself was thus unexpectedly suggested. And Vogel's detection of lines, or traces of lines, in their spectra, agreeing with absorption rays derived from their primary, lend support to the conjecture that they possess gaseous envelopes similar to his. The system of Jupiter, as it was discovered by Galileo, and investigated by Laplace, appeared in its outward aspect so symmetrical, and displayed in its inner mechanism such harmonious dynamical relations, that it might well have been deemed complete. Nevertheless, a new member has been added to it. Near midnight on September 9, 1892, Professor Barnard discerned with the Lick 36-inch a tiny speck of light, closely following the planet. He instantly divined its nature, watched its hurried disappearance in the adjacent glare, and made sure of the reality of his discovery on the ensuing night. It was a delicate business throughout, the Lilliputian luminary subsiding into invisibility before the slightest glint of Jovian light, and tarrying, only for brief intervals, far enough from the disk to admit of its exclusion by means of an occulting plate. The new satellite is estimated to be of the 13th stellar magnitude, and, if equally reflective of light with its next neighbor, Io, satellite number 1, its diameter must be about 100 miles. It revolves at a distance of 112,500 miles from Jupiter's center, and of 68,000 from his bulging equatorial surface. Its period of 11h. 57 m, 23s. Is just 2 hours longer than Jupiter's period of rotation, so that Phobos still remains a unique example of a secondary body revolving faster than its primary rotates. Jupiter's innermost moon conforms in its motion strictly, indeed inevitably, to the plane of his equatorial protuberance, following, however, a sensibly elliptical path the major axis of which is in rapid revolution. Its very insignificance raises the suspicion that it may not prove solitary. Possibly it belongs to a zone peopled by asteroidal satellites. More than 15,000 such small bodies could be furnished out of the materials of a single full-sized satellite spoiled in the making. But we must be content for the present to register the fact without seeking to penetrate the meaning of its existence. Very high and very fine telescopic power is needed for its perception. Outside the United States, it has been very little observed. The only instruments in this country successfully employed for its detection are, we believe, Dr. Common's 5-foot reflector and Mr. Newell's 25-inch refractor. In the course of his observations on Jupiter at Brussels in 1878, M. Neeson was struck with a rosy cloud attached to a whitish zone beneath the dark southern equatorial band. Its size was enormous. At the distance of Jupiter, its measured dimensions of 13 by 3 implied a real extension in longitude of 30,000, in latitude of something short of 7,000 miles. The earliest record of its appearance seems to be by Professor Pritchett, director of the Morrison Observatory, U.S., who figured and described it July 9, 1878. It was again delineated August 9, by Temple at Florence. In the following year it attracted the wonder and attention of almost every possessor of a telescope. Its color had by that time deepened into a full brick red, and was set off by contrast with a white equatorial spot of unusual brilliancy. During 3 ensuing years these remarkable objects continued to offer a visible and striking illustration of the compound nature of the planet's rotation. The red spot completed a circuit in 9 hours 55 minutes 36 seconds. The white spot in about 5.5 minutes less. Their relative motion was thus no less than 260 miles an hour, bringing them together in the same meridian at intervals of 44 days 10 hours 42 minutes. Neither, however, preserved continuously the same uniform rate of travel. The period of each had lengthened by some seconds in 1883, while sudden displacements, associated with the recovery of luster after recurrent fadings, were observed in the position of the white spot, recalling the leap forward of a reviving sunspot. Just the opposite effect attended the rekindling of the companion object. While semi-extinct in 1882–84, it lost little motion, but a fresh access of retardation was observed by Professor Young in connection with its brightening in 1886. This suggests very strongly that the red spot is fed from below. A shining aureola of faculae, described by Bredikhin at Moscow, and by Losey at Potsdam, as encircling it in September, 1879, was held to strengthen the solar analogy. The conspicuous visibility of this astonishing object lasted 3 years. When the planet returned to opposition in 1882–83, it had faded so considerably that Rico's uncertain glimpse of it at Palermo, May 31, 1883, was expected to be the last. It had, nevertheless, begun to recover in December, and presented to Mr. Denning in the beginning of 1886 much the same aspect as in October, 1882. Observed by him in an intermediate stage, February 25, 1885, when, a mere skeleton of its former self, it bore a striking likeness to an elliptical ring described in the same latitude by Mr. Gledhill in 1869–70. This, indeed, might be called the preliminary sketch for the famous object brought to perfection 10 years later, but which Mr. H.C. Russell of Sydney saw and drew still unfinished in June, 1876, before it had separated from its matrix, the dusky south tropical belt. In earlier times, too, a marking, at once fixed and transient, had been repeatedly perceived attached to the southernmost of the central belts. It gave Cassini in 1665 a rotation period of 9 hours 56 minutes, reappeared and vanished 8 times during the next 43 years, and was last seen by Maraldi in 1713. It was, however, very much smaller than the recent object, and showed no unusual color. The assiduous observations made on the Great Red Spot by Mr. Denning at Bristol and by Professor Hoff at Chicago afforded grounds only for negative conclusions as to its nature. It certainly did not represent the outpourings of a Jovian volcano. It was in no sense attached to the Jovian soil. If the phrase have any application to that planet, it was not a mere disclosure of a glowing mass elsewhere seethed over by rolling vapors. It was, indeed, certainly not self-luminous, a satellite projected upon it in transit having been seen to show as bright as upon the dusky equatorial bands. A fundamental objection to all 3 hypotheses is that the rotation of the spot was variable. It did not then ride at anchor, but floated free. Some held that its surface was depressed below the average cloud level, and that the cavity was filled with vapors. Professor Wilson, on the other hand, observing with the 16-inch equatorial of the Goodsell Observatory in Minnesota, received a persistent impression of the object being at a higher level than the other markings. A crucial experiment on this point was proposed by Mr. Stanley Williams in 1890. A dark spot moving faster along the same parallel was timed to overtake the red spot towards the end of July. A unique opportunity hence appeared to be at hand of determining the relative vertical depths of the 2 formations, one of which must inevitably, it was thought, pass above the other. No forecast included a third alternative, which was nevertheless adopted by the dark spot. It evaded the obstacle in its path by skirting round its southern edge. Nothing, then, was gained by the conjunction, beyond an additional proof of the singular repellent influence exerted by the red spot over the markings in its vicinity. It has, for example, gradually carved out a deep bay for its accommodation in the gray belt just north of it. The effect was not at first steadily present. A premonitory excavation was drawn by Schwab at Dessau, September 5, 1831, and again by Trouvelot, Barnard, and Elvins in 1879, yet there was no sign of it in the following year. Its development can be traced in Dr. Boedicker's beautiful delineations of Jupiter, made with the Parsonstown 3-foot reflector, from 1881 to 1886. They record the belt as straight in 1881, but as strongly indented from January, 1883, and the cavity now promises to outlast the spot. So long as it survives, however, the forces at work in the spot can have lost little of their activity. For it must be remembered that the belt has a shorter rotation period than the red spot, which, accordingly, as Mr. Elvins of Toronto has pointed out, breasts and diverts, by its interior energy, a current of flowing matter, ever ready to fill up its natural bed, and override the barrier of obstruction. The famous spot was described by Keeler in 1889, as, of a pale pink color, slightly lighter in the middle. Its outline was a fairly true ellipse, framed in by bright white clouds. The fading continuously in progress from 1887 was temporarily interrupted in 1891. The revival, indeed, was brief. Professor Barnard wrote in August, 1892, "The great red spot is still visible, but it has just passed through a crisis that seemingly threatened its very existence. For the past month it has been all but impossible to catch the feeblest trace of the spot, though the ever-persistent bay in the equatorial belt close north of it, and which has been so intimately connected with the history of the red spot, has been as conspicuous as ever. It is now, however, possible to detect traces of the entire spot. An obscuring medium seems to have been passing over it, and has now drifted somewhat preceding the spot. The object is now always inconspicuous, and often practically invisible, and may be said to float passively in the environing medium. Yet there are sparks beneath the ashes. A rosy tinge faintly suffused it in April, 1900, and its absolute end may still be remote. The extreme complexity of the planet's surface movements has been strikingly evinced by Mr. Stanley Williams's detailed investigations. He enumerated in 1896 9 principal currents, all flowing parallel to the equator, but unsymmetrically placed north and south of it, and showing scant signs of conformity to the solar rule of retardation with increase of latitude. The linear rate of the planet's equatorial rotation was spectroscopically determined by Bélopolsky and Deslandres in 1895. Both found it to fall short of the calculated speed, whence an enlargement, by self-refraction, of the apparent disk was inferred. Jupiter was systematically photographed with the Lick 36-inch telescope during the oppositions of 1890, 1891, and 1892, the image thrown on the plates, after eightfold direct enlargement, being 1 inch in diameter. Mr. Stanley Williams's measurements and discussion of the set for 1891 showed the high value of the materials thus collected, although much more minute details can be seen than can at present be photographed. The red spot shows as very distinctly annular in several of these pictures. Recently, the planet has been portrayed by Deslandres with the 62-foot Muden refractor. The extreme actinic feebleness of the equatorial bands was strikingly apparent on his plates. In 1870, Mr. Ranyard, whose death, December 14, 1894, was a serious loss to astronomy, acting upon an earlier suggestion of Sir William Huggins, collected records of unusual appearances on the disk of Jupiter, with a view to investigate the question of their recurrence at regular intervals. He concluded that the development of the deeper tinges of color, and of the equatorial porthole markings girdling the globe in regular alternations of bright and dusky, agreed, so far as could be ascertained, with epochs of sunspot maximum. The further inquiries of Dr. Losey at Bothkamp in 1873 went to strengthen the coincidence, which had been anticipated a priori by Zollner in 1871. Moreover, separate and distinct evidence was alleged by Mr. Denning in 1899 of decennial outbreaks of disturbance in north temperate regions. It may, indeed, be taken for granted that what Hahn terms the universal pulse of the solar system affects the vicissitudes of Jupiter. But the law of those vicissitudes is far from being so obviously subordinate to the rhythmical flow of central disturbance as are certain terrestrial phenomena. The great planet, being in fact himself a semi-sun, may be regarded as an originator, no less than a recipient, of agitating influences, the combined effects of which may well appear insubordinate to any obvious law. It is likely that Saturn is in a still earlier stage of planetary development than Jupiter. He is the lightest for his size of all the planets. In fact, he would float in water. And since his density is shown, by the amount of his equatorial bulging, to increase centrally, it follows that his superficial materials must be of a specific gravity so low as to be inconsistent, on any probable supposition, with the solid or liquid states. Moreover, the chief arguments in favor of the high temperature of Jupiter apply, with increased force, to Saturn. So that it may be concluded, without much risk of error, that a large proportion of his bulky globe, 73,000 miles in diameter, is composed of heated vapors, kept in active and agitated circulation by the process of cooling. His unique set of appendages has, since the middle of the last century, formed the subject of searching and fruitful inquiries, both theoretical and telescopic. The mechanical problem of the stability of Saturn's rings was left by Laplace in a very unsatisfactory condition. Considering them as rotating solid bodies, he pointed out that they could not maintain their position unless their weight were in some way unsymmetrically distributed, but made no attempt to determine the kind or amount of irregularity needed to secure this end. Some observations by Herschel gave astronomers an excuse for taking for granted the fulfillment of the condition thus vaguely postulated. And the question remained in abeyance until once more brought prominently forward by the discovery of the dusky ring in 1850. The younger Bond led the way, among modern observers, in denying the solidity of the structure. The fluctuations in its aspect were, he asserted in 1851, inconsistent with such a hypothesis. The fine dark lines of division, frequently detected in both bright rings, and as frequently relapsing into imperceptibility, were due, in his opinion, to the real nobility of their particles, and indicated a fluid formation. Professor Benjamin Pierce of Harvard University immediately followed with a demonstration, on abstract grounds, of their non-solidity. Streams of some fluid denser than water were, he maintained, the physical reality giving rise to the anomalous appearance first disclosed by Galileo's telescope. The mechanism of Saturn's rings, proposed as the subject of the Adams Prize, was dealt with by James Clerke Maxwell in 1857. His investigation forms the groundwork of all that is at present known in the matter. Its upshot was to show that neither solid nor fluid rings could continue to exist, and that the only possible composition of the system was by an aggregated multitude of unconnected particles, each revolving independently in a period corresponding to its distance from the planet. This idea of a satellite formation had been, remarkably enough, several times entertained and lost sight of. It was first put forward by Roberval in the 17th century, again by Jacques Cassini in 1715, and with perfect definiteness by Wright of Durham in 1750. Little heed, however, was taken of these casual anticipations of a truth which reappeared, a virtual novelty, as the legitimate outcome of the most refined modern methods. The details of telescopic observation accord, on the whole, admirably with this hypothesis. The displacements or disappearance of secondary dividing lines, the singular striated appearance, first remarked by Short in the 18th century, last by Perrotin and Lockyer at Nice, March 18, 1884, show the effects of waves of disturbance traversing a moving mass of gravitating particles. The broken and changing line of the planet's shadow on the ring gives evidence of variety in the planes of the orbits described by those particles. The whole ring system, too, appears to be somewhat elliptical. The satellite theory has derived unlooked-for support from photometric inquiries. Professor Seliger pointed out in 1888 that the unvarying brilliancy of the outer rings under all angles of illumination, from 0 degrees to 30 degrees, can be explained from no other point of view. Nor does the constitution of the obscure inner ring offer any difficulty. For it is doubtless formed of similar small bodies to those aggregated in the lucid members of the system, only much more thinly strewn, and reflecting, consequently, much less light. It is not, indeed, at first easy to see why these sparser flights should show as a dense dark shading on the body of Saturn. Yet this is invariably the case. The objection has been urged by Professor Hastings of Baltimore. The brightest parts of these appendages, he remarked, are more lustrous than the globe they encircle. But if the inner ring consists of identical materials, possessing presumably an equal reflective capacity, the mere fact of their scanty distribution would not cause them to show as dark against the same globe. Professor Seliger, however, replied that the darkening is due to the never-ending swarms of their separate shadows transiting the planet's disk. Sunlight is not, indeed, wholly excluded. Many rays come and go between the open ranks of the meteorites. For the dusky ring is transparent. The planet it encloses shows through it, as if veiled with a strip of crepe. A beautiful illustration of its quality in this respect was derived by Professor Barnard from an eclipse of Japetus, November 1, 1889. The eighth moon remained steadily visible during its passage through the shadow of the inner ring, but with a progressive loss of luster in approaching its bright neighbor. There was no breach of continuity. The satellite met no gap, corresponding to that between the dusky ring and the body of Saturn, through which it could shine with undiminished light, but was slowly lost sight of as it plunged into deeper and deeper gloom. The important facts were thus established, that the brilliant and obscure rings merge into each other, and that the latter thins out towards the Saturnian globe. The meteoric constitution of these appendages was beautifully demonstrated in 1895 by Professor Clerke, then director of the Allegheny Observatory, Pittsburgh. From spectrographs taken with the slit adjusted to coincidence with the equatorial plane of the system, he determined the comparative radial velocities of its different parts. And these supply a crucial test of Clerke-Maxwell's theory. For if the rings were solid, the swiftest rates of rotation should be at their outer edges, corresponding to wider circles described in the same period, while, if they are pulverulent, the inverse relation must hold good. This proved to be actually the case. The motion slowed off outward, in agreement with the diminishing speed of particles traveling freely, each in its own orbit. Keeler's result was promptly confirmed by Campbell, as well as by Deslandres and Belopolsky. A question of singular interest, and one which we cannot refrain from putting to ourselves, is, whether we see in the rings of Saturn a finished structure, destined to play a permanent part in the economy of the system. Or whether they represent merely a stage in the process of development out of the chaotic state in which it is impossible to doubt that the materials of all planets were originally merged. M. Otto Struve attempted to give a definite answer to this important query. A study of early and later records of observations disclosed to him, in 1851, an apparent progressive approach of the inner edge of the bright ring to the planet. The rate of approach he estimated at about 57 English miles a year, or 11,000 miles during the 194 years elapsed since the time of Huygens. Were it to continue, a collapse of the system must be far advanced within 3 centuries. But was the change real or illusory, a plausible, but deceptive inference from insecure data? M. Struve resolved to put it to the test. A set of elaborately careful micrometrical measures of the dimensions of Saturn's rings, executed by himself at Pulkowa in the autumn of 1851, was provided as a standard of future comparison. And he was enabled to renew them, under closely similar circumstances, in 1882. But the expected diminution of the space between Saturn's globe and his rings had not taken place. A slight extension in the width of the system, both outward and inward, was indeed hinted at. And it is worth notice that just such a separation of the rings was indicated by Clerke-Maxwell's theory, so that there is an a priori likelihood of its being in progress. Yet Hall's measures in 1884–87 failed to supply evidence of alteration with time, and Barnard's, executed at Lick in 1894–95, showed no sensible divergence from them. Hence, much weight cannot be laid upon Huygens's drawings and descriptions, which had been held to prove conclusively a partial filling up, since 1657, of the interval between the ring and the planet. The rings of Saturn replace, in Professor G.H. Darwin's view, an abortive satellite, scattered by tidal action into annular form. For they lie closer to the planet than is consistent with the integrity of a revolving body of reasonable bulk. The limit of possible existence for such a mass was fixed by Roche of Montpellier, in 1848, at 244 mean radii of its primary, while the outer edge of the ring system is distant 238 radii of Saturn from his center. The virtual discovery of its pulverulent condition dates, then, according to Professor Darwin, from 1848. He conjectures that the appendage will eventually disappear, partly through the dispersal of its constituent particles inward, and their subsidence upon the planet's surface, partly by their dispersal outward, to a region beyond Roche's limit, where coalescence might proceed unhindered by the strain of unequal attractions. One modest satellite, revolving inside Mimas, would then be all that was left of the singular appurtenances we now contemplate with admiration. There seems reason to admit that Kirkwood's law of commensurability has had some effect in bringing about the present distribution of the matter composing them. Here the influential bodies are Saturn's moons, while the divisions and boundaries of the rings represent the spaces where their disturbing action conspires to eliminate revolving particles. Kirkwood, in fact, showed, in 1867, that a body circulating in the chasm between the bright rings known as Cassini's division, would have a period nearly commensurable with those of 4 out of the 8 moons. And Meyer of Geneva subsequently calculated all such combinations, with the result of bringing out coincidences between regions of maximum perturbation and the limiting and dividing lines of the system. This is in itself a strong confirmation of the view that the rings are made up of independently revolving small bodies. On December 7, 1876, Professor Asaph Hall discovered at Washington a bright equatorial spot on Saturn, which he followed and measured through above 60 rotations, each performed in 10 hours 14 minutes 24 seconds. This, he was careful to add, represented the period, not necessarily of the planet, but only of the individual spot. The only previous determination of Saturn's axial movement, setting aside some insecure estimates by Schroeder, was Herschel's in 1794, giving a period of 10 hours 16 minutes. The substantial accuracy of Hall's result was verified by Mr. Denning in 1891. In May and June of that year, 10 vague bright markings near the equator were watched by Mr. Stanley Williams, who derived from them a rotation period only 2 seconds shorter than that determined at Washington. Nevertheless, similarly placed spots gave in 1892 and 1893 notably quicker rates. So that the task of timing the general drift of the Saturnian surface by the displacements of such objects is hampered, to an indefinite extent, by their individual proper motions. Saturn's outermost satellite, Japetus, is markedly variable, so variable that it sends us, when brightest, just 4.5 times as much light as when faintest. Moreover, its fluctuations depend upon its orbital position in such a way as to make it a conspicuous telescopic object when west, a scarcely discernible one when east of the planet. Herschel's inference of a partially obscured globe turning always the same face towards its primary seems the only admissible one, and is confirmed by Pickering's measurements of the varying intensity of its light. He remarked further that the dusky and brilliant hemispheres must be so posited as to divide the disk, viewed from Saturn, into nearly equal parts. So that this Saturnian moon, even when full, appears very imperfectly illuminated over 1/2 of its surface. Zollner estimated the albedo of Saturn at 0.51, Muller at 0.88, a value impossibly high, considering that the spectrum includes no vestige of original emissions. Closely similar to that of Jupiter, it shows the distinctive dark line in the red, wavelength 618, which we may call the red star line, and Janssen, from the summit of Etna in 1867 found traces in it of aqueous absorption. The light from the ring appears to be pure reflected sunshine unmodified by original atmospheric action. Uranus, when favorably situated, can easily be seen with the naked eye as a star between the 5th and 6th magnitudes. There is indeed some reason to suppose that he had been detected as a wandering orb by savage watchers of the skies in the Pacific long before he swam into Herschel's ken. Nevertheless, inquiries into his physical habitudes are still in an early stage. They are exceedingly difficult of execution, even with the best and largest modern telescopes, and their results remain clouded with uncertainty. It will be remembered that Uranus presents the unusual spectacle of a system of satellites traveling nearly at right angles to the plane of the ecliptic. The existence of this anomaly gives a special interest to investigations of his axial movement, which might be presumed, from the analogy of the other planets, to be executed in the same tilted plane. Yet this is far from being certainly the case. Mr. Buffum in 1870–72 caught traces of bright markings on the Uranian disk, doubtfully suggesting a rotation in about 12 hours in a plane not coincident with that in which his satellites circulate. Dusky bands resembling those of Jupiter, but very faint, were barely perceptible to Professor Young at Princeton in 1883. Yet, though almost necessarily inferred to be equatorial, they made a considerable angle with the trend of the satellite's orbits. More distinctly by the brothers Henry, with the aid of their fine refractor, two gray parallel rulings, separated by a brilliant zone, were discerned every clear night at Paris from January to June, 1884. What were taken to be the polar regions appeared comparatively dusky. The direction of the equatorial rulings, for so we may safely call them, made an angle of 40 degrees with the satellite's line of travel. Similar observations were made at Nice by M.M. Perrotin and Tholen, March to June, 1884, a lucid spot near the equator, in addition, indicating rotation in a period of about 10 hours. The discrepancy was, however, considerably reduced by Perrotin's study of the planet in 1889 with the new 30-inch equatorial. The dark bands, thus viewed to better advantage than in 1884, appeared to deviate no more than 10 degrees from the satellite's orbit plane. No definitive results, on the other hand, were derived by Professors Holden, Skeeberl, and Keeler from their observations of Uranus in 1889–90 with the potent instrument on Mount Hamilton. Shadings, it is true, were almost always, though faintly, seen, but they appeared under an anomalous, possibly an illusory aspect. They consisted, not of parallel, but of forked bands. Measurements of the little sea-green disk which represents to us the massive bulk of Uranus, by Young, Schiaparelli, Safric, H. C. Wilson and Perrotin, prove it to be quite distinctly bulged. The compression at once caught Barnard's trained eye in 1894, when he undertook at Lick a micrometrical investigation of the system. And he was surprised to perceive that the major axis of the elliptical surface made an angle of about 28 degrees with the line of travel pursued by the satellites. Nothing more can be learned on this curious subject for some years, since the pole of the planet is just now turned nearly towards the Earth, but Barnard's conclusion is unlikely to be seriously modified. He fixed the mean diameter of Uranus at 34,900 miles. But this estimate was materially reduced through Dr. C's elimination of irradiative effects by means of daylight measures, executed at Washington in 1901. The visual spectrum of this planet was first examined by Father Secchi in 1869, and later, with more advantages for accuracy, by Huggins, Vogel, and Keeler. It is a very remarkable one. In lieu of the reflected Fraunhofer lines, imperceptible perhaps through feebleness of light, 6 broad bands of original absorption appear, one corresponding to the blue-green ray of hydrogen, F. Another to the red star line of Jupiter and Saturn, the rest as yet unidentified. The hydrogen band seems much too strong and diffuse to be the mere echo of a solar line, and might accordingly be held to imply the presence of free hydrogen in the Uranian atmosphere. This, however, would be difficult of reconcilement with Keeler's identification of an absorption group in the yellow with a telluric water band. Notwithstanding its high albedo, 0.62, according to Zollner, proof is wanting that any of the light of Uranus is inherent. Mr. Albert Taylor announced, indeed, in 1889, his detection, with Common's giant reflector, of bright flutings in its spectrum, but Professor Keeler's examination proved them to be merely contrast effects. Sir William and Lady Huggins, moreover, obtained about the same time a photograph purely solar in character. The spectrum it represented was crossed by numerous Fraunhofer lines, and by no others. It was, then, presumably composed entirely of reflected light. Judging from the indications of an almost evanescent spectrum, Neptune, as regards physical condition, is the twin of Uranus, as Saturn of Jupiter. Of the circumstances of his rotation we are as good as completely ignorant. Mr. Maxwell Hall, indeed, noticed at Jamaica, in November and December, 1883, certain rhythmical fluctuations of brightness, suggesting revolution on an axis in slightly less than 8 hours. But Professor Pickering reduces the supposed variability to an amount altogether too small for certain perception, and Dr. G. Muller denies its existence in toto. It is true their observations were not precisely contemporaneous with those of Mr. Hall, who believes the partial obscurations recorded by himself to have been of a passing kind, and to have suddenly ceased after a fortnight of prevalence. Their less conspicuous renewal was visible to him in November, 1884, confirming a rotation period of 792 hours. It was ascertained at first by indirect means that the orbit of Neptune's satellite is inclined about 20 degrees to his equator. Mr. Marth, having drawn attention to the rapid shifting of its plane of motion, M. Tisserand and Professor Newcomb independently published the conclusion that such shifting necessarily results from Neptune's ellipsoidal shape. The movement is of the kind exemplified, although with inverted relations, in the precession of the equinoxes. The pole of the satellite, owing to the pole of Neptune's equatorial protuberance, describes a circle round the pole of his equator in a retrograde direction, and in a period of over 500 years. The amount of compression indicated for the primary body is, at the outside, 1/85, whence it can be inferred that Neptune possesses a lower rotatory velocity than the other giant planets. Direct verification of the trend theoretically inferred for the satellite's movement was obtained by Dr. C. in 1899. The Washington 26-inch refractor disclosed to him, under exceptionally favorable conditions, a set of equatorial belts on the disk of Neptune, and they took just the direction prescribed by theory. Their objective reality cannot be doubted, although Barnard was unable, either with the Lick or the Yerkes telescope, to detect any definite markings on this planet. Its diameter was found by him to be 32,900 miles. The possibility that Neptune may not be the most remote body circling round the Sun has been contemplated ever since he has been known to exist. Within the last few years the position at a given epoch of a planet far beyond his orbital verge has been approximately fixed by two separate investigators. Professor George Forbes of Edinburgh adopted in 1880 a novel plan of search for unknown members of the Solar System, the first idea of which was thrown out by M. Flammarion in November, 1879. It depends upon the movements of comets. It is well known that those of moderately short periods are, for a reason already explained, connected with the larger planets in such a way that the cometary aphelia fall near some planetary orbit. Jupiter claims a large retinue of such partial dependence, Neptune owns 6, and there are two considerable groups, the farthest distances of which from the Sun lie respectively near 100 and 300 times that of the Earth. At each of these vast intervals, one involving a period of 1,000, the other of 5,000 years, Professor Forbes maintains that an unseen planet circulates. He even computed elements for the nearer of the two, and fixed its place on the celestial sphere, but the photographic searches made for it by Dr. Roberts at Crowborough and by Mr. Wilson at Daramona proved unavailing. Undeterred by Dykemuller's discouraging opinion that cometary orbits extending beyond the recognized bounds of the Solar System are too imperfectly known to serve as the basis of trustworthy conclusions, the Edinburgh professor returned to the attack in 1901. He now sought to prove that the lost comet of 1556 actually returned in 1844, but with elements so transformed by ultra-Neptunian perturbations as to have escaped immediate identification. If so, the wanted planet has just entered the sign Libra, and, being larger than Jupiter, should be possible to find. Almost simultaneously with Forbes, Professor Todd set about groping for the same object by the help of a totally different set of indications. Adams's approved method commended itself to him. But the hypothetical divagations of Neptune having scarcely yet had time to develop, he was thrown back upon the residual errors of Uranus. They gave him a virtually identical situation for the new planet with that derived from the clustering of cometary aphelia. Yet its assigned distance was little more than half that of the nearer of Professor Forbes's remote pair, and it completed a revolution in 375 instead of 1,000 years. The agreement in them between the positions determined, on separate grounds, for the ultra-Neptunian traveler was merely an odd coincidence, nor can we be certain, until it is seen, that we have really got into touch with it. Footnotes. Phil. Trans, Volume 74, page 260. Novi Observations, page 105. Phil. Trans, Volume 1, page 243. MEM. De LAC, 1720, page 146. Phil. Trans, Volume 74, page 273. A large work, entitled Areographische Fragment, in which Schroeder embodied the results of his labors on Mars, 1785 to 1803, narrowly escaped the conflagration of 1813, and was published at Leiden in 1881. Beiträge, page 124. MEM. R. A. SOC, Volume 32, page 183. Astr. Knock, number 1468. Observatory, Volume 8, page 437. Month. Knot, Volumes 28, page 37, 29, page 232, 33, page 552. Flammarion, L'Astronomie, T.I., page 266. Smith, Cell. Cycle, Volume 1, page 148, first edition. Phil. Trans, Volume. XIII, page 417. Month. Knot, Volume 25, page 227. Phil. Mag, Volume 34, page 75. Proctor, Court. Jour of Science, Volume 10, page 185, Maunder, Sunday Mag, January, February, March, 1882, Campbell, Publ, Astra. Pack. SOC, Volume 6, page 273. AM. Jour. Of SC, Volume 28, page 163. Burton, Trans Roy. Dublin SOC, Volume 1, 1880, page 169. Month. Knot, Volume 27, page 179, Astroph. Journ, Volume 1, page 193. Untersuchungen über die Spektroderplane 10, page 20, Astroph. Journ, Volume 1, page 203. Publ. Astra. Pack. SOC, Volume 6, page 228, 9, page 109, Astra. An Astroph, Volume 13, page 752, Astroph. Jour, Volume 2, page 28. Ibid, Volume 5, page 328. Ibid, Volumes I, page 311, 3, page 254. C. Christensen, Bebladder, 1886, page 532. Astra. And Astrophysics, Volume 11, page 671. Flammarion, La Planète Mars, page 574. Memoirs Courants, t. 39. Lockyer, Nature, Volume 46, page 447. MEM. Specher. Italiani, t. 11, page 28. Bull. Astra, t. 3, page 324. Journ. Brit. Astra. As, Volume 1, page 88. Publ, Pack. Astra. SOC, Volume 2, page 299, Percival Lowell, Mars, 1896, Annals of the Lowell Observatory, Volume 2, 1900. Old and New Astra, page 545. L'Astronomie, t. 11, page 445. La Planète Mars, page 588. Month. Notices, Volume 56, page 166. L'Astronomie, t. 8. Astra. Knock, number 3271, Astra. And Astrophysics, Volume 13, page 716. Month. Knot, Volume 38, page 41, MEM. Roy. Astra. SOC, Volume 44, page 123. Astra. And Astrophysics, Volume 11, page 668. Ibid, page 850. Comptes rendus, T. CXV. Page 379. Astre. Jour, number 384, PUBL, Astre. Pack. SOC, Volume 6, page 109. CF Observatory Volume 17, pages 295 to 336. See Mr. Wentworth Earke's remarks in Trans Roy. Dublin SOC, Volume 1, page 29. Month. Knot, Volume 38, page 206. Annals Harvard Call. OBS, Volume 11, PT 2, page 217. Young, General Astre, page 366. Campbell, PUBL, Pack. Astre. SOC, Volume 6, page 270. Astre. Knock, number 3319. Witch of Atlas, stanza 3. I am indebted to Dr. Garnett for the reference. Recommended by Chandler, Astre. Jour. Number 452. Harvard Circulars, numbers 36, 37, 51. Astre. Knock, number 3687. Montangerand, Comptes Rendus, March 11, 1901. Pickering, Astroph. Jour, Volume 13, page 277. Harvard Circular, number 58. Astre. Knock, number 752. L. Neeson, and Ware, Bruxelles, 1881, page 269. According to Svedstrup, Astre. Knock, numbers 2240 to 41, the inclination to the ecliptic of the mean asteroid's orbit is equals 6 degrees. Smith's Report, 1876, page 358, the asteroids, Kirkwood, page 42, 1888. Tisserand, and Ware, Paris, 1891, p. b. 15, Newcomb, Astre. Jour, number 477, Backlund, Bull. Astre, T. 17, page 81, Parmentier, Bull. SOC Astre. De France, March, 1896, Observatory, Volume 18, page 207. Berberic, Astre. Knock, number 3088. Bull. Astre. T. 18, page 39. The Asteroids, page 48, PUBL, Astre. Pack. SOC, Volumes 2, page 48, 3, page 95. Comptes Rendus, T. 37, page 797. Bull. Astre, T. V, page 180. And Ware, Bruxelles, 1881, page 243. Johns Hopkins Uncircular, January, 1895. Observatory, Volume 18, page 127. Harvard Annals, Volume 11, Part 2, page 294. Astre. Knock, numbers 2724 to 5. Month. Knot, Volume 61, page 69. Astroph. Jour, Volume 7, page 25. Spectra der Plane 10, page 24. Tomei, page 93. Berlinische Monatschrift, 1785, page 211. Month. Knot, Volume 13, page 40. MEM. AM. AC, Volume 8, page 221. Photom, Unters, page 303. Astre. Knock, number 1851. MEM. De LAC, T. X, page 514. Ibid, 1692, page 7. Month. Knot, Volume 44, page 63. Photom. Unters, pages 165, 273, Potsdam PUBL, number 30. Vogel, SP der Plane 10, page 33, note. Proc. Roy. SOC, Volume 18, page 250. Month. Not, Volume 40, page 433. Sitzungsbericht, Berlin, 1895, 2, page 15. The anomalous shadow effects recorded by Webb, Cell. Objects, page 170, 4th edition, are obviously of atmospheric and optical origin. Engelmann, Über die Helligkeitsverhältnis der Jupiterstrabanten, page 59. Month. Not, Volume 28, page 11. Observatory, Volume 7, page 175. Month. Not, Volume 48, page 43. Publ, Astra. Pack. SOC, Volume 2, page 296. Pickering failed to obtain any photometric evidence of their variability. Harvard Annals, Volume 11, page 245. Astra. An Astroph, Volume 12, pages 194, 481. Annals Lowell OBS, Volume 2, PTI. Astra. Knock, Nos. 2995, 3206, month. Not, Volumes Lee, page 556, Liv, page 134. Barnard remains convinced that the oval forms attributed to Jupiter's satellites are illusory effects of their markings. Astra. Knock, numbers 3206, 3453, Astra. An Astroph, Volume 13, p. 272. Publ, Astra. Pack. SOC, Volume 3, page 355. Astra. Knock, number 1017. Publ, Astra. Pack. SOC, Volume 3, page 359. Astra. Knock, number 3432. Astra. Jour, numbers 275, 325, 367, 472, Observatory, Volume 15, page 425. Tisserand, Comptes Rendus, October 8, 1894. Cone, Astra. Knock, number 3404. Bull. A.C.R., Bruxelles, T. 48, page 607. Astra. Knock, number 2294. Ibid, number 2284. Denning, month. Not, Volume 44, pages 64, 66, Nature, Volume 25, page 226. Sidereal Mess, December, 1886, page 289. Astra. Knock, Nos. 2280, 2282. Month. Not, Volume 46, page 117. Proc. Roy. SOCN S. Wales, Volume 14, page 68. Phil. Trans, Volume 1, page 143. For indications relative to the early history of the red spot, see Holden, Publ, Astra. Pack. SOC, Volume 2, page 77. Noble, month. Not, Volume 47, page 515, A. S. Williams, Observatory, Volume 13, page 338. Astra. An Astrophysics, Volume 11, page 192. Month. Not, Volume 50, page 520. Observatory, Volume 13, pages 297, 326. Trans R. Dublin SOC, Volume 4, page 271, 1889. Publ, Astra. Pack. SOC, Volume 2, page 289. Astra. An Astrophysics, Volume 11, page 686. Denning, Knowledge, Volume 23, page 200, Observatory, Volume 24, page 312, Pop Astra, Volume 9, page 448, Nature, volume 55, page 89. Williams, Observatory, volume 23. Page 282. Month. Knot, volume 56, page 143. Belopolsky, Astro. Knock, number 3326. Publ, Astro. Pack. SOC, volume 4, page 176. Bull. Astro, 1900, page 70. Month. Knot, volume 31, page 34. Biobactingen, heft 2, page 99. Br. Sachs. Guess. Der Wiss, 1871, page 553. Month. Knot, volume 59, page 76. Beziehungen der Sonnenfleckenperiode, page 175. A. Hall, Astro. Knock, number 2269. Astro. Jour, Goulds, volume 2, page 17. Ibid, page 5. On the Stability of the Motion of Saturn's Rings, page 67. MEM. De LAC, 1715, page 47. Montucla, Histoire de Math, t. 4, page 19, An Original Theory of the Universe, page 115. Comptes Rendus, t. 98, page 718. Proctor, Saturn and its System, 1865, page 125. Periton, Comptes Rendus, t. CVI, page 1716. Ubhandel. Akkad. Der Wiss. Munich, BD, 16, page 407. Smiths. Report, 1880, Holden. Quoted by Drive E. Ending, Astro. Knock, number 2881. Astro. And Astrophysics, volume 11, page 119, month. Knot, volume 50, page 108. Astroph. Jour, volume 1, page 416. Ibid, volume 2, page 127. MEM. De LAC. Imp, St. Peter's, T. 7, 1853, page 464. Astro. Knock, number 2498. Washington Observations, App. 2, page 22. Month. Knot, volume 56, page 163. T. Lewis, Observatory, volume 18, page 379. Harper's Magazine, June, 1889. MEM. De l'Académique. De Montpellier, T. 8, page 296, 1873. Meteoric Astronomy, Chapter 12. He carried the subject somewhat farther in 1871. See Observatory, volume 6, page 335. Astro. Knock, number 2527. America Jour of SC, volume 14, page 325. Observatory, volume 14, page 369. Month. Knot, volume 54, page 297. Phil. Trans, volume 82, page 14. Smiths. Report, 1880. Comptes Rendus, T. 64, page 1304. Huggins, Proc. R. SOC, volume 46, page 231, Keeler, Astro. Knock, number 2927, Vogel, Astroph. Jour, volume 1, page 278. Month. Knot, volume 33, page 164. Astro. Knock, no 2545. Comptes Rendus, T. 98, page 1419. Comptes Rendus, T. 98, pages 718, 967. V. J. S. Astro. Guess, Jarg. 24, page 267. Publ, Astra. Pack. SOC, Volume 3, page 287. Astra. Knock, number 2526. Ibid, No. 2730. Astra. Jour, numbers 370, 374. Astra. Knock, number 3768. And de Phys, BD, Clavii, page 470, Astroph. Jour, volume 1, page 280. Astra. Knock, number 2927. Month. Knot, volume 49, page 405. Astra. Knock, number 2927, Scheiner's Spectral Analyse, page 221. Month. Knot, volume 44, page 257. Observatory, volume 7, pages 134, 221, 264. Month. Knot, volume 46, page 507. Comptes Rendus, T. Xi, page 804, Astra. And Astroph, volume 13, page 291, Astra. Jour, number 186. Astra. Jour, numbers 342, 436, 508. Astra. Pop. Page 661, La Nature, January 3, 1880. Proc. Roy. SOC Edin, Volumes X, page 429, 11, page 89. Viertelgerschrift. Astra. Guess, Jarg. 21, page 206. Proc. Roy. SOC Edin, Volume 23, page 370, Nature, Volume 64, page 524. America Jour of Science, Volume XX, page 225. Chapter 9. Theories of Planetary Evolution. We cannot doubt that the solar system, as we see it, is the result of some process of growth, that, during innumerable ages, the forces of nature were at work upon its materials, blindly modeling them into the shape appointed for them from the beginning by omnipotent wisdom. To set ourselves to inquire what that process was may be an audacity, but it is a legitimate, nay, an inevitable one. For man's implanted instinct to look before and after does not apply to his own little life alone, but regards the whole history of creation. From the highest to the lowest, from the microscopic germ of an alga or a fungus to the visible frame and furniture of the heavens. Kant considered that the inquiry into the mode of origin of the world was one of the easiest problems set by nature, but it cannot be said that his own solution of it was satisfactory. He, however, struck out in 1755 a track which thought still pursues. In his Allgemeine Naturgeschichte the growth of sun and planets was traced from the cradle of a vast and formless mass of evenly diffused particles. And the uniformity of their movements was sought to be accounted for by the unvarying action of attractive and repulsive forces, under the dominion of which their development was carried forward. In its modern form, that nebular hypothesis made its appearance in 1796. It was presented by Laplace with diffidence, as a speculation unfortified by numerical buttresses of any kind, yet with visible exultation at having, as he thought, penetrated the birth secret of our system. He demanded, indeed, more in the way of postulates than Kant had done. He started with a sun ready-made, and surrounded with a vast glowing atmosphere, extending into space out beyond the orbit of the farthest planet, and endowed with a slow rotatory motion. As this atmosphere or nebula cooled, it contracted. And as it contracted, its rotation, by a well-known mechanical law, became accelerated. At last a point arrived when tangential velocity at the equator increased beyond the power of gravity to control, and equilibrium was restored by the separation of a nebulous ring revolving in the same period as the generating mass. After a time, the ring broke up into fragments, all eventually reunited in a single revolving and rotating body. This was the first and farthest planet. Meanwhile the parent nebula continued to shrink and whirl quicker and quicker, passing, as it did so, through successive crises of instability, each resulting in, and terminated by, the formation of a planet, at a smaller distance from the center, and with a shorter period of revolution than its predecessor. In these secondary bodies the same process was repeated on a reduced scale, the birth of satellites ensuing upon their contraction, or not, according to circumstances. Saturn's ring, it was added, afforded a striking confirmation of the theory of annular separation, and appeared to have survived in its original form in order to throw light on the genesis of the whole solar system. While the four first discovered asteroids offered an example in which the debris of a shattered ring had failed to coalesce into a single globe. This scene of cosmical evolution was a characteristic bequest from the 18th century to the 19th. It possessed the self-sufficing symmetry and entireness appropriate to the ideas of a time of renovation, when the complexity of nature was little accounted of in comparison with the imperious orderliness of the thoughts of man. Since its promulgation, however, knowledge has transgressed many boundaries, and set at naught much ingenious theorizing. How has it fared with Laplace's sketch of the origin of the world? It has at least not been discarded as a feat. The groundwork of speculation on the subject is still furnished by it. It is, nevertheless, admittedly inadequate. Of much that exists it gives no account, or an erroneous one. The march of events certainly did not everywhere, even if it did anywhere, follow the exact path prescribed for it. Yet modern science attempts to supplement, but scarcely ventures to supersede it. Thought has, in many directions, been profoundly modified by Myers and Joule's discovery, in 1842, of the equivalence between heat and motion. Its corollary was the grand idea of the conservation of energy, now one of the cardinal principles of science. This means that, under the ordinary circumstances of observation, the old maxim ex nihilo nihil fit applies to force as well as to matter. The supplies of heat, light, electricity, must be kept up, or the stream will cease to flow. The question of the maintenance of the sun's heat was thus inevitably raised, and with the question of maintenance that of origin is indissolubly connected. Dar. Julius Robert Mayer, a physician residing at Heilbronn, was the first to apply the new light to the investigation of what Sir John Herschel had termed the great secret. He showed that if the sun were a body either simply cooling or in a state of combustion, it must long since have gone out. Had an equal mass of coal been set alight 4 or 5 centuries after the building of the Pyramid of Cheops, and kept burning at such a rate as to supply solar light and heat during the interim, only a few cinders would now remain in lieu of our undiminished glorious orb. Mayer looked round for an alternative. He found it in the meteoric hypothesis of solar conservation. The importance in the economy of our system of the bodies known as falling stars was then, in 1848, beginning to be recognized. It was known that they revolved in countless swarms round the sun, that the earth daily encountered millions of them, and it was surmised that the cone of the zodiacal light represented their visible condensation towards the attractive center. From the zodiacal light, then, Mayer derived the store needed for supporting the sun's radiations. He proved that, by the stoppage of their motion through falling into the sun, bodies would evolve from 4,600 to 9,200 times as much heat, according to their ultimate velocity, as would result from the burning of equal masses of coal. Their precipitation upon the sun's surface being brought about by the resisting medium observed to affect the revolutions of Encke's comet. There was, however, a difficulty. The quantity of matter needed to keep, by the sacrifice of its movement, the hearth of our system warm and bright would be very considerable. Meyer's lowest estimate put it at 94,000 billion kilograms per second, or a mass equal to that of our moon biannually. But so large an addition to the gravitating power of the sun would quickly become sensible in the movement of the bodies dependent upon him. Their revolutions would be notably accelerated. Mayer admitted that each year would be shorter than the previous one by a not insignificant fraction of a second, and postulated an unceasing waste of substance, such as Newton had supposed must accompany emission of the material corpuscles of light, to neutralize continual reinforcement. Meyer's views obtained a very small share of publicity, and owned Mr. Waterston as their independent author in this country. The meteoric, or dynamical, theory of solar sustentation was expounded by him before the British Association in 1853. It was developed with his usual ability by Lord Kelvin, in the following year. The inflow of meteorites, he remarked, is the only one of all conceivable causes of solar heat which we know to exist from independent evidence. We know it to exist, but we now also know it to be entirely insufficient. The supplies presumed to be contained in the zodiacal light would be quickly exhausted, a constant inflow from space would be needed to meet the demand. But if moving bodies were drawn into the sun at anything like the required rate, the air, even out here at 93 millions of miles distance, would be thick with them, the earth would be red-hot from their impacts. Geological deposits would be largely meteoric, to say nothing of the effects on the mechanism of the heavens. Lord Kelvin himself urged the inadmissibility of the extraplanetary theory of meteoric supply on the very tangible ground that, if it were true, the year would be shorter now, actually by 6 weeks, than at the opening of the Christian era. The intraplanetary supply, however, is too scanty to be anything more than a temporary makeshift. The meteoric hypothesis was naturally extended from the maintenance of the sun's heat to the formation of the bodies circling round him. The Earth, no less doubtless than the other planets, is still growing. Cosmical matter in the shape of falling stars and aerolites, to the amount, adopting Professor Newton's estimate, of 100 tons daily, is swept up by it as it pursues its orbital round. Inevitably the idea suggested itself that this process of appropriation gives the key to the life history of our globe. And that the momentary streak of fire in the summer sky represents a feeble survival of the glowing hailstorm by which in old times it was fashioned and warmed. Mr. E. W. Brayley supported this view of planetary production in 1864, and it has recommended itself to Haidinger, Helmholtz, Proctor, and Fay. But the negative evidence of geological deposits appears fatal to it. The theory of solar energy now generally regarded as the true one was announced by Helmholtz in a popular lecture in 1854. It depends upon the same principle of the equivalence of heat and motion which had suggested the meteoric hypothesis. But here the movement surrendered and transformed belongs to the particles, not of any foreign bodies, but of the sun itself. Drawn together from a wide ambit by the force of their own gravity, their fall towards the sun's center must have engendered a vast thermal store, of which 453/454 are computed to be already spent. Presumably, however, this stream of reinforcement is still flowing. In the very act of parting with heat, the sun develops a fresh stock. His radiations, in short, are the direct result of shrinkage through cooling. A diminution of the solar diameter by 380 feet yearly would just suffice to cover the present rate of emission, and would for ages remain imperceptible with our means of observation, since, after the lapse of 6,000 years, the lessening of angular size would scarcely amount to 1 second. But the process, though not terminated, is strictly a terminable one. In less than 5 million years, the sun will have contracted to half its present bulk. In 7 million more, it will be as dense as the Earth. It is difficult to believe that it will then be a luminous body. Nor can an unlimited past duration be admitted. Helmholtz considered that radiation might have gone on with its actual intensity for 22, Langley allows only 18 million years. The period can scarcely be stretched, by the most generous allowances, to double the latter figure. But this is far from meeting the demands of geologists and biologists. An attempt was made in 1881 to supply the sun with machinery analogous to that of a regenerative furnace, enabling it to consume the same fuel over and over again, and so to prolong indefinitely its beneficent existence. The inordinate waste of energy, which shocks our thrifty ideas, was simultaneously abolished. The Earth stops and turns variously to account 1/2250 millionth part of the solar radiations. Each of the other planets and satellites takes a proportionate share, the rest, being all but an infinitesimal fraction of the whole, is dissipated through endless space, to serve what purpose we know not. Now, on the late Sir William Siemens's plan, this reckless expenditure would cease, the solar incomings and outgoings would be regulated on approved economic principles, and the inevitable final bankruptcy would be staved off to remote ages. But there was a fatal flaw in its construction. He imagined a perpetual circulation of combustible materials, alternately surrendering and regaining chemical energy, the round being kept going by the motive force of the sun's rotation. This, however, was merely to perch the globe upon a tortoise, while leaving the tortoise in the air. The sun's rotation contains a certain definite amount of mechanical power, enough, according to Lord Kelvin, if directly converted into heat, to keep up the sun's emission during 116 years and 6 days, a mere moment in cosmical time. More economically applied, it would no doubt go farther. Its exhaustion would, nevertheless, under the most favorable circumstances, ensue in a comparatively short period. Many other objections equally unanswerable have been urged to the regenerative hypothesis, but this one suffices. Dr. Kroll's collision hypothesis is less demonstrably unsound, but scarcely less unsatisfactory. By the mutual impact of two dark masses rushing together with tremendous speed. He sought to provide the solar nebula with an immense original stock of heat for the reinforcement of that subsequently evolved in the course of its progressive contraction. The sun, while still living on its capital, would thus have a larger capital to live on, and the time demands of the less exacting geologists and biologists might be successfully met. But the primitive event, assumed for the purpose of dispensing them from the inconvenience of hurrying up their phenomena, is not one that a sane judgment can readily admit to have ever, in point of actual fact, happened. There remains, then, as the only intelligible rationale of solar sustentation, Helmholtz's shrinkage theory. And this has a very important bearing upon the nebular view of planetary formation. It may, in fact, be termed its complement. For it involves the idea that the sun's materials, once enormously diffused, gradually condensed to their present volume with development of heat and light, and, it may plausibly be added, with the separation of dependent globes. The data furnished by spectrum analysis, too, favor the supposition of a common origin for sun and planets by showing their community of substance. While gaseous nebulae present examples of vast masses of tenuous vapor, such as our system may plausibly be conjectured to have primitively sprung from. But recent science raises many objections to the details, if it supplies some degree of confirmation to the fundamental idea of Laplace's cosmogony. The detection of the retrograde movement of Neptune's satellite made it plain that the anomalous conditions of the Uranian world were due to no extraordinary disturbance, but to a systematic variety of arrangement at the outskirts of the solar domain. So that, were a trans-Neptunian planet discovered, we should be fully prepared to find it rotating, and surrounded by satellites circulating from east to west. The uniformity of movement, upon the probabilities connected with which the French geometer mainly based his scheme, thus at once vanishes. The excessively rapid revolution of the inner Martian moon is a further stumbling block. On Laplace's view, no satellite can revolve in a shorter time than its primary rotates, for in its period of circulation survives the period of rotation of the parent mass which filled the sphere of its orbit at the time of giving it birth. And rotation quickens as contraction goes on, therefore, the older time of axial rotation should invariably be the longer. This obstacle can, however, as we shall presently see, be turned. More serious is one connected with the planetary periods, pointed out by Babinet in 1861. In order to make them fit in with the hypothesis of successive separation from a rotating and contracting body, certain arbitrary assumptions have to be made of fluctuations in the distribution of the matter forming that body at the various epochs of separation. Such expedients usually merit the distrust which they inspire. Primitive and permanent irregularities of density in the solar nebula, such as Miss Young's calculations suggest, do not, on the other hand, appear intrinsically improbable. Again, it was objected by Professor Kirkwood in 1869 that there could be no sufficient cohesion in such an enormously diffused mass as the planets are supposed to have sprung from to account for the wide intervals between them. The matter separated through the growing excess of centrifugal speed would have been cast off, not by rarely recurring efforts, but continually, fragmentarily, pari passu with condensation and acceleration. Each wisp of nebula, as it found itself unduly hurried, would have declared its independence, and set about revolving and condensing on its own account. The result would have been a meteoric, not a planetary system. Moreover, it is a question whether the relative ages of the planets do not follow an order just the reverse of that concluded by Laplace. Professor Newcomb holds the opinion that the rings which eventually constituted the planets divided from the main body of the nebula almost simultaneously, priority, if there were any, being on the side of the inner and smaller ones, while in M. phase cosmogony, the retrograde motion of the systems formed by the two outer planets is ascribed, on grounds, it is true, of dubious validity, to their comparatively late origin. This ingenious scheme was designed, not merely to complete, but to supersede that of Laplace, which, undoubtedly, through the inclusion by our system of oppositely directed rotations, forfeits its claim simply and singly to account for the fundamental peculiarities of its structure. M. phase leading contention is that, under the circumstances assumed by Laplace, not the two outer planets alone, but the whole company must have been possessed of retrograde rotation. For they were formed, ex hypothesi, after the Sun. Central condensation had reached an advanced stage when the rings they were derived from separated, the principle of inverse squares consequently held good, and Kepler's laws were in full operation. Now, particles circulating in obedience to these laws can only, since their velocity decreases outward from the center of attraction, coalesce into a globe with a backward axial movement. Nor was Laplace blind to this flaw in his theory. But his effort to remove it, though it passed muster for the best part of a century, was scarcely successful. His planet-forming rings were made to rotate all in one piece, their outer parts thus necessarily traveling at a swifter linear rate than their inner parts, and eventually uniting, equally of necessity, into a forward-spinning body. The strength of cohesion involved may, however, safely be called impossible, especially when it is considered that nebulous materials were in question. The reform proposed by M. phase consists in admitting that all the planets inside Uranus are of pre-solar origin, that they took globular form in the bosom of a nearly homogeneous nebula, revolving in a single period, with motion accelerated from center to circumference, and hence agglomerating into masses with a direct rotation. Uranus and Neptune owe their exceptional characteristics to their later birth. When they came into existence, the development of the Sun was already far advanced, central force had acquired virtually its present strength, unity of period had been abolished by its predominance, and motion was retarded outward. Thus, what we may call the relative chronology of the solar system is thrown once more into confusion. The order of seniority of the planets is now no easier to determine than the who first, who last, among the victims of Hector's spear. For M. phase arrangements, notwithstanding the skill with which he has presented them, cannot be unreservedly accepted. The objections to them, thoughtfully urged by M. C. Wolf and Professor Darwin, are grave. Not the least so is his omission to take account of an agency of change presently to be noticed. A further valuable discussion of the matter was published by M. du Liggins in 1897. His views are those of Faye, modified to disarm the criticisms they had encountered. And special attention may be claimed for his weighty remark that each planet has a life history of its own, essentially distinct from those of the others, and, despite original unity, not to be confounded with them. The drift of recent investigations seems, indeed, to be to find the embryonic solar system already potentially complete in the parent nebula, like the oak in an acorn, and to relegate detailed explanations of its peculiarities to the dim prenebular foretime. We now come to a most remarkable investigation, one, indeed, unique in its profession to lead us back with mathematical certainty towards the origin of a heavenly body. We refer to Professor Darwin's inquiries into the former relations of the Earth and Moon. They deal exclusively with the effects of tidal friction, and primarily with those resulting, not from oceanic, but from bodily tides, such as the Sun and Moon must have raised in past ages on a liquid or viscous earth. The immediate effect of either is, as already explained, to destroy the rotation of the body on which the tide is raised, as regards the tide-raising body, bringing it to turn always the same face towards its disturber. This, we can see, has been completely brought about in the case of the Moon. There is, however, a secondary or reactive effect. Action is always mutual. Precisely as much as the Moon pulls the terrestrial tidal wave backward, the tidal wave pulls the Moon forward. But pulling a body forward in its orbit implies the enlargement of that orbit. In other words, the Moon is, as a consequence of tidal friction, very slowly receding from the Earth. This will go on, other circumstances remaining unchanged, until the lengthening day overtakes the more tardily lengthening month, when each will be of about 1,400 hours. A position of what we may call tidal equilibrium between Earth and Moon will, apart from disturbance by other bodies, then be attained. If, however, it be true that, in the time to come, the Moon will be much farther from us, it follows that in the time past she was much nearer to us than she now is. Tracing back her history by the aid of Professor Darwin's clue, we at length find her revolving in a period of somewhere between 2 and 4 hours, almost in contact with an Earth rotating just at the same rate. This was before tidal friction had begun its work of grinding down axial velocity and expanding orbital range. But the position was not one of stable equilibrium. The slightest inequality must have set on foot a series of uncompensated changes. If the Moon had whirled the least iota faster than the Earth spun, she must have been precipitated upon it. Her actual existence shows that the trembling balance inclined the other way. By a second or two to begin with, the month exceeded the day. The tidal wave crept ahead of the Moon, tidal friction came into play, and our satellite started on its long spiral journey outward from the parent globe. This must have occurred, it is computed, at least 54 million years ago. That this kind of tidal reactive effect played its part in bringing the Moon into its present position, and is still, to some slight extent, at work in changing it, there can be no doubt whatever. An irresistible conjecture carried the explorer of its rigidly deducible consequences one step beyond them. The Moon's time of revolution, when so near the Earth as barely to escape contact with it, must have been, by Kepler's law, more than 2 and less than 2.5 hours. Now it happens that the most rapid rate of rotation of a fluid mass of the Earth's average density, consistent with spheroidal equilibrium, is 2 hours and 20 minutes. Quicken the movement but by 1 second and the globe must fly asunder. Hence the inference that the Earth actually did fly asunder through overfast spinning, the ensuing disruption representing the birth throes of the Moon. It is likely that the event was hastened or helped by solar tidal disturbance. To recapitulate. Analysis tracks backward the two bodies until it leaves them in very close contiguity, one rotating and the other revolving in approximately the same time, and that time certainly not far different from, and quite possibly identical with, the critical period of instability for the terrestrial spheroid. Is this, Professor Darwin asks, a mere coincidence, or does it not rather point to the breakup of the primeval planet into two masses in consequence of a too rapid rotation? We are tempted, but are not allowed to give an unqualified assent. Mr. James Nolan of Victoria has made it clear that the Moon could not have subsisted as a continuous mass under the powerful disruptive strain which would have acted upon it when revolving almost in contact with the present surface of the Earth. And Professor Darwin, admitting the objection, concedes to our satellite, in its initial stage, the alternative form of a flock of meteorites. But such a congregation must have been quickly dispersed, by tidal action, into a meteoric ring. The same investigator subsequently fixed 6,500 miles from center to center as the minimum distance at which the Moon could have revolved in its entirety. And he concluded it necessary to suppose that, after the birth of a satellite, if it takes place at all in this way, a series of changes occur which are quite unknown. The evidence, however, for the efficiency of tidal friction in bringing about the actual configuration of the lunar terrestrial system is not invalidated by this failure to penetrate its natal mystery. Under its influence the principal elements of that system fall into interdependent mutual relations. It connects, casually and quantitatively, the periods of the Moon's revolution and of the Earth's rotation, the obliquity of the ecliptic, the inclination and eccentricity of the lunar orbit. All this can scarcely be accidental. Professor Darwin's first researches on this subject were communicated to the Royal Society, December 18, 1879. They were followed, January 20, 1881, by an inquiry on the same principles into the earlier condition of the entire solar system. The results were a warning against hasty generalization. They showed that the lunar terrestrial system, far from being a pattern for their development, was a singular exception among the bodies swayed by the sun. Its peculiarity resides in the fact that the moon is proportionately by far the most massive attendant upon any known planet. Its disturbing power over its primary is thus abnormally great, and tidal friction has, in consequence, played a predominant part in bringing their mutual relations into their present state. The comparatively late birth of the moon tends to ratify this inference. The dimensions of the Earth did not differ, according to our present authority, very greatly from what they now are when her solitary offspring came, somehow, into existence. This is found not to have been the case with any other of the planets. It is unlikely that the satellites of Jupiter, Saturn, or Mars, we may safely add, of Uranus or Neptune, ever revolved in much narrower orbits than those they now traverse. It is practically certain that they did not, like our moon, originate very near the present surfaces of their primaries. What follows? The tide-raising power of a body grows with vicinity in a rapidly accelerated ratio. Lunar tides must then have been on an enormous scale when the moon swung round at a fraction of its actual distance from the Earth. But no other satellite with which we are acquainted occupied at any time a corresponding position. Hence no other satellite ever possessed tide-raising capabilities in the least comparable to those of the moon. We conclude once more that tidal friction had an influence here very different from its influence elsewhere. Quite possibly, however, that influence may be more nearly spent than in less advanced combinations of revolving globes. Mr. Nolan concluded in 1895 that it still retains appreciable efficacy in the several domains of the outer planets. The moons of Jupiter and Saturn are, by his calculations, in course of sensible retreat, under compulsion of the perennial ripples raised by them on the surfaces of their gigantic primaries. He thus connects the interior position of the fifth Jovian satellite with its small mass. The feebleness of its tide-raising power obliged it to remain behind its companions. For there is no sign of its being more juvenile than the Galilean quartet. The yielding of plastic bodies to the strain of unequal attractions is a phenomenon of far-reaching consequence. We know that the sun as well as the moon causes tides in our oceans. There must, then, be solar, no less than lunar, tidal friction. The question at once arises, what part has it played in the development of the solar system? Has it ever been one of leading importance, or has its influence always been, as it now is, subordinate, almost negligible? To this, too, Professor Darwin supplies an answer. It can be stated without hesitation that the sun did not give birth to the planets, as the Earth has been supposed to have given birth to the moon, by the disruption of its already condensed, though viscous and glowing mass, pushing them then gradually backward from its surface into their present places. For the utmost possible increase in the length of the year through tidal friction is 1 hour, and 5 minutes is a more probable estimate. So far as the pull of tide waves raised on the sun by the planets is concerned, then, the distances of the latter have never been notably different from what they now are. Though that cause may have converted the paths traversed by them from circles into ellipses. Over their physical history, however, it was probably in a large measure influential. The first vital issue for each of them was, satellites or no satellites. Were they to be governors as well as governed, or should they revolve in sterile isolation throughout the eons of their future existence? Here there is strong reason to believe that solar tidal friction was the overruling power. It is remarkable that planetary fecundity increases, at least so far outward as Saturn, with distance from the Sun. Can these two facts be in any way related? In other words, is there any conceivable way by which tidal influence could prevent or impede the throwing off of secondary bodies? We have only to think for a moment in order to see that this is precisely one of its direct results. Tidal friction, whether solar or lunar, tends to reduce the axial movement of the body it acts upon. But the separation of satellites depends, according to the received view, upon the attainment of a disruptive rate of rotation. Hence, if solar tidal friction were strong enough to keep down the pace below this critical point, the contracting mass would remain intact, there would be no satellite production. This, in all probability, actually occurred in the case both of Mercury and Venus. They cooled without dividing, because the solar friction brake applied to them was too strong to permit acceleration to pass the limit of equilibrium. The complete destruction of their relative axial movement has been rendered probable by recent observations, and that the process went on rapidly is a reasonable further inference. The Earth barely escaped the fate of loneliness incurred by her neighbors. Her first and only epoch of instability was retarded until she had nearly reached maturity. The late appearance of the Moon accounts for its large relative size, through the increased cohesion of an already strongly condensed parent mass, and for the distinctive peculiarities of its history and influence on the producing globe. Solar tidal friction, although it did not hinder the formation of 2-minute dependence of Mars, has been invoked to explain the anomalously rapid revolution of one of them. Phobos, we have seen, completes more than 3 revolutions while Mars rotates once. But this was probably not always so. The 2 periods were originally nearly equal. The difference, it is alleged, was brought about by tidal waves raised by the Sun on the semi-fluid spheroid of Mars. Rotatory velocity was thereby destroyed, the Martian day slowly lengthened, and, as a secondary consequence, the period of the inner satellite, become shorter than the augmented day, began progressively to diminish. So that Phobos, unlike our Moon, was in the beginning farther from its primary than now. But here again Mr. Nolan entered a caveat. Applying the simple test of numerical evaluation, he showed that before solar tidal friction could lengthen the rotation period of Mars by so much as 1 minute, Phobos should have been precipitated upon its surface. For the enormous disparity of mass between it and the Sun is so far neutralized by the enormous disparity in their respective distances from Mars that solar tidal force there is only 50 times that of the little satellite. But the tidal effects of a satellite circulating quicker than its primary rotates exactly reverse those of one moving, like our Moon, comparatively slowly, so that the tides raised by Phobos tend to shorten both periods. Its orbital momentum, however, is so extremely small in proportion to the rotational momentum of Mars, that any perceptible inroad upon the latter is attended by a lavish and ruinous expenditure of the former. It is as if a man owning a single 5-pound note were to play for equal stakes with a man possessing $1 million. The bankruptcy sure to ensue is typified by the coming fate of the Martian inner satellite. The catastrophe of its fall needs to bring it about only a very feeble reactive pull compared with the friction which the Sun should apply in order to protract the Martian day by 1 minute. And from the proportionate strength of the forces at work, it is quite certain that one result cannot take place without the other. Nor can things have been materially different in the past. Hence the idea must be abandoned that the primitive time of rotation of Mars survives in the period of its inner satellite. The anomalous shortness of the latter may, however, in M. Wolf's opinion, be explained by the traînées elliptiques with which Roche supplemented nebular annulation. These are traced back to the descent of separating strata from the shoulders of the great nebulous spheroid towards its equatorial plane. Their rotational velocity being thus relatively small, they formed inner rings, very much nearer to the center of condensation than would have been possible on the unmodified theory of Laplace. Phobos might, in this view, be called a polar offset of Mars, and the rings of Saturn are thought to own a similar origin. Outside the orbit of Mars, solar tidal friction can scarcely be said to possess at present any sensible power. But it is far from certain that this was always so. It seems not unlikely that its influence was the overruling one in determining the direction of planetary rotation. M. Faye, as we have seen, objected to Laplace's scheme that only retrograde secondary systems could be produced by it. In this he was anticipated by Kirkwood, who, however, supplied an answer to his own objection. Sun-rays tides must have acted with great power on the diffused masses of the embryo planets. By their means they doubtless very soon came to turn, in lunar fashion, the same hemisphere always towards their center of motion. This amounts to saying that even if they started with retrograde rotation, it was, by solar tidal friction, quickly rendered direct. For it is scarcely necessary to point out that a planet turning an invariable face to the Sun rotates in the same direction in which it revolves, and in the same period. As, with the progress of condensation, tides became feebler and rotation more rapid, the accelerated spinning necessarily proceeded in the sense thus prescribed for it. Hence the backward axial movements of Uranus and Neptune may very well be a survival, due to the inefficiency of solar tides at their great distance, of a state of things originally prevailing universally throughout the system. The general outcome of Mr. Darwin's researches has been to leave Laplace's cosmogony untouched. He concludes nothing against it, and, what perhaps tells with more weight in the long run, has nothing to substitute for it. In one form or the other, if we speculate at all on the development of the planetary system, our speculations are driven into conformity with the broad lines of the nebular hypothesis, to the extent, at least, of admitting an original material unity and motive uniformity. But we can see now, better than formerly, that these supply a bare and imperfect sketch of the truth. We should err gravely were we to suppose it possible to reconstruct, with the help of any knowledge our race is ever likely to possess, the real and complete history of our admirable system. The subtlety of nature, Bacon says, transcends in many ways the subtlety of the intellect and senses of man. By no mere barren formula of evolution, indiscriminately applied all round, the results we marvel at, and by a fragment of which our life is conditioned, were brought forth. But by the manifold play of interacting forces, variously modified and variously prevailing, according to the local requirements of the design they were appointed to execute. Footnotes. Exposition du Système du Monde, T. 2, page 295. In later editions a retrospective clause was added admitting a prior condition of all but evanescent nebulosity. Mech. Cell, Lib 14, ch 3. Beitrag zur Dynamik des Himmels, page 12. Trans Roy. SOC of Edinburgh, volume 21, page 66. Newcomb, Pop. Astre, page 521, 2nd edition. M. Williams, Nature, volume 3, page 26. Comp. Brit. Almanac, page 94. Radeau, Bull. Astre, T. 2, page 316. Newcomb, Pop. Astre, pages 521 to 525. Proc. Roy. SOC, volume 33, page 393. To this hostile argument, as urged by Mr. E. Douglas Archibald, Sir W. Siemens opposed the increase of rotative velocity through contraction, Nature, volume 25, page 505. But contraction cannot restore lost momentum. Stellar Evolution, and its Relations to Geological Time, 1889. Comptes Rendus, T. Lee, page 481. See also Kirkwood, Observatory, volume 3, page 409. Fouché, Comptes Rendus, T. 99, page 903. Astroph. Jour, volume 13, page 338. Month. Not, volume 29, page 96. Pop. Astre, page 257. Sur l'origine du monde, 1884. Kirkwood adverted to it in 1864, A.M. Jour, volume 38, page 1. Bull. Astre, T. 2. Nature, volume 31, page 506. Formation mécanique du système du monde, Bull. Astre, T. 14, page 313, O. Calandro. See also, Le Problème solaire, by l'Abbé Th. Morux, 1900. Phil. Trans, volume Clerke, page 713. Mr. J. Nolan has pointed out, Nature, volume 34, page 287, that the length of the equal day and month will be reduced to about 1,240 hours by the effects of solar tidal friction. Phil. Trans, Vol. XIII, page 835. Nature, Volume 33, page 368, see also Nolan, Ibid, Volume 34, page 286. Phil. Trans, Volume XIII, page 422. Ibid, Volume XIII, page 491. Ibid, page 530. Satellite Evolution, Melbourne, 1895, Knowledge, Volume 18, page 205. Phil. Trans, Volume XIII, page 533. This was perceived by M. ed. Roche in 1872. MEM. De l'Académique. Des Sciences de Montpellier, T. 8, page 247. Nature, Volume 34, page 287. Bull. Astre, T. 2, page 223. Montpellier Mems, T. 8, page 242. America Jour, Volume 38, 1864, page 1. Wolf, Bull. Astre, T. 2, page 76. Chapter 10. Recent Comets. On the 2nd of June, 1858, Giambattista Donati discovered at Florence a feeble round nebulosity in the constellation Leo, about 1/10 the diameter of the full moon. It proved to be a comet approaching the Sun. But it changed little in apparent place or brightness for some weeks. The gradual development of a central condensation of light was the first symptom of coming splendor. At Harvard, in the middle of July, a strong stellar nucleus was seen. On August 14 a tail began to be thrown out. As the comet wanted still over 6 weeks of the time of its perihelion passage, it was obvious that great things might be expected of it. They did not fail of realization. Not before the early days of September was it generally recognized with the naked eye, though it had been detected without a glass at Pulkowa, August 19. But its growth was thenceforward surprisingly rapid, as it swept with accelerated motion under the hindmost foot of the Great Bear, and past the starry locks of Berenice. A sudden leap upward in luster was noticed on September 12, when the nucleus shone with about the brightness of the pole star, and the tail, notwithstanding large foreshortening, could be traced with the lowest telescopic power over 6 degrees of the sphere. The appendage, however, attained its full development only after perihelion, September 30, by which time, too, it lay nearly square to the line of sight from the Earth. On October 10 it stretched in a magnificent scimitar-like curve over a third and upwards of the visible hemisphere, representing a real extension in space of 54 million miles. But the most striking view was presented on October 5, when the brilliant star Arcturus became involved in the brightest part of the tail, and during many hours contributed, its luster undiminished by the interposed nebula screen, to heighten the grandeur of the most majestic celestial object of which living memories retain the impress. Donati's comet was, according to Admiral Smith's testimony, outdone, as a mere sight object, by the great comet of 1811, but what it lacked in splendor, it surely made up in grace, and variety of what we may call scenic effects. Some of these were no less interesting to the student than impressive to the spectator. At Pulkowa, on the September 16, Winnock, the first director of the Strasbourg Observatory, observed a faint outer envelope resembling a veil of almost evanescent texture flung somewhat widely over the head. Next evening, the first of the secondary tails appeared, possibly as part of the same phenomenon. This was a narrow straight ray, forming a tangent to the strong curve of the primary tail, and reaching to a still greater distance from the nucleus. It continued faintly visible for about 3 weeks, during part of which time it was seen in duplicate. For from the chief train itself, at a point where its curvature abruptly changed, issued, as if through the rejection of some of its materials, a second beam nearly parallel to the first, the rigid line of which contrasted singularly with the softly diffused and waving aspect of the plume of light from which it sprang. Olbers's theory of unequal repulsive forces was never more beautifully illustrated. The triple tail seemed a visible solar analysis of cometary matter. The processes of luminous emanation going on in this body forcibly recalled the observations made on the comets of 1744 and 1835. From the middle of September, the nucleus, estimated by Bond to be under 500 miles in diameter, was the center of action of the most energetic kind. 7 distinct envelopes were detached in succession from the nebulosity surrounding the head, and after rising towards the Sun during periods of from 4 to 7 days, finally cast their material backward to form the right and left branches of the great train. The separation of these by an obscure axis, apparently as black, quite close up to the nucleus, as the sky, indicated for the tail a hollow, comb-like structure. While the repetition of certain spots and rays in the same corresponding situation on one envelope after another served to show that the nucleus, to some local peculiarity of which they were doubtless due, had no proper rotation, but merely shifted sufficiently on an axis to preserve the same aspect towards the Sun as it moved round it. This observation of Bond's was strongly confirmatory of Bessel's hypothesis of opposite polarities in such bodies' opposite sides. The protrusion towards the Sun, on September 25, of a brilliant luminous fan-shaped sector completed the resemblance to Halley's comet. The appearance of the head was now somewhat that of a bat's-wing gaslight. There were, however, no oscillations to and fro, such as Bessel had seen and speculated upon in 1835. As the size of the nucleus contracted with approach to perihelion, its intensity augmented. On October 2, it outshone Arcturus, and for a week or 10 days was a conspicuous object half an hour after sunset. Its luster, setting aside the light derived from the tail, was, at that date, 6,300 times what it had been on June 15, though theoretically, taking into account, that is, only the differences of distance from Sun and Earth, it should have been only 1/33 of that amount. Here, it might be thought, was convincing evidence of the comet itself becoming ignited under the growing intensity of the solar radiations. Yet experiments with the polariscope were interpreted in an adverse sense, and Bond's conclusion that the comet sent us virtually unmixed reflected sunshine was generally acquiesced in. It was, nevertheless, negatived by the first application of the spectroscope to these bodies. Very few comets have been so well or so long observed as Donati's. It was visible to the naked eye during 112 days. It was telescopically discernible for 275, the last observation having been made by Mr. William Mann at the Cape of Good Hope, March 4, 1859. Its course through the heavens combined singularly with the orbital place of the Earth to favor curious inspection. The tail, when near its greatest development, lost next to nothing by the effects of perspective, and at the same time lay in a plane sufficiently inclined to the line of sight to enable it to display its exquisite curves to the greatest advantage. Even the weather was, on both sides of the Atlantic, propitious during the period of greatest interest, and the moon as little troublesome as possible. The volume compiled by the younger Bond is a monument to the care and skill with which these advantages were turned to account. Yet this stately apparition marked no turning point in the history of cometary science. By its study knowledge was indeed materially advanced, but along the old lines. No quick and vivid illumination broke upon its path. Quite insignificant objects, as we have already partly seen, have often proved more vitally instructive. Donati's comet has been identified with no other. Its path is an immensely elongated ellipse, lying in a plane far apart from that of the planetary movements, carrying it at perihelion considerably within the orbit of Venus, and at aphelion out into space to 5½ times the distance from the Sun of Neptune. The entire circuit occupies over 2,000 years, and is performed in a retrograde direction, or against the order of the signs, before its next return, about the year 4000 AD. The enigma of its presence and its purpose may have been to some extent, though we may be sure not completely, penetrated. On June 30, 1861, the Earth passed, for the second time in the century, through the tail of a great comet. Some of our readers may remember the unexpected disclosure, on the withdrawal of the Sun below the horizon on that evening, of an object so remarkable as to challenge universal attention. A golden yellow planetary disk, wrapped in dense nebulosity, shone out while the June twilight of these latitudes was still in its first strength. The number and complexity of the envelopes surrounding the head produced, according to the late Mr. Webb, a magnificent effect. Portions of 6 distinct emanations were traceable. It was as though a number of light, hazy clouds were floating round a miniature full moon. As the sky darkened, the tail emerged to view. Although in brightness and sharpness of definition it could not compete with the display of 1858, its dimensions proved to be extraordinary. It reached upwards beyond the zenith when the head had already set. By some authorities its extreme length was stated at 118 degrees, and it showed no trace of curvature. Most remarkable, however, was the appearance of 2 widely divergent rays, each pointing towards the head, though cut off from it by sky illumination, of which one was seen by Mr. Webb, and both by Mr. Williams at Liverpool, a quarter of an hour before midnight. There seems no doubt that Webb's interpretation was the true one, and that these beams were, in fact, the perspective representation of a conical or cylindrical tail, hanging closely above our heads. And probably just being lifted up out of our atmosphere. The cometary train was then rapidly receding from the Earth, so that the sides of the outspread fan of light shown by it when we were right in the line of its axis must have appeared, as they did, to close up in departure. The swiftness with which the visually opened fan shut proved its vicinity, and, indeed, Mr. Hind's calculations showed that we were not so much near as actually within its folds at that very time. Already M. Liais, from his observations at Rio de Janeiro, June 11th to 14th, and Mr. Tebbutt, by whom the comet was discovered in New South Wales on May 13th, had anticipated such an encounter. While the former subsequently proved that it must have occurred in such a way as to cause an immersion of the Earth in cometary matter to a depth of 300,000 miles. The comet then lay between the Earth and the Sun at a distance of about 14 million miles from the former. Its tail stretched outward just along the line of intersection of its own with the terrestrial orbit to an extent of 15 million miles. So that our globe, happening to pass at the time, found itself during some hours involved in the flimsy appendage. No perceptible effects were produced by the meeting, it was known to have occurred by theory alone. A peculiar glare in the sky, thought by some to have distinguished the evening of June 30th, was, at best, inconspicuous. Nor were there any symptoms of unusual electric excitement. The Greenwich instruments were, indeed, disturbed on the following night, but it would be rash to infer that the comet had art or part in their agitation. The perihelion passage of this body occurred June 11, 1861, and its orbit has been shown by M. Kreutz of Bonn, from a very complete investigation founded on observations extending over nearly a year, to be an ellipse traversed in a period of 409 years. Towards the end of August, 1862, a comet became visible to the naked eye high up in the northern hemisphere, with a nucleus equaling in brightness the lesser stars of the Plough and a feeble tail 20 degrees in length. It thus occupied quite a secondary position among the members of its class. It was, nevertheless, a splendid object in comparison with a telescopic nebulosity discovered by Temple at Marseilles, December 19, 1865. This, the sole comet of 1866, slipped past perihelion, January 11, without pomp of train or other appendages, and might have seemed hardly worth the trouble of pursuing. Fortunately, this was not the view entertained by observers and computers. Since upon the knowledge acquired of the movements of these two bodies has been founded one of the most significant discoveries of modern times. The first of them is now styled the comet, 1862-3, of the August meteors, the second, 1866I. That of the November meteors. The steps by which this curious connection came to be ascertained were many, and were taken in succession by a number of individuals. But the final result was reached by Schiaparelli of Milan, and remains deservedly associated with his name. The idea prevalent in the 18th century as to the nature of shooting stars was that they were mere aerial ignes fatui, inflammable vapors accidentally kindled in our atmosphere. But Halley had already entertained the opinion of their cosmical origin. And Chladni in 1794 formally broached the theory that space is filled with minute-circulating atoms, which, drawn by the Earth's attraction, and ignited by friction in its gaseous envelope, produce the luminous effects so frequently witnessed. Acting on his suggestion, Brandes and Ben Zenberg, two students at the University of Göttingen, began in 1798 to determine the heights of falling stars by simultaneous observations at a distance. They soon found that they move with planetary velocities in the most elevated regions of our atmosphere, and by the ascertainment of this fact laid a foundation of distinct knowledge regarding them. Some of the data collected, however, served only to perplex opinion, and even caused Chladni temporarily to renounce his. Many high authorities, headed by Laplace in 1802, declared for the lunar volcanic origin of meteorites. But thought on the subject was turbid, and inquiry seemed only to stir up the mud of ignorance. It needed one of those amazing spectacles, at which man assists, no longer in abject terror for his own frail fortunes, but with keen curiosity in the vivid expectation of new knowledge, to bring about a clarification. On the night of November 12 to 13, 1833, a tempest of falling stars broke over the earth. North America bore the brunt of its pelting. From the Gulf of Mexico to Halifax, until daylight with some difficulty put an end to the display, the sky was scored in every direction with shining tracks and illuminated with majestic fireballs. At Boston the frequency of meteors was estimated to be about half that of flakes of snow in an average snowstorm. Their numbers, while the first fury of their coming lasted, were quite beyond counting. But as it waned, a reckoning was attempted, from which it was computed, on the basis of that much diminished rate, that 240,000 must have been visible during the 9 hours they continued to fall. Now there was one very remarkable feature common to the innumerable small bodies which traversed, or were consumed in our atmosphere that night. They all seemed to come from the same part of the sky. Traced backward, their paths were invariably found to converge to a point in the constellation Leo. Moreover, that point traveled with the stars in their nightly round. In other words, it was entirely independent of the Earth and its rotation. It was a point in interplanetary space. The effective perception of this fact amounted to a discovery, as Olmsted and Twining, who had simultaneous ideas on the subject, were the first to realize. Denison Olmsted was then professor of mathematics in Yale College. He showed early in 1834 that the emanation of the showering meteors from a fixed, radiant, proved their approach to the Earth along nearly parallel lines, appearing to diverge by an effect of perspective. And that those parallel lines must be sections of orbits described by them round the Sun and intersecting that of the Earth. For the November phenomenon was now seen to be a periodical one. On the same night of the year 1832, although with less dazzling and universal splendor than in America in 1833, it had been witnessed over great part of Europe and in Arabia. Olmsted accordingly assigned to the cloud of cosmical particles, or comet, as he chose to call it, by terrestrial encounters with which he supposed the appearances in question to be produced, a period of about 182 days. Its path a narrow ellipse, meeting, near its farthest end from the Sun, the place occupied by the Earth on November 12. Once for all, then, as the result of the starfall of 1833, the study of luminous meteors became an integral part of astronomy. Their membership of the solar system was no longer a theory or a conjecture, it was an established fact. The discovery might be compared to, if it did not transcend in importance, that of the asteroidal group. C'est un nouveau monde planétaire, Arago wrote, que commence à s'y révéler à nous. Evidences of periodicity continued to accumulate. It was remembered that Humboldt and Bonpland had been the spectators at Cumana, after midnight on November 12, 1799, of a fiery shower little inferior to that of 1833, and reported to have been visible from the equator to Greenland. Moreover, in 1834 and some subsequent years, there were waning repetitions of the display, as if through the gradual thinning out of the meteoric supply. The extreme irregularity of its distribution was noted by Olbers in 1837, who conjectured that we might have to wait until 1867 to see the phenomenon renewed on its former scale of magnificence. This was the first hint of a 33 or 34-year period. The falling stars of November did not alone attract the attention of the learned. Similar appearances were traditionally associated with August 10th by the popular phrase in which they figured as the Tears of St. Lawrence. But the association could not be taken on trust from medieval authority. It had to be proved scientifically, and this Quetelet of Brussels succeeded in doing in December 1836. A second meteoric revolving system was thus shown to exist. But its establishment was at once perceived to be fatal to the cosmical cloud hypothesis of Olmsted. For if it be a violation of probability to attribute to one such agglomeration a period of an exact year, or submultiple of a year, it would be plainly absurd to suppose the movements of two or more regulated by such highly artificial conditions. An alternative was proposed by Adolf Erman of Berlin in 1839. No longer in clouds, but in closed rings, he supposed meteoric matter to revolve round the Sun. Thus the mere circumstance of intersection by a meteoric of the terrestrial orbit, without any coincidence of period, would account for the Earth meeting some members of the system at each annual passage through the node or point of intersection. This was an important step in advance, yet it decided nothing as to the forms of the orbits of such annular assemblages, nor was it followed up in any direction for a quarter of a century. Hubert A. Newton took up, in 1864, the dropped thread of inquiry. The son of a mathematical mother, he attained, at the age of 25, to the dignity of professor of mathematics in Yale University, and occupied the post until his death in 1896. The diversion of his powers, however, from purely abstract studies stimulated their effective exercise, and constituted him one of the founders of meteoric astronomy. A search through old records carried the November phenomenon back to the year 902 AD, long distinguished as the Year of the Stars. For in the same night in which Taormina was captured by the Saracens, and the cruel Aglabite tyrant Ibrahim ibn Ahmed died by the judgment of God before Cosenza, stars fell from heaven in such abundance as to amaze and terrify beholders far and near. This was on October 13th, and recurrences were traced down through the subsequent centuries, always with a day's delay in about 70 years. It was easy, too, to derive from the dates a cycle of 33¼ years, so that Professor Newton did not hesitate to predict the exhibition of an unusually striking meteoric spectacle on November 13 to 14, 1866. For the astronomical explanation of the phenomena, recourse was had to a method introduced by Erman of computing meteoric orbits. It was found, however, that conspicuous recurrences every 33 or 34 years could be explained on the supposition of 5 widely different periods, combined with varying degrees of extension in the revolving group. Professor Newton himself gave the preference to the shortest, of 354½ days, but indicated the means of deciding with certainty upon the true one. It was furnished by the advancing motion of the node, or that day's delay of the November shower every 70 years, which the old chronicles had supplied data for detecting. For this is a strictly measurable effect of gravitational disturbance by the various planets, the amount of which naturally depends upon the course pursued by the disturbed bodies. Here the great mathematical resources of Professor Adams were brought to bear. By laborious processes of calculation, he ascertained that 4 out of Newton's 5 possible periods were entirely incompatible with the observed nodal displacement. While for the 5th, that of 33¼ years, a perfectly harmonious result was obtained. This was the last link in the chain of evidence proving that the November meteors, or Leonids, as they had by that time come to be called, revolve round the Sun in a period of 33/27 years. In an ellipse spanning the vast gulf between the orbits of the Earth and Uranus, the group being so extended as to occupy nearly 3 years in defiling past the scene of terrestrial encounters. But before it was completed in March 1867, the subject had assumed a new aspect and importance. Professor Newton's prediction of a remarkable star shower in November 1866 was punctually fulfilled. This time, Europe served as the main target of the celestial projectiles, and observers were numerous and forewarned. The display, although, according to Mr. Baxendell's memory, inferior to that of 1833, was of extraordinary impressiveness. Dense crowds of meteors, equal in luster to the brightest stars, and some rivaling Venus at her best, darted from east to west across the sky with enormous apparent velocities, and with a certain determinateness of aim. As if let fly with a purpose, and at some definite object. Nearly all left behind them trains of emerald green or clear blue light, which occasionally lasted many minutes, before they shriveled and curled up out of sight. The maximum rush occurred a little after 1 o'clock on the morning of November 14, when attempts to count were overpowered by frequency. But during a previous interval of 7 minutes 5 seconds, for observers at Mr. Bishop's observatory at Twickenham reckoned 514, and during an hour 1120. Before daylight the Earth had fairly cut her way through the star-bearing stratum, the ethereal rockets had ceased to fly. This event brought the subject of shooting stars once more vividly to the notice of astronomers. Schiaparelli had, indeed, been already attracted by it. The results of his studies were made known in 4 remarkable letters, addressed, before the close of the year 1866, to Father Secchi, and published in the Bulletino of the Roman Observatory. Their upshot was to show, in the first place, that meteors possess a real velocity considerably greater than that of the Earth, and travel, accordingly, to enormously greater distances from the Sun along tracks resembling those of comets in being very eccentric, in lying at all levels indifferently, and in being pursued in either direction. It was next inferred that comets and meteors equally have an origin foreign to the solar system, but are drawn into it temporarily by the Sun's attraction, and occasionally fixed in it by the backward pull of some planet. But the crowning fact was reserved for the last. It was the astonishing one that the August meteors move in the same orbit with the bright comet of 1862, that the comet, in fact, is but a larger member of the family named Perseids, because their radiant point is situated in the constellation Perseus. This discovery was quickly capped by others of the same kind. Leverrier published, January 21, 1867, Elements for the November Swarm, founded on the most recent and authentic observations, at once identified by Dr. C. F. W. Peters of Altona with Appolzer's elements for Tempel's comet of 1866. A few days later, Schiaparelli, having recalculated the orbit of the meteors from improved data, arrived at the same conclusion. While Professor Weiss of Vienna pointed to the agreement between the orbits of a comet which had appeared in 1861 and of a star shower found to recur on April 20, Lyrates, as well as between those of Biela's comet and certain conspicuous meteors of November 28. These instances do not seem to be exceptional. The number of known or suspected accordances of cometary tracks with meteor streams contained in a list drawn up in 1878 by Professor Alexander S. Herschel, who has made the subject peculiarly his own, amounts to 76. Although the 4 first detected still remain the most conspicuous, and perhaps the only absolutely sure examples of a relation as significant as it was, to most astronomers, unexpected. There had, indeed, been anticipatory ideas. Not that Kepler's comparison of shooting stars to minute comets, or masklines, force resultera che essi sono comete, in a letter to the Abate Cesaris, December 12, 1774, need count for much. But Chladni, in 1819, considered both to be fragments or particles of the same primitive matter, irregularly scattered through space as nebulae. And Morstad of Prague suggested about 1837 that the meteors of November might be dispersed atoms from the tail of Biela's comet, the path of which is cut across by the Earth near that epoch. Professor Kirkwood, however, by a luminous intuition, penetrated the whole secret, so far as it has yet been made known. In an article published, or rather buried, in the Danville Quarterly Review for December, 1861, he argued, from the observed division of Biela, and other less noted instances of the same kind, that the Sun exercises a divelent influence on the nuclei of comets, which may be presumed to continue its action until their corporate existence, so to speak, ends in complete pulverization. May not, he continued, our periodic meteors be the debris of ancient but now disintegrated comets, whose matter has become distributed round their orbits? The gist of Schiaparelli's discovery could not be more clearly conveyed. For it must be borne in mind that with the ultimate destiny of comets' tails this had nothing to do. The tenuous matter composing them is, no doubt, permanently lost to the body from which it emanated. But science does not pretend to track its further wanderings through space. It can, however, state categorically that these will no longer be conducted along the paths forsaken under solar compulsion. From the central, and probably solid parts of comets, on the other hand, are derived the granules by the swift passage of which our skies are seamed with periodic fires. It is certain that a loosely agglomerated mass, such as cometary nuclei most likely are, must gradually separate through the unequal action of gravity on its various parts, through, in short, solar tidal influence. Thenceforward its fragments will revolve independently in parallel orbits, at first as a swarm, finally, when time has been given for the full effects of the lagging of the slower moving particles to develop, as a closed ring. The first condition is still, more or less, that of the November meteors, those of August have already arrived at the second. For this reason, Leverrier pronounced, in 1867, the Perseid to be of older formation than the Leonid system. He even assigned a date at which the introduction of the last-named bodies into their present orbit was probably effected through the influence of Uranus. In 126 AD, a close approach must have taken place between the planet and the parent comet of the November stars, after which its regular returns to perihelion, and the consequent process of its disintegration, set in. Though not complete, it is already far advanced. The view that meteorites are the dust of decaying comets was now to be put to a definite test of prediction. Biela's comet had not been seen since its duplicate return in 1852. Yet it had been carefully watched for with the best telescopes, its path was accurately known, every perturbation it could suffer was scrupulously taken into account. Under these circumstances, its repeated failure to come up to time might fairly be thought to imply a cessation from visible existence. Might it not, however, be possible that it would appear under another form, that a star shower might have sprung from and would commemorate its dissolution? An unusually large number of falling stars were seen by Brandis, December 6, 1798. Similar displays were noticed in the years 1830, 1838, and 1847, and the point from which they emanated was shown by Hayes at Aix-la-Chapelle to be situated near the bright star Gamma Andromedae. Now this is precisely the direction in which the orbit of Biela's comet would seem to lie, as it runs down to cut the terrestrial track very near the place of the Earth at the above dates. The inference was, then, an easy one, that the meteors were pursuing the same path with the comet, and it was separately arrived at, early in 1867, by Weiss, Darist, and Gall. But Biela travels in the opposite direction to Tempel's comet and its attendant, Leonids. Its motion is direct, or from west to east, while theirs is retrograde. Consequently, the motion of its node is in the opposite direction too. In other words, the meeting place of its orbit with that of the Earth retreats, and very rapidly, along the ecliptic instead of advancing. So that if the Andromedes stood in the supposed intimate relation to Biela's comet, they might be expected to anticipate the times of their recurrence by as much as a week in half a century. All doubt as to the fact may be said to have been removed by Signor Zizili's observation of the annual shower in more than usual abundance at Bergamo, November 30, 1867. The missing comet was next due at perihelion in the year 1872, and the probability was contemplated by both Weiss and Gall of its being replaced by a copious discharge of falling stars. The precise date of the occurrence was not easily determinable, but Gall thought the chances in favor of November 28. The event anticipated the prediction by 24 hours. Scarcely had the sun set in Western Europe on November 27, when it became evident that Biela's comet was shedding over us the pulverized products of its disintegration. The meteors came in volleys from the foot of the chained lady, their numbers at times baffling the attempt to keep a reckoning. At Moncalieri, about 8 p.m., they constituted, as Father Denza said, a real rain of fire. For observers counted, on an average, 400 each minute and a half, and not a few fireballs, equaling the moon in diameter, traversed the sky. On the whole, however, the stars of 1872, though about equally numerous, were less brilliant than those of 1866, the phosphorescent tracks marking their passage were comparatively evanescent and their movement sluggish. This is easily understood when we remember that the Andromedes overtake the Earth, while the Leonids rush to meet it, the velocity of encounter for the first class of bodies being under 12, for the second above 44 miles a second. The spectacle was, nevertheless, magnificent. It presented itself successively to various parts of the earth, from Bombay and the Mauritius to New Brunswick and Venezuela, and was most diligently and extensively observed. Here it had well-nigh terminated by midnight. It was attended by a slight aurora, and although Tacchini had telegraphed that the state of the sun rendered some show of polar lights probable, it has too often figured as an accompaniment of star showers to permit the coincidence to rank as fortuitous. Admiral Wrangel was accustomed to describe how, during the prevalence of an aurora on the Siberian coast, the passage of a meteor never failed to extend the luminosity to parts of the sky previously dark. And an enhancement of electrical disturbance may well be associated with the flittings of such cosmical atoms. A singular incident connected with the meteors of 1872 has now to be recounted. The late Professor Klinkerfues, who had observed them very completely at Göttingen, was led to believe that not merely the debris strewn along its path, but the comet itself must have been in immediate proximity to the Earth during their appearance. If so, it might be possible, he thought, to descry it as it retreated in the diametrically opposite direction from that in which it had approached. On November 30th, accordingly, he telegraphed to Mr. Pogson, the Madras astronomer, Biela touched Earth November 27th, search near Theta Centauri, the anti-radiant, as it is called, being situated close to that star. Bad weather prohibited observation during 36 hours, but when the rain clouds broke on the morning of December 2nd, there a comet was, just in the indicated position. In appearance it might have passed well enough for one of the Biela twins. It had no tail, but a decided nucleus, and was about 45 seconds across, being thus altogether below the range of naked eye discernment. It was again observed December 3rd, when a short tail was perceptible. But overcast skies supervened, and it has never since been seen. Its identity accordingly remains in doubt. It seems tolerably certain, however, that it was not the lost comet, which ought to have passed that spot 12 weeks earlier, and was subject to no conceivable disturbance capable of delaying to that extent its revolution. On the other hand, there is the strongest likelihood that it belonged to the same system, that it was a third fragment, torn from the parent body of the Andromedes at a period anterior to our first observations of it. In 13 years Biela's comet, or its relics, travels nearly twice round its orbit, so that a renewal of the meteoric shower of 1872 was looked for on the same day of the year 1885. The probability being emphasized by an admonitory circular from Denect. Astronomers were accordingly on the alert, and were not disappointed. In England, observation was partially impeded by clouds, but at Malta, Palermo, Beirut, and other southern stations, the scene was most striking. The meteors were both larger and more numerous than in 1872. Their numbers in the densest part of the drift were estimated by Professor Newton at 75,000 per hour, visible from one spot to so large a group of spectators that practically none could be missed. Yet each of these multitudinous little bodies was found by him to travel in a clear cubical space of which the edge measured 20 miles. Thus the dazzling effect of a luminous throng was produced without jostling or overcrowding, by particles, it might almost be said, isolated in the void. Their aspect was strongly characteristic of the Andromede family of meteors. They invariably, Mr. Denning wrote, traversed short paths with very slow motions, and became extinct in evolved streams of yellowish sparks. The conclusion seemed obvious, that these meteors are formed of very soft materials, which expand while incandescent, and are immediately crumbled and dissipated into exiguous dust. The Biela meteors of 1885 did not merely gratify astronomers with a fulfilled prediction, but were the means of communicating to them some valuable information. Although their main body was cut through by the moving Earth in 6 hours, and was not more than 100,000 miles across, skirmishers were thrown out to nearly 1,000,000 miles on either side of the compact central battalions. Members of the system were, on the 26th of November, recorded by Mr. Denning at the hourly rate of about 130, and they did not wholly cease to be visible until December 1st. They afforded besides a particularly well-marked example of that diffuseness of radiation previously observed in some less conspicuous displays. Their paths seemed to diverge from an area rather than from a point in the sky. They came so ill to focus that divergences of several degrees were found between the most authentically determined radiants. These incongruities are attributed by Professor Newton to the irregular shape of the meteoroids producing unsymmetrical resistance from the air, and hence causing them to glance from their original direction on entering it. Thus, their luminous tracks did not always represent, even apart from the effects of the Earth's attraction, the true prolongation of their course through space. The Andromedes of 1872 were laggards behind the comet from which they sprang. Those of 1885 were its avant-couriers. That wasted and disrupted body was not due at the node until January 26, 1886, 60 days, that is, after the Earth's encounter with its meteoric fragments. These are now probably scattered over more than 500 million miles of its orbits, yet Professor Newton considers that all must have formed one compact group with Biela at the time of its close approach to Jupiter about the middle of 1841. For otherwise both comet and meteorites could not have experienced, as they seem to have done, the same kind and amount of disturbance. The rapidity of cometary disintegration is thus curiously illustrated. A short-lived persuasion that the missing heavenly body itself had been recovered, was created by Mr. Edwin Holmes's discovery, at London, November 6, 1892, of a tolerably bright, tailless comet, just in a spot which Biela's comet must have traversed in approaching the intersection of its orbit with that of the Earth. A hasty calculation by Berberich assigned elements to the newcomer seeming not only to ratify the identity, but to promise a quasi-encounter with the Earth on November 21. The only effect of the prediction, however, was to raise a panic among the Negroes of the southern states of America. The comet quietly ignored it, and moved away from instead of towards the appointed meeting place. Its projection, then, on the night of its discovery, upon a point of the Biela orbit was by a mere caprice of chance. North America, nevertheless, was visited on November 23 by a genuine Andromede shower. Although the meteors were less numerous than in 1885, Professor Young estimated that 30,000, at the least, of their orange fire streaks came, during 5 hours, within the range of view at Princeton. Brédikhine estimated the width of the space containing them at about 2,700,000 miles. The anticipation of their due time by 4 days implied, if they were a prolongation of the main Biela group, the nucleus of which passed the spot of encounter 5 months previously, a recession of the node since 1885 by no less than 3 degrees. Unless, indeed, Mr. Denning were right in supposing the display to have proceeded from an associated branch of the main swarm through which we passed in 1872 and 1885. The existence of separated detachments of Biela meteors, due to disturbing planetary action, was contemplated as highly probable by Schiaparelli. Such may have been the belated flights met with in 1830, 1838, 1841, and 1847, and such the advance flight plunged through in 1892. A shower looked for November 23, 1899, did not fall, and no further display from this quarter is probable until November 17, 1905, although one is possible a year earlier. The Leonids, through the adverse influence of Jupiter and Saturn, inflicted upon multitudes of eager watchers a still more poignant disappointment. A dense part of the swarm, having nearly completed a revolution since 1866, should, traveling normally, have met the Earth November 15, 1899. In point of fact, it swerved sunward, and the millions of meteorites which would otherwise have been sacrificed for the illumination of our skies escaped a fiery doom. The contingency had been forecast in the able calculations of Dr. Johnstone Stoney and Dr. A. M. W. Downing, superintendent of the Nautical Almanac Office, but the verification scarcely compensated the failure. Nor was the situation retrieved in the following years. Only ragged fringes of the great tempest cloud here and there touched our globe. As the same investigators warned us to expect, the course of the meteorites had been not only rendered sinuous by perturbation, but also broken and irregular. We can no longer count upon the Leonids. Their glory, for scenic purposes, is departed. The comet associated with them also evaded observation. Although it doubtless kept its tryst with the Sun in the spring of 1899, the attendant circumstances were too unfavorable to allow it to be seen from the Earth. By an almost fantastic coincidence, nevertheless, a faint comet was photographed, November 14, 1898, by Dr. Chase, of the Yale College Observatory, close to the Leonid radiant, whither a meteorograph was directed with a view to recording trails left by precursors of the main Leonid body. A promising start, too, was made on the same occasion with meteoric researches from sensitive plates. Indeed, Skeeberl and Colton had already, in 1896, determined the height of a Leonid by means of photographs taken at stations on different ridges of Mount Hamilton. And Professor Pickering has prosecuted similar work at Harvard, with encouraging results. Everything in this branch of science depends upon how far they can be carried. Without the meteorograph, rigid accuracy in the observation of shooting stars is unattainable, and rigid accuracy is the sine qua non for obtaining exact knowledge. Biela does not offer the only example of cometary disruption. Setting aside the unauthentic reports of early chroniclers, we meet the double comet discovered by Liais at Olinda, Brazil, February 27, 1860, of which the division appeared recent, and about to be carried farther. But a division once established, separation must continually progress. The periodic times of the fragments will never be identical. One must drop a little behind the other at each revolution, until at length they come to travel in remote parts of nearly the same orbit. Thus the comet predicted by Klinkerfues and discovered by Pogson had already lagged to the extent of 12 weeks, and we shall meet instances farther on where the retardation is counted, not by weeks, but by years. Here original identity emerges only from calculation and comparison of orbits. Comets, then, die, as Kepler wrote long ago, sicut bombuses philo fundendo. This certainty, anticipated by Kirkwood in 1861, we have at least acquired from the discovery of their generative connection with meteors. Nay, their actual materials become, in smaller or larger proportions, incorporated with our globe. It is not, indeed, universally admitted that the ponderous masses of which, according to Daubry's estimate, at least 600 fall annually from space upon the Earth, ever formed part of the bodies known to us as comets. Some followed Skermak in attributing to aerolites a totally different origin from that of periodical shooting stars. That no clear line of demarcation can be drawn is no valid reason for asserting that no real distinction exists. And it is certainly remarkable that a meteoric fusillade may be kept up for hours without a single solid projectile reaching its destination. It would seem as if the celestial army had been supplied with blank cartridges. Yet, since a few detonating meteors have been found to proceed from ascertained radiance of shooting stars, it is difficult to suppose that any generic difference separates them. Their assimilation is further urged, though not with any demonstrative force, by two instances, the only two on record, of the tangible descent of an aerolite during the progress of a star shower. On April 4, 1095, the Saxon Chronicle informs us that stars fell so thickly that no man could count them, and adds that one of them having struck the ground in France, a bystander cast water upon it, which was raised in steam with a great noise of boiling. And again, on November 27, 1885, while the skirts of the Andromede tempest were trailing over Mexico, a ball of fire was precipitated from the sky at Mazapil, within view of a ranchman. Scientific examination proved it to be a siderite, or mass of nickel iron. Its weight exceeded 8 pounds, and it contained many nodules of graphite. We are not, however, authorized by the circumstances of its arrival to regard the Mazapil fragment of cosmic metal as a specimen torn from Biela's comet. In this, as in the preceding case, the coincidence of the fall with the shower may have been purely casual, since no hint is given of any sort of agreement between the tracks followed by the sample provided for curious study and the swarming meteors consumed in the upper air. Professor Newton's inquiries into the tracks pursued by meteorites previous to their collisions with the Earth tend to distinguish them, at least specifically, from shooting stars. He found that nearly all had been traveling with a direct movement in orbits the perihelia of which lay in the outer half of the space separating the Earth from the Sun. Shooting stars, on the contrary, are entirely exempt from such limitations. The Yale professor concluded that the larger meteorites moving in our solar system are allied much more closely with the group of comets of short period than with the comets whose orbits are nearly parabolic. They would thus seem to be more at home than might have been expected amid the planetary family. Father Carbonell has, moreover, shown that meteorites, if explosion products of the Earth or Moon, should, with rare exceptions, follow just the kind of paths assigned to them, from data of observation, by Professor Newton. Yet it is altogether improbable that projectiles from terrestrial volcanoes should, at any geological epoch, have received impulses powerful enough to enable them, not only to surmount the Earth's gravity, but to penetrate its atmosphere. A striking, indeed, an almost startling, peculiarity, on the other hand, divides from their congeners a class of meteors identified by Mr. Denning during 10 years' patient watching of such phenomena at Bristol. These are described as meteors with stationary radiance, since for months together they seem to come from the same fixed points in the sky. Now this implies quite a portentous velocity. The direction of meteor radiance is affected by a kind of aberration, analogous to the aberration of light. It results from a composition of terrestrial with meteoric motion. Hence, unless that of the Earth in its orbit be by comparison insignificant, the visual line of encounter must shift, if not perceptibly from day to day, at any rate conspicuously from month to month. The fixity, then, of many systems observed by Mr. Denning seems to demand the admission that their members travel so fast as to throw the Earth's movement completely out of the account. The required velocity would be, by Mr. Ranyard's calculation, at least 880 miles a second. But the aspect of the meteors justifies no such extravagant assumption. Their seeming swiftness is very various, and, what is highly significant, it is notably less when they pursue than when they meet the Earth. Yet the incredible and unaccountable fact of the existence of these long radiants, although doubted by Tisserand because of its theoretical refractoriness, must apparently be admitted. The first plausible explanation of them was offered by Professor Turner in 1899. They represent, in his view, the cumulative effects of the Earth's attraction. The validity of his reasoning is, however, denied by M. Brédikhine, who prefers to regard them as a congeries of separate streams. The enigma they present has evidently not yet received its definitive solution. The Perseids afford, on the contrary, a remarkable instance of a shifting radiant. Mr. Denning's observations of these yellowish, leisurely meteors extend over nearly 6 weeks, from July 8 to August 16, the point of radiation meantime progressing no less than 57 degrees in right ascension. Doubts as to their common origin were hence freely expressed, especially by Mr. Monk of Dublin. But the late Dr. Kleiber showed, by strict geometrical reasoning, that the 49 radiants successively determined for the shower were all, in fact, comprised within one narrowly limited region of space. In other words, the application of the proper correction for the terrestrial movement, and the effects of attraction by which each individual shooting star is compelled to describe a hyperbola round the Earth's center, reduces the extended line of radiance to a compact group, with the cometary radiant for its central point. The cometary radiant being the spot in the sky met by a tangent to the orbit of the Perseid comet of 1862 at its intersection with the orbit of the Earth. The reality of the connection between the comet and the meteors could scarcely be more clearly proved, while the vast dimensions of the stream into which the latter are found to be diffused cannot but excite astonishment not unmixed with perplexity. The first successful application of the spectroscope to comets was by Donati in 1864. A comet discovered by Tempel, July 4, brightened until it appeared like a star somewhat below the second magnitude, with a feeble tail 30 degrees in length. It was remarkable as having, on August 7, almost totally eclipsed a small star, a very rare occurrence. On August 5 Donati admitted its light through his train of prisms, and found it, thus analyzed, to consist of 3 bright bands, yellow, green, and blue, separated by wider dark intervals. This implied a good deal. Comets had previously been considered, as we have seen, to shine mainly, if not wholly, by reflected sunlight. They were now perceived to be self-luminous, and to be formed, to a large extent, of glowing gas. The next step was to determine what kind of gas it was that was thus glowing in them, and this was taken by Sir William Huggins in 1868. A comet of subordinate brilliancy, known as Comet 1868-2, or sometimes as Winx, was the subject of his experiment. On comparing its spectrum with that of an olefiant gas vacuum tube rendered luminous by electricity, he found the agreement exact. It has since been abundantly confirmed. All the 18 comets tested by light analysis, between 1868 and 1880, showed the typical hydrocarbon spectrum common to the whole group of those compounds, but probably due immediately to the presence of acetylene. Some minor deviations from the laboratory pattern, in the shifting of the maxima of light from the edge towards the middle of the yellow and blue bands, have been experimentally reproduced by Vogel and Hasselberg in tubes containing a mixture of carbonic oxide with olefiant gas. Their illumination by disruptive electric discharges was, however, a condition sine qua non for the exhibition of the cometary type of spectrum. When a continuous current was. Plate 2. Great Comet. Photographed, May 5, 1901, with the 13-inch astrographic refractor of the Royal Observatory, Cape of Good Hope. Employed, the carbonic oxide bands asserted themselves to the exclusion of the hydrocarbons. The distinction has great significance as regards the nature of comets. Of particular interest in this connection is the circumstance that carbonic oxide is one of the gases evolved by meteoric stones and irons under stress of heat. For it must apparently have formed part of an aeriform mass in which they were immersed at an earlier stage of their history. In a few exceptional comets the usual carbon bands have been missed. 2 such were observed by Sir William Huggins in 1866 and 1867 respectively. In each a green ray, approximating in position to the fundamental nebular line, crossed an otherwise unbroken spectrum. And Holmes's comet of 1892 displayed only a faint prismatic band devoid of any characteristic feature. Now these 3 might well be set down as partially effete bodies. But a brilliant comet, visible in southern latitudes in April and May, 1901, so far resembled them in the quality of its light as to give a spectrum mainly, if not purely, continuous. This, accordingly, is no symptom of decay. The earliest comet of first-class luster to present itself for spectroscopic examination was that discovered by Coggia at Marseilles, April 17, 1874. Invisible to the naked eye till June, it blazed out in July a splendid ornament of our northern skies, with a just perceptibly curved tail, reaching more than halfway from the horizon to the zenith. And a nucleus surpassing in brilliancy the brightest stars in the Swan. Brédikhine, Vogel, and Huggins were unanimous in pronouncing its spectrum to be that of marsh or olefiant gas. Father Secchi, in the clear sky of Rome, was able to push the identification even closer than had heretofore been done. The complete hydrocarbon spectrum consists of 5 zones of variously colored light. 3 of these only, the 3 central ones, had till then been obtained from comets. Owing, it was supposed, to their temperature not being high enough to develop the others. The light of Coggia's comet, however, was found to contain all 5, traces of the violet band emerging June 4, of the red, July 2. Presumably, all 5 would show universally in cometary spectra, were the dispersed rays strong enough to enable them to be seen. The gaseous surroundings of comets are, then, largely made up of a compound of hydrogen with carbon. Other materials are also present, but the hydrocarbon element is probably unfailing and predominant. Its luminosity is, there is little doubt, an effect of electrical excitement. Zollner showed in 1872 that, owing to evaporation and other changes produced by rapid approach to the Sun, electrical processes of considerable intensity must take place in comets. And that their original light is immediately connected with these, and depends upon solar radiation, rather through its direct or indirect electrifying effects, than through its more obvious thermal power, may be considered a truth permanently acquired to science. They are not, it thus seems, bodies incandescent through heat, but glowing by electricity, and this is compatible, under certain circumstances, with a relatively low temperature. The gaseous spectrum of comets is accompanied, in varying degrees, by a continuous spectrum. This is usually derived most strongly from the nucleus, but extends, more or less, to the nebulous appendages. In part, it is certainly due to reflected sunlight, in part, most likely, to the ignition of minute solid particles. Footnotes. Month. Not, Volume 19, page 27. MEM. De LAC. Imp. T. 2, 1859, page 46. Harvard Annals, Volume 3, page 368. Ibid, p. 371. Month. Not, Volume 22, page 306. Stothard and Ibid, Volume 21, page 243. Intel. Observer, Volume 1, page 65. Comptes Rendus, T. LXI, page 953. Smith's Report, 1881, Holden, Nature, Volume 25, page 94, Observatory, Volume 21, page 378, W. T. Lin. Über den Ursprung der von Pallas gefundenen Eisenmassen, page 24. Arago, Anwer, 1836, page 294. Humboldt had noticed the emanation of the shooting stars of 1799 from a single point, or radiant, as Greg long afterwards termed it. But no reasoning was founded on the observation. A.M. Journ. Of S.C., Volume 26, page 132. Anwer, 1836, page 297. And De l'Observe, Bruxelles, 1839, page 248. Ibid, 1837, page 272. Astre. Knock, numbers 385, 390. A.M. Jour, of S.C., Volume 38. Second Serre. Page 377. Ibid, Volume 38, page 61. Month. Not, Volume 27, page 247. A.M. Jour, of S.C., Volume 43. Second Serre, page 87. Grant, Month. Not, Volume 27, page 29. P. Smith, Ibid, page 256. Hind, Ibid, page 49. Reproduced in Les Mondes, T. 13. Comptes Rendus, T. 64, page 96. Astre. Knock, number 1626. Ibid, number 1632. Month. Not, Volume 38, page 369. Schiaparelli, Lo Stelle Cadenti, page 54. Über für Meteor, page 406. Astre. Knock, number 347, Madler, see also Boguslawski, Die Kometen, p. 98, 1857. Nature, Volume 6, page 148. A. S. Herschel, Month. Not, Volume 32, page 355. Astre. Knock, numbers 1632, 1633, 1635. Nature, Volume 7, page 122. A. S. Herschel, Report Brit. As, 1873, page 390. Humboldt, Cosmos, Volume 1, p. 114, Aut S. Trans. Month. Not, Volume 33, page 128. Even this was denied by Bruns, Astra. Knock, number 2054. A.M. Jour, Volume 31, page 425. Month. Not, Volume 46, page 69. In Schiaparelli's opinion, centuries must have elapsed while the observed amount of scattering was being produced. Lo Stelle Cadenti, 1886, page 112. Astra. An Astroph, Volume 11, page 943. Bull. De l'Académique. St. Petersburg, T. 35, page 598. 1894. Observatory, Volume 16, page 55. Lo Stelle Cadenti, page 133, Rendiconti del Istituto Lombardo, T. 3, Ser. 2, page 23. Denning, Memoirs Roy. Astra. SOC, Volume 53, page 214, Abelman, Astra. Knock, number 3516. Proc. Roy. SOC, March 2, 1899. Nature, November 9, 1899. Berberic, Astra. Knock, number 3526. Elkin, Astroph. Jour, Volume 9, page 22. Elkin, Astroph. Jour, Volume 10, page 24. Pop Astre, September, 1897, page 232. Month. Not, Volume 20, page 336. Revue de Deux Mondes, December 15, 1885, page 889. Palgrave, Phil. Trans, Volume CXXV, page 175. W. E. Hidden, Century Mag, Volume 34, page 534. America Jour of Science, Volume 36, p. I. 1888. Revue de Questions Scientifiques, January, 1899, p. 194, Tisserand, Bull. Astre, T. 8, page 460. Month. Not, Volume 45, page 93. Observatory, Volume 8, page 4. Denning, Month. Not, Volume 38, page 114. Comptes Rendus, T. 6, page 344. Month. Not, Volume 59, page 140. Bull. De l'Académique. St. Petersburg. T. 12, page 95. Publ, Astra. Pack. SOC, Volume 3, page 114. Month. Not, Volume 52, page 341. Astra. Knock, number 1488. Anwer, Paris, 1883, page 185. Phil. Trans, Volume Clovii, page 556. Hasselberg, MEM. De LAC. Imp de St. Petersburg, T. 28. 7th Ser, number 2, page 66. Scheiner, Die Spektralanalyse der Gestern, page 234. Kaiser, Astra. An Astroph, Volume 13, page 368, refers the anomalies of the carbon spectrum in comets wholly to instrumental sources. Dewar, Proc. Roy. INST, Volume 11, p. 541. Proc. R. SOC, Volume 15, page 5, month. Not, Volume 27, page 288. Keeler, Astra. An Astrophysics, Volume 11, page 929, Vogel, Astra. Knock, number 3142. Proc. Roy. SOC, Volume 23, page 154. Hasselberg, Loch Sit, page 58. Über die Natur der Cometen, page 112. Hasselberg, Locke Sit, page 38. Chapter 11. Recent Comets, continued. The mystery of comets' tails had been to some extent penetrated. So far, at least, that, by making certain assumptions strongly recommended by the facts of the case, their forms can be, with very approximate precision, calculated beforehand. We have, then, the assurance that these extraordinary appendages are composed of no ethereal or supersensual stuff, but of matter such as we know it, and subject to the ordinary laws of motion, though in a state of extreme tenuity. Olbers, as already stated, originated in 1812 the view that the tails of comets are made up of particles subject to a force of electrical repulsion proceeding from the Sun. It was developed and enforced by Bessel's discussion of the appearances presented by Halley's comet in 1835. He, moreover, provided a formula for computing the movement of a particle under the influence of a repulsive force of any given intensity, and thus laid firmly the foundation of a mathematical theory of cometary emanations. Professor W. A. Norton, of Yale College, considerably improved this by inquiries begun in 1844, and resumed on the apparition of Donati's comet, and Dr. C. F. Pape at Altona gave numerical values for the impulses outward from the Sun, which must have actuated the materials respectively of the curved and straight tails adorning the same beautiful and surprising object. The physical theory of repulsion, however, was, it might be said, still in the air. Nor did it even begin to assume consistency until Zollner took it in hand in 1871. It is perfectly well ascertained that the energy of the push or pull produced by electricity depends, other things being the same, upon the surface of the body acted on, that of gravity upon its mass. The efficacy of solar electrical repulsion relatively to solar gravitational attraction grows, consequently, as the size of the particle diminishes. Make this small enough, and it will virtually cease to gravitate, and will unconditionally obey the impulse to recession. This principle Zollner was the first to realize in its application to comets. It gives the key to their constitution. Admitting that the Sun and they are similarly electrified, their more substantially aggregated parts will still follow the solicitations of his gravity, while the finely divided particles escaping from them will, simply by reason of their minuteness, fall under the sway of his repellent electric power. They will, in other words, form tails. Nor is any extravagant assumption called for as to the intensity of the electrical charge concerned in producing these effects. Zollner, in fact, showed that it need not be higher than that attributed by the best authorities to the terrestrial surface. 40 years have elapsed since M. Bredikhin, director successively of the Moscow and of the Pulkowa observatories, turned his attention to these curious phenomena. His persistent inquiries on the subject, however, date from the appearance of Coggia's comet in 1874. On computing the value of the repulsive force exerted in the formation of its tail, and comparing it with values of the same force arrived at by him in 1862 for some other conspicuous comets, it struck him that the numbers representing them fell into three well-defined classes. I suspect, he wrote in 1877, that comets are divisible into groups, for each of which the repulsive force is perhaps the same. This idea was confirmed on fuller investigation. In 1882 the appendages of 36 well-observed comets had been reconstructed theoretically, without a single exception being met with to the rule of the three types. A further study of 40 comets led, in 1885, only to a modification of the numerical results previously arrived at. In the first of these, the repellent energy of the Sun is 14 times stronger than his attractive energy. The particles forming the enormously long straight rays projected outward from this kind of comet leave the nucleus with a mean velocity of just 7 km per second, which, becoming constantly accelerated, carries them in a few days to the limit of visibility. The great comets of 1811, 1843, and 1861, that of 1744, so far as its principal tail was concerned, and Halley's comet at its various apparitions, belonged to this class. Less narrow limits were assigned to the values of the repulsive force employed to produce the second type. For the axis of the tail, it exceeds by 1/10, equals 1/1, the power of solar gravity. For the anterior edge, it is more than twice, 2/2, for the posterior only half as strong. The corresponding initial velocity, for the axis, is 1,500 meters a second, and the resulting appendage a scimitar-like or plumy tail, such as Donati's and Coggia's comets furnished splendid examples of. Tails of the third type are constructed with forces of repulsion from the Sun ranging from 1/10 to 3/10 that of his gravity, producing an accelerated movement of attenuated matter from the nucleus. Beginning at the leisurely rate of 300 to 600 meters a second. They are short, strongly bent, brush-like emanations, and in bright comets seem to be only found in combination with tails of the higher classes. Multiple tails, indeed, that is, tails of different types emitted simultaneously by one comet, are perceived, as experience advances and observation becomes closer, to be rather the rule than the exception. Now what is the meaning of these three types? Is any translation of them into physical fact possible? To this question Brédikhine supplied, in 1879, a plausible answer. It was already a current surmise that multiple tails are composed of different kinds of matter, differently acted on by the Sun. Both Olbers and Bessel had suggested this explanation of the straight and curved emanations from the comet of 1807. Norton had applied it to the faint light tracks proceeding from that of Donati, Winnick to the varying deviations of its more brilliant plumage. Brédikhine defined and ratified the conjecture. He undertook to determine, provisionally as yet, the several kinds of matter appropriated severally to the three classes of tails. These he found to be hydrogen for the first, hydrocarbons for the second, and iron for the third. The ground of this apportionment is that the atomic weights of these substances bear to each other the same inverse proportion as the repulsive forces employed in producing the appendages they are supposed to form. And Zollner had pointed out in 1875 that the heliofugal power by which comets' tails are developed would, in fact, be effective just in that ratio. Hydrogen, as the lightest known element, that is, the least under the influence of gravity, was naturally selected as that which yielded most readily to the counterpersuasions of electricity. Hydrocarbons had been shown by the spectroscope to be present in comets, and were fitted by their specific weight, as compared with that of hydrogen, to form tails of the second type. While the atoms of iron were just heavy enough to compose those of the third, and, from the plentifulness of their presence in meteorites, might be presumed to enter, in no inconsiderable proportion, into the mass of comets. These three substances, however, were by no means supposed to be the sole constituents of the appendages in question. On the contrary, the great breadth of what, for the present, were taken to be characteristically iron tails was attributed to the presence of many kinds of matter of high and slightly different specific weights. While the expanded plume of Donati was shown to be, in reality, a whole system of tails, made up of many substances, each spreading into a separate hollow cone, more or less deviating from, and partially superposed upon the others. Yet these felicities of explanation must not make us forget that the chemical composition attributed to the first type of cometary trains has, so far, received no countenance from the spectroscope. The emission lines of free, incandescent hydrogen have never been derived from any part of these bodies. Dissentient opinions, accordingly, were expressed as to the cause of their structural peculiarities. Ranyard, Zenker, and others advocated the agency of heat repulsion in producing them. Kier somewhat obscurely explains them through the evolution of gases by colliding particles. Herz of Vienna concludes tails to be mere illusory appendages produced by electrical discharges through the rare medium assumed to fill space. But Hearn conclusively showed that no such medium could possibly exist without promptly bringing ruin upon our daedal Earth and its revolving companions. On the whole, modern researches tend to render superfluous the chemical diversities postulated by Brédikhine. Electricity alone seems competent to produce the varieties of cometary emanation they were designed to account for. The distinction of types rests on a solid basis of fact, but probably depends upon differences rather in the mode of action than in the kind of substance acted upon. Suggestive sketches of electrical and light pressure theories of comets have been published respectively by Mr. Fessenden of Allegheny, and by M. Arrhenius at Stockholm. Although evidently of a tentative character, they possess great interest. Bredikhine's hypothesis was promptly and profusely illustrated. Within 3 years of its promulgation, 5 bright comets made their appearance, each presenting some distinctive peculiarity by which knowledge of these curious objects was materially helped forward. The first of these is remembered as the Great Southern Comet. It was never visible in these latitudes, but made a short though stately progress through southern skies. Its earliest detection was at Córdoba on the last evening of January, 1880. And it was seen on February 1, as a luminous streak, extending just after sunset from the southwest horizon towards the pole, in New South Wales, at Montevideo, and the Cape of Good Hope. The head was lost in the solar rays until February 4, when Dr. Gould, then director of the National Observatory of the Argentine Republic at Córdoba, caught a glimpse of it very low in the west, and on the following evening, Mr. Eddy, at Grahamstown, discovered a faint nucleus, of a straw-colored tinge, about the size of the annular nebula in Lyra. Its condensation, however, was very imperfect, and the whole apparition showed an exceedingly filmy texture. The tail was enormously long. On February 5 it extended, large perspective retrenchment notwithstanding, over an arc of 50 degrees, but its brightness nowhere exceeded that of the Milky Way in Taurus. There was little curvature perceptible. The edges of the appendage ran parallel, forming a nebulous causeway from star to star, and the comparison to an auroral beam was appropriately used. The aspect of the famous comet of 1843 was forcibly recalled to the memory of Mr. Janisch, governor of St. Helena, and the resemblance proved not merely superficial. But the comet of 1880 was less brilliant, and even more evanescent. After only 8 days of visibility, it had faded so much as no longer to strike, though still discoverable by the unaided eye, and on February 20 it was invisible with the great Córdoba equatorial pointed to its known place. But the most astonishing circumstance connected with this body is the identity of its path with that of its predecessor in 1843. This is undeniable. Dr. Gould, Mr. Hind, and Dr. Copeland, each computed a separate set of elements from the first rough observations, and each was struck with an agreement between the two orbits so close as to render them virtually indistinguishable. Can it be possible, Mr. Hind wrote to Sir George Airy, that there is such a comet in the system, almost grazing the sun's surface in perihelion, and revolving in less than 37 years. I confess I feel a difficulty in admitting it, notwithstanding the above extraordinary resemblance of orbits. Mr. Hind's difficulty was shared by other astronomers. It would, indeed, be a violation of common sense to suppose that a celestial visitant so striking in appearance had been for centuries back an unnoticed frequenter of our skies. Various expedients, accordingly, were resorted to for getting rid of the anomaly. The most promising at first sight was that of the resisting medium. It was hard to believe that a body, largely vaporous, shooting past the sun at a distance of less than 100,000 miles from his surface, should have escaped powerful retardation. It must have passed through the very midst of the corona. It might easily have had an actual encounter with a prominence. Escape from such proximity might, indeed, very well have been judged beforehand to be impossible. Even admitting no other kind of opposition than that dubiously supposed to have affected Encke's comet, the result in shortening the period ought to be of the most marked kind. It was proved by Appolzer that if the comet of 1843 had entered our system from stellar space with parabolic velocity it would, by the action of a medium such as Encke postulated, varying in density inversely as the square of the distance from the sun, have been brought down, by its first perihelion passage, to elliptic movement in a period of 24 years. With such rapid diminution that its next return would be in about 10. But such restricted observations as were available on either occasion of its visibility gave no sign of such a rapid progress towards engulfment. Another form of the theory was advocated by Klinkerfues. He supposed that 4 returns of the same body had been witnessed within historical memory, the first in 371 BC, the next in 1668, besides those of 1843 and 1880. An original period of 2039 years being successively reduced by the withdrawal at each perihelion passage of 1/1320 of the velocity acquired by falling from the far extremity of its orbit towards the Sun, to 175 and 37 years. A continuance of the process would bring the comet of 1880 back in 1897. Unfortunately, the earliest of these apparitions cannot be identified with the recent ones unless by doing violence to the plain meaning of Aristotle's words in describing it. He states that the comet was first seen during the frosts and in the clear skies of winter, setting due west nearly at the same time as the Sun. This implies some considerable north latitude. But the objects lately observed had practically no north latitude. They accomplished their entire course above the ecliptic in 2 hours and a quarter, during which space they were barely separated a hand's breadth, one might say, from the Sun's surface. For the purposes of the desired assimilation, Aristotle's comet should have appeared in March. It is not credible, however, that even a native of Thrace should have termed March winter. With the comet of 1668 the case seemed more dubious. The circumstances of its appearance are barely reconcilable with the identity attributed to it, although too vaguely known to render certainty one way or the other attainable. It might, however, be expected that recent observations would at least decide the questions whether the comet of 1843 could have returned in less than 37, and whether the comet of 1880 was to be looked for at the end of 17.5 years. But the truth is that both these objects were observed over so small an arc, 8 degrees and 3 degrees respectively, that their periods remained virtually undetermined. For while the shape and position of their orbits could be and were fixed with a very close approach to accuracy, the length of those orbits might vary enormously without any very sensible difference being produced in the small part of the curves traced out near the Sun. Dr. Wilhelm Meyer, however, arrived, by an elaborate discussion, at a period of 37 years for the comet of 1880, while the observations of 1843 were admittedly best fitted by Hubbard's ellipse of 533 years, but these Dr. Meyer supposed to be affected by some constant source of error, such as would be produced by a mistaken estimate of the position of the comet's center of gravity. He inferred finally that, in spite of previous non-appearances, the two comets represented a single regular denizen of our system. Returning once in 37 years along an orbit of such extreme eccentricity that its movement might be described as one of precipitation towards and rapid escape from the Sun, rather than of sedate circulation round it. The geometrical test of identity has hitherto been the only one which it was possible to apply to comets, and in the case before us it may fairly be said to have broken down. We may, then, tentatively, and with much hesitation, try a physical test, though scarcely yet, properly speaking, available. We have seen that the comets of 1843 and 1880 were strikingly alike in general appearance, though the absence of a formed nucleus in the latter, and its inferior brilliancy, detracted from the convincing effect of the resemblance. Nor was it maintained when tried by exact methods of inquiry. M. Brédikhine found that the gigantic ray emitted in 1843 belonged to his type number 1, that of 1880 to type number 2. The particles forming the one were actuated by a repulsive force 10 times as powerful as those forming the other. It is true that a second noticeably curved tail was seen in Chile, March 1, and at Madras, March 11, 1843. And the conjecture was accordingly hazarded that the materials composing on that occasion the principal appendage having become exhausted, those of the secondary one remained predominant, and reappeared alone in the hydrocarbon train of 1880. But the one known instance in point is against such a supposition. Halley's comet, the only great comet of which the returns have been securely authenticated and carefully observed, has preserved its type unchanged through many successive revolutions. The dilemma presented to astronomers by the great southern comet of 1880 was unexpectedly renewed in the following year. On the 22nd of May, 1881, Mr. John Tebbutt of Windsor, New South Wales, scanning the western sky, discerned a hazy-looking object which he felt sure was a strange one. A marine telescope at once resolved it into two small stars and a comet, the latter of which quickly attracted the keen attention of astronomers, for Dr. Gould, computing its orbit from his first observations at Córdoba, found it to agree so closely with that arrived at by Bessel for the comet of 1807 that he telegraphed to Europe, June 1, announcing the unexpected return of that body. So unexpected that theoretically it was not possible before the year 3346, and Bessel's investigation was one which inspired and eminently deserved confidence. Here, then, once more the perplexing choice had to be made between a premature and unaccountable reappearance and the admission of a plurality of comets moving nearly in the same path. But in this case facts proved decisive. Tebbutt's comet passed the Sunday, June 16, at a distance of 68 millions of miles, and became visible in Europe 6 days later. It was, in the opinion of some, the finest object of the kind since 1861. In traversing the constellation Auriga on its debut in these latitudes, it outshone Capella. On June 24 and some subsequent nights, it was unmatched in brilliancy by any star in the heavens. In the telescope, the two interlacing arcs of light, which had adorned the head of Coggia's comet were reproduced, while a curious dorsal spine of strong illumination formed the axis of the tail, which extended in clear skies over an arc of 20 degrees. It belonged to the same type as Donati's great plume, the particles composing it being driven from the sun by a force twice as powerful as that urging them towards it. But the appendage was, for a few nights, and by two observers perceived to be double. Temple, on June 27, and Louis Boss, at Albany, New York. June 26 and 28, saw a long straight ray corresponding to a far higher rate of emission than the curved train, and shown by Brédikhine to be a member of the so-called hydrogen class. It had vanished by July 1, but made a temporary reappearance July 22. The appendages of this comet were of remarkable transparency. Small stars shone wholly undimmed across the tail, and a very nearly central transit of the head over one of the 7th magnitude on the night of June 29. Produced, if any change, an increase of brilliancy in the object of this spontaneous experiment. Dr. Meyer, indeed, at the Geneva Observatory, detected apparent signs of refractive action upon rays thus transmitted, but his observations remain isolated, and were presumably illusory. The track pursued by this comet gave peculiar advantages for its observation. Ascending from Auriga through Camelopardalis, it stood, July 19, on a line between the pointers and the pole, within 8 degrees of the latter, and thus remained for a lengthened period constantly above the horizon of northern observers. Its brightness, too, was no transient blaze, but had a lasting quality which enabled it to be kept steadily in view during nearly 9 months. Visible to the naked eye until the end of August, the last telescopic observation of it was made February 14, 1882, when its distance from the Earth considerably exceeded 300 million miles. Under these circumstances, the knowledge acquired of its orbit was of more than usual accuracy, and showed conclusively that the comet was not a simple return of Bessel's. For this would involve a period of 74 years, whereas Tebbutt's comet cannot revisit the Sun until after the lapse of 2.5 millenniums. Nevertheless, the twin bodies move so nearly in the same path that an original connection of some kind is obvious, and the recent example of Biela readily suggested a conjecture as to what the nature of that connection might have been. The comets of 1807 and 1881 are, then, regarded with much probability as fragments of a primitive disrupted body, one following in the wake of the other at an interval of 74 years. Imperfect photographs were taken of Donati's comet both in England and America, but Tebbutt's comet was the first to which the process was satisfactorily applied. The difficulties to be overcome were very great. The chemical intensity of cometary light is, to begin with, extraordinarily small. Janssen estimated it at 1/300,000 of moonlight. Hence, if the ordinary process by which lunar photographs are taken had been applied to the comet of 1881, an exposure of at least 3 days would have been required in order to get an impression of the head with about a 10th part of the tail. But by that time a new method of vastly increased sensitiveness had been rendered available, by which dry gelatin plates were substituted for the wet collodion plates hitherto in use. And this improvement alone reduced the necessary time of exposure to 2 hours. It was brought down to half an hour by Jansen's employment of a reflector specially adapted to give an image illuminated 8 or 10 times as strongly as that produced in the focus of an ordinary telescope. The photographic feebleness of cometary rays was not the only obstacle in the way of success. The proper motion of these bodies is so rapid as to render the usual devices for keeping a heavenly body steadily in view quite inapplicable. The machinery by which the diurnal movement of the sphere is followed, must be especially modified to suit each eccentric career. This, too, was done, and on June 30, 1881, Jansen secured a perfect photograph of the brilliant object then visible, showing the structure of the tail with beautiful distinctness to a distance of 2 to 1/2 degree from the head. An impression to nearly 10 degrees was obtained about the same time by Dr. Henry Draper at New York, with an exposure of 162 minutes. Tebbutt's, or Comet 1881-3, was also the first comet of which the spectrum was so much as attempted to be chemically recorded. Both Huggins and Draper were successful in this respect, but Huggins was more completely so. The importance of the feat consisted in its throwing open to investigation a part of the spectrum invisible to the eye, and so affording an additional test of cometary constitution. The result was fully to confirm the origin from carbon compounds assigned to the visible rays, by disclosing additional bands belonging to the same series in the ultraviolet. As well as to establish unmistakably the presence of a not inconsiderable proportion of reflected solar light by the clear impression of some of the principal Fraunhofer lines. Thus the polariscope was found to have told the truth, though not the whole truth. The photograph so satisfactorily communicative was taken by Sir William Huggins on the night of June 24. And on the 29th, at Greenwich, the telltale Fraunhofer lines were perceived to interrupt the visible range of the spectrum. This was at first so vividly continuous, that the characteristic cometary bands could scarcely be detached from their bright background. But as the nucleus faded towards the end of June, they came out strongly, and were more and more clearly seen, both at Greenwich and at Princeton, to agree, not with the spectrum of hydrocarbons glowing in a vacuum tube, but with that of the same substances burning in a Bunsen flame. It need not, however, be inferred that cometary materials are really in a state of combustion. This, from all that we know, may be called an impossibility. The additional clue furnished was rather to the manner of their electrical illumination. The spectrum of the tail was, in this comet, found to be not essentially different from that of the head. Professor Wright of Yale College ascertained a large percentage of its light to be polarized in a plane passing through the sun, and hence to be reflected sunlight. A faint continuous spectrum corresponded to this portion of its radiance. But gaseous emissions were also present. At Potsdam, on June 30, the hydrocarbon bands were indeed traced by Vogel to the very end of the tail. And they were kept in sight by Young at a greater distance from the nucleus than the more equably dispersed light. There seems little doubt that, as in the solar corona, the relative strength of the two orders of spectra is subject to fluctuations. The comet of 1881-3 was thus of signal service to science. It afforded, when compared with the comet of 1807, the first undeniable example of two such bodies traveling so nearly in the same orbit as to leave absolutely no doubt of the existence of a genetic tie between them. Cometary photography came to its earliest fruition with it, and cometary spectroscopy made a notable advance by means of it. Before it was yet out of sight, it was provided with a successor. At Ann Arbor Observatory, Michigan, on July 14, a comet was discovered by Dr. Skeebrel, which, as his claim to priority is undisputed, is often allowed to bear his name, although designated, in strict scientific parlance, Comet 1881-4. It was observed in Europe after 3 days, became just discernible by the naked eye at the end of July, and brightened consistently up to its perihelion passage, August 22, when it was still about 50 million miles from the Sun. During many days of that month, the uncommon spectacle was presented of two bright comets circling together, though at widely different distances, round the north pole of the heavens. The newcomer, however, never approached the pristine luster of its predecessor. Its nucleus, when brightest, was comparable to the star Scior Caroli, a narrow, perfectly straight ray proceeding from it to a distance of 10 degrees. This was easily shown by Brédikhine to belong to the hydrogen type of tails, while a strange, faint second tail, or bifurcation of the first one, observed by Captain Noble, August 24, fell into the hydrocarbon class of emanations. It was seen, August 22 and 24, by Dr. F. Turby of Louvain, as a short nebulous brush, like the abortive beginning of a congeries of curving trains, but appeared no more. Its well-attested presence was significant of the complex constitution of such bodies, and the manifold kinds of action progressing in them. The only peculiarity in the spectrum of Skeeberl's comet consisted in the almost total absence of continuous light. The carbon bands were nearly isolated and very bright. Barely from the nucleus proceeded a rainbow-tinted streak, indicative of solid or liquid matter, which, in this comet, must have been a very scanty amount. Its visit to the Sun in 1881 was, so far as is known, the first. The elements of its orbit showed no resemblance to those of any previous comet, nor any marked signs of periodicity. So that, although it may be considered probable, we do not know that it is moving in a closed curve, or will ever again penetrate the precincts of the solar system. It was last seen from the southern hemisphere, October 19, 1881. The third of a quartet of lucid comets visible within 16 months, was discovered by Mr. C. S. Wells at the Dudley Observatory, Albany, March 17, 1882. 2 days later it was described by Mr. Louis Boss as a great comet in miniature, so well defined and regularly developed were its various parts and appendages. Discernible with optical aid early in May, it was on June 5 observed on the meridian at Albany just before noon, an astronomical event of extreme rarity. Comet Wells, however, never became an object so conspicuous as to attract general attention, owing to its immersion in the evening twilight of our northern June. But the study of its spectrum revealed new facts of the utmost interest. All the comets till then examined had been found, with the 2 transiently observed exceptions already mentioned, to conform to one invariable type of luminous emission. Individual distinctions there had been, but no specific differences. Now all these bodies had kept at a respectful distance from the Sun, for of the great comet of 1880 no spectroscopic inquiries had been made. Comet Wells, on the other hand, approached its surface within little more than 5 million miles on June 10, 1882, and the vicinity had the effect of developing a novel feature in its incandescence. During the first half of April its spectrum was of the normal type, though the carbon bands were unusually weak. But with approach to the Sun they died out, and the entire light seemed to become concentrated into a narrow, unbroken, brilliant streak, hardly to be distinguished from the spectrum of a star. This unusual behavior excited attention, and a strict watch was kept. It was rewarded at the Dunecht Observatory, May 27, by the discernment of what had never before been seen in a comet, the yellow ray of sodium. By June 1, this had kindled into a blaze overpowering all other emissions. The light of the comet was practically monochromatic. And the image of the entire head, with the root of the tail, could be observed, like a solar prominence, depicted, in its new saffron vesture of vivid illumination, within the jaws of an open slit. At Potsdam, the bright yellow line was perceived with astonishment by Vogel on May 31, and was next evening identified with Fraunhofer's D. Its character led him to infer a very considerable density in the glowing vapor emitting it. Hasselberg founded an additional argument in favor of the electrical origin of cometary light on the changes in the spectrum of Comet Wells. For they were closely paralleled by some earlier experiments of Weidmann, in which the gaseous spectra of vacuum tubes were at once effaced on the introduction of metallic vapors. It seemed as if the metal had no sooner been rendered volatile by heat, than it usurped the entire office of carrying the discharge, the resulting light being thus exclusively of its production. Had simple incandescence by heat been in question, the effect would have been different, the 2 spectra would have been superposed without prejudice to either. Similarly, the replacement of the hydrocarbon bands in the spectrum of the comet by the sodium line proved electricity to be the exciting agent. For the increasing thermal power of the sun might, indeed, have ignited the sodium, but it could not have extinguished the hydrocarbons. Sir William Huggins succeeded in photographing the spectrum of Comet Wells by an exposure of 1 hour and a quarter. The result was to confirm the novelty of its character. None of the ultraviolet carbon groups were apparent. But certain bright rays, as yet unidentified, had imprinted themselves. Otherwise the spectrum was strongly continuous, uninterrupted even by the Fraunhofer lines detected in the spectrum of Tebbutt's comet. Hence it was concluded that a smaller proportion of reflected light was mingled with the native emissions of the later arrival. All that is certainly known about the extent of the orbit traversed by the first comet of 1882 is that it came from, and is now retreating towards, vastly remote depths of space. An American computer found a period indicated for it of no less than 400,000 years. A Thrain of Dingelstadt arrived at one of 3,617. Both are perhaps equally insecure. We have now to give some brief account of one of the most remarkable cometary apparitions on record, and, with the single exception of that identified with the name of Halley, the most instructive to astronomers. The lessons learned from it were as varied and significant as its aspect was splendid, although from the circumstance of its being visible in general only before sunrise, the spectators of its splendor were comparatively few. The discovery of a great comet at Rio Janeiro, September 11, 1882, became known in Europe through a telegram from M. Krills, director of the observatory at that place. It had, however, as appeared subsequently, been already seen on the 8th by Mr. Finley of the Cape Observatory, and at Auckland as early as September 3. A later, but very singularly conditioned detection, quite unconnected with any of the preceding, was effected by Dr. Common at Ealing. Since the eclipse of May 17, when a comet, named Tophet, in honor of the Khedive of Egypt, was caught on Dr. Schuster's photographs, entangled, one might almost say, in the outer rays of the corona, he had scrutinized the neighborhood of the sun on the infinitesimal chance of intercepting another such body on its rapid journey thence or thither. We record with wonder that, after an interval of exactly 4 months, that infinitesimal chance turned up in his favor. On the forenoon of Sunday, September 17, he saw a great comet close to, and rapidly approaching the sun. It was, in fact, then within a few hours of perihelion. Some measures of position were promptly taken, but a cloud veil covered the interesting spectacle before midday was long past. Mr. Finley at the Cape was more completely fortunate. Divided from his fellow observer by half the world, he unconsciously finished, under a clearer sky, his interrupted observation. The comet, of which the silvery radiance contrasted strikingly with the reddish-yellow glare of the sun's margin it drew near to, was followed continuously right into the boiling of the limb, a circumstance without precedent in cometary history. Dr. Elkin, who watched the progress of the event with another instrument, thought the intrinsic brilliancy of the nucleus scarcely surpassed by that of the sun's surface. Nevertheless it had no sooner touched it than it vanished as if annihilated. So sudden was the disappearance, at 4h. 50 m. 58's, Cape mean time, that the comet was at first believed to have passed behind the sun. But this proved not to have been the case. The observers at the Cape had witnessed a genuine transit. Nor could non-visibility be explained. Plate 3. The Great Comet of September, 1882. Photographed at the Royal Observatory, Cape of Good Hope. By equality of luster. For the gradations of light on the sun's disk are amply sufficient to bring out against the dusky background of the limb any object matching the brilliancy of the center. While an object just equally luminous with the limb must inevitably show dark at the center. The only admissible view, then, is that the bulk of the comet was of too filmy a texture, and its presumably solid nucleus too small, to intercept any noticeable part of the solar rays, a piece of information worth remembering. On the following morning, the object of this unique observation showed, in Sir David Gill's words, an astonishing brilliancy as it rose behind the mountains on the east of Table Bay. and seemed in no way diminished in brightness when the sun rose a few minutes afterward. It was only necessary to shade the eye from direct sunlight with the hand at arm's length, to see the comet, with its brilliant white nucleus and dense white, sharply bordered tail of quite half a degree in length. All over the world, wherever the sky was clear during that day, September 18th, it was obvious to ordinary vision. Since 1843 nothing had been seen like it. From Spain, Italy, Algeria, southern France, dispatches came in announcing the extraordinary appearance. At Córdoba, in South America, the blazing star near the sun was the one topic of discourse. Moreover, and this is altogether extraordinary, the records of its daylight visibility to the naked eye extend over 3 days. At Reyes, near Tarragona, it showed bright enough to be seen through a passing cloud when only 3 of the sun's diameters from his limb, just before its final rush past perihelion on September 17th. While at Cartagena in Spain, on September 19th, it was kept in view during 2 hours before and 2 hours after noon, and was similarly visible in Algeria on the same day. But still more surprising than the appearance of the body itself were the nature and relations of the path it moved in. The first rough elements computed for it by Mr. Tebbutt, Dr. Chandler, and Mr. White, assistant at the Melbourne Observatory, showed at once a striking resemblance to those of the twin comets of 1843 and 1880. This suggestive fact became known in this country, September 27th, through the medium of a Denec circular. It was fully confirmed by subsequent inquiries, for which ample opportunities were luckily provided. The likeness was not, indeed, so absolutely perfect as in the previous case, it included some slight, though real differences. But it bore a strong and unmistakable stamp, broadly challenging explanation. 2 hypotheses only were really available. Either the comet of 1882 was an accelerated return of those of 1843 and 1880, or it was a fragment of an original mass to which they also had belonged. For the purposes of the first view the resisting medium was brought into full play. The opinion of its efficacy was for some time both prevalent and popular, and formed the basis, moreover, of something of a sensational panic. For a comet which, at a single passage through the sun's atmosphere, encountered sufficient resistance to shorten its period from 37 to 2 years and 8 months, must, in the immediate future, be brought to rest on his surface. And the solar conflagration thence ensuing was represented in some quarters, with more license of imagination than countenance from science, as likely to be of catastrophic import to the inhabitants of our little planet. But there was a test available in 1882 which it had not been possible to apply either in 1843 or in 1880. The 2 bodies visible in those years had been observed only after they had already passed perihelion. The third member of the group, on the other hand, was accurately followed for a week before that event, as well as during many months after it. Finley's and Elkin's observation of its disappearance at the sun's edge formed, besides, a peculiarly delicate test of its motion. The opportunity was thus afforded, by directly comparing the comet's velocity before and after its critical plunge through the solar surroundings, of ascertaining with approximate certainty whether any considerable retardation had been experienced in the course of that plunge. The answer distinctly given was that there had not. The computed and observed places on both sides of the sun fitted harmoniously together. The effect, if any were produced, was too small to be perceptible. This result is, in itself, a memorable one. It seems to give the coup de grace to Encke's theory, discredited, in addition, by Backlund's investigation, of a resisting medium growing rapidly denser inwards. For the perihelion distance of the comet of 1882, though somewhat greater than that of its predecessors, was nevertheless extremely small. It passed at less than 300,000 miles of the sun's surface. But the ethereal substance long supposed to obstruct the movement of Encke's comet would there be nearly 2,000 times denser than at the perihelion of the smaller body, and must have exerted a conspicuous retarding influence. That none such could be detected seems to argue that no such medium exists. Further evidence of a decisive kind was not wanting on the question of identity. The Great September Comet of 1882 was in no hurry to withdraw itself from curious terrestrial scrutiny. It was discerned with the naked eye at Córdoba as late as March 7, 1883, and still showed in the field of the Great Equatorial on June 1 as an excessively faint whiteness. It was then about 480 millions of miles from the Earth, a distance to which no other comet, not even excepting the peculiar one of 1729, had been pursued. Moreover, an arc of 340 out of the entire 360 degrees of its circuit had been described under the eyes of astronomers, so that its course came to be very well known. That its movement is in a very eccentric ellipse, traversed in several hundred years, was ascertained. The later inquiries of Dr. Kreutz, completed in a volume published in 1901, demonstrated the period to be of about 800 years, while that of its predecessor in 1843 might possibly agree with it, but is much more probably estimated at 512 years. The hypothesis that they, or any of the comets associated with them, were returns of an individual body is peremptorily excluded. They may all, however, have been separated from one original mass by the divellent action of the Sun at close quarters. Each has doubtless its own period, since each has most likely suffered retardations or accelerations special to itself, which, though trifling in amount, would avail materially to alter the length of the major axis, while leaving the remaining elements of the common orbit virtually unchanged. A fifth member was added to the family in 1887. On the 18th of January in that year, M. Thome discovered at Córdoba a comet reproducing with curious fidelity the lineaments of that observed in the same latitudes 7 years previously. The narrow ribbon of light, contracting towards the Sun, and running outward from it to a distance of 35 degrees, the unsubstantial head, availed nothingness, as it appeared, since no distinct nucleus could be made out. The quick fading into invisibility, were all accordant peculiarities, and they were confirmed by some rough calculations of its orbit, showing geometrical affinity to be no less unmistakable than physical likeness. The observations secured were indeed, from the nature of the apparition, neither numerous nor over-reliable, and the earliest of them dated from a week after perihelion, passed, almost by a touch-and-go escape, January 11. On January 27, this mysterious object could barely be discerned telescopically at Córdoba. That it belonged to the series of southern comets can scarcely be doubted. But the inference that it was an actual return of the comet of 1880, improbable in itself, was negatived by its non-appearance in 1894. Meyer's incorporation with this extraordinary group of the eclipse comet of 1882 has been approved by Kreutz, after searching examination. The idea of cometary systems was first suggested by Thomas Clausen in 1831. It was developed by the late M. Hooke, director of the Utrecht Observatory, in 1865 and some following years. He found that in quite a considerable number of cases, the paths of 2 or 3 comets had a common point of intersection far out in space, indicating with much likelihood a community of origin. This consisted, according to his surmise, in the disruption of a parent mass during its sweep round the star latest visited. Be this as it may, the fact is undoubted that numerous comets fall into groups, in which similar conditions of motion betray a pre-existent physical connection. Never before, however, had geometrical relationship been so notorious as between the comets now under consideration. And never before, in a comet still, it might be said, in the prime of life, had physical peculiarities tending to account for that affinity been so obvious as in the chief member of the group. Observation of a granular structure in cometary nuclei dates far back into the 17th century, when Cycadus and Hevelius described the central parts of the comets of 1618 and 1652 respectively as made up of a congeries of minute stars. Analogous symptoms of a loose state of aggregation have of late been not unfrequently detected in telescopic comets, besides the instances of actual division offered by those connected with the names of Biela and Liais. The forces concerned in producing these effects seem to have been peculiarly energetic in the great comet of 1882. The segmentation of the nucleus was first noticed in the United States and at the Cape of Good Hope, September 30. It proceeded rapidly. At Kiel, on October 5 and 7, Professor Kruger perceived two centers of condensation. A definite and progressive separation into three masses was observed by Professor Holden, October 13 and 17. A few days later, M. Temple found the head to consist of four lucid aggregations, ranged nearly along the prolongation of the caudal axis, and Dr. Common, January 27, 1883, saw five nuclei in a line like pearls on a string. This remarkable character was preserved to the last moment of the comet's distinct visibility. It was a consequence, according to Dr. Kreutz, of violent interior action in the comet itself while close to the Sun. There were, however, other curious proofs of a disaggregative tendency in this body. On October 9, Schmidt discovered at Athens a nebulous object 4 degrees southwest of the Great Comet, and traveling in the same direction. It remained visible for a few days, and, from Oppenheim's and Hein's calculations, there can be little doubt that it was really the offspring by fission of the body it accompanied. This is rendered more probable by the unexampled spectacle offered, October 14, to Professor Barnard, then of Nashville, Tennessee, of 6 or 8 distinct cometary masses within 6 degrees south by west of the comet's head. None of which reappeared on the next opportunity for a search. A week later, however, one similar object was discerned by Mr. W. R. Brooks, in the opposite direction from the comet. Thus space appeared to be strewn with the filmy debris of this beautiful but fragile structure all along the track of its retreat from the Sun. Its tail was only equaled, if it were equaled, in length by that of the comet of 1843. It extended in space to the vast distance of 200 millions of miles from the head, but, so imperfectly were its proportions displayed to terrestrial observers, that it at no time covered an arc of the sky of more than 30 degrees. This apparent extent was attained, during a few days previous to September 25, by a faint, thin, rigid streak, noticed only by a few observers, by Elkin at the Cape Observatory, Eddy at Grahamstown, and Krills at Rio Janeiro. It diverged at a low angle from the denser curved train, and was produced, according to Brédikhine, by the action of a repulsive force 12 times as strong as the counterpole of gravity. It belonged, that is, to type 1. While the great bifurcate appendage, obvious to all eyes, corresponded to the lower rate of emission characteristic of type 2. This was remarkable for the perfect definiteness of its termination, for its strongly forked shape, and for its unusual permanence. Down to the end of January, 1883, its length, according to Schmidt's observations, was still 93 million miles. And a week later it remained visible to the naked eye, without notable abridgment. Most singular of all was an anomalous extension of the appendage towards the Sun. During the greater part of October and November, a luminous tube or sheath, of prodigious dimensions, seemed to surround the head, and project in a direction nearly opposite to that of the usual outpourings of attenuated matter. Its diameter was computed by Schmidt to be, October 15, no less than 4 million miles, and it was described by Krills as a truncated cone of nebulosity, stretching 3 degrees or 4 degrees sunwards. This, and the entire anterior part of the comet, were again surrounded by a thin, but enormously voluminous paraboloidal envelope, observed by Schiaparelli for a full month from October 19. There can be little doubt that these abnormal effluxes were a consequence of the tremendous physical disturbance suffered at perihelion. And it is worth remembering that something analogous was observed in the comet of 1680, Newton's, also noted for its excessively close approach to the Sun, and possibly moving in a related orbit. The only plausible hypothesis as to the mode of their production is that of an opposite state of electrification in the particles composing the ordinary and extraordinary appendages. The spectrum of the great comet of 1882 was, in part, a repetition of that of its immediate predecessor, thus confirming the inference that the previously unexampled sodium blaze was in both a direct result of the intense solar action to which they were exposed. But the D-line was, this time, not seen alone. At Denect, on the morning of September 18, Drs. Copeland and J. G. Losey succeeded in identifying 6 brilliant rays in the green and yellow with as many prominent iron lines. A very significant addition to our knowledge of cometary constitution, and one which lent countenance to Bredikhine's assumption of various kinds of matter issuing from the nucleus with velocities inversely as their atomic weights. All the lines equally showed a slight displacement, indicating a recession from the Earth of the radiating body at the rate of 37 to 46 miles a second. A similar observation, made by M. Tholen at Nice on the same day, gave emphatic sanction to the spectroscopic method of estimating movement in the line of sight. Before anything was as yet known of the comet's path or velocity, he announced, from the position of the double sodium line alone, that at 3 p.m. on September 18 it was increasing its distance from our planet by from 61 to 76 kilometers per second. M. Bigourdan's subsequent calculations showed that its actual swiftness of recession was at that moment 73 kilometers. Changes in the inverse order to those seen in the spectrum of Comet Wells soon became apparent. In the earlier body, carbon bands had died out with approach to perihelion, and had been replaced by sodium emissions. In its successor, sodium emissions became weakened and disappeared with retreat from perihelion, and found their substitute in carbon bands. Professor Rico was, in fact, able to infer, from the sequence of prismatic phenomena, that the comet had already passed the Sun, thus establishing a novel criterion for determining the position of a comet in its orbit by the varying quality of its radiations. Recapitulating what was learnt from the 5 conspicuous comets of 1880 to 82, we find that the leading facts acquired to science were these 3. First, that comets may be met with pursuing each other, after intervals of many years, in the same, or nearly the same, track, so that identity of orbit can no longer be regarded as a sure test of individual identity. Secondly, that at least the outer corona may be traversed by such bodies with perfect apparent impunity. Finally, that their chemical constitution is highly complex, and that they possess, in some cases at least, a metallic core resembling the meteoric masses which occasionally reach the Earth from planetary space. A group of 5 comets, including Halley's, own a sort of cliental dependence upon the planet Neptune. They travel out from the Sun just to about his distance from it, as if to pay homage to a powerful protector, who gets the credit of their establishment as periodical visitors to the solar system. The second of these bodies to effect a looked-for return was a comet, the 16th within 10 years, discovered by Pons, July 20, 1812, and found by Encke to revolve in an elliptic orbit, with a period of nearly 71 years. It was not, however, until September 1, 1883, that Mr. Brooks caught its reappearance. It passed perihelion January 25, and was last seen June 2, 1884. At its brightest, it had the appearance of a second-magnitude star, furnished with a poorly developed double tail, and was fairly conspicuous to the naked eye in southern Europe, from December to March. One exceptional feature distinguished it. Its fluctuations in form and luminosity were unprecedented in rapidity and extent. On September 21, Dr. Chandler observed it at Harvard as a very faint, diffused nebulosity, with slight central condensation. On the next night, there was found in its place a bright star of the 8th magnitude, scarcely marked out, by a bare trace of environing haze, from the genuine stars it counterfeited. The change was attended by an 8-fold augmentation of light, and was proved by Schiaparelli's confirmatory observations to have been accomplished within a few hours. The stellar disguise was quickly cast aside. The comet appeared on September 23 as a wide nebulous disk, and soon after faded down to its original dimness. Its distance from the Sun was then no less than 200 million miles, and its spectrum showed nothing unusual. These strange variations recurred slightly on October 15, and with marked emphasis on January 1, when they were witnessed with amazement, and photometrically studied by Müller of Potsdam. The entire cycle this time was run through in less than 4 hours, the comet having, in that brief space, condensed, with a vivid outburst of light, into a seeming star, and the seeming star having expanded back again into a comet. Scarcely less transient, though not altogether similar, changes of aspect were noted by M. Perrotin, January 13 and 19, 1884. On the latter date, the continuous spectrum given by a reddish-yellow disk surrounding the true nucleus seemed intensified by bright knots corresponding to the rays of sodium. A comet discovered by Mr. Saarthal at the Royal Observatory, Cape of Good Hope, February 19, 1888, distinguished itself by blazing up, on May 19, to 4 or 5 times its normal brilliancy, at the same time throwing out from the head 2 lustrous lateral branches. These had, on June 1, spread backward so as to join the tail, with an effect like the playing of a fountain. 10 or 11 days later, they had completely disappeared, leaving the comet in its former shape and insignificance. Its abrupt display of vitality occurred 2 full months after perihelion. On the morning of July 7, 1889, Mr. W. R. Brooks, of Geneva, New York, eminent as a successful comet hunter, secured one of his customary trophies. The faint object in question was moving through the constellation Cetus, and turned out to be a member of Jupiter's numerous family of comets, revolving round the Sun in a period of 7 years. Its past history came then, to a certain extent, within the scope of investigation, and proved to have been singularly eventful, nor had the body escaped scatheless from the vicissitudes to which it had been exposed. Observing from Mount Hamilton, August 2 and 5, Professor Barnard noticed this comet, 1889, v. to be attended in its progress through space by 4 outriders, the 2 brighter companions. The fainter pair survived a very short time, were perfect miniatures, Professor Barnard tells us, of the larger comet, each having a small, fairly defined head and nucleus, with a faint, hazy tail, the more distant one being the larger and less developed. The 3 comets were in a straight line, nearly east and west, their tails lying along this line. There was no connecting nebulosity between these objects, the tails of the 2 smaller not reaching each other, or the large comet. To all appearance they were absolutely independent comets. Nevertheless, Spitalier, at Vienna, in the early days of August, perceived, as it were, a thin cocoon of nebulosity woven round the entire trio. One of them faded from view September 5. The other actually outshone the original comet on August 31, but was plainly of inferior vitality. It was last seen by Barnard on November 25, with the 36-inch refractor, while its primary afforded an observation for position with the 12-inch, March 20, 1890. A cause for the disruption it had presumably undergone had, before then, been plausibly assigned. The adventures of Lexell's comet have long served to exemplify the effects of Jupiter's despotic sway over such bodies. Although bright enough in 1770 to be seen with the naked eye, and ascertained to be circulating in 5½ years, it had never previously been seen, and failed subsequently to present itself. The explanation of this anomaly, suggested by Lexell, and fully confirmed by the analytical inquiries both of Laplace and Leverrier, was that a very close approach to Jupiter in 1767 had completely changed the character of its orbit, and brought it within the range of terrestrial observation. While in 1779, after having only twice traversed its new path, at its second return it was so circumstanced as to be invisible from the Earth, it was, by a fresh encounter, diverted into one entirely different. Yet the possibility was not lost sight of that the great planet, by inverting its mode of action, might undo its own work, and fling the comet once more into the inner part of the solar system. This possibility seemed to be realized by Chandler's identification of Brooks's and Lexell's comet. An exceedingly close approach to Jupiter in 1886 had, he found reason to believe, produced such extensive alterations in the elements of its motion as to bring the errant body back to our neighborhood in 1889. But his inference, though ratified by Mr. Charles Lane Poor's preliminary calculations, proved dubious on closer inquiry, and was rendered wholly inadmissible by the circumstances attending the return of Brooks's comet in 1896. The companion objects watched by Barnard in 1889 had by that time, perhaps, become dissipated in space, for they were not redetected. They represented, in all likelihood, wreckage from a collision with Jupiter, dating, perhaps, so far back as 1791, when Mr. Lane Poor found that one of the fateful meetings to which short-period comets are especially subject had taken place. The Lexell-Brooks case was almost duplicated by the resemblance to de Vico's lost comet of 1844 of one detected November 20, 1894, by Edward, son of Lewis Swift. Schulhoff announced the identity, and Chandler, under reserve, vouched for it. Had the comet continued to pursue the track laboriously laid down for it at Boston, and shown itself at the due epoch in 1900, its individuality might have been considered assured. But the formidable vicegerent of the Sun once more interposed, and, in 1897, swept it out of the terrestrial range of view. Hence the recognition remains ambiguous. On the morning of March 7, 1892, Professor Lewis Swift discovered the brightest comet that had been seen by northern observers since 1882. About the time of perihelion, which occurred on April 6, it was conspicuous, as it crossed the celestial equator from Aquarius towards Pegasus, with a nucleus equal to a third magnitude star, and a tail 20 degrees long. This tail was multiple, and multiple in a most curiously variable manner. It divided up into many thin nebulous streaks, the number and relative luster of which underwent rapid and marked changes. Their permanent record on Barnard's and W.H. Pickering's plates marked a noteworthy advance in cometary photography. Plate 4 reproduces two of the Lick pictures, taken with a 6-inch camera, on April 5 and 7 respectively, with, in each case, an exposure of about 1 hour. The tail is in the first composed of 3 main branches, the middle one having sprung out since the previous morning, and the branches are, in their turn, split up into finer rays, to the number of perhaps a dozen in all. In the second a very different state of things is exhibited. The southern component, Professor Barnard remarked, which was the brightest on the 5th, had become diffused and fainter, while the middle tail was very bright and broad. Its southern side, which was the best defined, was wavy in numerous places, the tail appearing as if disturbing currents were flowing at right angles to it. At 42 degrees from the head the tail made an abrupt bend towards the south, as if its current was deflected by some obstacle. In the densest portion of the tail, at the point of deflection, are a couple of dark holes, similar to those seen in some of the nebulae. The middle portion of the tail is brighter, and looks like crumpled silk in places. Next morning the southern was the prominent branch, and it was loaded, at 1 degree 42 from the head, with a strange excrescence, suggesting the budding out of a fresh comet in that incongruous situation. Some of these changes, Professor Barnard thought, might possibly be explained by a rotation of the tail on an axis passing through the nucleus, and Pickering, who formed a similar opinion on Independent. Plate 4. 1-2. Photographs of Swift's Comet. By Professor E. E. Barnard. Number 1. Taken April 4, 1892, exposure 1H. Number 2. Taken April 6, 1892, exposure 1H, 5M. Grounds, assigned about 94 hours as the period of the gyrating movement. He, moreover, determined accelerative velocities outward from the Sun of definite condensations in the tail, indicating for its materials, on Bredikhine's theory, a density less than 1/2 that of hydrogen. This conclusion applied also to Roordame's comet, which exhibited a year later phenomena analogous to those remarked in Swift's. Their photographic study led Professor Hussey to significant inferences as to the structure and rapid changes of cometary appendages. 7 comets were detected in 1892, and all, strange to say, were visible together towards the close of the year. Among them was a faint object, which unexpectedly left a trail on a plate exposed by Professor Barnard to the stars in Aquila on October 12. This was the first comet actually discovered by photography, the Sohag comet having been simultaneously seen and pictured. It has a period of about 6 years. Holmes's comet is likewise periodical, in rather less than 7 years. Its path, which is wholly comprised between the orbits of Mars and Jupiter, is less eccentric than that of any other known comet. Subsequently to its discovery, on November 6, it underwent some curious vicissitudes. At first bright and condensed, it expanded rapidly with increasing distance from the Sun, to which it had made its nearest approach on June 13, until, by the middle of December, It was barely discernible with powerful telescopes as a feebly luminous mist on the face of the sky. But on January 16, 1893, observers in Europe and America were bewildered to find, as if substituted for it, a yellow star of the 7th magnitude, enveloped in a thin nebulous husk, which enclosed a faint miniature tail. This condensation and recovery of light lasted in its full intensity only a couple of days. The almost evanescent faintness of Holmes's comet at its next return accounted for its invisibility previous to 1892, when it was evidently in a state of peculiar excitement. Mr. Perrine was barely able, with the Lick 36-inch, to find the vague nebulous patch which occupied its predicted place on June 10, 1899. The origin of comets has been long and eagerly inquired into, not altogether apart from the cheering guidance of ascertained facts. Sir William Herschel regarded them as fragments of nebulae, scattered debris of embryo worlds. And Laplace approved of and adopted the idea. But there was a difficulty. No comet has yet been observed to travel in a decided hyperbola. The typical cometary orbit, apart from disturbance, is parabolic, that is to say, it is indistinguishable from an enormously long ellipse. But this circumstance could only be reconciled with the view that the bodies thus moving were casual visitors from outer space, by making, as Laplace did, the tacit assumption that the solar system was at rest. His reasoning was, indeed, thereby completely vitiated, as Gauss pointed out in 1815. And the objections then urged were reiterated by Schiaparelli, who demonstrated in 1871 that a large preponderance of well-marked hyperbolic orbits should result if comets were picked up en route by a swiftly advancing sun. The fact that their native movement is practically parabolic shows it to have been wholly imparted from without. They passively obeyed the pull exerted upon them. In other words, their condition previous to being attracted by the sun was one very nearly of relative repose. They shared, accordingly, the movement of translation through space of the solar system. This significant conclusion had been indicated, on other grounds, as the upshot of researches undertaken independently by Carrington and Mohn in 1860. With a view to ascertaining the anticipated existence of a relationship between the general lie of the paths of comets and the direction of the sun's journey. It is tolerably obvious that if they wander at haphazard through interstellar regions their apparitions should markedly aggregate towards the vicinity of the constellation Lyra. That is to say, we should meet considerably more comets than would overtake us, for the very same reason that falling stars are more numerous after than before midnight. Moreover, the comets met by us should be, apparently, swifter moving objects than those coming up with us from behind, because, in the one case, our own real movement would be added to, in the other subtracted from, theirs. But nothing of all this can be detected. Comets approached the sun indifferently from all quarters, and with velocities quite independent of direction. We conclude, then, that the cosmical current which bears the solar system towards its unknown goal carries also with it nebulous masses of undefined extent, and at an undefined remoteness, fragments detached from which, continually entering the sphere of the sun's attraction, flit across our skies under the form of comets. These are, however, almost certainly so far strangers to our system that they had no part in the long processes of development by which its present condition was attained. They are, perhaps, survivals of an earlier, and by us scarcely in dimly conceivable state of things, when the swirling chaos from which sun and planets were, by a supreme edict, to emerge, had not as yet separately begun to be. Footnotes. Astr. Knock, numbers 1172-4. Bericht Sachs. Guess, 1871, page 174. Natur der Com 10, page 124, Astr. Knock, number 2086. Annals de l'Obs. De Moscou, T3, PTI, page 37. Bull. Astr. T3, page 598. The value of the repellent force for the comet of 1811, which offered peculiar facilities for its determination, was found equals 17.5. Fay, Comptes Rendus, T. 93, page 13. Annals, TV, PT2, page 137. AM. Jour of SC, volume 32. Second Serre, p. 57. Astre. Knock, number 2082. Annales de l'Obs. De Moscou, T6, PTI, page 60. Astre. Register, March, 1883. Astre. Knock, number 3018. Ibid, number 3093. Constitution de l'Espace Céleste, page 224. Astroph. Jour, volume 3, page 36. Physikalische Zeitschrift, November 10th and 17th, 1900, Astroph. Jour, volume 13, page 344. C.F. Schwarzschild, Sitzungsb, München, 1901, Heft 3, J. Hahn, Nature, volumes LXV, page 415, 66, page 55. Astre. Knock, number 2307. Ibid, number 2304. Observatory, volume 3, page 390. Astre. Knock, number 2319. Über die Kometen von 371 v. Chr. 1668, 1843, I. UND 1880 I. Göttingen, 1880. Meteor, Lib I, Cap. 6. MEM. SOC Phys. De Genève, T. 28, page 23. Annales de l'Obs. De Moscou, T. 7, point. I, page 60. Brédikhine, Annals, T. 8, page 68. AM. Jour of SC, volume 22, page 305. Messrs. Burton and Green observed a dilatation of the stellar image into a nebulous patch by the transmission of its rays through a nuclear jet of the comet. AM. Jour of SC, volume 22, page 163. Archives des Sciences, T. 8, page 535. C.F. Perrine's negative results for Swift's comet in 1899, Astre. Knock, number 3602. Reen concluded in 1896 for a definitive period of 2,429 years, Observatory, volume 19, p. 282. Holden, Publ, Astre. Pack. SOC, volume 9, page 89. Anwer, Paris, 1882, page 781. Anwer, 1882, page 766. AM. Jour of SC, volume 22, page 134. Report Brit. Association, 1881, page 520. Month. Not, volume 42, page 14, AM. Jour of SC, volume 22, p. 136. Piazzi Smith, Nature, volume 24, page 430. Astre. Knock, number 2395. Ibid. Astre. Knock, number 2411. Month. Not, volume 42, page 49. Astre. Knock, number 2414. Copernicus, volume 2, page 229. Astre. Knock, numbers 2434, 2437. Ibid, number 2441. Report Brit. Association, 1882, page 442. J. J. Parsons, A.M. Jour of Science, volume 27, page 34. Astre. Knock, number 2441. Observatory, volume 5, page 355. The transit had been foreseen by Mr. Tebbit, but it occurred after sunset in New South Wales. Observatory, volume 5. Page 354. Gould, Astr. Nock, number 2481. Flammarion, Comptes Rendus, t. 95, page 558. Captain Ray's sextant observation of the comet of 1843, a few hours before perihelion, was too rough to be of use. Astr. Nock, number 2538. Nature, volume 29, p. 135. Astr. Nock, number 2482. Viertelgerschrift Astr. Guess, Jarg. 24, page 308, Bull. Astr. T. 7, page 513. Observatory, volume 24, page 167. The attention of the author was kindly directed to this point by Professor Young of Princeton, N.J. C.F. Reber-Paschwitz, Sirius, B.D., 16, page 233. Oppenheim, Astr. Nock, number 2902. Astr. Nock, number 2717. Grothuisen's Analecton, Heft 7, page 48. Month. Knot, volumes 25, 26, 28. C.F. Plummer, Observatory, volume 13, page 263. Nature, volume 27, page 246. Astr. Nock, number 2468. Athenaeum, February 3, 1883. Astr. Nock, numbers 2462, 2466. Ibid, number 2489. Annals, Moscow, T. 9, pt 2, page 52. Comptes Rendus, T. 97, page 797. Astr. Nock, number 2966. Copernicus, volume 2, page 235. Comptes Rendus, T. 96, page 371. Astr. Nock, number 2553. Ibid. Astr. Nock, number 2568. Annales de l'Observatoire de Nice, T. 2, c. 53. Fenny, Astr. Nock, number 2844, Cameraman, Ibid, number 2849. Publ, Astr. Pack. SOC, volume 1, page 72. Anwer, Paris, 1891, page 301. Astr. Nock, number 2989. Comptes Rendus, T. 25, page 564. Astr. Journ, numbers 205, 231. Ibid, numbers 228, 244, 380. Observatory, volume 18, pages 60, 163, Denning and Lynn. Astr. Nock, number 3267. Plummer, Knowledge, volume 19, page 156. Astr. Jour, numbers 333, 338. Astr. An Astroph, volume 11, page 387. Knowledge, volume 15, page 299. Harvard Annals, volume 32, pt 2, page 272. Ibid, page 287. Publ, Astr. Pack. SOC, volume 7, page 161. H.C. Wilson, Astr. An Astroph, volume 12, page 121. Observatory, volume 16, page 92. Barnard, Astr. An Astroph, volume 12, page 180, Astroph. Jour, volume 3, page 41. Palisa, Astr. Nock, number 3147, Denning, Observatory, volume 16, page 142. Phil. Trans. Volume CI, page 306. Conde Temps, 1816, page 213. Ovra, T. 6, page 581. MEM. Del Istit. Lombardo, T. 12, page 164, Rendiconti, T. 7, page 77, 1874. W. Forster, Pop Myth, 1879, page 7. Fabry, Études sur la probabilité de comets hyperboliques, Marseille, 1893, page 158. MEM. R. A. SOC, volume 29, page 335. Month. Not, volume 23, page 203. Chapter 12. Stars and Nebulae. That a science of stellar chemistry should not only have become possible, but should already have made material advances, is assuredly one of the most amazing features in the swift progress of knowledge our age has witnessed. Custom can never blunt the wonder with which we must regard the achievement of compelling rays emanating from a source devoid of sensible magnitude through immeasurable distance, to reveal, by its distinctive qualities, the composition of that source. The discovery of revolving double stars assured us that the great governing force of the planetary movements, and of our own material existence, sways equally the courses of the farthest suns in space. The application of prismatic analysis certified to the presence in the stars of the familiar materials, no less of the earth we tread, than of the human bodies built up out of its dust and circumambient vapors. We have seen that, as early as 1823, Fraunhofer ascertained the generic participation of stellar light in the peculiarity by which sunlight, spread out by transmission through a prism, shows numerous transverse rulings of interrupting darkness. No sooner had Kirchhoff supplied the key to the hidden meaning of those ciphered characters than it was eagerly turned to the interpretation of the dim scrolls unfolded in the spectra of the stars. Donati made at Florence in 1860 the first efforts in this direction, but with little result, owing to the imperfections of the instrumental means at his command. His comparative failure, however, was a prelude to other success. Almost simultaneously, in 1862, the novel line of investigation was entered upon by Huggins near London, by Father Secchi at Rome, and by Lewis M. Rutherford in New York. Fraunhofer's device of using a cylindrical lens for the purpose of giving a second dimension to stellar spectra was adopted by all, and was, indeed, indispensable. For a luminous point, such as a star appears, becomes, when viewed through a prism, a variegated line, which, until broadened into a band by the intervention of a cylindrical lens, is all but useless for purposes of research. This process of rolling out involves, it is true, much loss of light, a scanty and precious commodity, as coming from the stars, but the loss is an inevitable one. And so fully is it compensated by the great light-grasping power of modern telescopes that important information can now be gained from the spectroscopic examination of stars far below the range of the unarmed eye. The effective founders of stellar spectroscopy, then, since Rutherford shortly turned his efforts elsewhither, were Father Secchi, the eminent Jesuit astronomer of the Collegio Romano, where he died, February 26, 1878, and Sir William Huggins, with whom the late Professor W. A. Miller was associated. The work of each was happily directed so as to supplement that of the other. With less perfect appliances, the Roman astronomer sought to render his extensive rather than precise. At Tulse Hill searching accuracy over a narrow range was aimed at and attained. To Father Secchi is due the merit of having executed the first spectroscopic survey of the heavens. Above 4,000 stars were passed in review by him, and classified according to the varying qualities of their light. His provisional establishment, 1863–67, of 4 types of stellar spectra has proved a genuine aid to knowledge through the facilities afforded by it for the arrangement and comparison of rapidly accumulating facts. Moreover, it is scarcely doubtful that these spectral distinctions correspond to differences in physical condition of a marked kind. The first order comprises more than half the visible and probably an overwhelming proportion of the faintest stars. Sirius, Vega, Regulus, Altair, are amongst its leading members. Their spectra are distinguished by the breadth and intensity of the four dark bars due to the absorption of hydrogen, and by the extreme faintness of the metallic lines, of which, nevertheless, hundreds are disclosed by careful examination. The light of these Sirian orbs is white or bluish, and it is found to be rich in ultraviolet rays. Capella and Arcturus belong to the second, or solar type of stars, which is about 1/6 less numerously represented than the first. Their spectra are quite closely similar to that of sunlight, in being ruled throughout by innumerable fine dark lines, and they share its yellowish tinge. The third class includes most red and variable stars, commonly synonymous, of which Betelgeuse in the shoulder of Orion, and Mira, in the Whale, are noted examples. Their characteristic spectrum is of the fluted description. It shows like a strongly illuminated range of 7 or 8 variously tinted columns seen in perspective, the light falling from the red end towards the violet. This kind of absorption is produced by the vapors of metalloids or of compound substances. To the fourth order of stars belongs also a colonnaded spectrum, but reversed, the light is thrown the other way. The three broad zones of absorption which interrupt it are sharp towards the red, insensibly gradated towards the violet end. The individuals composing class 4 are few and apparently insignificant, the brightest of them not exceeding the 5th magnitude. They are commonly distinguished by a deep red tint, and gleam like rubies in the field of the telescope. Father Secchi, who in 1867 detected the peculiarity of their analyzed light, ascribed it to the presence of carbon in some form in their atmospheres, and this was confirmed by the researches of H.C. Vogel, director of the Astrophysical Observatory at Potsdam. The hydrocarbon bands, in fact, seen bright in comets, are dark in these singular objects, the only ones in the heavens, save one bright line star and a rare meteor, which display a cometary analogy of the fundamental sort revealed by the spectroscope. The members of all four orders are, however, emphatically suns. They possess, it would appear, photospheres radiating all kinds of light, and differ from each other mainly in the varying qualities of their absorptive atmospheres. The principle that the colors of stars depend, not on the intrinsic nature of their light, but on the kinds of vapors surrounding them, and stopping out certain portions of that light, was laid down by Huggins in 1864. The phenomena of double stars seem to indicate a connection between the state of the investing atmospheres, by the action of which their often brilliantly contrasted tints are produced, and their mutual physical relations. A tabular statement put forward by Professor Holden in June, 1880, made it, at any rate, clear that inequality of magnitude between the components of binary systems accompanies unlikeness in color. And that stars more equally matched in one respect are pretty sure to be so in the other. Besides, blue and green stars of a decided tinge are never solitary, they invariably form part of systems. So that association has undoubtedly a predominant influence upon color. Nevertheless, the crude notion thrown out by Zollner in 1865, that yellow and red stars are simply white stars in various stages of cooling, obtained for a time undeserved currency. Darrest, indeed, protested against it, and Ångström, in 1868, substituted atmospheric quality for mere color as a criterion of age and temperature. His lead was followed by Lockyer in 1873, and by Vogel in 1874. The scheme of classification due to the Potsdam astrophysicist differed from Father Secchi's only in presenting his third and fourth types as subdivisions of the same order, and in inserting three subordinate categories. But their variety was rationalized by the addition of the seductive idea of progressive development. Thus, the white Sirian stars were represented as the youngest because the hottest of the sidereal family. Those of the solar pattern as having already wasted much of their store by radiation, and being well advanced in middle life, while the red stars with banded spectra figured as effete suns, hastening rapidly down the road to final extinction. Vogel's scheme is, however, incomplete. It traces the downward curve of decay, but gives no account of the slow ascent to maturity. The present splendor of Vega, for instance, was prepared, according to all creative analogy, by almost endless processes of gradual change. What was its antecedent condition? The question has been variously answered. Dr. Johnstone Stoney advocated, in 1867, the comparative youth of red stars. A. Ritter, of Aix-la-Chapelle, divided them, in 1883, into two squadrons, posted, the one on the ascending, the other on the descending branch of the temperature curve, and corresponding, presumably, with Secchi's third and fourth orders of stars with banded spectra. Whether, in the interim, they should display spectra of the Sirian or of the solar type was made to depend on their greater or less massiveness. But the relation actually existing perhaps inverts that contemplated by Ritter. Certainly, the evidence collected by Mr. Maunder in 1891 strongly supports the opinion that the average solar star is a weightier body than the average Sirian star. On November 17, 1887, Sir Norman Lockyer communicated to the Royal Society the first of a series of papers embodying his meteoritic hypothesis of cosmical constitution, stated and supported more at large in a separate work bearing that name. Published in 1890. The fundamental proposition wrought out in it was that all self-luminous bodies in the celestial space are composed either of swarms of meteorites or of masses of meteoric vapor produced by heat. On the basis of this supposed community of origin, sidereal objects were distributed in 7 groups along a temperature curve ascending from nebulae and gaseous, or bright-line stars, through red stars of the third type, and the younger division of solar stars, to the high Sirian level. Then descending through the more strictly solar stars to red stars of the fourth type, carbon stars, below which lay only the caput mortuum entitled Group 7. The groundwork of this classification was, however, insecure, and has given way. Certain spectroscopic coincidences, avowedly only approximate, suggesting that stars and nebulae of every species might be formed out of variously aggregated meteorites, failed of verification by exact inquiry. And spectroscopic coincidences admit of no compromise. Those that are merely approximate are, as a rule, unmeaning. In his presidential address at the Cardiff meeting of the British Association in 1891, Dr. Huggins adhered in the main to the line of advance traced by Vogel. The inconspicuousness of metallic lines in the spectra of the white stars he attributed, not to the paucity, but to the high temperature of the vapors producing them, and the consequent deficiency of contrast between their absorption rays and the continuous light of the photospheric background. Such a state of things would more probably, in his opinion, be found in conditions anterior to the solar stage, while a considerable cooling of the sun would probably give rise to banded spectra due to compounds. He adverted also to the influential effects upon stellar types of varying surface gravity, which being a function of both mass and bulk necessarily gain strength with wasting heat and consequent shrinkage. The same leading ideas were more fully worked out in An Atlas of Representative Stellar Spectra, published by Sir William and Lady Huggins in 1899. They were, moreover, splendidly illustrated by a set of original spectrographic plates, while precision was added to the adopted classification by the separation of helium from hydrogen stars. The spectrum of the exotic substance terrestrially captured in 1895 is conspicuous by absorption, as Vogel, Lockyer, and Deslandres promptly recognized in a considerable number of white stars. Among them the Pleiades and most of the brilliants in Orion. Mr. Maclean, whose valuable spectrographic survey of the heavens was completed at the Cape in 1897, found reason to conclude that they are in the first stage of development from gaseous nebulae. And in this the Tulse Hill investigators unhesitatingly concur. The strongest evidence for the primitive state of white stars is found in their nebular relations. The components of groups, still involved and entangled with silver braids of cosmic mist, show, perhaps invariably, spectra of the helium type, occasionally crossed by bright rays. Possibly all such stars have passed through a bright-line stage. But further evidence on the point is needed. Relative density furnishes another important test of comparative age, and Sirian stars are, on the whole, undoubtedly more bulky proportionately to their mass than solar stars. The rule, however, seems to admit of exceptions, hence the change from one kind of spectrum to the other is not inevitably connected with the attainment of a particular degree of condensation. There is reason to believe that it is anticipated in the more massive globes, despite their comparatively slow cooling, as a consequence of the greater power of gravity over their investing vaporous envelopes. This conclusion is enforced by the relations of double star spectra. The fact that, in unequal pairs, the chief star most frequently shows a solar, its companion a Sirian, spectrum can scarcely be otherwise explained than by admitting that, while the sequence of types is pursued in an invariable order, it is pursued much more rapidly in larger than in small orbs. It need not, indeed, be supposed that all stars are identical in constitution, and present identical life histories. Individualities in the one, and divergencies in the other, must be allowed for. Yet the main track is plainly continuous, and leads by insensible gradations from nebulae through helium stars to the Sirian, and onward to the solar type, whence, by an inevitable transition, fluted, or Antarean, spectra develop. The first known examples of the class of gaseous stars, Beta Lyrae and Gamma Cassiopeiae, were noticed by Father Secchi at the outset of his spectroscopic inquiries. Both show bright lines of hydrogen and helium, so that the peculiarity of their condition probably consists in the intense ignition of their chromospheric surroundings. Their entire radiating surfaces might be described as faculous. That is to say, brilliant formations, such as have been photographed by Professor Hale on the Sun's disk, cover, perhaps, the whole, instead of being limited to a small portion of the photospheric area. But this state of things is more or less inconstant. Some at least of the bright rays indicative of it are subject to temporary extinctions. Already in 1871–72, Dr. Vogel suspected the prevalence of such vicissitudes. And their reality was ascertained by M. Eugen von Gothard. After the completion of his new astrophysical observatory at Harany in the autumn of 1881, he repeatedly observed the spectra of both stars without perceiving a trace of bright lines. And was thus taken quite by surprise when he caught a twinkling of the crimson C in Gamma Cassiopeiae, August 13, 1883. A few days later, the whole range including D_3 was lustrous. Duly apprised of the recurrence of a phenomenon he had himself vainly looked for during some years, M. von Konkoly took the opportunity of the great Vienna refractor being placed at his disposal to examine with it the relight spectrum on August 27. In its wealth of light C was dazzling. D_3 and the green and blue hydrogen rays shone somewhat less vividly, D and the group B showed faintly dark. While three broad absorption bands, sharply terminated towards the red, diffused towards the violet, shaded the spectrum near its opposite extremities. The previous absence of bright lines from the spectrum of this star was, however, by no means so protracted or complete as M. von Gothard supposed. At Denect, C was superbly visible, December 20, 1879. F was seen bright on October 28 of the same year, and frequently at Greenwich in 1880–81. The curious fact has, moreover, been adverted to by Dr. Copeland, that C is much more variable than F. To Vogel, June 18, 1872, the first was invisible, while the second was bright. At Denect, January 11, 1887, the conditions were so far inverted that C was resplendent, F comparatively dim. No spectral fluctuations were detected in Gamma Cassiopeiae by Keeler in 1889, but even with the giant telescope of Mount Hamilton, the helium ray was completely invisible. It made, nevertheless, capricious appearances at South Kensington during that autumn, and again October 21, 1894, while in September, 1892, Belopolsky could obtain no trace of it on orthochromatic plates exposed with the 30-inch Pulkowa refractor. Still more noteworthy is the circumstance that the well-known green triplet of magnesium, B, recorded as dark by Keeler in 1889, came out bright on 52 spectrographs of the star taken by Father Sitgreaves during the years 1891–99. No fluctuations in the hydrogen spectrum were betrayed by them, but subordinate lines of unknown origin showed alternate fading and vivification. The spectrum of Beta Lyrae undergoes transitions to some extent analogous, yet involving a different set of considerations. First noticed by von Gothard in 1882, they were imperfectly made out, 2 years later, to be of a cyclical character. This, however, could only be effectively determined by photographic means. Beta Lyrae is a short-period variable. Its light changes with great regularity from 3.4 to 4.4 magnitude every 12 days and 22 hours, during which time it attains a twofold maximum, with an intervening secondary minimum. The question, then, is of singular interest, whether the changes of spectral quality visible in this object correspond to its changes in visual brightness. A distinct answer in the affirmative was supplied through Mrs. Fleming's examination of the Harvard plates of the star's spectrum, upon which, in 1891, she found recorded diverse complex changes of bright and dark lines obviously connected with the phases of luminous variation, and obeying, in the long run, precisely the same period. Something more will be said presently as to the import of this discovery. Bright hydrogen lines have so far been detected, for the most part photographically at Harvard College, in about 60 stars, including Pleione, the surmised lost Pleiad, P Cygni, noted for instability of light in the 17th century, and the extraordinary southern variable, Eta Carinii. In most of these objects other vivid rays are associated with those due to hydrogen. A blaze of hydrogen, moreover, accompanies the recurring outbursts of about 150 long-period variables, giving banded spectra of the third type. Professor Pickering discovered the first example of this class, towards the close of 1886, in Mira Ceti. Further detections were made visually by Mr. Espin, and the conjunction of bright hydrogen lines with dusky bands has been proved by Mrs. Fleming's long experience in studying the Harvard photographs, to indicate unerringly the subjection of the stars thus characterized to variations of luster accomplished in some months. A third variety of gaseous star is named after M.M. Wolf and Rayet, who discovered, at Paris in 1867, its 3 typical representatives, close together in the constellation Cygnus. 6 further specimens were discovered by Dr. Copeland, 5 of them in the course of a trip for the exploration of visual facilities in the Andes in 1883, and a large number have been made known through spectral photographs taken in both hemispheres under Professor Pickering's direction. At the close of the 19th century, over 100 such objects had been registered, none brighter than the 6th magnitude, with the single exception of Gamma Argus, the resplendent continuous spectrum of which, first examined by Respighi and Lockyer in 1871, is embellished with the yellow and blue rays distinctive of the type. Here, then, we have a stellar globe apparently at the highest point of sun-like incandescence, sharing the peculiarities of bodies verging towards the nebulous state. Examined with instruments of adequate power, their spectra are seen to be highly complex. They include a fairly strong continuous element, a numerous set of absorption lines, and a range of emission lines, more or less completely represented in different stars. Especially conspicuous is a broad effluence of azure light, found by Dr. Vogel in 1883, and by Sir William and Lady Huggins in 1890, to be of multiple structure, and hence to vary in its mode of display. Its suggested identification with the blue carbon fluting was disproved at Tulse Hill. Metallic vapors give no certain sign of their presence in the atmospheres of these remarkable bodies, but nebulum is stated to shine in some. Hydrogen and helium account for a large proportion of their spectral rays. 32 Wolf-Rayet stars were investigated, spectroscopically and spectrographically, by Professor Campbell with the Great Lick refractor in 1892–94. And several disclosed the singularity, already noticed by him in Gamma Argus, of giving out mixed series, the members of which change from vivid to obscure with increase of refrangibility. It is difficult to imagine by what chromospheric machinery this curious result can be produced. Alcyone in the Pleiades presents the same characteristic. Alone among the hydrogen lines, crimson C glows in its spectrum, while all the others are dark. Luminosity of the Wolf-Rayet kind is particularly constant, both in quantity and quality. It seems to be incapable of developing save under galactic conditions. All the stars marked by it lie near the central line of the Milky Way, or in the Magellanic Clouds. They tend also to gather into groups. Circles of 4 degrees radius include respectively 7 in Argo, 8 in Cygnus. The first spectroscopic star catalogue was published by Dr. Vogel at Potsdam in 1883. It included 4,051 stars, distributed over a zone of the heavens extending from 20 degrees north to 20 degrees south of the celestial equator. More than half of these were white stars, while red stars with banded spectra occurred in the proportion of about 1/13 of the whole. To the latter genus, M. Dünner, then of Lund, now director of the UPS Observatory, devoted a work of standard authority, issued at Stockholm in 1884. This was a catalogue with descriptive particulars of 352 stars showing banded spectra, 297 of which belonged to Secchi's third, 55 to his fourth class, Vogel's 3A and 3B. Since then discovery has progressed so rapidly, at first through the telescopic reviews of Mr. Espin, then in the course of the photographic survey carried on at Harvard College, that considerably over 1,000 stars are at present recognized as of the family of Betelgeuse and Mira, while about 250 have so far exhibited the spectral pattern of 19 Piscium. One fact well ascertained as regards both species is the invariability of the type. The prismatic flutings of the one, and the broader zones of the other, are as if stereotyped. They undergo, in their fundamental outlines, no modification, though varying in relative intensity from star to star. They are always accompanied by, or superposed upon, a spectrum of dark lines, in producing which sodium and iron have an obvious share. And certain bright rays, noticed by Secchi with imperfect appliances as enhancing the chiaroscuro effects in carbon stars, came out upon plates exposed by Hale and Ellerman in 1898 with the stellar spectrograph of the Yerkes Observatory. Their genuineness was shortly afterwards visually attested by Keeler, Campbell, and Dünner, but no chemical interpretation has been found for them. A fairly complete preliminary answer to the question, what are the stars made of, was given by Sir William Huggins in 1864. By laborious processes of comparison between stellar dark lines and the bright rays emitted by terrestrial substances, he sought to assure his conclusions, regardless of cost and time and pains. He averred, indeed, that, taking into account restrictions by weather and position, the thorough investigation of a single star spectrum would be the work of some years. Of two, however, those of Betelgeuse and Aldebaran, he was able to furnish detailed and accurate drawings. The dusky flutings in the prismatic light of the first of these stars have not been identified with the absorption of any particular substance. But associated with them are metallic lines, of which 78 were measured, and a good many identified by Huggins, while the wavelengths of 97 were determined by Vogel in 1871. A photographic research, made by Keeler at the Allegheny Observatory in 1897, convinced him that the linear spectrum of third-type stars of the Betelgeuse pattern essentially repeats that of the Sun, but with marked differences in the comparative strength of its components. Hydrogen rays are inconspicuously present. That an exalted temperature reigns, at least in the lower strata of the atmosphere, is certified by the vaporization there of matter so refractory to heat as iron. 9 elements, among them iron, sodium, calcium, and magnesium, were recognized by Huggins as having stamped their signature on the spectrum of Aldebaran. While the existence in Sirius, and nearly all the other stars inspected, of hydrogen, together with sundry metals, was rendered certain or highly probable. This was admitted to be a bare gleaning of results. Nor is there reason to suppose any of his congeners inferior to our Sun in complexity of constitution. Definite knowledge on the subject, however, made little advance beyond the point to which it was brought by Huggins's early experiments until spectroscopic photography became thoroughly effective as a means of research. In this, as in so many other directions, Sir William Huggins acted as pioneer. In March, 1863, he obtained microscopic prints of the spectra of Sirius and Capella. But they told nothing. No lines were visible in them. They were mere characterless streaks of light. 9 years later Dr. Henry Draper of New York got an impression of 4 lines in the spectrum of Vega. Then Huggins attacked the subject again in 1876, when the 18-inch speculum of the Royal Society had come into his possession, using prisms of Iceland spar and lenses of rock crystal, and this time with better success. A photograph of the spectrum of Vega showed 7 strong lines. Still he was not satisfied. He waited and worked for 3 years longer. At length, on December 18, 1879, he was able to communicate to the Royal Society results answering to his expectations. The delicacy of eye and hand needed to obtain them may be estimated from the single fact that the image of a star had to be kept, by continual minute adjustments, exactly projected upon a slit 1/350 of an inch in width during nearly an hour. In order to give it time to imprint the characters of its analyzed light upon a gelatin plate raised to the highest pitch of sensitiveness. But by this time he had secured in his wife a rarely qualified assistant. The ultraviolet spectrum of the white stars, of which Vega was taken as the type, was thus shown to be a very remarkable one. A group of broad dark lines intersected it, arranged at intervals diminishing regularly upward, and falling into a rhythmical succession with the visible hydrogen lines. All belonged presumably to the same substance. And the presumption was rendered a certainty by direct photographs of the hydrogen spectrum taken by H. W. Vogel at Berlin a few months earlier. In them 7 of the white star series of grouped lines were visible. And the full complement of 12 appeared on Cornu's plates in 1886. In yellow stars, such as Capella and Arcturus, the same rhythmical series was partially represented, but associated with a great number of other lines. Their state, as regards ultraviolet absorption, approximating to that of the Sun. While the redder stars betrayed so marked a deficiency in actinic rays that from Betelgeuse, with an exposure 40 times that required for Sirius, only a faint spectral impression could be obtained, and from Aldebaran. In the strictly invisible region, almost none at all. Thus, by the means of stellar light analysis, acquaintance was first made with the ultraviolet spectrum of hydrogen. And its harmonic character, as expressed by Balmer's law, supplies a sure test for discriminating, among newly discovered lines, those that appertain from those that are unrelated to it. Deslandres' 5 additional prominence rays, for instance, were at once seen to make part of the series, because conforming to its law. While a group of 6 dusky bands, photographed by Sir William and Lady Huggins, April 4, 1890, near the extreme upper end of the spectrum of Sirius, were pronounced without hesitation, for the opposite reason, to have nothing to do with hydrogen. Their true affinities are still a matter for inquiry. As regards the hydrogen spectrum, however, the stars had further information in reserve. Until recently, it was supposed to consist of a single harmonic series, although, by analogy, 3 should coexist. In 1896, accordingly, a second, bound to the first by unmistakable numerical relationships, was recognized by Professor Pickering in spectrographs of the 2.5 magnitude star Zeta Puppis. And the identification was shortly afterwards extended to prominent Wolf-Rayet emission lines. The discovery was capped by Dr. Rydberg's indication of the Wolf-Rayet blue band at lambda 4688 as the fundamental member of the third, and principal, hydrogen series. None of the Pickering lines, as they may be called to distinguish them from the Huggins series, can be induced to glimmer in vacuum tubes. They seem to characterize bodies in a primitive state, and are in many cases associated with absorption rays of oxygen, the identification of which by Mr. Maclean in 1897 was fully confirmed by Sir David Gill. The typical oxygen star is Beta Crucis, one of the brilliants of the Southern Cross, but the distinctive notes of its spectrum occur in not a few specimens of the helium class. Thus, Sir William and Lady Huggins photographed several ultraviolet oxygen lines in Beta Lyrae, and found in Rigel signs of the presence of nitrogen, which, as well as silicium, proves to be a tolerably frequent constituent of such orbs. For some unknown reason, metalloids tend to become effaced, as metals, in the normal course of stellar development, exert a more and more conspicuous action. Dar. Scheiner's spectrographic researches at Potsdam in 1890 and subsequently exemplify the immense advantages of self-registration. In a restricted section of the spectrum of Capella, he was enabled to determine nearly 300 lines with more precision than had then been attained in the measurement of terrestrial spectra. This star appeared to be virtually identical with the Sun in physical constitution, although it emits, according to the best available data, about 140 times as much light, and is hence presumably 1,600 times more voluminous. An equally close examination of the spectrum of Betelgeuse showed the predominance in it of the linear absorption of iron, but its characteristic flutings do not extend to the photographic region. Spectra of the second and third orders are for this reason not easily distinguished on the sensitive plate. A spectrographic investigation of all the brighter northern stars was set on foot in 1886 at the Observatory of Harvard College, under the form of a memorial to Dr. H. Draper, whose promising work in that line was brought to a close by his premature death in 1882. No individual exertions could, however, have realized a tithe of what has been and is being accomplished under Professor Pickering's able direction, with the aid of the Draper and other instruments, supplemented by Mrs. Draper's liberal provision of funds. A novel system was adopted, or, rather, an old one, originally used by Fraunhofer, was revived. The use of a slit was discarded as unnecessary for objects like the stars, devoid of sensible dimensions, and giving hence a naturally pure spectrum. And a large prism, placed in front of the object glass, analyzed at once, with slight loss of light, the rays of all the stars in the field. Their spectra were taken, as it were, wholesale. As many as 200 stars down to the 8th magnitude were occasionally printed on a single plate with a single exposure. No cylindrical lens was employed. The movement of the stars themselves was turned to account for giving the desirable width to their spectra. The star was allowed, by disconnecting or suitably regulating the clock, to travel slowly across the line of its own dispersed light, so broadening it gradually into a band. Excellent results were secured in this way. About 50 lines appear in the photographed spectrum of Aldebaran, and 8 in that of Vega. On January 26, 1886, with an exposure of 34 minutes, a simultaneous impression was obtained of the spectra, among many others, of close upon 40 Pleiades. With few and doubtful exceptions, they all proved to belong to the same type. An additional argument for the common origin of the stars forming this beautiful group was thus provided. The Draper Catalogue of Stellar Spectra was published in 1890. It gives the results of a rapid analytical survey of the heavens north of 25 degrees of southern declination, and includes 10,351 stars, down to about the 8th magnitude. The telescope used was of 8 inches aperture and 45 focus, its field of view, owing to the portrait lens, or doublet, form given to it, embracing with fair definition no less than 100 square degrees. An objective prism 8 inches square was attached, and exposures of a few minutes were given to the most sensitive plates that could be procured. In this way the sky was twice covered in duplicate, each star appearing, as a rule, on 4 plates. The registration of their spectra was sought to be made more distinctive than had previously been attempted, Secchi's first type being divided into 4, his second into 5 subdivisions. But the differences regarded in them could be confidently established only for stars above the 6th magnitude. The work supplies none the less valuable materials for general inferences as to the distribution and relations of the spectral types. The labor of its actual preparation was borne by a staff of ladies under the direction of Mrs. Fleming. Materials for its completion to the southern pole have been accumulated with the identical instrument used at Cambridge, transferred for the purpose in 1889 to Peru, and the forthcoming second Draper catalogue will comprise 30,000 stars in both hemispheres. As supplements to this great enterprise, 2 important detailed discussions of stellar spectra were issued in 1897 and 1901 respectively. The first, by Miss A. C. Maury, dealt with 681 bright stars visible in the northern hemisphere. The second, by Miss A. J. Cannon, with 1,122 southern stars. Both authors traced, with care and ability, the minute gradations by which the long process of stellar evolution appears to be accomplished. The progress of the Draper Memorial researches was marked by discoveries of an unexampled kind. The principle upon which motion in the line of sight can be detected and measured with the spectroscope has already been explained. It depends, as our readers will remember, upon the removal of certain lines, dark or bright, it matters not which, from their normal places by almost infinitesimal amounts. The whole spectrum of the moving object, in fact, is very slightly shoved hither or thither, according as it is traveling towards or from the eye. But, for convenience of measurement, one line is usually picked out from the rest, and attention concentrated upon it. The application of this method to the stars, however, is encompassed with difficulties. It needs a powerfully dispersive spectroscope to show line displacements of the minute order in question, and powerful dispersion involves a strictly proportionate enfeeblement of light. This, where the supply is already to a deplorable extent niggardly, can ill be afforded, for which reason the operation of determining a star's approach or recession is, even apart from atmospheric obstacles, an excessively delicate one. It was first executed by Sir William Huggins early in 1868. Selecting the brightest star in the heavens as the most promising subject of experiment. He considered the F line in the spectrum of Sirius to be just so much displaced towards the red as to indicate, the orbital motion of the Earth being deducted, recession at the rate of 29 miles a second. And the reality and direction of the movement were ratified by Vogel and Losey's observation, March 22, 1871, of a similar, but even more considerable displacement. The inquiry was resumed by Huggins with improved apparatus in the following year, when the velocities of 30 stars were approximately determined. The retreat of Sirius, which proved slower than had at first been supposed, was now announced to be shared, at rates varying from 12 to 29 miles, by Betelgeuse, Rigel, Castor, Regulus, and 5 of the principal stars in the Plough. Arcturus, on the contrary, gave signs of rapid approach, as well as Pollux, Vega, Deneb in the Swan, and the brightness of the pointers. Numerically, indeed, these results were encompassed with uncertainty. Thus, Arcturus is now fully ascertained to be traveling towards the Sun at the comparatively slow pace of less than 5 miles a second, and Sirius moves twice as fast in the same direction. The great difficulty of measuring so distended a line as the Sirian F might, indeed, well account for some apparent anomalies. The scope of Sir William Huggins's achievement was not, however, to provide definitive data, but to establish as practicable the method of procuring them. In this he was thoroughly successful, and his success was of incalculable value. Spectroscopic investigations of stellar movements may confidently be expected to play a leading part in the unravelment of the vast and complex relations which we can dimly detect as prevailing among the innumerable orbs of the sidereal world. For it supplements the means which we possess of measuring by direct observation movements transverse to the line of sight, and thus completes our knowledge of the courses and velocities of stars at ascertained distances, while supplying for all a valuable index to the amount of perspective foreshortening of apparent movement. Thus some, even if an imperfect, knowledge may at length be gained of the revolutions of the stars, of the systems they unite to form, of the paths they respectively pursue, and of the forces under the compulsion of which they travel. The applicability of the method to determining the orbital motions of double stars was pointed out by Fox Talbot in 1871, but its use for their discovery revealed itself spontaneously through the Harvard College photographs. In spectrograms of Zeta Ursae Majoris, Mizar, taken in 1887, and again in 1889, the K line was seen to be double, while on other plates it appeared single. A careful study of Miss A. C. Maury of a series of 70 impressions indicated for the doubling a period of 52 days, and showed it to affect all the lines in the spectrum. The only available, and no doubt the true, explanation of the phenomenon was that two similar and nearly equal stars are here merged into one telescopically indivisible. Their combined light giving a single or double spectrum, according as their orbital velocities are directed across or along our line of sight. The movements of a revolving pair of stars must always be opposite in sense, and proportionately equal in amount. That is, they at all times travel with speeds in the inverse ratio of their masses. Hence, unless the plane of their orbits be perpendicular to a plane passing through the eye, there must be two opposite points where their velocities in the line of sight reach a maximum, and two diametrically opposite points where they touch zero. The lines in their common spectrum would thus appear alternately double and single twice in the course of each revolution. To that of Mizar, at first supposed to need 104 days for its completion, a period of only 20 days 14 hours was finally assigned by Vogel. Anomalous spectral effects, probably due to the very considerable eccentricity of the orbit, long impeded its satisfactory determination. The mean distance apart of the component stars, as now ascertained, is just 22 million miles, and their joint mass quadruples that of the Sun. But these are minimum estimates. For if the orbital plane be inclined, much or little, to the line of sight, the dimensions and mass of the system should be proportionately increased. An analogous discovery was made by Miss Maury in 1889. But in the spectrum of Beta Aurigui, the lines open out and close up on alternate days, indicating a relative orbit with a radius of less than 8 million miles, traversed in about 4 days. This implies a rate of travel for each star of 65 miles a second, and a combined mass 7 times that of the Sun. The components are approximately equal, both in mass and light, and the system formed by them is transported towards us with a speed of some 16 miles a second. The line shiftings so singularly communicative proceed, in this star, with perfect regularity. This new class of spectroscopic binaries could never have been visually disclosed. The distance of Beta Aurigui from the Earth, as determined, somewhat doubtfully, by Professor Pritchard, is nearly 3 1/3 million times that of the Earth from the Sun, parallax equals 0.006. Whence it has been calculated that the greatest angular separation of the revolving stars is only 0.005 of a second of arc. To make this evanescent interval perceptible, a telescope 80 feet in aperture would be required. The zodiacal star, Spica, Alpha Virginis, was announced by Dr. Vogel, April 24, 1890, to belong to the novel category, with the difference, however, of possessing a nearly dark, instead of a brilliantly lustrous companion. In this case, accordingly, the telltale spectroscopic variations consist merely in a slight swinging to and fro of single lines. No second spectrum leaves a legible trace on the plate. Spica revolves in 4 days at the rate of 57 miles a second, or quicker, in proportion as its orbit is more inclined to the line of sight, round a center at a minimum distance of 3 millions of miles. But the position of the second star being unknown, the mass of the system remains indeterminate. The lesser component of the splendid, slowly revolving binary, Castor, is also closely double. Its spectral lines were found by Belopolsky in 1896 to oscillate once in nearly 3 days, the secondary globe being apparently quite obscure. Further study of the movements thus betrayed elicited the fact that the major axis of the eclipse traversed revolves in a period of 2,100 days, as a consequence, most likely, of the flattened shape of the stars. Still more unexpected was the simultaneous assignment, by Campbell and Newell, of a duplex character to Capella. Here both components shine, though with a different quality of light, one giving a pure solar spectrum, the other claiming prismatic affinity with Procyon. Their mutual circulation is performed in 104 days, and the radius of their orbit cannot be less, and may be a great deal more, than 51 million miles. Hence the possibility is not excluded that the star, which has an authentic parallax of 0.08, may be visually resolved. Indeed, signs of elongation were thought to be perceptible with the Greenwich 28-inch refractor, while only round images could be seen at Lick. Another noteworthy case is that of Polaris, found by Campbell to have certainly one, and probably 2 obscure attendants. Through his systematic investigations of stellar radial velocities with the Mills spectrograph, knowledge in this department has, since 1897, progressed so rapidly that the spectroscopic binaries of our acquaintance already number 1/2. And 10 times as many more doubtless lie within easy range of detection. Now it is evident that a spectroscopic binary, if the plane of its motion made a very small angle with the line of sight, would be a variable star. For, during a few hours of each revolution, some at least of its light should be cut off by a transit of its dusky companion. Such eclipse stars are actually found in the heavens. The best and longest known member of the group is Algol in the head of Medusa, the demon star of the Arabs. This remarkable object, normally above the third magnitude, loses and regains 3/5 of its light once in 68 hours, the change being completed in about 12 hours. Its definite and limited nature, and punctual recurrence, suggested to Gudrick of York, by whom the periodicity of the star was discovered in 1783, the interposition of a large dark satellite. But the conditions involved by the explanation were first seriously investigated by Pickering in 1880. He found that the phenomena could be satisfactorily accounted for by supposing an obscure body 0.764 the bright star's diameter to revolve round it in a period identical with that of its observed variation. This theoretical forecast was verified with singular exactitude at Potsdam in 1889. A series of spectral photographs taken there showed each of Algol's minima to be preceded by a rapid recession from the Earth, and succeeded by a rapid movement of approach towards it. They take place, accordingly, when the star is at the furthest point from ourselves of an orbit described round an invisible companion, the transits of which across its disk betray themselves to notice by the luminous vicissitudes they occasion. The diameter of this orbit, traversed at the rate of 26 miles a second, is just 2 million miles. And it is an easy further inference from the duration and extent of the phases exhibited that Algol itself must be, in round numbers, 1 million, its attendant 830,000 miles in diameter. Assuming both to be of the same density, Vogel found their respective masses to be 4/9 and 2/9 that of the Sun, and their distance asunder to be 3,230,000 miles. This singularly assorted pair of stars possibly form part of a larger system. Their period of revolution is shorter now by 6 seconds than it was in Gudrick's time, and Dr. Chandler has shown, by an exhaustive discussion, that its inequalities are comprised in a cycle of about 130 years. They arise, in his view, from a common revolution, in that period, of the close couple about a third distant body, emitting little or no light, in an orbit inclined 20 degrees to our line of vision, and of approximately the size of that described by Uranus round the Sun. The time spent by light in crossing this orbit causes an apparent delay in the phases of the variable, when Algol and its eclipsing satellite are on its further side from ourselves, balanced by acceleration while they traverse its hither side. Dr. Chandler derives confirmation for his plausible and ingenious theory from a supposed undulation in the line traced out by Algol's small proper motion, but the reality of this disturbance has yet to be established. Meanwhile, M. Tisserand, late director of the Paris Observatory, preferred to account for Algol's inequalities on the principle later applied by Belopolsky to those of Castor. That is to say, he assumed a revolving line of apsides in an elliptical orbit traversed by a pretty strongly compressed pair of globes. The truth of this hypothesis can be tested by close observation of the phases of the star during the next few years. The variable in the head of Medusa is the exemplar of a class including 26 recognized members, all of which doubtless represent occulting combinations of stars. But their occultations result merely from the accident of their orbital planes passing through our line of sight. Hence the heavens must contain numerous systems similarly constituted, though otherwise situated as regards ourselves, some of which, like Spica Virginis, will become known through their spectroscopic changes, while others, because revolving in planes nearly tangent to the sphere, or at right angles to the visual line, may never disclose to us their true nature. Among eclipsing stars should probably be reckoned the peculiar variables, Beta Lyrae and V Puppis, each believed to consist of a pair of bright stars revolving almost in contact. 3 stars, on the other hand, distinguished by rapid and regular fluctuations, have been proved by Belopolsky to be attended by non-occulting satellites, which circulate, nevertheless, in the identical periods of light change. Gore's Catalogue of Known Variables included, in 1884, 190 entries, and the number was augmented to 243 on its revision in 1888. Chandler's first list of 225 such objects, published about the same time, received successive expansions in 1893 and 1896, and finally included 400 entries. A new catalogue of variable stars, still wider in scope, will shortly be issued by the German Astronomische Gesellschaft. Mr. W. Roberts's researches on southern variables have greatly helped to give precision, while adding to the extent of knowledge in this branch. Dr. Gould held the opinion that most stars fluctuate slightly in brightness through surface alterations similar to, but on a larger scale than those of the Sun, and the solar analogy might be pushed somewhat further. It perhaps affords a clue to much that is perplexing in stellar behavior. Wolf pointed out in 1852 the striking resemblance in character between curves representing sunspot frequency and curves representing the changing luminous intensity of many variable stars. There were the same steep ascent to maximum and more gradual decline to minimum, the same irregularities in heights and hollows, and, it may be added, the same tendency to a double maximum, and complexity of superposed periods. It is impossible to compare the two sets of phenomena thus graphically portrayed without reaching the conclusion that they are of closely related origin. But the correspondence indicated is not, as has often been hastily assumed, between maxima of sunspots and minima of stellar brightness, but just the reverse. The luminous outbursts, not the obscurations of variable stars, obey a law analogous to that governing the development of spots on the Sun. Objects of the kind do not, then, gain light through the closing up of dusky chasms in their photospheres, but by an actual increase of surface brilliancy, together with an immense growth of these brilliant formations, prominences and faculae, which, in the Sun, accompany, or are appended to spots. A comparison of light curves with curves of spot frequency leaves no doubt on this point. And the strongest corroborative evidence is derived from the emergence of bright lines in the spectra of long-period variables rising to their recurring maxima. Every kind and degree of variability is exemplified in the heavens. At the bottom of the scales are stars like the Sun, of which the luster is, tried by our instrumental means, sensibly steady. At the other extreme are ranged the astounding apparitions of new, or temporary, stars. Within the last 36 years 11 of these stellar guests, as the Chinese call them, have presented themselves, and we meet with a 12th no farther back than April 27, 1848. But of the new star, in Ophiuchus found by Mr. Hind on that night, little more could be learnt than of the brilliant objects of the same kind observed by Tycho and Kepler. The spectroscope had not then been invented. Let us hear what it had to tell of later arrivals. About 30 minutes before midnight of May 12, 1866, Mr. John Birmingham of Millbrook, near Tuam, in Ireland, saw with astonishment a bright star of the second magnitude unfamiliarly situated in the constellation of the Northern Crown. 4 hours earlier, Schmidt of Athens had been surveying the same part of the heavens, and was able to testify that it was not visible there. That is to say, a few hours, or possibly a few minutes, sufficed to bring about a conflagration, the news of which may have occupied hundreds of years in traveling to us across space. The rays which were its messengers, admitted within the slit of Sir William Huggins's spectroscope, May 16, proved to be of a composition highly significant as to the nature of the catastrophe. The star, which had already declined below the third magnitude, showed what was described as a double spectrum. To the dusky flutings of Secchi's third type 4 brilliant rays were added. The chief of these agreed in position with lines of hydrogen. So that the immediate cause of the outburst was inferred to have been the eruption, or ignition, of vast masses of that subtle kind of matter. The universal importance of which throughout the cosmos is one of the most curious facts revealed by the spectroscope. T Coroni, as the new star was called, quickly lost its adventitious splendor. 9 days after its discovery it was again invisible to the naked eye. It is now a pale yellow, slightly variable star near the 10th magnitude, and finds a place as such in Archlander's charts. It was thus obscurely known before it made its sudden leap into notoriety. The next, temporary, discovered by Dr. Schmidt at Athens, November 24, 1876, could lay no claim to previous recognition even in that modest rank. It was strictly a parvenu. There was no record of its existence until it made its appearance as a star of nearly the third magnitude, in the constellation of the Swan. Its spectrum was examined, December 2, by Cornu at Paris, and a few days later by Vogel and O. Losey at Potsdam. It proved of a closely similar character to that of T. Coroni. A range of bright lines, including those of hydrogen, and probably of helium, stood out from a continuous background impressed with strong absorption. It may be presumed that in reality the gaseous substances, which, by their sudden incandescence, had produced the apparent conflagration, lay comparatively near the surface of the star. While the screen of cooler materials intercepting large portions of its light was situated at a considerable elevation in its atmosphere. The object, meanwhile, steadily faded. By the end of the year it was of no more than 7th magnitude. After the second week of March, 1877, strengthening twilight combined with the decline of its radiance to arrest further observation. It was resumed, September 2, at Denect, with a strange result. Practically the whole of its scanty light, it had then sunk below the 10th magnitude, was perceived to be gathered into a single bright line in the green, and that the most characteristic line of gaseous nebulae. The star had, in fact, so far as outward appearance was concerned, become transformed into a planetary nebula, many of which are so minute as to be distinguishable from small stars only by the quality of their radiations. It is now, having sunk to about the 14th magnitude, entirely beyond the reach of spectroscopic scrutiny. Perhaps none of the marvelous changes witnessed in the heavens has given a more significant hint as to their construction than the stellar blaze kindled in the heart of the great Andromeda Nebula some undetermined number of years or centuries before its rays reached the Earth in the month of August. 1885. The first published discovery was by Dr. Hartwig at Dorpat on August 31, but it was found to have been already seen, on the 19th, by Mr. Isaac W. Ward of Belfast, and on the 17th by M. Ludovic Gully of Rouen. The negative observations, on the 16th, of Temple and Max Wolf, limited very narrowly the epoch of the apparition. Nevertheless, it did not, like most temporaries, attain its maximum brightness all at once. When first detected, it was of the 9th, by September 1 it had risen to the 7th magnitude, from which it so rapidly fell off that in March it touched the limit of visibility, 16th magnitude, with the Washington 26-inch. Its light bleached very perceptibly as it faded. During the earlier stages of its decline, the contrast was striking between the sharply defined, ruddy disk of the star, and the hazy, greenish-white background upon which it was projected, and with which it was inevitably suggested to be in some sort of physical connection. Let us consider what evidence was really available on this point. To begin with, the position of the star was not exactly central. It lay 16 seconds of arc to the southwest of the true nebular nucleus. Its appearance did not then signify a sudden advance of the nebula towards condensation, nor was it attended by any visible change in it save the transient effect of partial effacement through superior brightness. Equally indecisive information was derived from the spectroscope. To Vogel, Hasselberg, and Young, the light of the nova seemed perfectly continuous, but Huggins caught traces of bright lines on September 2, confirmed on the 9th. And Copeland succeeded, on September 30, in measuring 3 bright bands with an acute-angled prism specially constructed for the purpose. A shimmer of F was suspected, and had also been perceived by Mr. O. T. Sherman of Yale College. Still, the effect was widely different from that of the characteristic blazing spectrum of a temporary star, and prompted the surmise that here, too, a variable might be under scrutiny. The star, however, was certainly so far new, that its rays, until their sudden accession of strength, were too feeble to affect even our reinforced senses. Not one of the 1,283 small stars recorded in charts of the nebula could be identified with it, and a photograph taken by Dr. Common, August 16, 1884, on which a multitude of stars down to the 15th magnitude had imprinted themselves, showed the uniform soft gradation of nebulous light to be absolutely unbroken by a stellar indication in the spot reserved for the future occupation of the nova. So far, then, the view that its relation to the nebula was a merely optical one might be justified, but it became altogether untenable when it was found that what was taken to be a chance coincidence had repeated itself within living memory. On the 21st of May, 1860, M. Auers perceived at Königsberg a 7th magnitude star shining close to the center of a nebula in Scorpio, numbered 80 in Messier's catalogue. 3 days earlier it certainly was not there, and 3 weeks later it had vanished. The effect to Mr. Pogson, who independently discovered the change, May 28, was as if the nebula had been replaced by a star, so entirely were its dim rays overpowered by the concentrated blaze in their midst. Now, it is simply incredible that 2 outbursts of so uncommon a character should have accidentally occurred just on the line of sight between us and the central portions of 2 nebulae. We must, then, conclude that they showed on these objects because they took place in them. The most favored explanation is that they were what might be called effects of overcrowding, that some of the numerous small bodies, presumably composing the nebulae, jostled together, in their intricate circlings, and obtained compensation in heat for their sacrifice of motion. But this is scarcely more than a plausible makeshift of perplexed thought. Mr. W. H. S. Monk, on the other hand, has suggested that new stars appear when dark bodies are rendered luminous by rushing through the gaseous fields of space, just as meteors kindle in our atmosphere. The idea, which has been revived and elaborated by Dr. Seliger of Munich, is ingenious, but was not designed to apply to our present case. Neither of the objects distinguished by the striking variations just described is of gaseous constitution. That in Scorpio appears under high magnifying powers as a compressed cluster, that in Andromeda is perhaps, as Sir J. Herschel suggested, optically nebulous through the smallness of its constituent stars, if stars they deserve to be called. On the 8th of December, 1891, Dr. Max Wolf took a photograph of the region about Chi Aurigui. No stranger so bright as the 8th magnitude was among the stars depicted upon it. On the 10th, nevertheless, a stellar object of the 5th magnitude, situated a couple of degrees to the northeast of Beta Tauri and previously unrecorded, where 11th magnitude stars appeared, imprinted itself upon a Harvard negative. Subsequent photographs taken at the same place showed it to have gained about half a magnitude by the 20th, but the plates were not then examined, and the discovery was left to be modestly appropriated by an amateur, the Reverend Dr. Anderson of Edinburgh, by whom it was announced, February 1, 1892, through the medium of an anonymous postcard, to Dr. Copeland, the Astronomer Royal for Scotland. By him and others, the engines of modern research were promptly set to work. And to good purpose. Nova Aurigui was the first star of its kind studied by the universal chemical method. It is the first, accordingly, of which authentic records can be handed down to posterity. They are of a most remarkable character. The spectrum of the new object was photographed at Stonyhurst and South Kensington on February 3, a few days later, at Harvard and Lick in America, at Potsdam and Herenie on the continent of Europe. But by far the most complete impression was secured, February 22, with an exposure of 1 hour and 3/4, by Sir William and Lady Huggins, through whose kindness it is reproduced in Plate V, Figure 1. The range of bright lines displayed in it is of astonishing vividness and extent. It includes all the hydrogen rays dark in the spectrum of Sirius, separately printed for comparison, besides many others still more refrangible, as yet unidentified. Very significant, too, is the marked character of the great prominence lines H and K. The visual spectrum of the nova was splendidly effective. A. Plate V. Photographic and visual spectrum of Nova Aurigui. Figure 1. From a photograph taken by Sir William and Lady Huggins, February 22, 1892. Figure 2. From a drawing made by Lady Huggins, February 2 to 6, 1892. Quartet of brilliant green rays, 2 of them due to helium, caught the eye. And they had companions too numerous to be easily counted. The hydrogen lines were broad and bright, sea-blazed, as Mr. Espin said, like a danger signal on a dark night. The sodium pair were identified at Tulse Hill, and the yellow helium ray was suspected to lurk close beside them. Fig. 2 in the same plate shows the spectrum as it was seen and mapped by Lady Huggins, February 2nd to 6th, together with the spectra employed to test the nature of the emissions dispersed in it. One striking feature will be at once remarked. It is that of the pairing of bright with dark lines. Both in the visible and the photographic regions this singular peculiarity was unmistakable. And since the two series plainly owned the same chemical origin, their separate visibility implied large displacement. Otherwise they would have been superposed, not juxtaposed. Measurements of the bright rays, accordingly, showed them to be considerably pushed down towards the red, while their dark companions were still more pushed up towards the blue end. Thus the spectrum of Nova Aurigui, like that of Beta Lyrae, with which it had many points in common, appeared to be really double. It was supposed to combine the light of two distinct bodies, one, of a gaseous nature, moving rapidly away from the Earth, the other, giving a more sun-like spectrum, approaching it with even higher speed. The relative velocity determined at Potsdam for these oppositely flying masses amounted to 550 miles a second. And this prodigious rate of separation was fully maintained during 6 weeks. It did not then represent a mere periastral rush past. To the bodies exhibiting its effects, and parting company forever under its stress, it must have belonged, with slight diminution, in perpetuity. The luminous outburst by which they became visible was explained by Sir William Huggins, in a lecture delivered at the Royal Institution, May 13, 1892, on the tidal theory of Klinkerfues and Wilsing. Disturbances and deformations due to the mutual attraction of two bulky globes at a close approach would, he considered, give rise to enormous eruptions of the hotter matters from within, immensely greater, but similar in kind, to solar eruptions. And accompanied, probably, by large electrical disturbances. The multiple aspect and somewhat variable character of both bright and dark lines were plausibly referred to processes of reversal, such as are nearly always in progress above sunspots. But the long duration of the star's suddenly acquired luster did not easily fit in with the adopted rationale. A direct collision, on the other hand, was out of the question, since there had obviously been little, if any, sacrifice of motion. And the substitution of a nebula for one of the stars compelled recourse to scarcely conceivable modes of action for an explanation of the perplexing peculiarities of the compound spectrum. An unexpected denouement, however, threw all speculations off the track. The nova contained most of its brightness, fluctuations notwithstanding, until March 9. After which date it ran swiftly and uniformly down towards what was apprehended to be total extinction. No marked change of spectrum attended its decline. When last examined at Tulse Hill, March 24, all the more essential features of its prismatic light were still faintly recognizable. The object was steadily sinking on April 26, when a, supposed, final glimpse of it was caught with the Lick 36-inch. It was then of about the 16th magnitude. But on August 17 it had sprung up to the 10th, as Professors Holden, Skeebrel, and Campbell perceived with amazement on turning the same instrument upon its place. And to Professor Barnard it appeared, 2 nights later, not only revived, but transformed into the nucleus of a planetary nebula, 3 across. The reality of this seeming distension, however, at once disputed, was eventually disproved. It unquestionably arose from the imperfect focusing power of the telescope for rays of unusual quality. The rekindled nova was detected in this country by Mr. H. Corder, on whose notification Mr. Espin, on August 21, examined its nearly monochromatic spectrum. The metamorphosis of Nova Cygni seemed repeated. The light of the new object, like that of its predecessor, was mainly concentrated in a vivid green band, identified with the chief nebular line by Copeland, Vaughan Gothard, and Campbell. The second nebular line was also represented. Indeed, the last-named observer recognized nearly all the 18 lines measured by him in the nova as characteristic of planetary nebulae. Of particular interest is the emergence in the star spectrum photographed by von Gothard of an ultraviolet line originally discovered at Tulse Hill in the Orion Nebula, which is also very strong in the Lyra Annular Nebula. Obviously, then, the physical constitution of Nova Aurigui became profoundly modified during the 4 months of its invisibility. The spectrum of February was or appeared compound, that of August was simple, it could be reasonably associated only with a single light source. Many of the former brilliant lines, too, had vanished, and been replaced by others, at first inconspicuous or absent. As a result, the solar prominence type, to which the earlier spectrum had seemed to conform, was completely effaced in the later. The cause of these alterations remains mysterious, yet its effects continue. The chromatic behavior of the semi-extinct nova, when scrutinized with great refractors, shows its waning light to be distinctly nebular. Like nearly all its congeners, the star is situated in the full stream of the Milky Way, and we learn without surprise that micrometrical measures by Burnham and Barnard failed to elicit from it any sign of parallactic shifting. It is hence certain that the development of light, of which the news reached the Earth in December, 1891, must have been on a vast scale, and of ancient date. Nova Aurigui at its maximum assuredly exceeded the Sun many times in brightness. And its conflagration can scarcely have occurred less, and may have occurred much more, than 100 years ago. By means of the photographic surveys of the skies, carried on in both hemispheres under Professor Pickering's superintendence, such amazing events have been proved to be of not infrequent occurrence. Within 6 years 5 new stars were detected from Draper Memorial, or chart plates by Mrs. Fleming, besides the retrospective discovery of a sixth which had rapidly burnt itself out, 8 years previously, in Perseus. Nova Normi was the immediate successor of Nova Aurigui, Nova Carini and Nova Centauri lit up in 1895, the latter in a pre-existent nebula. Nova Sagittarii and Nova Aquili attained brief maxima in 1898 and 1899 respectively. Now, 3 out of these 5 stars reproduced with singular fidelity the spectrum of Nova Aurigui. They displayed the same brilliant rays shadowed, invariably on their blue sides, by dark ones. Palpably, then, the arrangement was systematic and significant. It could not result merely from the casually directed, opposite velocities of bodies meeting in space. The hypothesis of stellar encounters accordingly fell to the ground, and has been provided with no entire satisfactory substitute. Most speculators now fully recognize that motion displacements cannot be made to account for the doubled spectra of novae, and seek recourse instead to some kind of physical agency for producing the observed effect. And since this is also visible in certain permanent, though peculiar objects, notably in P Cygni, Beta Lyrae, and Eta Carini, the acting cause must also evidently be permanent and inherent. The new star of the new century was a visual discovery. Dr. Anderson duplicated, with added éclat, his performance of 9 years back. In the early morning of February 22, 1901, he perceived that Algol had a neighbor of nearly its own brightness, which a photograph taken by Mr. Stanley Williams, at Brighton, proved to have risen from below the 12th magnitude within the preceding 28 hours. And it was still swiftly ascending. On the 23rd, it outshone Capella. For a brief space it took rank as the premier star of the northern hemisphere. A decline set in promptly, but was pursued hesitatingly. The light fluctuated continually over a range of a couple of magnitudes, and with a close approach, during some weeks, to a 3-day periodicity. A year after the original outburst, the star was still conspicuous with an opera glass. The spectrum underwent amazing changes. At first continuous, save for fine dark lines of hydrogen and helium, it unfolded within 48 hours a composite range of brilliant and dusky bands disposed in the usual fashion of novae. These lasted until far on in March, when hydrogen certainly, and probably other substances as well, ceased to exert any appreciable absorptive action. Blue emissions of the Wolf-Rayet type then became occasionally prominent, in remarkable correspondence with the varying luster of the star. Finally, a band at lambda 3969, found by Wright at Lick to characterize nebular spectra, assumed abnormal importance, and in July the nebular transformation might be said to be complete. Striking alterations of color attended these spectral vicissitudes. White to begin with, the star soon turned deep red, and its redness was visibly intensified at each of its recurring minima of light. Blanching, however, ensued upon the development of its nebulous proclivities, and its surviving rays are of a steely hue. All the more important investigations of Nova Persei were conducted by photographic means. Libraries of spectral plates were collected at the Yerkes and Lick observatories, at South Kensington, Stonyhurst, and Potsdam, and await the more exhaustive interpretation of the future. Meanwhile, extraordinary revelations have been supplied by immediate photographic delineation. On August 22 and 23, 1901, Professor Max Wolf, by long exposures with the 16-inch Bruce twin objectives of the Königsstuhl Observatory, Heidelberg, obtained indications of a large nebula finely ramified, extending southeast of the nova. And the entire formation came out in 4 hours with the Yerkes 2-foot reflector, directed to it by Mr. Ritchie on September 20. It proved to be a great spiral encircling, and apparently emanating from, the star. But if so, tumultuously, and under stress of catastrophic impulsions. A picture obtained by Mr. Perrine with the Crossley refractor, in 7H. 19M, on November 7 and 8, disclosed the progress of a startling change. Comparison with the Yerkes photograph showed that during the intervening 48 days four clearly identifiable condensations had become displaced, all to the same extent of about 90 seconds of arcade, and in fairly concordant directions, suggesting motion round the nova as well as away from it. The velocity implied, however, is so prodigious as virtually to exclude the supposition of a bodily transport of matter. It should be at the rate of no less than 20,000 miles a second, admitting the object to be at a distance from us corresponding to an annual parallax of 1/10 of a second, and actual measurements show it to be indefinitely more remote. The fact of rapid variations in the nebula was reaffirmed, though with less precision, from Yerkes photographs of November 9 and 13, Mr. Ritchie inferring a general expansion of its southern portions. Much further evidence must be at hand before a sane judgment can be formed as to the nature of the strange events taking place in that secluded corner of the galaxy. And it is highly probable that the illumination of the nebulous wreaths round the star will prove no less evanescent than the blazing of the star itself. We have been compelled somewhat to anticipate our narrative as regards inquiries into the nature of nebulae. The excursions of opinion on the point were abruptly restricted and defined by the application to them of the spectroscope. On August 29, 1864, Sir William Huggins sifted through his prisms the rays of a bright planetary nebula in Draco. To his infinite surprise, they proved to be mainly of one color. In other words, they avowed their origin from a mass of glowing vapor. As to what kind of vapor it might be by which Herschel's conjecture of a shining fluid diffused at large throughout the cosmos was thus unexpectedly verified, an answer only partially satisfactory could be afforded. The conspicuous bright line of the Draco nebula seemed to agree in position with one emitted by nitrogen, but has since proved to be distinct from it. Of its two fainter companions, one was unmistakably the F line of hydrogen, while the other, in position intermediate between the two, still remains unidentified. By 1868 Huggins had satisfactorily examined the spectra of about 70 nebulae, of which 1/3 displayed a gaseous character. All of these gave the green ray fundamental to the nebular spectrum, and emanating from an unknown form of matter named by Sir William Huggins, nebulum. It is associated with 7 or 8 hydrogen lines, with 3 of yellow helium, and with a good many of undetermined origin. The absence of the crimson radiation of hydrogen, perceived with difficulty only in some highly condensed objects, is an anomaly very imperfectly explained as a physiological effect connected with the extreme faintness of nebular light. An approximate coincidence between the chief nebular line and a fluting of magnesium having been alleged by Lockyer in support of his meteoritic hypothesis of nebular constitution, it became of interest to ascertain its reality. The task was accomplished by Sir William and Lady Huggins in 1889 and 1890, and by Professor Keeler, with the advantages of the Mount Hamilton apparatus and atmosphere, in 1890–91. The upshot was to show a slight but sure discrepancy as to place, and a marked diversity as to character, between the two qualities of light. The nebular ray, wavelength 5007 millionths of a millimeter, is slightly more refrangible than the magnesium fluting edge, and it is sharp and fine, with no trace of the unilateral haze necessarily clinging even to the last remnant of a banded formation. Planetary and annular nebulae are, without exception, gaseous, as well as those termed irregular, which frequent the region of the Milky Way. Their constitution usually betrays itself to the eye by their blue or greenish color, while those yielding a continuous spectrum are of a dull white. Among the more remarkable of these are the well-known nebula in Andromeda, and the Great Spiral in Canes Venatici. And, as a general rule, the emissions of all such nebulae as present the appearance of star clusters grown misty through excessive distance are of the same kind. It would, however, be eminently rash to conclude thence that they are really aggregations of sun-like bodies. The improbability of such an inference has been greatly enhanced by the occurrence, at an interval of a quarter of a century, of stellar outbursts in the midst of two of them. For it is practically certain that the temporary stars were equally remote with the hazy formations they illuminated. Hence, if the constituent particles of the latter be suns, the incomparably vaster orbs by which their feeble light was well nigh obliterated must, as was argued by Mr. Proctor, have been on a scale of magnitude such as the imagination recoils from contemplating. Nevertheless, Dr. Scheiner, not without much difficulty, obtained, in January, 1899, spectrographic prints of the Andromeda Nebula, indicative, he thought, of its being a cluster of solar stars. Sir William and Lady Huggins, on the other hand, saw, in 1897, bright intermixed with dark bands in the spectrum of the same object. And Mr. Maunder conjectures all white nebulae to be made up of sunlets in which the coronal element predominates, while chromospheric materials assert their presence in nebulae of the green variety. Among the ascertained analogies between the stellar and nebular systems is that of variability of light. On October 11, 1852, Mr. Hind discovered a small nebula in Taurus. Chacornac observed it at Marseilles in 1854, but was confounded 4 years later to find it vanished. D'Arrest missed it October 3, and redetected it December 29, 1861. It was easily seen in 1865–66, but invisible in the most powerful instruments from 1877 to 1880. Barnard, however, made out an almost evanescent trace of it, October 15, 1890, with the Great Lick telescope, and saw it easily in the spring of 1895, while 6 months later it evaded his most diligent search. Then again, on September 28, 1897, the Yerkes 40-inch disclosed it to him as a mere shimmer at the last limit of visibility. And it came out in 3 diffuse patches on plates to which, on December 6 and 27, 1899, Keeler gave prolonged exposures with the Crossley reflector. Moreover, a fairly bright adjacent nebula, perceived by O. Struve in 1868 and observed shortly afterwards by D'Arrest, has totally vanished, and was most likely only a temporary apparition. These are the most authentic instances of nebular variability. Many others have been more or less plausibly alleged. But Professor Holden's persuasion, acquired from an exhaustive study of the records since 1758, that the various parts of the Orion Nebula fluctuate continually in relative luster, has not been ratified by photographic evidence. The case of the Trifid Nebula in Sagittarius, investigated by Holden in 1877, is less easily disposed of. What is certain is that a remarkable triple star, centrally situated, according to the observations of both the Herschels, 1784–1833, in a dark space between the 3 great lobes of the nebula, is now, and has been since 1839, densely involved in one of them. And since the hypothesis of relative motion is on many grounds inadmissible, the change that has apparently taken place must be in the distribution of light. One no less conspicuous was adduced by Mr. H.C. Russell, director of the Sydney Observatory. A particularly bright part of the Great Argo Nebula, as drawn by Sir John Herschel, has, it would seem, almost totally disappeared. He noticed its absence in 1871, using a 7-inch telescope, failed equally later on to find it with an 11 to 1/2 inch, and his long-exposure photographs show no vestige of it. The same structure is missing from, or scarcely traceable in, a splendid picture of the nebula taken by Sir David Gill in 12 hours distributed over 4 nights in March 1892. An immense gaseous expanse has, it would seem, sunk out of sight. Materially it is no doubt there, but the radiance has left it. Nebulae have no ascertained proper motions. No genuine change of place in the heavens has yet been recorded for any one of them. All equally hold aloof, so far as telescopic observation shows, from the busy journeyings of the stars. This seeming immobility is partly an effect of vast distance. Nebular parallax has, up to the present, proved evanescent, and nebular parallactic drift, in response to the sun's advance through space, remains likewise imperceptible. It may hence be presumed that no nebulae occur within the sphere occupied by the nearer stars. But the difficulty of accurately measuring such objects must also be taken into account. Displacements which would be conspicuous in stars might easily escape detection in ill-defined, hazy masses. Thus the measures executed by d'Arrest in 1857 have not yet proved effective for their designed purpose of contributing to the future detection of proper motions. Some determinations made by Mr. Burnham with the Lick refractor in 1891, will ultimately afford a more critical test. He found that nearly all planetary nebulae include a sharp stellar nucleus, the position of which with reference to neighboring stars could be fixed no less precisely than if it were devoid of nebulous surroundings. Hence, the objects located by him cannot henceforward shift, were it only to the extent of a small fraction of a second, without the fact coming to the knowledge of astronomers. The spectroscope, however, here as elsewhere, can supplement the telescope, and what it has to tell, it tells at once, without the necessity of waiting on time to ripen results. Sir William Huggins made, in 1874, the earliest experiments on the radial movements of nebulae. But with only a negative upshot. None of the 6 objects examined gave signs of spectral alteration, and it was estimated that they must have done so had they been in course of recession from or approach towards the Earth by as much as 25 miles a second. With far more powerful appliances, Professor Keeler renewed the attempt at Lick in 1890–91. His success was unequivocal. 10 planetary nebulae yielded perfectly satisfactory evidence of line-of-sight motion, the swiftest traveler being the well-known greenish globe in Draco, found to be hurrying towards the Earth at the rate of 40 miles a second. For the Orion Nebula, a recession of about 11 miles was determined, the whole of which may, however, very well belong to the solar system itself, which, by its translation towards the constellation Lyra, is certainly leaving the great nebula pretty rapidly behind. The anomaly of seeming nebular fixity has nevertheless been removed, and the problem of nebular motion has begun to be solved through the demonstrated possibility of its spectroscopic investigation. Keeler's were the first trustworthy determinations of radial motion obtained visually. That the similar work on the stars begun at Greenwich in 1874, and carried on for 13 years, remained comparatively unfruitful, was only what might have been expected. The instruments available there being altogether inadequate for the attainment of a high degree of accuracy. The various obstacles in the way of securing it were overcome by the substitution of the sensitive plate for the eye. Air tremors are thus rendered comparatively innocuous. And measurements of stellar lines displaced by motion with reference to fiducial lines from terrestrial sources, photographed on the same plates, can be depended upon within vastly reduced limits of error. Studies for the realization of the spectrographic method were begun by Dr. Vogel and his able assistant, Dr. Scheiner, at Potsdam in 1887. Their preliminary results, communicated to the Berlin Academy of Sciences, March 15, 1888, already showed that the requirements for effective research in this important branch were at last about to be complied with. An improved instrument was erected in the autumn of the same year, and the 51 stars, bright enough for determination with a refractor of 11 inches aperture, were promptly taken in hand. A list of their motions in the line of sight, published in 1892, was of high value, both in itself and for what it promised. One noteworthy inference from the data it collected was that the eye tends, under unfavorable circumstances, to exaggerate the line displacements it attempts to estimate. The velocities photographically arrived at were of much smaller amounts than those visually assigned. The average speed of the Potsdam stars came out only 10.4 miles a second, the quickest among them being Aldebaran, with a recession of 30 miles a second. More lately, however, Deslandres and Campbell have determined for Zeta Herculis and Eta Cephei respectively approaching rates of 44 and 54 miles a second. The installation, in 1900, of a photographic refractor 31.5 inches in aperture, coupled with a 20-inch guiding telescope, will enable Dr. Vogel to investigate spectrographically some hundreds of stars fainter than the second magnitude. And the materials thus accumulated should largely help to provide means for a definite and complete solution of the more than secular problem of the Sun's advance through space. The solution should be complete, because including a genuine determination of the Sun's velocity, apart from assumptions of any kind. M. Hohmann's attempt, in 1885, to extract some provisional information on the subject from the radial movements of visually determined stars gave a fair earnest of what might be done with materials of a better quality. He arrived at a goal for the Sun's way shifted eastward to the constellation Cygnus, a result congruous with the marked tendency of recently determined apexes to collect in or near Lyra. And the most probable corresponding velocity seemed to be about 19 miles a second, or just that of the Earth in its orbit. A more elaborate investigation of the same kind, based by Professor Campbell in 1900 upon the motions of 280 stars, determined with extreme precision, suffered incompleteness through lack of available data from the southern hemisphere. The outcome, accordingly, was an apex most likely correctly placed as regards right ascension, but displaced southward by some 15 degrees. The speed of 12 miles a second, assigned to the solar translation, approximates doubtless very closely to the truth. A successful beginning was made in nebular spectrography by Sir William Huggins, March 7, 1882. 5 lines in all stamped themselves upon the plate during 45 minutes of exposure to the rays of the strange object in Orion. Of these, 4 were the known visible lines, and a 5th, high up in the ultraviolet, at wavelength 3727, has evidently peculiar relationships, as yet imperfectly apprehended. It is strong in the spectra of many planetaries. It helped to characterize the nebular metamorphosis of Nova Aurigui, yet failed to appear in Nova Persei. 2 additional hydrogen lines, making 6 in all, were photographed at Tulse Hill, from the Orion Nebula, in 1890, and Dr. Copeland's detection in 1886 of the yellow ray D3 gave the first hint of the presence of helium in this prodigious formation. Nor are there wanting spectroscopic indications of its physical connection with the stars visually involved in it. Sir William and Lady Huggins found a plate exposed February 5, 1888, impressed with 4 groups of fine bright lines, originating in the continuous light of 2 of the trapezium stars, but extending some way into the surrounding nebula. And Dr. Scheiner argued a wider relationship from the common possession, by the nebula and the chief stars in the constellation Orion, of a blue line, bright in the one case, dark in the others, since identified as a member of one of the helium series. The structural unity of the stellar and nebular orders in this extensive region of the sky has also, by direct photographic means, been unmistakably affirmed. The first promising autographic picture of the Orion Nebula was obtained by Draper, September 30, 1880. The marked approach towards a still more perfectly satisfactory result shown by his plates of March 1881 and 1882, was unhappily cut short by his death. Meanwhile, M. Janssen was at work in the same field from 1881, with his accustomed success. But Dr. A. Ainsley Common left all competitors far behind with a splendid picture, taken January 30, 1883, by means of an exposure of 37 minutes in the focus of his 3-foot silver-on-glass mirror. Photography may thereby be said to have definitely assumed the office of historiographer to the nebulae, since this one impression embodies a mass of facts hardly to be compassed by months of labor with the pencil, and affords a record of shape and relative brightness in the various parts of the stupendous object it delineates, which must prove invaluable to the students of its future condition. Its beauty and merit were officially recognized by the award of the Astronomical Society's Gold Medal in 1884. A second picture of equal merit, obtained by the same means, February 28, 1883, with an exposure of 1 hour, is reproduced in the frontispiece. The vignette includes 2 specimens of planetary photography. The Jupiter, with the great red spot conspicuous in the southern hemisphere, is by Dr. Common. It dates from September 3, 1879, and was accordingly one of the earliest results with his 36-inch, the direct image in which imprinted itself in a fraction of a second, and was subsequently enlarged on paper about 12 times. The exquisite little picture of Saturn was taken at Paris by M. Paul and Prosper Henry, December 21, 1885, with their 13-inch photographic refractor. The telescopic image was in this case magnified 11 times previous to being photographed, an exposure of about 5 seconds being allowed, and the total enlargement, as it now appears, is 19 times. A trace of the dusky ring perceptible on the original negative is lost in the print. A photograph of the Orion Nebula taken by Dr. Roberts in 67 minutes, November 30, 1886, made a striking disclosure of the extent of that prodigious object. More than 6 times the nebulous area depicted on Dr. Common's plates is covered by it, and it plainly shows an adjacent nebula, separately catalogued by Messier, to belong to the same vast formation. This disposition to annex and appropriate has come out more strongly with every increase of photographic power. Plates exposed at Harvard College in March, 1888, with an 8-inch portrait lens, the same used in the preparation of the Draper catalogue, showed the old established fish-mouth nebula not only to involve the stars of the sword handle, but to be in tolerably evident connection with the most easterly of the 3 belt stars, from which a remarkable nebulous appendage was found to proceed. A still more curious discovery was made by W. H. Pickering in 1889. Photographs taken in 3 hours from the summit of Wilson's Peak in California revealed the existence of an enormous, though faint spiral structure, enclosing in its span of nearly 17 degrees the entire stellar and nebulous group of the belt and sword, from which it most likely, although not quite traceably, issues as if from a nucleus. A startling glimpse is thus afforded of the cosmical importance of that strange hiatus in the heavens which excited the wonder of Huygens in 1656. The inconceivable attenuation of the gaseous stuff composing it was virtually demonstrated by Mr. Ranyard. In March, 1885, Sir Howard Grubb mounted for Dr. Isaac Roberts, at Maghull, near Liverpool. His observatory has since been transferred to Crowborough in Sussex, a silver-on-glass reflector of 20 inches aperture, constructed expressly for use in celestial photography. A series of nebula pictures, obtained with this fine instrument, have proved highly instructive both as to the structure and extent of these wonderful objects. Above all, one of the great Andromeda Nebula, to which an exposure of 3 hours was given on October 1, 1888. In it a convoluted structure replaced and rendered intelligible the anomalously rift mass seen by Bond in 1847. The effects of annular condensation appeared to have stamped themselves upon the plate, and 2 attendant nebulae presented the aspect of satellites already separated from the parent body, and presumably revolving round it. The Ring Nebula in Lyra was photographed at Paris in 1886, and shortly afterwards by von Gothard with a 10-inch reflector, and he similarly depicted in 1888 the 2 chief spiral and other nebulae. Photographs of the Lyra Nebula taken at Algiers in 1890, and at the Vatican Observatory in 1892, were remarkable for the strong development of a central star, difficult of telescopic discernment, but evidently of primary importance to the annular structure around. The uses of photography in celestial investigations become every year more manifold and more apparent. The earliest chemical star pictures were those of Castor and Vega, obtained with the Cambridge refractor in 1850 by Whipple of Boston under the direction of W. C. Bond. Double star photography was inaugurated under the auspices of G. P. Bond, April 27, 1857, with an impression, obtained in 8 seconds, of Mizar, the middle star in the handle of the plough. A series of measures from 62 similar images gave the distance and position angle of its companion with about the same accuracy attainable by ordinary micrometrical operations. And the method and upshot of these novel experiments were described in 3 papers remarkably forecasting the purposes to be served by stellar photography. The matter next fell into the able hands of Rutherford, who completed in 1864 a fine object glass, of 11½ inches, corrected for the ultraviolet rays, consequently useless for visual purposes. The sacrifice was recompensed by conspicuous success. A set of measurements from his photographs of nearly 50 stars in the Pleiades, and their comparison with Bessel's places, enabled Dr. Gould to announce, in 1866, that during the intervening third of a century no changes of importance had occurred in their relative positions. And Mr. Harold Jacobi similarly ascertained the fixity of 75 of Rutherford's Atlantids, between the epoch 1873, and that of Drive. Elkin's heliometric triangulation of the cluster in 1886, extending the interval to 27 years by subsequent comparisons with plates taken at Lick, September 27, 1900. Positive, however, as well as negative results have ensued from the application of modern methods to that antique group. On October 19, 1859, Wilhelm Tempel, a Saxon peasant by origin, later a skilled engraver, discovered with a small telescope, bought out of his scanty savings, an elliptical nebulosity, stretching far to the southward from the star Merope. It attracted the attention of many observers, but was so often missed, owing to its extreme susceptibility to adverse atmospheric influences, as to rouse unfounded suspicions of its variability. The detection of this evasive object gave a hint, barely intelligible at the time, of further revelations of the same kind by more cogent means. A splendid photograph of 1,421 stars in the Pleiades, taken by the M.M. Henry with 3 hours exposure, November 16, 1885, showed one of the brightest of them to have a small spiral nebula, somewhat resembling a strongly curved comet's tail, attached to it. The reappearance of this strange appurtenance on 3 subsequent plates left no doubt of its real existence, visually attested at Pulkowa, February 5, 1886, by one of the first observations made with the 30-inch equatorial. Much smaller apertures, however, sufficed to disclose the Maya Nebula, once it was known to be there. Not only did it appear greatly extended in the Vienna 27-inch, but M.M. Perotin and Tholen saw it with the nice 15-inch, N.M. Cameraman of Geneva, employing special precautions, with a refractor of only 10 inches aperture. The advantage derived by him for bringing it into view, from the insertion into the eyepiece of a uranium film, gives, with its photographic intensity, valid proof that a large proportion of the light of this remarkable object is of the ultraviolet kind. The beginning thus made was quickly followed up. A picture of the Pleiades procured at McGill in 89 minutes, October 23, 1886, revealed nebulous surroundings to no less than 4 leading stars of the group, namely, Alcyone, Electra, Merope, and Maya. And a second impression, taken in 3 hours on the following night, showed further, that the nebulosity extends in streamers and fleecy masses till it seems almost to fill the spaces between the stars, and to extend far beyond them. The coherence of the entire mixed structure was, moreover, placed beyond doubt by the visibly close relationship of the stars to the nebulous formations surrounding them in Dr. Roberts's striking pictures. Thus Goldschmidt's notion that all the clustered Pleiades constitute, as it were, a second Orion trapezium in the midst of a huge formation of which Tempel's nebula is but a fragment, has been to some extent verified. Yet it seemed fantastic enough in 1863. Then in 1888 the M.M. Henry gave exposures of 4 hours each to several plates, which exhibited on development some new features of the entangled nebulae. The most curious of these was the linking together of stars by nebulous chains. In one case 7 aligned stars appeared strung on a silvery filament, like beads on a rosary. The rows of stars, so often noticed in the sky, may, then, be concluded to have more than an imaginary existence. Of the 2,326 stars recorded in these pictures, a couple of hundred among the brightest can, at the outside, be reckoned as genuine Pleiades. The great majority were relegated, by Pickering's and Stratonoff's counts of the stellar populace in and near the cluster, to the position of outsiders from it. They are undistinguished denizens of the abysmal background upon which it is projected. Investigations of its condition were carried a stage further by Barnard. On November 14, 1890, he discovered visually with the Lick refractor a close nebulous satellite to Merope, photographs of which were obtained by Keeler in 1898. It appears in them of a rudely pentagonal shape, a prominent angle being directed towards the adjacent star. Finally, an exposure of 10 hours made by Barnard with the Willard lens indicated the singular fact that the entire group is embedded in a nebulous matrix, streaky outliers of which blur a wide surface of the celestial vault. The artist's conviction of the reality of what his picture showed was confirmed by negatives obtained by Bailey at Arequipa in 1897, and by H. C. Wilson at Northfield, Minnesota, in 1898. With the Ealing 3-foot reflector, sold by Dr. Common to Mr. Crossley, and by him presented to the Lick Observatory, Professor Keeler took in 1899 a series of beautiful and instructive nebula photographs. One of the Trifid may be singled out as of particular excellence. An astonishing multitude of new nebulae were revealed by trial exposures with this instrument. A conservative estimate gave 120,000 as the number coming within its scope. Moreover, the majority of those actually recorded were of an unmistakable spiral character, and they included most of Sir John Herschel's double nebulae, previously supposed to exemplify the primitive history of binary stellar systems. Dr. Max Wolf's explorations with a 6-inch Voigtlander lens in 1901 emphatically reaffirmed the inexhaustible wealth of the nebular heavens. In one restricted region, midway between Praecipe and the Milky Way, he located 135 nebulae, where only 3 had until then been catalogued. And he counted 108 such objects clustering round the star 31 Commi Berenices, and so closely that all might be occulted together by the moon. The general photographic catalogue of nebulae which Dr. Wolf has begun to prepare will thus be a most voluminous work. The history of celestial photography at the Cape of Good Hope began with the appearance of the great comet of 1882. No special apparatus was at hand. So Sir David Gill called in the services of a local artist, Mr. Alice of Mowbray, with whose camera, strapped to the Observatory Equatorial, pictures of conspicuous merit were obtained. But their particular distinction lay in the multitude of stars begemming the background. The sight of them at once opened to the royal astronomer a new prospect. He had already formed the project of extending Argelander's Durchmusterung from the point where it was left by Schönfeld to the southern pole. And his ideas regarding the means of carrying it into execution crystallized at the needle touch of the cometary experiments. He resolved to employ photography for the purpose. The exposure of plates was accordingly begun, under the care of Mr. Ray Woods, in 1885, and in less than 6 years, the sky, from 19 degrees of south latitude to the pole, had been covered in duplicate. Their measurement, and the preparation of a catalogue of the stars imprinted upon them, were generously undertaken by Professor Kapteyn, and his laborious task has at length been successfully completed. The publication, in 1900, of the third and concluding volume of the Cape Photographic Durchmusterung, placed at the disposal of astronomers a photographic census of the heavens fuller and surer than the corresponding visual enumeration executed at Bonn. It includes 454,875 stars, nearly to the 10th magnitude, and their positions are reliable to about 1 second of arc. The production of this important work was thus a result of the Cape Comet pictures, yet not the most momentous one. They turned the scale in favor of recourse to the camera when the M.M. Henry encountered, in their continuation of Chacornac's half-finished enterprise of ecliptical charting, sections of the Milky Way defying the enumerating efforts of eye and hand. The perfect success of some preliminary experiments made with an instrument constructed by them expressly for the purpose was announced to the Academy of Sciences at Paris, May 2, 1885. By its means stars estimated as of the 16th magnitude clearly recorded their presence and their places. And the enormous increase of knowledge involved may be judged of from the fact that, in a space of the Milky Way in Cygnus 2 degrees 15 by 3 degrees, where 170 stars had been mapped by the old laborious method, about 5,000 stamped their images on a single Henry plate. These results suggested the grand undertaking of a general photographic survey of the heavens, and Gill's proposal, June 4, 1886, of an international congress for the purpose of setting it on foot was received with acclamation. And promptly acted upon. 56 delegates of 17 different nationalities met in Paris, April 16, 1887, under the presidency of Admiral Mouchet, to discuss measures and organize action. They resolved upon the construction of a photographic chart of the whole heavens, comprising stars of a 14th magnitude, to the surmised number of 20 millions. To be supplemented by a catalogue, framed from plates of comparatively short exposure, giving start to the 11th magnitude. These will probably amount to about 1,250,000. For procuring both sets of plates, instruments were constructed precisely similar to that of the M.M. Henry, which is a photographic refractor, 13 inches in aperture, and 11 feet focus, attached to a guiding telescope of 11 inches aperture, corrected, of course, for the visual rays. Each place covers an area of 4 square degrees, and since the series must be duplicated to prevent mistakes, about 22,000 plates will be needed for the chart alone. The task of preparing them was apportioned among 18 observatories scattered over the globe, from Mexico to Melbourne. But 3 in South America, having become disabled or inert, were replaced in 1900 by those at Cordoba, Montevideo, and Perth, Western Australia. Meanwhile, the publication of results has begun, and is likely to continue for at least a quarter of a century. The first volume of measures from the Potsdam catalogue plates was issued in 1899, and its successors, if on the same scale, must number nearly 400. Moreover, 96 heliogravure enlargements from the Paris chart plates, distributed in the same year, supplied a basis for the calculation that the entire atlas of the sky, composed of similar sheets, will form a pile 30 feet high and 2 tons in weight. It will, however, possess an incalculable scientific value. For millions of stars can be determined by its means, from their imprinted images, with an accuracy comparable to that attainable by direct meridian observations. One of the most ardent promoters of the scheme it may be expected to realize was Admiral Mouchet, the successor of Leverrier in the direction of the Paris Observatory. But it was not granted to him to see the fruition of his efforts. He died suddenly June 25, 1892. Although not an astronomer by profession, he had been singularly successful in pushing forward the cause of the science he loved, while his genial and open nature won for him wide personal regard. He was replaced by M. Tisserand, whose mathematical eminence fitted him to continue the traditions of Delaunay and Leverrier. But his career, too, was unhappily cut short by an unforeseen death on October 20, 1896. And the more eminent among the many qualifications of his successor, M. Maurice Loewy, are of the practical kind. The sublime problem of the construction of the heavens has not been neglected amid the multiplicity of tasks imposed upon the cultivators of astronomy by its rapid development. But data of a far higher order of precision, and indefinitely greater in amount, than those at the disposal of Herschel or Struve must be accumulated before any definite conclusions on the subject are possible. The first organized effort towards realizing this desideratum was made by the German Astronomical Society in 1865, 2 years after its foundation at Heidelberg. The original program consisted in the exact determination of the places of all Argelander's stars to the 9th magnitude, exclusive of the polar zone, from the reobservation of which, say, in the year 1950. Astronomers of 2 generations hence may gather a vast store of knowledge, directly of the apparent motions, indirectly of the mutual relations binding together the suns and systems of space. 13 observatories in Europe and America joined in the work, now virtually terminated. Its scope was, after its inception, widened to include southern zones as far as the Tropic of Capricorn. This having been rendered feasible by Schonfeld's extension, 1875 to 1885, of Argelander's survey. 30,000 additional stars thus taken in were allotted in zones to 5 observatories. Another important undertaking of the same class is the re-observation of the 47,300 stars in Lalande's Histoire Céleste. Begun under Arago in 1855, its upshot has been the publication of the Great Paris Catalogue, issued in 8 volumes, between 1887 and 1902. From a careful study of their secular changes in position, M. Bossert has already derived the proper motions of a couple of thousand out of nearly 50,000 stars enumerated in it. Frudiar. Gould's unceasing labors during his 15 years' residence at Córdoba, a detailed acquaintance with southern stars was brought about. His Uranometria Argentina, 1879, enumerates the magnitudes of 8,198 out of 10,649 stars visible to the naked eye under those transparent skies, 33,160 down to 9.5 magnitude are embraced in his zones. And the Argentine General Catalogue of 32,468 southern stars was published in 1886. Valuable work of the same kind has been done at the Leander McCormick Observatory, Virginia, by Professor O. Stone. While the late Redcliffe Observer's Cape Catalogue for 1880 affords inestimable aid to the practical astronomer south of the line, which has been reinforced with several publications issued by the present Astronomer Royal at the Cape. Moreover, the gigantic task entered upon in 1860 by Dr. C. H. F. Peters, director of the Litchfield Observatory, Clinton, New York, and of which a large installment was finished in 1882, deserves honorable mention. It was nothing less than to map all stars down to, and even below, the 14th magnitude, situated within 30 degrees on either side of the ecliptic. And so to afford a sure basis for drawing conclusions with respect to the changes going on in the starry heavens. It is tolerably safe to predict that no work of its kind and for its purpose will ever again be undertaken. In a small part of one night stars can now be got to register themselves more numerously and more accurately than by the eye and hand of the most skilled observer in the course of a year. Fundamental catalogues, constructed by the old, time-honored method, will continue to furnish indispensable starting points for measurement, and one of especial excellence was published by Professor Newcomb in 1899. But the relative places of the small crowded stars, the sidereal Omicron iota, pi Omicron lambda lambda Omicron iota, will henceforth be derived from their autographic statements on the sensitive plate. Even the secondary purpose, that of asteroidal discovery, served by detailed stellar enumeration, is more surely attained by photography than by laborious visual comparison. For planetary movement betrays itself in a comparatively short time by turning the imprinted image of the object affected by it from a dot into a trail. In the arduous matter of determining star distances progress has been steady, and bids fair to become rapidly accelerated. Together, yet independently, Gill and Elkin carried out, at the Cape Observatory in 1882–83, an investigation of remarkable accuracy into the parallaxes of 9 southern stars. One of these was the famous Alpha Centauri, the distance of which from the Earth was ascertained to be just 1/3 greater than Henderson had made it. The parallax of Sirius, on the other hand, was doubled, or its distance halved. While Canopus proved to be quite immeasurably remote, a circumstance which, considering that, among all the stellar multitude, it is outshone only by the radiant dog star, gives a stupendous idea of its real splendor and dimensions. Inquiries of this kind were, for some years, successfully pursued at the Observatory of Dunsink, near Dublin. Annual perspective displacements were by Dr. Bruno detected in several stars, and in others remeasured with a care which inspired just confidence. His parallax for Alpha Lyrae, 0-13, was authentic, though slightly too large. Elkin's final results gave pi equals 0.082. And the received value for the parallax of the swiftly traveling star, Groombridge 1830, scarcely differs from that arrived at by him in 1871, pi equals 009. His successor as Astronomer Royal for Ireland, Sir Robert Stawell Ball, now Lowndean Professor of Astronomy in the University of Cambridge, has done good service in the same department. For besides verifying approximately Struve's parallax of half a second of arc for 61 Cygni, he refuted, in 1811, by a sweeping search for, so-called, large parallaxes, certain baseless conjectures of comparative nearness to the Earth. In the case of red and temporary stars, of 450 objects thus cursorily examined, only one star of the 7th magnitude, numbered 1618 in Groombridge's circumpolar catalogue, gave signs of measurable vicinity. Similarly, a reconnaissance among rapidly moving stars lately made by Dr. Chase with the Yale heliometer yielded no really large, and only 8 appreciable parallaxes among the 92 subjects of his experiments. A second campaign in stellar parallax was undertaken by Gill and Elkin in 1887. But this time the two observers were in opposite hemispheres. Both used heliometers. Dr. Elkin had charge of the fine instrument then recently erected in Yale College Observatory. Sir David Gill employed one of 7 inches, just constructed under his directions, in first-rate style, by the Repsolds of Hamburg. Dr. Elkin completed in 1888 his share of the more immediate joint program, which consisted in the determination, by direct measurement, of the average parallax of stars of the first magnitude. It came out, for the 10 northern luminaries, after several revisions, 0.098, equivalent to a light journey of 33 years. The deviations from this average were, indeed, exceedingly wide. 2 of the stars, Betelgeuse and Alpha Cygni, gave no certain sign of any perspective shifting, of the rest, Procyon, with a parallax of 0.334, proved the nearest to our system. At the mean distance concluded for these 10 brilliant stars, the Sun would show as of only 5th magnitude, hence it claims a very subordinate rank among the suns of space. Sir David Gill's definitive results were published in 1900. As the average parallax of the 11 brightest stars in the southern hemisphere, they gave 0.13, a value enhanced by the exceptional proximity of Alpha Centauri. Yet 4 of these conspicuous objects, Canopus, Rigel, Spica, and Beta Crucis, gave no sign of perspective response to the annual change in our point of view. The list included 11 fainter stars with notable proper motions, and most of these proved to have fairly large parallaxes. Among other valuable contributions to this difficult branch may be instanced Bruno Peters' measurements of 11 stars with the Leipzig heliometer, 1887–92. Kapteyn's application of the method by differences in right ascension to 15 stars observed on the meridian 1885–89, and Flint's more recent similar determinations at Madison, Wisconsin. The great merit of having rendered photography available for the sounding of the celestial depths belongs to Professor Pritchard. The subject of his initial experiment was 61 Cygni. From measurements of 200 negatives taken in 1886, he derived for that classic star a parallax of 0.438, in satisfactory agreement with Ball's of 0.468. A detailed examination convinced the Astronomer Royal of its superior accuracy to Bessel's result with the heliometer. The Sevillian professor carried out his project of determining all second-magnitude stars to the number of about 30, conveniently observable at Oxford, obtaining as the general outcome of the research an average parallax of 0.056. For objects of that rank. But this value, though in itself probable, cannot be accepted as authoritative, in view of certain inaccuracies in the work adverted to by Jacobi, Hermann Davis, and Gill. The method has, nevertheless, very large capabilities. Professor Kapteyn showed, in 1889, the practicability of deriving parallaxes wholesale from plates exposed at due intervals, and applied his system, in 1900, with encouraging success, to a group of 248 stars. The apparent absence of spurious shiftings justified the proposal to follow up the completion of the astrographic chart with the initiation of a photographic, parallax Durchmusterung. Observers of double stars are among the most meritorious, and need to be among the most patient and painstaking workers in sidereal astronomy. They are scarcely as numerous as could be wished. Dr. Doberk, distinguished as a computer of stellar orbits, complained in 1882 that data sufficient for the purpose had not been collected for above 30 or 40 binaries out of between 5 and 600 certainly or probably within reach. The progress since made is illustrated by Mr. Gore's useful catalogue of computed binaries, including 59 entries, presented to the Royal Irish Academy, June 9, 1890. Few have done more toward supplying the deficiency of materials than the late Baron Ercole Dembowski of Milan. He devoted the last 30 years of his life, which came to an end January 19, 1881, to the revision of the Dorpat catalogue, and left behind him a store of micrometrical measures as numerous as they are precise. Of living observers in this branch, Mr. S. W. Burnham is beyond question the foremost. While pursuing legal avocations at Chicago, he diverted his scanty leisure by exploring the skies with a 6-inch telescope mounted in his backyard. And had discovered, in May, 1882, 1,000 close and mostly very difficult double stars. Summoned as chief assistant to the New Lick Observatory in 1888, he resumed the work of his predilection with the 36-inch and 12-inch refractors of that establishment. But although devoting most of his attention to much-needed remeasurements of known pairs, he incidentally divided no less than 274 stars, the majority of which lay beyond the resolving power of less keen and effectually aided eyesight. One of his many interesting discoveries was that of a minute companion to Alpha Ursae Majoris, the first pointer, which already gives unmistakable signs of orbital movement round the shining orb it is attached to. Another pair, Kappa Pegasi, detected in 1880, was found in 1892 to have more than completed a circuit in the interim. Its period of a little over 11 years is the shortest attributable to a visible binary system, except that of Delta Equulei, provisionally determined by Professor Hussey in 1900 at 5-7 years. And indicated by spectroscopic evidence to be of uncommon brevity. Burnham's catalogue of 1,290 double stars, discovered by him from 1871 to 1899, is a record of unprecedented interest. Nearly all the 690 pairs included in it, 2 or less than 2 apart, must be physically connected. And they offer a practically unlimited field for investigation, while the notes, diagrams, and orbits appended profusely to the various entries, are eminently helpful to students and computers. The author is continuing his researches at the Yerkes Observatory, having quitted the Lick establishment in 1892. The first complete enrollment of southern double stars was made by Mr. R. T. A. Innes in 1899. The couples enumerated, 21% of which are separated by less than 1 second of arc, are 2,140 in number. They include 305 discovered by himself. Dr. C. gathered a rich harvest of nearly 500 new southern pairs with the Lowell 24-inch refractor in 1897. Professor Hoff's discoveries in more northerly zones amount to 623, Hussey's at Lick to 350, and Aitken's already to over 300. There is as yet no certainty that the stars of 61 Cygni form a true binary combination. Mr. Burnham, indeed, holds them to be in course of definitive separation. And Professor Hall's observations at Washington, 1879 to 1891, although favoring their physical connection, are far from decisive on the point. Dr. Wilsing, from certain anomalous displacements of their photographed images, concluded in 1893 the presence of an invisible third member of the system, revolving in a period of 22 months, but the effects noticed by him were probably illusory. Important series of double-star observations were made by Perrotin at Nice in 1883-4, by Hall, with the 26-inch Washington Equatorial, 1874 to 1891, by Schiaparelli from 1875 onward, by Glasenapp, O. Stone, Leavenworth, Seabrook, and many besides. Finally, Professor Hussey's revision of the Pulkowa catalogue is a work of the teres ac rotundus kind, which leaves little or nothing to be desired. The methods employed in double star determinations remain, at the beginning of the 20th century, essentially unchanged. The camera has scarcely encroached upon this part of the micrometer's domain. A research of striking merit into the origin of binary stars was published in 1892 by Dr. T.J.J. C. in the form of an inaugural dissertation for his doctor's degree in the University of Berlin. The main result was to show the powerful effects of tidal friction in prescribing the course of their development from double nebulae, revolving almost in contact, to double suns, far apart, yet inseparable. The high eccentricities of their eventual orbits were shown to result necessarily from this mode of action, which must operate with enormous strength on closely conjoined, nearly equal masses. Such as the rapidly revolving pairs disclosed by the spectroscope. That these are still in an early stage of their life history is probable in itself, and is reaffirmed by the exceedingly small density indicated for eclipsing stars by the ratio of phase duration to period. Stellar photometry, initiated by the elder Herschel, and provided with exact methods by his son at the Cape, by Steinheil and Seidel at Munich, has of late years assumed the importance of a separate department of astronomical research. Two monumental works on the subject, compiled on opposite sides of the Atlantic, were thus appropriately coupled in the bestowal of the Royal Astronomical Society's Gold Medal in 1886. Harvard College Observatory led the way under the able direction of Professor E. C. Pickering. His photometric catalogue of 4,260 stars, constructed from nearly 95,000 observations of light intensity during the years 1879 to 82, constitutes a record of incalculable value for the detection and estimation of stellar variability. It was succeeded in 1885 by Professor Pritchard's Uranometria Nova Oxoniensis, including photometric determinations of the magnitude of all naked-eye stars, from the pole to 10 degrees south of the equator to the number of 2,784. The instrument employed was the wedge photometer, which measures brightness by resistance to extinction. A wedge of neutral tint glass, accurately divided to scale, is placed in the path of the stellar rays. When the thickness of it they have power to traverse furnishes a criterion of their intensity. Professor Pickering's meridian photometer, on the other hand, is based upon Zollner's principle of equalization effected by a polarizing apparatus. After all, however, as Professor Pritchard observed, the eye is the real photometer, and its judgment can only be valid over a limited range. Absolute uniformity, then, in estimates made by various means, under varying conditions, and by different observers, is not to be looked for, and it is satisfactory to find substantial agreement attainable and attained. Only in an insignificant fraction of the stars common to the Harvard and Oxford catalogues discordances are found exceeding 1/3 of a magnitude. A large proportion, 71%, agree within 1/4, a considerable minority, 31%. Within 1/10 of a magnitude. The Harvard photometry was extended, on the same scale, to the opposite pole in a catalogue of the magnitudes of 7,922 southern stars, founded on Professor Bailey's observations in Peru, 1889–91. Measurements still more comprehensive were subsequently executed at the primary establishment. With a meridian photometer of augmented power, the surprising number of 473,216 settings were made during the years 1891–98, nearly all by the indefatigable director himself, and they afforded materials for a photometric Durchmusterung. Published in 1901, including all stars to 7th 5 magnitude north of declination -40 degrees. A photometric zone, 20 degrees wide, has for some time been in course of observation at Potsdam by M. Müller and Kempf. The instrument employed by them is constructed on the polarizing principle as adapted by Zollner. Photographic photometry has meanwhile risen to an importance if anything exceeding that of visual photometry. For the usefulness of the great international star chart now being prepared would be gravely compromised by systematic mistakes regarding the magnitudes of the stars registered upon it. No entirely trustworthy means of determining them have, however, yet been found. There is no certainty as to the relative times of exposure needed to get images of stars representative of successive photometric ranks. All that can be done is to measure the proportionate diameters of such images, and to infer, by the application of a law learned from experience, the varied intensities of light to which they correspond. The law is, indeed, neither simple nor constant. Different investigators have arrived at different formulae, which, being purely empirical, vary their nature with the conditions of experiment. Probably the best expedient for overcoming the difficulty is that devised by Pickering, of simultaneously photographing a star and its secondary image, reduced in brightness by a known amount. The results of its use will be exhibited in a catalogue of 40,000 stars to the 10th magnitude, one for each square degree of the heavens. A photographic photometry of all the lucid stars, modeled on the visual photometry of 1884, is promised from the same copious source of novelties. The magnitudes of the stars in the Draper catalogue were determined, so to speak, spectrographically. The quantity measured in all cases was the intensity of the hydrogen line near G. By the employment of this definite and uniform test, results were obtained, of special value indeed, but in strong disaccord with those given by less exclusive determinations. Thought, meantime, cannot be held aloof from the great subject upon the future illustration of which so much patient industry is being expended. Nor are partial glimpses denied to us of relations fully discoverable, perhaps, only through centuries of toil. Some important points in cosmical economy have, indeed, become quite clear within the last 50 years, and scarcely any longer admit of a difference of opinion. One of these is that of the true status of nebulae. This was virtually settled by Sir J. Herschel's description in 1847 of the structure of the Magellanic Clouds. But it was not until Whewell, in 1853, and Herbert Spencer, in 1858, enforced the conclusions necessarily to be derived therefrom that the conception of the nebulae as remote galaxies, which Lord Rosse's resolution of many interstellar points had appeared to support, began to withdraw into the region of discarded and half-forgotten speculations. In the nubeculae, as Whewell insisted, there coexist, in a limited compass and in indiscriminate position, stars, clusters of stars, nebulae, regular and irregular, and nebulous streaks and patches. These, then, are different kinds of things in themselves, not merely different to us. There are such things as nebulae side by side with stars and with clusters of stars. Nebulous matter resolvable occurs close to nebulous matter irresolvable. This argument from coexistence in nearly the same region of space, reiterated and reinforced with others by Mr. Spencer, was urged with his accustomed force and freshness by Mr. Proctor. It is unanswerable. There is no maintaining nebulae to be simply remote worlds of stars in the face of an agglomeration like the Nubecula Major, containing in its, certainly capacious, bosom both stars and nebulae. Add the facts that a considerable proportion of these perplexing objects are gaseous, and that an intimate relation obviously subsists between the mode of their scattering and the lie of the Milky Way. And it becomes impossible to resist the conclusion that both nebular and stellar systems are parts of a single scheme. As to the stars themselves, the presumption of their approximate uniformity in size and brightness has been effectually dissipated. Differences of distance can no longer be invoked to account for dissimilarity in luster. Minute orbs, altogether invisible without optical aid, are found to be indefinitely nearer to us than such radiant objects as Canopus, Betelgeuse, or Rigel. Moreover, intensity of light is perceived to be a very imperfect index to real magnitude. Brilliant suns are swayed from their course by the attractive power of massive yet faintly luminous companions, and suffer eclipse from obscure interpositions. Besides, effective luster is now known to depend no less upon the qualities of the investing atmosphere than upon the extent and radiative power of the stellar surface. Red stars must be far larger in proportion to the light diffused by them than white or yellow stars. There can be no doubt that our sun would at least double its brightness were the absorption suffered by its rays to be reduced to the Syrian standard. And, on the other hand, that it would lose half its present efficiency as a light source if the atmosphere partially veiling its splendors were rendered as dense as that of Aldebaran. Thus, variety of all kinds is seen to abound in the heavens. And it must be admitted that the consequent insecurity of all hypotheses as to the relative distances of individual stars singularly complicates the question of their allocation in space. Nevertheless, something has been learned even on that point. And the tendency of modern research is, on the whole, strongly confirmatory of the views expressed by Herschel in 1802. He then no longer regarded the Milky Way as the mere visual effect of an enormously extended stratum of stars, but as an actual aggregation, highly irregular in structure, made up of stellar clouds and groups and nodosities. All the facts since ascertained fit in with this conception, to which Proctor added arguments favoring the view, since adopted by Barnard and Easton, that the stars forming the galactic stream are not only situated more closely together, but are also really, as well as apparently, of smaller dimensions than the lucid orbs studding our skies. By the laborious process of isographically charting the whole of Argelander's 324,000 stars, he brought out in 1871 signs of relationship between the distribution of the brighter stars and the complex branchings of the Milky Way, which has been stamped as authentic by Newcomb's recent statistical inquiries. There is, besides, a marked condensation of stars, especially in the southern hemisphere, towards a great circle inclined some 20 degrees to the galactic plane. And these were supposed by Gould to form with the Sun a subordinate cluster, of which the components are seen projected upon the sky as a zone of stellar brilliance. The zone has, however, galactic rather than solar affinities, and represents, perhaps, not a group, but a stream. The idea is gaining ground that the Milky Way is designed, in its main outlines, on a spiral pattern, and that its various branches and sections are consequently situated at very different distances from ourselves. Proctor gave a preliminary interpretation of their complexities on this principle, and Easton of Rotterdam has renewed the attempt with better success. A most suggestive delineation of the Milky Way, completed in 1889, after 5 years of labor, by Dr. Otto Boedicker, Lord Rosse's astronomer at Parsonstown, was published by Lithography in 1892. It showed a curiously intricate structure, composed of dimly luminous streams, and shreds, and patches, intermixed with dark gaps and channels. Ramifications from the main trunk ran out towards the Andromeda Nebula, and the Beehive cluster in Cancer involved the Pleiades and Hyades, and, winding round the constellation of Orion, just attained the Sword-Handle Nebula. The last delicate touches had scarcely been put to the picture, when the laborious iron-hand method was, in this quarter, as already in so many others, superseded by a more expeditious process. Professor Barnard took the first photographs ever secured of the true Milky Way, July 28, August 1 and 2, 1889, at the Lick Observatory. Special conditions were required for success. Above all, a wide field and a strong light grasp, both complied with through the use of a 6-inch portrait lens. Even thus, the sensitive plate needed some hours to pick out the exceedingly faint stars collected in the galactic clouds. These cannot be photographed under the nebulous aspect they wear to the eye. The camera takes note of their real nature, and registers their constituent stars rank by rank. Hence the difficulty of disclosing them. In the photographs made with the 6-inch portrait lens, Professor Barnard wrote, besides myriads of stars, there are shown, for the first time, the vast and wonderful cloud forms, with all their remarkable structure of lanes, holes, and black gaps, and sprays of stars. They present to us these forms in all their delicacy and beauty, as no eye or telescope can ever hope to see them. In Plate 6, one of these strange galactic landscapes is reproduced. It occurs in the bow of Sagittarius, not far from the Trifid Nebula, where the aggregations of the Milky Way are more than usually varied and characteristic. One of their distinctive features comes out with particular prominence. Plate 6. Region of the Milky Way in Sagittarius, showing a double black aperture. Photographed by Professor E. E. Barnard. It will be noticed that the bright mass near the center of the plate is tunneled with dark holes and furrowed by dusky lanes. Such interruptions recur perpetually in the Milky Way. They are exemplified on the largest scale in the Great Rift, dividing it into two branches all the way from Cygnus to Crux, and they are reproduced in miniature in many clusters. Mr. H. C. Russell, at Sydney in 1890, successfully imitated Professor Barnard's example. His photographs of the southern Milky Way have many points of interest. They show the Great Rift, black to the eye, yet densely star-strewn to the perception of the chemical retina, while the coal sack appears absolutely dark only in its northern portion. His most remarkable discovery, however, was that of the spiral character of the two nubeculae. With an effective exposure of 4.5 hours, the greater cloud came out as a complex spiral, with two centers. While the similar conformation of its minor companion developed only after 8 hours of persistent actinic action. The revelation is full of significance. Scarcely less so, although after a different fashion, is the disclosure on plates exposed by Dr. Max Wolf, with a 5-inch lens, in June, 1891, of a vastly extended nebula, bringing some of the leading stars in Cygnus into apparently organic connection with the piles of galactic stardust likewise involved by it. Barnard has similarly found great tracts of the Milky Way to be photographically nebulous, and the conclusion seems inevitable that we see in it a prodigious mixed system, resembling that of the Pleiades in point of composition, though differing widely from it in plan of structure. Of corroborative testimony, moreover, is the discovery independently resulting from Gill's and Pickering's photographic reviews, that stars of the first type of spectrum largely prevail in the galactic zone of the heavens. With approach to that zone, Kapteyn noticed a steady growth of actinic intensity relative to visual brightness in the stars depicted on the Cape Durchmusterung plates. In other words, stellar light is, in the Milky Way, bluer than elsewhere. And the reality of the primitive character hence to be inferred for the entire structure was, in a manner, certified by Mr. Maclean's observation that helium stars, the supposed immediate products of nebulous matter, crowd towards its medial plane. The first step towards the unravelment of the tangled web of stellar movements was taken when Herschel established the reality, and indicated the direction of the sun's journey. But the gradual shifting backward of the whole of the celestial scenery amid which we advance accounts for only a part of the observed displacements. The stars have motions of their own besides those reflected upon them from ours. All attempts, however, to grasp the general scheme of these motions have hitherto failed. Yet they have not remained wholly fruitless. The community of slow movement in Taurus, upon which Madler based his famous theory, has proved to be a fact, and one of very extended significance. In 1870 Mr. Proctor undertook to chart down the directions and proportionate amounts of about 1,600 proper motions, as determined by Messrs. Stone and Main, with the result of bringing to light the remarkable phenomenon termed by him stardrift. Quite unmistakably, large groups of stars, otherwise apparently disconnected, were seen to be in progress together, in the same direction and at the same rate, across the sky. An example of this kind of unanimity was alleged by him in the 5 intermediate stars of the Plough. And that the agreement in thwartwise motion is no casual one is practically demonstrated by the concordant radial velocities determined at Potsdam for 4 out of the 5 objects in question. All of these approached the Earth at the rate of about 18 miles a second, and the fifth and faintest, Delta Ursae, though not yet measured, may be held to share their advance. One of them, moreover, Zeta Ursae, alias Mizar, carries with it 3 other stars, Alcor, the Arab rider of the horse, visible to the naked eye, besides a telescopic and a spectroscopic attendant. So that the group may be regarded as octuple. It is of vast compass. Dr. Hoefler assigned to it in 1897, although on grounds more or less hypothetical, a mean parallax corresponding to a light journey of 192 years. Which would give to the marching squadron a total extent of at least 14 times the distance from the Sun to Alpha Centauri, while implying for its brightest member, Epsilon Ursae Majoris, the luster of 600 suns. The organizing principle of this grand scheme must long remain mysterious. It is no solitary example. Particular association, indeed, as was surmised by Michel far back in the 18th century, appears to be the rule rather than an exception in the sidereal system. Stars are bound together by twos, by threes, by dozens, by hundreds. Our own sun is, perhaps, not exempt from this gregarious tendency. Yet the search for its companions has, up to the present, been unavailing. Gould's cluster seems remote and intangible. Kapteyn's collection of solar stars proved to have been a creation of erroneous data, and was abolished by his unrelenting industry. Rather, we appear to have secured a compartment to ourselves for our long journey through space. A practical certainty has, at any rate, been gained that whatever aggregation holds the Sun as a constituent is of a far looser build than the Pleiades or Praesepe. Of all such majestic communities the laws and revolutions remain, as yet, inaccessible to inquiry. Centuries may elapse before even a rudimentary acquaintance with them begins to develop. While the economy of the higher order of association, which we must reasonably believe that they unite to compose, will possibly continue to stimulate and baffle human curiosity to the end of time. Footnotes. Report Brit. Association, 1868, page 166. Rutherford gave a rudimentary sketch of a classification of the kind in December, 1862, but based on imperfect observation. C.A.M. Jour, of S.C., Volume 35, page 77. Publicationem, Potsdam, No. 14, 1884, page 31. Von Konkoly once derived from a slow-moving meteor a hydrocarbon spectrum. A. S. Herschel, Nature, Volume 24, page 507. Phil. Trans, Volume Cliv, page 429. A.M. Jour, of S.C., Volume 19, page 467. Photom, Unters, page 243. Spectre Solaire, page 38. Mr. J. Birmingham, in the introduction to his catalogue of red stars, adduced sundry instances of color change in a direction the opposite to that assumed by Zollner to be the inevitable result of time. Trans. Art. Irish Academic, Volume 26, page 251. A learned discussion by Dr. T. J. J. C., moreover, enforces the belief that Sirius was absolutely red 1800 years ago. Astra. An Astroph, Volume 11, page 269. Phil. Trans, Volume Kluxiv, page 492. Astra. Nock, number 2000. Proc. Roy. SOC. Volume 16, page 31, 17, page 48. Annalen der Physik, BD, XX, page 155. Ibid, page 153. Knowledge, Volume 14, page 101. Meteoritic Hypothesis, page 380. Phil. Trans, Volume XIII. A, page 128, Spectra of Southern Stars, page 3. See the author's System of the Stars, page 84. A designation applied by Sir Norman Lockyer to third-type stars. See Ante, page 198. Bothkamp Beobachtingen, Heft 2, page 146. Astra. Nock, number 2539. Ibid, number 2548, Observatory, volume 6, page 332. Month. Knot, volume 47, page 92. Publ, Astra. Pack. SOC, volume 1, page 80, Observatory, volume 13, page 46. Lockyer, Proc. Roy. SOC, volume 57, page 173. Astra. Nock, number 3129. Month. Knot, volume 59, page 505. Astra. Nock, number 2581. Ibid, numbers 2651-2. Ibid. Number 3051, Astra. An Astrophysics, volume 11, page 25, Belopolsky, Astra. Knock, number 3129. Comptes Rendus, TLXV, page 292. Copernicus, volume 3, page 207. System of the Stars, page 70, Harvard Annals, volume 28, pt 2, page 243, Miss Cannon. Potsdam Publ, number 14, page 17. Proc. Roy. SOC, volume 49, page 33. Miss A. J. Cannon, Harvard Annals, volume 28, pt 2, page 141. Astr. An Astroph, volume 13, page 448. Potsdam Publ, number 2. The results of von Konkoly's extension of Vogel's work to 15 degrees of south declination were published in Ojala Biobaktingen, BD 8, Th2, 1887. Astroph. Jour, volumes 8, page 237, 9, page 271. Ibid, volume 9, page 119. Phil. Trans, volume. Cliv, page 413. Some preliminary results were embodied in a note communicated to the Royal Society, February 19, 1863, Proc. Roy. SOC, volume 12, page 444. Both Camp Biob, Hefti, page 25. Astroph. Jour, volume 6, page 423. Phil. Trans, volume Cliv. Page 429, note. Month. Not, volume 23, page 180. Proc. Roy. SOC, volume 25, page 446. Phil. Trans, volume Clerke, page 669, Atlas of Stellar Spectra, page 22. Astr. Knock, number 2301, Monetsp, Berlin, 1879, page 119, 1880, page 192. Jour de Physique, T.V. Page 98. System of the Stars, page 39. C. Ante, page 198. Proc. Roy. SOC, volume 48, page 314. Harvard Circulars, numbers 12, 18, Astroph. Jour, volume 5, page 92. Astroph. Jour, volume 6, page 233. McLean, Phil. Trans, volume XIII. A, page 129. Proc. Roy. SOC, volume 62, page 417. Ibid, April 27, 1899, Astroph. Jour, volume 10, page 272. Astr. Knock, number 3565. Ibid, number 3583. Lunt, Astroph. Jour, volume 11, page 262, Proc. Roy. SOC, volume 66, page 44, Lockyer, Ibid, November 23, 1899, Nature, volume. LXI, page 263. Dye Spectral Analyse, page 314. Henry Draper Memorial, First and Report, 1887. MEM. America Academic, volume 11, page 215. Harvard Annals, volume 27. Harvard Annals, volume 28, parts 1 and 2. C. Ante, page 201. Phil. Trans, volume Clavii. Page 529. Schellen, Die Spektralanalyse, BD, 2, page 326, edition 1883. Proc. Roy. SOC, volume 20, page 386. System of the Stars, page 199. Pickering, A.M. Jour of SC, volume 39, page 46, Vogel, Astr. Knock. Number 3017. Sitzungsbericht, Berlin, May 2, 1901. Astroph. Jour, Volume 13, page 324. The relative orbit of a double star is that described by one round the other as a fixed point. Micrometrical measures are always thus executed. But in reality both stars move in opposite directions, and at rates inversely as their masses round their common center of gravity. Vogel, Astr. Nock, numbers 3017, 3039. Huggins, President Address, 1891, Cornu, sur la méthode Dopplerfaisceau p.d. 38. Sitzungsb, Berlin, 1890, page 401, Astr. Nock, number 2995. Ibid. Astroph. Jour, volume 5, page 1, Newell, month. Knot, volume 57, page 575. Bull. De l'Académique. De St. Petersburg, tt. 6, 8. Astroph. Jour, volume 10, page 177, month. Knot, volume 60, page 418. Vogel, Sitzungsb, Berlin, April 19, 1900. Month. Knot, volume 60, page 595. Hussey, Astr. Jour, number 484. Astroph. Jour, volumes X, page 180, 14, page 140, Lick Bulletin, number 4, Belopolsky, Astr. Nock, number 3637. The significance of the name El Ghul leaves little doubt that the Arab astronomers took note of this star's variability. E. M. Clerke, Observatory, Volume 15, page 271. Phil. Trans, Volume 73, page 484. Proc. America Academic, Volume 16, page 17. Observatory, Volume 4, page 116. For a preliminary essay by T. S. Aldous, see Phil. Mag, Volume 39, page 363, 1870. Astr. Nock, number 2947. Astr. Jour, numbers 165-6, 255-6, 509. See also Knowledge, Volume 15, page 186. Boschinger, V. J. S. Astr. Guess. Jarg. 29, but C. F. Searle, Harvard Annals, Volume 29, page 223, Boss, Astr. Jour, number 343. Comptes Rendus, T. CXX, page 125. Myers, Astroph. Jour, Volume 7, page 1, W. Roberts, Ibid, Volume 13, page 181. Proc. Art. Irish A.C., July, 1884. Ibid. Volume 1, page 97. Astr. Jour, numbers 179, 180. Ibid, numbers 300, 379. Astr. Jour, numbers 491-2. System of the Stars, page 125. Proc. Roy. SOC, Volume 15, page 146. Weiss, Astr. Nock, number 1590, Espin, Ibid, number 3200. Comptes Rendus, T. 83, page 1172. Monitzp, Berlin, 1877, pages 241, 826. Copernicus, Volume 2, page 101. Burnham, month. Knot, Volume 52, page 457. Astr. Nock, number 2682. A. Hall, A.M. Jour, of S.C., Volume 31, page 301. Young, Sid. Messenger, Volume 4, page 282, Hasselberg, Astr. Nock, No. 2690. Report Brit. Association, 1885, page 935. Month. Knot, volume 47, page 54. Nature, volume 32, page 522. Astra. Knock, numbers 1267, 2715. Month. Knot, volume 21, page 32. Observatory, volume 8, page 335. Astra. Knock, number 3118, Astra. An Astroph, volume 11, page 907. Cape Results, page 137. Trans Art SOC of Edinburgh, volume 27, page 51, Astra. An Astroph, August, 1892, page 593. Vogel, Astra. Knock, number 3079. Observatory, volume 15, page 287, Seliger, Astra. Knock, number 3118, Astra. An Astroph, volume 11, page 906. Ranyard, Knowledge, volume 15, page 110. Proc. Roy. SOC, volume 51, page 492. Burnham, Month. Knot, volume 53, page 58. Astra. Knock, numbers 3118, 3143. Rens, Ibid, numbers 3119, 3238, Huggins, Astra. An Astroph, volume 13, page 314. Astra. Knock, number 3111. Belopolsky, Astra. Knock, number 3120. Nature, September 15, 1892. Astra. Knock, numbers 3122, 3129. Ibid, number 3133, Astra. An Astroph, volume 11, page 715. Publ, Astra. Pack. SOC, volume 4, page 244. Barnard, Astroph. Jour, volume 14, p. 152, Campbell, Observatory, volume 24, page 360. Pop Astra, March, 1895, page 307. Harvard Circular, number 4, December 20, 1895. The first nova Persei was spectrographically recorded in 1887. Vogel, Sitzungsb, Berlin, April 19, 1900, page 389. Sydgreaves, Observatory, volume 24, page 191. Ibid, Knowledge, volume 25, page 10. Lick Bulletin, number 8. Astra. Knock, number 3736. Astroph. Jour, volume 14, page 167. Lick Bulletin, number 10. Astroph. Jour, volumes 14, page 293, 15, page 129. Cf. The Theories on the Subject of M. Wolf, Astra. Knock, numbers 3752, 3753, Captian, Ibid, number 3756, F. W. Very, Ibid, number 3771, and W. E. Wilson, Proc. Roy. Dublin SOC, number 45, page 556. Phil. Trans, volume Cliv, page 437. Phil. Trans, volume Clavii. Page 540. The true proportion seems to be about 1/10, Harvard Annals, volume 26, pt 2, page 205, the Tulse-Hill working list having been formed of specially selected objects. Shiner, Astra. Knock, number 3476, Astroph. Jour, volume 7, p. 231, Campbell, Ibid, Volumes 9, page 312, X, page 22. Proc. Roy. SOC, Volumes 46, page 40, 48, page 202. PUBL, Astr. Pac. SOC, Volume 2, page 265, Proc. Roy. SOC, Volume 49, page 399. Astr. Nock, No 3549. Atlas of Stellar Spectra, page 125. Knowledge, Volume 19, page 39. Astr. Nock, numbers 1366, 1391, 1689, Chambers, Descriptive Astra. 3rd edition, page 543, Flammarion, L'Univers Sidereal, page 818. Month. Knot, Volume 51, page 94. Ibid, Volume 59, page 372. Ibid, Volume 60, page 424. Dreyer, Ibid. Volume 52, page 100. Washington OBS, Volume 25, App. 1. A.M. Jour of SC, Volume 14, page 433, C. Dreyer, Month. Knot, Volume 47, page 419. Ibid, Volume 51, page 496. Reproduced in Knowledge, April, 1893. Unless an exception be found in the Pleiades nebulae, which may be assumed to share the small apparent movement of the stars they adhere to. Abhandel. Akkad. Der Wyss, Leipzig, 1857, BD, 3, page 295. Month. Knot, Volume 52, page 31. Proc. Roy. SOC. 1874, page 251. PUBL, Astr. Pac. SOC, Volume 2, page 278. System of the Stars, page 257. Proc. Roy. SOC, Volume 49, page 399. Potsdam PUBL, BD, 7, THI. Astr. Nock, number 2714, Schoenfeld, V. J. S. Astr. Guess, Jarg. 21, page 58. Astroph. Journ. Volume 13, page 80. Proc. Roy. SOC, Volume 33, page 425, Report Brit. Association, 1882, page 444. An impression of the 4 lower lines in the same spectrum was almost simultaneously obtained by Dr. Draper. Comptes Rendus, T. 94, page 1243. Proc. Roy. SOC, Volume 48, page 213. Month. Knot, Volume 48, page 360. Proc. Roy. SOC, Volume 46, page 40, System of the Stars, page 79. Sitzungsb, Berlin, February 13, 1890. Washington OBS, Volume 25, App. I, page 226. Comptes Rendus, T. 92, page 261. Month. Knot, Volume 43, page 255. Harvard Annals, Volume 18, page 116. Sid. Mess, Volume 9, page 1. Knowledge, Volume 15, page 191. Month. Knot, Volume 49, page 65. System of the Stars, page 269. Astr. Nock, numbers 2749, 2754. Vogel, Astr. Nock, 2854. Nature, Volume 43, page 419. L'Astronomie, T. XL, page 171. Astr. Nock, Band 47, page 1, 48, page 1, 49, page 81. Pickering, MEM. A.M. A.C., Volume 11, page 180. Gould on Celestial Photography, Observatory, Volume 2, page 16. Annals N.Y. Academic. Of Sciences, Volume 6, page 239, 1892, Elkin, Publ, Astr. Pack. SOC, Volume 4, page 134. Trans-Yale Observatory, Volume 1, PTI. Astroph. Jour, Volume 13, page 56. Astr. Nock, number 2719. Ibid, number 2726. Ibid, number 2730. Month. Knott, Volume 47, p. 24. Les Mons, T. 3, page 529. Mouchet, Comptes Rendus, T. CVI, page 912. Astr. Nock, number 3422. Ibid, number 3441. Ibid, numbers 3018, 3032. Journ. Brit. Astr. Association, Volume 9, page 133. Astr. Nock, number 3253. Observatory, Volume 21, pages 351, 386. Reproduced in Astroph. Journ, Volume 11, page 324. Ibid, page 347. Astr. Nock, number 3704. Sitzungsp. Bayer. Akkad, March 23, 1901. Annals of the Cape Observatory, Volumes 3, 4, v. Month. Knott, Volume 60, page 381. D. Klumpke, Observatory, Volume 15, p. 305. Gilbert, Sid. Mess, Volume 1, page 288. Astr. Papers for the America Ephemeris, Volume 8, pt 2. Nature, Volume 24, page 91, Dunsink Observations, PTV, 1884. Elkin, Report for 1891-92, page 25, Newcomb, The Stars, page 151. Annals of the Cape Observatory, Volume 8, pt 2. Some of the measures were made by Messrs. Finlay and de Sitter. Astr. Nock, number 3483, Observatory, Volume 21, page 180. Annalen der Sternwarte in Leiden, BD, 7. Report of Harvard Conference in 1898, Snyder. Researches in Stellar Parallax, pt 2, 1892. V. J. S. Astr. Guess, Jarg, 28, page 117. Bulletin de la Carte du Ciel, No. 1, page 262. Publ, of the Astre. Laboratory at Groningen, No. 1. Nature, Volume 26, page 177. Proc. R. Irish Academic, Volume 1, page 571, Ser. 3. MEM. R. A. S., Volume 47, page 178. Astr. Nock, number 3142. Publ, Astr. Pack. SOC, number 76. Campbell, Lick Bulletin, number 4. Publ, Yerkes Observatory, Volume 1, 1900. Annals Cape Observatory, Volume 2, pt 2. Astr. Jour, numbers 431-2. W. J. Hussey, Publ, Astr. Pack. SOC, number 74. Astr. Jour, number 258. Sitzungsbericht, Berlin, October 26, 1893. Annals de l'Obs. Denis, T. 2. Washington Observations, 1888, App. I. Publ, Lick Observatory, Volume 5, 1901. T. Lewis, Observatory, Volume 16, page 312. Harvard Annals, Volume 14, PTI, 1884. Observatory, Volume 8, page 309. Month. Knot, Volume 46, page 277. Harvard Annals, Volume 34. Ibid, Volume 45. Carte Faute. Ducil. Réunion du Comique Permanent, Paris, 1891, page 100. Essays, Second Serre, The Nebular Hypothesis. On the Plurality of Worlds, page 214, second edition. Proctor, Month. Knot, Volume 29, page 342. This remark was first made by J. Michel, Phil. Trans, Volume 57, page 25, 1767. Pop Astre, number 45. Astroph. Jour, Volume 1, page 220. Month. Knot, Volumes 31, page 175, 32, page 1. The Stars, page 273. System of the Stars, page 384, Old and New Astronomy, page 749, Ranyard. Astroph. Jour, Volume 12, page 156. Publ, Astre. Pac. SOC, Volume 2, page 242. Month. Knot, Volume 51, pages 40, 97. For reproductions of some of the photographs in question, see Knowledge, Volume 14, page 50. Astre. Nock, number 3048, Observatory, Volume 14, page 301. Proc. Roy. Inst. May 29, 1891, Gill. Annals Cape OBS, 3, Introduction, page 22. Proc. Roy. SOC, Volume 18, page 169. Astre. Nock, number 3456, Observatory, Volume 21, page 65, Newcomb, The Stars, page 80. Month. Knot, Volume 40, page 249. Chapter 13. Methods of Research. Comparing the methods now available for astronomical inquiries with those in use 40 years ago, we are at once struck with the fact that they have multiplied. The telescope has been supplemented by the spectroscope and the photographic camera. Now, this really involves a whole world of change. It means that astronomy has left the place where she dwelt apart in rapt union with mathematics, indifferent to all things on earth save only to those mechanical improvements which should aid her to penetrate further into the heavens. And has descended into the forum of human knowledge, at once a suppliant and a patron, alternately invoking help from and promising it to each of the sciences, and patiently waiting upon the advances of all. The science of the heavenly bodies has, in a word, become a branch of terrestrial physics, or rather a higher kind of integration of all their results. It has, however, this leading peculiarity, that the materials for the whole of its inquiries are telescopically furnished. They are such as come very imperfectly, or not at all, within the cognizance of the unarmed eye. Spectroscopic and photographic apparatus are simply additions to the telescope. They do not supersede or render it of less importance. On the contrary, the efficacy of their action depends primarily upon the optical qualities of the instruments they are attached to. Hence the development, to their fullest extent, of the powers of the telescope is a vital moment to the progress of modern physical astronomy, while the older mathematical astronomy could afford to remain comparatively indifferent to it. The colossal Rosse reflector still marks, as to size, the Ne plus ultra of performance in that line. A mirror 4 feet in diameter was, however, sent out to Melbourne by the late Thomas Grubb of Dublin in 1870. This is mounted in a Cassegrainian manner, so that the observer looks straight through it towards the object viewed, of which he really sees a twice reflected image. The dust-laden atmosphere of Melbourne is said to impede very seriously the usefulness of this originally fine instrument. It may be doubted whether so large a spectrum will ever again be constructed. A new material for the mirrors of reflecting telescopes, proposed by Steinheil in 1856, and independently by Foucault in 1857, has in a great measure superseded the use of a metallic alloy. This is glass upon which a thin film of silver has been deposited by a chemical process originally invented by Liebig. It gives a peculiarly brilliant reflective surface, throwing back more light than a metallic mirror of the same area, in the proportion of about 16:9. Resilvering, too, involves much less risk and trouble than repolishing a speculum. The first use of this plan on a large scale was in an instrument of 36 inches aperture, finished by Calver for Dr. Common in 1879. To its excellent qualities turned to account with rare skill, his triumphs in celestial photography are mainly due. A more daring experiment was the construction and mounting, by Dr. Common himself, of a 5-foot reflector. But the first glass disc ordered from France for the purpose proved radically defective. When figured, polished, and silvered, towards the close of 1888, it gave elliptical instead of circular star images. A new one had to be procured, and was ready for astronomical use in 1891. The satisfactory nature of its performance is vouched for by the observations made with it upon Jupiter's new satellite in December, 1892. This instrument, to which a Newtonian form has been given, had no rival in respect of light concentration at the time when it was built. It has now too, the Paris 50-inch refractor and the Yerkes 5-foot reflector. It is, however, in the construction of refracting telescopes that the most conspicuous advances have recently been made. The Harvard College 15-inch achromatic was mounted and ready for work in June, 1847. A similar instrument had already for some years been in its place at Pulkowa. It was long before the possibility of surpassing these masterpieces of German skill presented itself to any optician. For 15 years it seemed as if a line had been drawn just there. It was first transgressed in America. A portrait painter of Cambridgeport, Massachusetts, named Alvan Clerke, had for some time amused his leisure with grinding lenses, the singular excellence of which was discovered in England by Mr. Dawes in 1853. 7 years passed, and then an order came from the University of Mississippi for an object glass of the unexampled size of 18 inches. An experimental glance through it to test its definition resulted, as we have seen, in the detection of the companion of Sirius, January 31, 1862. It never reached its destination in the South. War troubles supervened, and it was eventually sent to Chicago, where it served Professor Hoff in his investigations of Jupiter, and Mr. Burnham in his scrutiny of double stars. The next step was an even longer one, and it was again taken by a self-taught optician, Thomas Cook, the son of a shoemaker at Allerthorpe, in the East Riding of Yorkshire. Mr. Newell of Gateshead ordered from him in 1863 a 25-inch object glass. It was finished early in 1868, but at the cost of shortening the life of its maker, who died October 19, 1868, before the giant refractor he had toiled at for 5 years was completely mounted. This instrument, the fine qualities of which had long been neutralized by an unfavorable situation, was presented by Mr. Newell to the University of Cambridge, a few weeks before his death, April 21, 1889. Under the care of his son, Mr. Frank Newell, it has proved highly efficient in the delicate work of measuring stellar radial motions. Close upon its construction followed that of the Washington 26-inch, for which $20,000 were paid to Alvan Clerke. The most illustrious point in its career, entered upon in 1873, has been the discovery of the satellites of Mars. Once known to be there, these were, indeed, found to be perceptible with very moderate optical means. Mr. Wentworth Erck saw Deimos with a 7-inch Clerke, but the first detection of such minute objects is a feat of a very different order from their subsequent observation. Dar. C's perception with this instrument, in 1899, of Neptune's cloud belts, and his refined series of micrometrical measures of the various planets, attest the unimpaired excellence of its optical qualities. It held the primacy for more than 8 years. Then, in December 1880, the place of honor had to be yielded to a 27-inch achromatic, built by Howard Grubb, son and successor of Thomas Grubb, for the Vienna Observatory. This, in its turn, was surpassed by 2 of respectively 29.5 and 30 inches, sent by Gautier of Paris to Nice, and by Alvan Clerke to Pulkowa. And an object glass, 3 feet in diameter, was in 1886 successfully turned out by the latter firm for the Lick Observatory in California. The difficulties, however, encountered in procuring discs of glass of the size and purity required for this last venture seem to indicate that a term to progress in this direction was not far off. The flint was, indeed, cast with comparative ease in the workshops of M. File at Paris. The flawless mass weighed 170 kilograms, was over 38 inches across, and cost $10,000. But with the crown part of the designed achromatic combination things went less smoothly. The production of a perfect disc was only achieved after 19 failures, involving a delay of more than 2 years. And the glass for a third lens, designed to render the telescope available at pleasure for photographic purposes, proved to be strained, and consequently went to pieces in the process of grinding. It has been replaced by one of 33 inches, with which a series of admirable lunar and other photographs have been taken. Nor is the difficulty in obtaining suitable material the only obstacle to increasing the size of refractors. The secondary spectrum, as it is called, also interposes a barrier troublesome to surmount. True achromatism cannot be obtained with ordinary flint and crown glass. And although in lenses of Jena glass, outstanding color is reduced to about 1/6 its usual amount, their term of service is fatally abridged by rapid deterioration. Nevertheless, a 13-inch objective of the new variety was mounted at Königsberg in 1898, and discs of Jena crown and flint, 23 inches across, were purchased by Brashear at the Chicago exhibition of 1893. An achromatic combination of 3 kinds of glass, devised by Mr. A. Taylor for Messrs. Cook of York, has less serious drawbacks, but has not yet come into extensive use. Meanwhile, in giant telescopes affected to the full extent by chromatic aberration, such as the Lick and Yerkes refractors, the differences of focal length for the various colors are counted by inches. And this not through any lack of skill in the makers, but by the necessity of the case. Embarrassing consequences follow. Only a small part of the spectrum of a heavenly body, for instance, can be distinctly seen at one time. And a focal adjustment of half an inch is required in passing from the observation of a planetary nebula to that of its stellar nucleus. A refracting telescope loses, besides, one of its chief advantages over a reflector when its size is increased beyond a certain limit. That advantage is the greater luminosity of the images given by it. Considerably more light is transmitted through a glass lens than is reflected from an equal metallic surface. But only so long as both are of moderate dimensions. For the glass necessarily grows in thickness as its area augments, and consequently stops a larger percentage of the rays it refracts. So that a point at length arrives, fixed by the late Dr. Robinson at a diameter a little short of 3 feet, where the glass and the metal are, in this respect, on an equality, while above it the metal has the advantage. And since silvered glass gives back considerably more light than speculum metal, the stage of equalization with lenses is reached proportionately sooner where this material is employed. The most distinctive faculty of reflectors, however, is that of bringing rays of all refrangibilities to a focus together. They are naturally achromatic. None of the beams they collect are thrown away in color fringes, obnoxious both in themselves and as a waste of the chief object of astrophysicists' greed, light. Reflectors, then, are in this respect specially adapted to photographic and spectrographic use. But they have a countervailing drawback. The penalties imposed by bigness are for them peculiarly heavy. Perfect definition becomes with increasing size, more and more difficult to attain. Once attained, it becomes more and more difficult to keep. For the huge masses of material employed to form great object glasses or mirrors tend with every movement to become deformed by their own weight. Now, the slightest bending of a mirror is fatal to its performance, the effect being doubled by reflection. While in a lens alteration of figure is compensated by the equal and contrary flexures of the opposing surfaces, so that the emergent beams pursue much the same paths as if the curves of the refracting medium had remained theoretically perfect. For this reason work of precision must remain the province of refracting telescopes, although great reflectors retain the primacy in the portraiture of the heavenly bodies, as well as in certain branches of spectroscopy. Professor Hale, accordingly, summarized a valuable discussion on the subject by asserting that the astrophysicist may properly consider the reflector to be an even more important part of his instrumental equipment than the refractor. A new era in its employment west of the Atlantic opened with the transfer from Halifax to Mount Hamilton of the Crossley reflector. Its prerogatives in nebular photography were splendidly indicated in 1899 by Professor Keeler's exquisite and searching portrayals of the cloud worlds of space, and those obtained 2 years later, with a similar, though smaller, instrument, by Professor Ritchie of the Yerkes Observatory, were fully comparable with them. The performances of the Yerkes 5-foot reflector still belong to the future. Ambition as regards telescopic power is by no means yet satisfied. Nor ought it to be. The advance of astrophysical researches of all kinds depends largely upon light grasp. For the spectroscopic examination of stars, for the measurement of their motions in the line of sight, for the discovery and study of nebulae, for stellar and nebular photography, the cry continually is, more light. There is no enterprising head of an observatory but must feel cramped in his designs if he can command no more than 14 or 15 inches of aperture, and he aspires to greater instrumental capacity, not merely with a view to the chances of discovery, but for the steady prosecution of some legitimate line of inquiry. Thus projects of telescope building on a large scale are rife, and some obtain realization year by year. Sir Howard Grubb finished in 1893 a 28-inch achromatic for the Royal Observatory, Greenwich. The Thomson Equatorial, mounted at the same establishment in 1897, carries on a single axis a 26-inch photographic refractor and a 30-inch silvered glass reflector. The Victoria Telescope, inaugurated at the Cape in 1901, comprises a powerful spectrographic apparatus, together with a chemically corrected 24-inch refractor, the whole being the munificent gift of Mr. Frank McLean. At Potsdam, at Meudon, at Paris, at Allegheny, engines for light concentration have been, or shortly will be, erected of dimensions which, 2 generations back, would have seemed extravagant and impossible. Perhaps the finest, though not absolutely the greatest, among them, marked the summit and end of the performances of Alvan G. Clerke, the last survivor of the Cambridgeport firm. In October, 1892, Mr. Yerkes of Chicago offered an unlimited sum for the provision of the University of that city with a superlative telescope. And it happened, fortunately, that a pair of glass discs, nearly 42 inches in diameter, and of perfect quality, were ready at hand. They had been cast by Mantois for the University of Southern California, when the erection of a great observatory on Wilson's Peak was under consideration. In the Clerke workshop they were combined into a superb objective, brought to perfection by trials and delicate touches extending over nearly 5 years. Then the maker accompanied it to its destination, by the shore of a far western Lake Geneva, and died immediately after his return, June 9, 1897. Nor has the implement of celestial research he just lived to complete been allowed to rust unburnished. Manipulated by Hale, Burnham, and Barnard, it has done work that would have been impracticable with less efficient optical aid. Its construction thus marks a noticeable enlargement of astronomical possibilities, exemplified, to cite one among many performances, by Barnard's success in keeping track of cluster variables when below the common limit of visual perception. With the Lick telescope results have also been achieved testifying to its unsurpassed excellence. Holden's and Skeebrill's views of planetary nebulae, Burnham's and Hussey's hair's-breadth star-splitting operations, Keeler's measurements of nebular radial motion, Barnard's detections and prolonged pursuit of faint comets. His discovery of Jupiter's tiny moon, Campbell's spectroscopic determinations, all this could only have been accomplished, even by an exceptionally able and energetic staff, with the aid of an instrument of high power and quality. But there was another condition which should not be overlooked. The best telescope may be crippled by a bad situation. The larger it is, indeed, the more helpless is it to cope with atmospheric troubles. These are the worst plagues of all those that afflict the astronomer. No mechanical skill avails to neutralize or alleviate them. They augment with each increase of aperture, they grow with the magnifying powers applied. The rays from the heavenly bodies, when they can penetrate the cloud veils that too often bar their path, reach us in an enfeebled, scattered, and disturbed condition. Hence the twinkling of stars, the boiling effects at the edges of sun, moon, and planets, hence distortions of bright, effacements of feeble telescopic images. Hence, too, the paucity of the results obtained with many powerful light-gathering machines. No sooner had the Parsonstown telescope been built than it became obvious that the limit of profitable augmentation of size had, under climatic conditions at all nearly resembling those prevailing there, been reached, if not overpassed. And Lord Rosse himself was foremost to discern the need of pausing to look round the world for a clearer and stiller air than was to be found within the bounds of the United Kingdom. With this express object Mr. Lassell transported his 2-foot Newtonian to Malta in 1852, and mounted there, in 1860, a similar instrument of fourfold capacity, with which, in the course of about 2 years, 600 new nebulae were discovered. Professor Piazzi Smith's experiences during a trip to the Peak of Tenerife in 1856 in search of astronomical opportunities gave countenance to the most sanguine hopes of deliverance, at suitable elevated stations, from some of the oppressive conditions of low-level stargazing. Yet for a number of years nothing effectual was done for their realization. Now, at last, however, mountain observatories are not only an admitted necessity but an accomplished fact. And Newton's long forecast of a time when astronomers would be compelled, by the developed powers of their telescopes, to mount high above the grosser clouds, in order to use them, had been justified by the event. James Lick, the millionaire of San Francisco, had already chosen, when he died, October 1, 1876, a site for the new observatory, to the building and endowment of which he had devoted a part of his large fortune. The situation of the establishment is exceptional and splendid. Planted on one of the 3 peaks of Mount Hamilton, a crowning summit of the Californian Coast Range, at an elevation of 4,200 feet above the sea, in a climate scarce rivaled throughout the world. It commands views both celestial and terrestrial which the lover of nature and astronomy may alike rejoice in. Impediments to observation are there found to be most materially reduced. Professor Holden, who was appointed, in 1885, President of the University of California and Director of the new observatory affiliated to it, stated that during 6 or 7 months of the year an unbroken serenity prevails, and that half the remaining nights are clear. The power of continuous work thus afforded is of itself an inestimable advantage, and the high visual excellences testified to by Mr. Burnham's discovery, during a 2-month trip to Mount Hamilton in the autumn of 1879, of 42 new double stars with a 6-inch achromatic, gave hopes since fully realized of a brilliant future for the Lick establishment. Its advantages are shared, as Professor Holden desired them to be, by the whole astronomical world. A sort of appellate jurisdiction was at once accorded to the great equatorial, and more than one disputed point has been satisfactorily settled by recourse to it. Its performances, considered both as to quality and kind, are unlikely to be improved upon by merely outbidding it in size, unless the care expended upon the selection of its site be imitated. Professor Pickering thus showed his customary prudence in reserving his efforts to procure a great telescope until Harvard College owned a dependent observatory where it could be employed to advantage. This was found by Mr. W. H. Pickering, after many experiments in Colorado, California, and Peru, at Arequipa, on a slope of the Andes, 8,000 feet above the sea level. Here the post provided for by the Boyden Fund was established in 1891, under ideal meteorological conditions. Temperature preserves a golden mean, the barometer is almost absolutely steady. The yearly rainfall amounts to no more than 3 or 4 inches. No wonder, then, that the seeing there is of the extraordinary excellence attested by Mr. Pickering's observations. In the absence of bright moonlight, he tells us, 11 Pleiades can always be counted. The Andromeda Nebula appears to the naked eye conspicuously bright, and larger than the full moon. Third-magnitude stars have been followed to their disappearance at the true horizon. The zodiacal light spans the heavens as a complete arch, the Gegenschein, forming a regular part of the scenery of the heavens. Corresponding telescopic facilities are enjoyed. The chief instrument at the station, a 13-inch equatorial by Clerke, shows the fainter parts of the Orion Nebula, photographed at Harvard College in 1887, by which the dimensions given to it in Bond's drawing are doubled. Stars are at times seen encircled by half a dozen immovable diffraction rings, up to 12 of which have been counted round Alpha Centauri. While on many occasions no available increase of magnifying power availed to bring out any wavering in the limbs of the planets. Moreover, the series of fine nights is nearly unbroken from March to November. The facilities thus offered for continuous photographic research rendered feasible Professor Bailey's amazing discovery of variable star clusters. They belong exclusively to the globular class, and the peculiarity is most strikingly apparent in the groups known as Omicron Centauri, and Messier 3, 5, and 15. A large number of their minute components run through perfectly definite cycles of change in periods usually of a few hours. Altogether, about 500 cluster variables have been recorded since 1895. It should be mentioned that Mr. David Packer and Dr. Common discerned, about 1890, some premonitory symptoms of light fluctuation among the crowded stars of Messier 5. With the Bruce telescope, a photographic doublet 24 inches in diameter, a store of 5,686 negatives was collected at Arequipa between 1896 and 1901. Some were exposed directly, others with the intervention of a prism. And all are available for important purposes of detection or investigation. Vapors and air currents do not alone embarrass the use of giant telescopes. Mechanical difficulties also oppose a formidable barrier to much further growth in size. But what seems a barrier often proves to be only a fresh starting point, and signs are not wanting that it may be found so in this case. It is possible that the monumental domes and huge movable tubes of our present observatories will, in a few decades, be as much things of the past as Huygens's aerial telescopes. It is certain that the thin edge of the wedge of innovation has been driven into the old plan of equatorial mounting. M. Loewy, the present director of the Paris Observatory, proposed to Delaunay in 1871 the direction of a telescope on a novel system. The design seemed feasible, and was adopted. But the death of Delaunay and the other untoward circumstances of the time interrupted its execution. Its resumption, after some years, was rendered possible by M. Bischofsheim's gift of 25,000 francs for expenses, and the Coude or bent equatorial has been, since 1882, one of the leading instruments at the Paris establishment. Its principle is briefly this: the telescope is, as it were, its own polar axis. The anterior part of the tube is supported at both ends, and is thus fixed in a direction pointing towards the pole, with only the power of twisting axially. The posterior section is joined onto it at right angles, and presents the object glass, accordingly, to the celestial equator, in the plane of which it revolves. Stars in any other part of the heavens have their beams reflected upon the object glass by means of a plane rotating mirror placed in front of it. The observer, meanwhile, is looking steadfastly down the bent tube towards the invisible southern pole. He would naturally see nothing whatever were it not that a second plane mirror is fixed at the elbow of the instrument, so as to send the rays which have traversed the object glass to his eye. He never needs to move from his place. He watches the stars, seated in an armchair in a warm room, with as perfect convenience as if he were examining the seeds of a fungus with a microscope. Nor is this a mere gain of personal ease. The abolition of hardship includes a vast accession of power. Among other advantages of this method of construction are, first, that of added stability, the motion given to the ordinary equatorial being transferred, in part, to an auxiliary mirror. Next, that of increased focal length. The fixed part of the tube can be made almost indefinitely long without inconvenience, and with enormous advantage to the optical qualities of a large instrument. Finally, the costly and unmanageable cupola is got rid of, a mere shed serving all purposes of protection required for the coup d'etat. The desirability of some such change as that which M. Loewy has realized has been felt by others. Professor Pickering sketched, in 1881, a plan for fixing large refractors in a permanently horizontal position, and reflecting into them, by means of a shifting mirror, the objects desired to be observed. The observations for his photometric catalogues are, in fact, made with a broken transit, in which the line of sight remains permanently horizontal, whatever the altitude of the star examined. Sir Howard Grubb, moreover, set up, in 1882, a kind of siderostat at the Crawford Observatory, Cork. In a paper read before the Royal Society, January 21, 1884, he proposed to carry out the principle on a more extended scale. And shortly afterwards undertook its application to a telescope 18 inches in aperture for the Armagh Observatory. The chief honors, however, remain to the Paris inventor. None of the prognosticated causes of failure have proved effective. The loss of light from the double reflection is insignificant. The menaced deformation of images is, through the exquisite skill of the M. Henry in producing plane mirrors of all but absolute perfection, quite imperceptible. The definition was admitted to be singularly good. Sir David Gill stated in 1884 that he had never measured a double star so easily as he did Gamma Leonis by its means. Sir Norman Lockyer pronounced it to be one of the instruments of the future. And the principle of its construction was immediately adopted by the directors of the Besançon and Algiers observatories, as well as for a 17-inch telescope destined for a new observatory at Buenos Aires. At Paris, it has since been carried out on a larger scale. A coup d'etat of 23.5 inches aperture and 62 feet focal length was in 1890 installed at the National Observatory, and has served M. Loewy for his ingenious studies on refraction and aberration, above all, for taking the magnificent plates of his lunar atlas. The bent form is capable of being, but has not yet been, adapted to reflectors. The coelostat, in the form given to it by Professor Turner, has proved an invaluable adjunct to eclipse equipments. It consists essentially of a mirror rotating in 48 hours on an axis in its own plane, and parallel to the Earth's axis. In the field of a telescope kept rigidly pointed toward such a mirror, stars appear immovably fixed. The employment of long focus lenses for coronal photography is thus facilitated, and the size of the image is proportional to the length of the focus. Professor Barnard, accordingly, depicted the totality of 1900 with a horizontal telescope 61.5 feet long, fed by a mirror 18 inches across, the diameter of the moon on his plates being 7 inches. The largest siderostat in the world is the Paris 50-inch refractor, which formed the chief attraction of the Palais d'Optique at the exhibition of 1900. It has a focal length of nearly 200 feet, and can be used either for photographic or for visual purposes. Celestial photography has not reached its grand climacteric. Yet its earliest beginnings already seem centuries behind its present performances. The details of its gradual yet rapid improvement are of too technical a nature to find a place in these pages. Suffice it to say that the dryplate process, with which such wonderful results have been obtained, appears to have been first made available by Sir William Huggins in photographing the spectrum of Vega in 1876. And was then successively adopted by Common, Draper, and Janssen. Nor should Captain Abney's remarkable extension of the powers of the camera be left unnoticed. He began his experiments on the chemical action of red and infrared rays in 1874, and at length succeeded in obtaining a substance, the blue bromide of silver, highly sensitive to these slower vibrations of light. With its aid he explored a vast, unknown, and forever invisible region of the solar spectrum, presenting to the Royal Society, December 5, 1879, a detailed map of its infrared portion, wavelength 7,600 to 10,750. From which valuable inferences may yet be derived as to the condition of the various kinds of matter ignited in the solar atmosphere. Upon plates rendered orthochromatic by staining with alizarin, or other dyestuffs, the whole visible spectrum can now be photographed. But those with their maximum of sensitiveness near G are found preferable, except where the results of light analysis are sought to be completely recorded. And since photographic refractors are corrected for the blue rays, exposures with them of orthochromatic surfaces would be entirely futile. The chemical plate has two advantages over the human retina. First, it is sensitive to rays which are utterly powerless to produce any visual effect. Next, it can accumulate impression almost indefinitely, while from the retina they fade after 1/10 part of a second, leaving it a continually renewed tabula rasa. It is, accordingly, quite possible to photograph objects so faint as to be altogether beyond the power of any telescope to reveal, witness the chemical disclosure of the invisible nebula encircling Nova Persei, and we may thus eventually learn whether a blank space in the sky truly represents the end of the stellar universe in that direction, or whether farther and farther worlds roll and shine beyond, veiled in the obscurity of immeasurable distance. Of many ingenious improvements in spectroscopic appliances, the most fundamentally important relate to what are known as gratings. These are very finely striated surfaces, by which light waves are brought to interfere, and are thus sifted out, strictly according to their different lengths, into normal spectra. Since no universally valid measures can be made in any others, their production is quite indispensable to spectroscopic science. Fraunhofer, who initiated the study of the diffraction spectrum, used a real grating of very fine wires, but rulings on glass were adopted by his successors, and were by Nobert executed with such consummate skill that a single square inch of surface was made to contain 100,000 hand-drawn lines. Such rare and costly triumphs of art, however, found their way into very few hands, and practical availability was first given to this kind of instrument by the inventiveness and mechanical dexterity of two American investigators. Both Rutherford's and Rowland's gratings are machine-ruled, and reflect instead of transmitting the rays they analyze, but Rowland's present to them a very much larger diffractive surface, and consequently possess a higher resolving power. The first preliminary to his improvements was the production, in 1882, of a faultless screw, those previously in use having been the inevitable source of periodical errors in striation, giving, in their turn, ghost lines as subjects of spectroscopic study. Their abolition was not one of Rowland's least achievements. With his perfected machine, a metallic area of 6¼ by 4¼ inches can be ruled with exquisite accuracy to almost any degree of fineness. He considered, however, 43,000 lines to the inch to be the limit of usefulness. The ruled surface is, moreover, concave, and hence brings the spectrum to a focus without a telescope. A slit and an eyepiece are alone needed to view it, and absorption of light by glass lenses is obviated, an advantage especially sensible in dealing with the ultra or infravisible rays. The high qualities of Rowland's great photographic map of the solar spectrum were thus based upon his previous improvement of the instrumental means used in its execution. The amount of detail shown in it is illustrated by the appearance on the negatives of 150 lines between H and K, and many lines depict themselves as double which, until examined with a concave grating, had passed for one and indivisible. A corresponding hand drawing, for which M. Tholen received in 1886 the Lalande Prize, exhibits, not the diffractive, but the prismatic spectrum as obtained with bisulfide of carbon prisms of large dispersive power. About 1/3 of the visible gamut of the solar radiations, A to B, is covered by it. It includes 3,200 lines, and is over 10 meters long. The grating is an expensive tool in the way of light. Where there is none to spare, its advantages must be foregone. They could not, accordingly, be turned to account in stellar spectroscopy until the Lick telescope was at hand to supply more abundant material for research. By the use thus made possible of Rowland's gratings, Professor Keeler was able to apply enormous dispersion to the rays of stars and nebulae, and so to attain a previously unheard of degree of accuracy in their measurement. His memorable detection of nebular movement in line of sight ensued as a consequence. Professor Campbell, his successor, has since obtained, by the same means, the first satisfactory photographs of stellar diffraction spectra. The means at the disposal of astronomers have not multiplied faster than the tasks imposed upon them. Looking back to the year 1800, we cannot fail to be astonished at the change. The comparatively simple and serene science of the heavenly bodies known to our predecessors, almost perfect so far as it went, incurious of what lay beyond its grasp, has developed into a body of manifold powers and parts. Each with its separate mode and means of growth, full of strong vitality, but animated by a restless and unsatisfied spirit, haunted by the sense of problems unsolved, and tormented by conscious impotence to sound the immensities it perpetually confronts. Knowledge might be said, when the Mécanique Céleste issued from the press, to be bounded by the solar system, but even the solar system presented itself under an aspect strangely different from what it now wears. It consisted of the Sun, 7 planets, and twice as many satellites, all circling harmoniously in obedience to a universal law, by the compensating action of which the indefinite stability of their mutual relations was secured. The occasional incursion of a comet, or the periodical presence of a single such wanderer chained down from escape to outer space by planetary attraction, availed nothing to impair the symmetry of the majestic spectacle. Now, not alone the ascertained limits of the system have been widened by 1,000 millions of miles, with the addition of one more giant planet and 7 satellites to the ancient classes of its members. But a complexity has been given to its constitution baffling description or thought. 500 circulating planetary bodies bridge the gap between Jupiter and Mars, the complete investigation of the movements of any one of which would overtask the energies of a lifetime. Meteorites, strangers, apparently, to the fundamental ordering of the solar household, swarm, nevertheless, by millions in every cranny of its space, returning at regular intervals like the comets so singularly associated with them, or sweeping across it with hyperbolic velocities, brought, perhaps, from some distant star. And each of these cosmical grains of dust has a theory far more complex than that of Jupiter. It bears within it the secret of its origin, and fulfills a function in the universe. The Sun itself is no longer a semi-fabulous, fire-girt globe, but the vast scene of the play of forces as yet imperfectly known to us, offering a boundless field for the most arduous and inspiring researches. Among the planets the widest variety in physical habitudes is seen to prevail, and each is recognized as a world apart, inviting inquiries which, to be effective, must necessarily be special and detailed. Even our own moon threatens to break loose from the trammels of calculation, and commits errors, which sap the very foundations of the lunar theory, and suggest the formidable necessity for its complete revision. Nay, the steadfast earth has forfeited the implicit confidence placed in it as a timekeeper. And questions relating to the stability of the earth's axis and the constancy of the earth's rate of rotation are among those which it behoves the future to answer. Everywhere there is multiformity and change, stimulating a curiosity which the rapid development of methods of research offers the possibility of at least partially gratifying. Outside the solar system, the problems which demand a practical solution are virtually infinite in number and extent. And these have all arisen and crowded upon our thoughts within less than 100 years. For sidereal science became a recognized branch of astronomy only through Herschel's discovery of the revolutions of double stars in 1802. Yet already it may be, and has been called, the astronomy of the future, so rapidly has the development of a keen and universal interest attended and stimulated the growth of power to investigate this sublime subject. What has been done is little, is scarcely a beginning, yet it is much in comparison with the total blank of a century past. And our knowledge will, we are easily persuaded, appear in turn the merest ignorance to those who come after us. Yet it is not to be despised, since by it we reach up groping fingers to touch the hem of the garment of the Most High. Appendix. Table I. Chronology, 1774 to 1893. 1774, March 4 Herschel's first observation. Subject, the Orion Nebula. 1774 sunspots geometrically proved to be depressions by Wilson. 1774 first experimental determination of the Earth's mean density by Maskelyne. 1781, March 13 discovery of Uranus. 1782 Herschel's first catalogue of double stars. 1783 Herschel's first investigation of the Sun's movement in space. 1783 Goodrich's discovery of Algol's law of variation. 1784 Analogy between Mars and the Earth pointed out by Herschel. 1784 Construction of the heavens investigated by Herschel's method of stargazing. Cloven disk, plan of the Milky Way. 1784 Discovery of binary stars anticipated by Michel. 1786 Herschel's first catalogue of nebulae. 1787, Jan. 11 Discovery by Herschel of two Uranian moons, Oberon and Titania. 1787, November 19th Acceleration of the Moon explained by Laplace. 1789 Herschel's second catalogue of nebulae, and classification by age of these objects. 1789 Completion of Herschel's 40-foot reflector. 1789, August 28. And September 17 his discovery with it of the two inner Saturnian satellites. 1789 Repeating circle invented by Borda. 1789 5-foot circle constructed by Ramsden for Piazzi. 1790 Maskelyne's catalogue of 36 fundamental stars. 1791 Herschel propounds the hypothesis of a fluid constitution for nebulae. 1792 Atmospheric refraction in Venus announced by Schroeder. 1794 Rotation period of Saturn fixed by Herschel at 10h. 16 m, page 446. 1795 Herschel's theory of the solar constitution. 1796 Herschel's first measures of comparative stellar brightness. 1796 Laplace's nebular hypothesis published in Exposition du Système du Monde. 1797 Publication of Olbers's method of computing cometary orbits. 1798 Retrograde motions of Uranian satellites detected by Herschel. 1799 Publication of first two volumes of Mécanique Céleste. 1799, May 7 Transit of Mercury observed by Schroeder. 1799, November 12 Star shower observed by Humboldt at Cumana. 1800 Monatliche correspondence started by von Zach. 1800 Invisible heat rays detected in the solar spectrum by Herschel. 1801, January 1 Discovery of Ceres by Piazzi. 1801 Publication of Lalande's Histoire Céleste. 1801 Investigation by Herschel of solar emissive variability in connection with spot development. 1802, March 28 Discovery of Pallas by Olbers. 1802 Herschel's third catalogue of nebulae. 1802 Herschel's discovery of binary stars. 1802 Marks of clustering in the Milky Way noted by Herschel. 1802 Wollaston records 7 dark lines in the solar spectrum. 1802, November 9 Transit of Mercury observed by Herschel. 1804, September 2 Transit of Mercury observed by Herschel. 1804 Foundation of Optical Institute at Munich. 1805 Herschel's second determination of the solar apex. 1807, March 29 Discovery of Vesta by Olbers. 1811 Herschel's theory of the development of stars from nebulae. 1811, February 9 Death of Maskelyne. Pond appointed to succeed him as Astronomer Royal. 1811, September 12 Perihelion passage of Great Comet. 1814 Herschel demonstrates the irregular distribution of stars in space. 1815 Fraunhofer maps 324 dark lines in the solar spectrum. 1818 Publication of Bessel's Fundamenta Astronomiae. 1819 Recognition by Encke of the first short-period comet. 1819, June 26 Passage of the Earth through the tail of a comet. 1820 Foundation of the Royal Astronomical Society. 1821 Foundation of Paramatta Observatory. 1821, September 1 Number of Astronomische Nachrichten. 1822, May 24 First calculated return of Encke's comet. 1822, August 25 Death of Herschel. Page 447. 1823 Bessel introduces the correction of observations for personal equation. 1823 Fraunhofer examines the spectra of fixed stars. 1824 Distance of the Sun concluded by Encke to be 95¼ million miles. 1824 Publication of Lohrmann's lunar chart. 1824 Dorpat refractor mounted equatorially. 1826 Commencement of Schwab's observations of sunspots. 1826, February 27 Biela's discovery of a comet. 1827 Orbit of a binary star calculated by Savary. 1829 Completion of the Royal Observatory at the Cape of Good Hope. 1829 The Königsberg heliometer mounted. 1830 Publication of Bessel's Tabulae Regiomontanae. 1832 Discovery by Brewster of atmospheric lines in the solar spectrum. 1833 Magnetic Observatory established at Göttingen. 1833, November 12, 13-star shower visible in North America. 1833 Completion of Sir J. Herschel's survey of the northern heavens. 1834, January 16 Sir J. Herschel's landing at the Cape. 1835, September Airy appointed Astronomer Royal in succession to Pond. 1835, November 16 Perihelion passage of Halley's comet. 1837 Solar movement determined by Argelander. 1837 Bessel's application of the heliometer to measurements of stellar parallax. 1837 Publication of Beer and Madler's Der Mond. 1837, December 16 Outburst of Eta Carinii observed by Sir J. Herschel. 1837 Thermal power of the Sun measured by Herschel and Pouillet. 1838 Parallax of 61 Cygni determined by Bessel. 1839, Jan. 9 Parallax of Alpha Centauri announced by Henderson. 1839 Completion of Pulkowa Observatory. 1839 Solidity of the Earth concluded by Hopkins. 1840, March 2 Death of Olbers. 1840 First attempt to photograph the Moon by J. W. Draper. 1842 Doppler announces principle of color change by motion. 1842 Conclusion of Bailey's experiments in weighing the Earth. 1842, July 8 Total solar eclipse. Corona and prominences observed by Airy, Bailey, Arago, and Struve. 1843, February 27 Perihelion passage of Great Comet. 1845, February completion of Parsonstown reflector. 1845, April discovery with it of spiral nebulae, page 448. 1845, April 2nd daguerreotype of the Sun taken by Foucault and Fizeau. 1845, October 21 place of Neptune assigned by Adams. 1845, December 8 discovery of Astrea by Henck. 1845, December 29 duplication of Biela's comet observed at Yale College. 1846 Melloni's detection of heating effects from moonlight. 1846, March 17 death of Bessel. 1846, September 23 discovery of Neptune by Gall. 1846, October 10 Neptune's satellite discovered by Lassell. 1847 publication of Sir J. Herschel's results of observations at the Cape of Good Hope. 1847 cyclonic theory of sunspots stated by him. 1848 J. R. Meyer's meteoric hypothesis of solar conservation. 1848 motion displacements of Fraunhofer lines adverted to by Fizeau. 1848, April 27 new star in Ophiuchus observed by Hind. 1848, September 19 simultaneous discovery of Hyperion by Bond and Lassell. 1849 first experimental determination of the velocity of by Fizeau. 1848, April 27 new star in Ophiuchus observed by Hind. 1848, September 19 simultaneous discovery of Hyperion by Bond and Lassell. 1849 first experimental determination of the velocity of light, Fizeau. 1850, July 17 Vega photographed at Harvard College. 1850, November 15 discovery by Bond of Saturn's dusky ring. 1851 Struve's first measurements of Saturn's ring system. 1851, July 28 total solar eclipse observed in Sweden. 1851, October 24 discovery by Lassell of two inner Uranian satellites.